Hey there, everyone. My name is Ryan Schul. Welcome to my data science channel. And today's lesson, I want to teach you how Google Maps works on a very simplified level. Okay, so it does get quite complicated on the back end and under the hood. There's a bunch of stuff going on, but fundamentally, there's a few basic principles that Google adheres to, and that's very straightforward and very simple to comprehend, right? So I put together a lesson today that's going to show everybody how this actually works, okay? And my first caveat is that I'll just say I don't work at Google. I never have worked at Google, but I can tell you almost with absolute certainty this is how the Google Maps algorithm works, or if it's not, it's extremely similar to this technique that we're going to look today, okay? So the concept is widely used. It's been vetted, tested over time, proven itself to be quite scalable up and out, and it's really like the industry standard way of doing it. Okay, if Google has some kind of small modification or enhancement that they add in, and I'm sure they do, being Google, I'm sure they have some things, right, that are proprietary, but I'm going to show you fundamentally how this thing works on a very basic and very primitive level. And again, Google probably adds in a little special sauce, but basically this is how it goes. Okay, so below we're going to try to do a couple different things. We're going to map some systems called navigation systems, okay? And we're going to peel back the layers of complexity, which is not that much really, and you're going to see basically how to go from one point to another, to another, to another. So from your origin to your destination and any stopover points in between, we're going to accommodate all of those scenarios, okay? This is called Dijkstra's algorithm, and it's used to compute the shortest path between the starting point and the destination point, whatever you choose, okay? And you have to envision or imagine that this is kind of arbitrary or random starting point too, because you can tell Google Maps at any point in your trip, okay, I want to start planning my trip right now, right? But Google Maps is not going to know in advance when you are going to start using the service, right? So they have to pick up wherever you are, wherever you're located, whether you're biking, walking, driving, it's going to have to detect where you are and then plan the route. So the beginning is a little bit arbitrary, it's a little bit random, but the execution is very well planned out and very methodical and very much optimized. We're going to see how this works. Okay, we're going to look at a few different types of scenarios here: real world or real-time traffic data, which Google gets from a combination of different sources. Google Maps users' phones, so myself, yourself, and all of the other people in the local area using phones. They'll collect data from that, from satellite feeds, from sensors and cameras in cars occasionally. I don't think they use that extensively, but that is one source. And then historical traffic data, given the time of day, the day of the week, and the location, and so on and so forth, okay? So let's say we have a pretty simple hypothetical example here. We're going to use NX Graph. This is called Networks Graph, and I do have a few other videos that are very similar to this. Well, somewhat different, somewhat related, somewhat different. I try not to duplicate efforts or replicate my work here, but inevitably there is going to be some overlap. There's only so much you can talk about in the data science space without going full circle and coming back to where you start from, right? So there is slight overlap. And I do have some other videos if you're interested in network graphing or network analysis. I have some videos on my channel. You can check those out. So this is in sync with those, but slightly different take. We're going to focus a little bit more on Google Maps, not just network analysis. Okay, so let's say we have a few different locations here. This is going to be contained in a list. That's why I have the square brackets and it's comma separated with apostrophes around each of one of these different items here, right, to indicate that this is a string or an object. So we have our locations as a list. We have our city map, which contains our locations, right? You can see that that matches. And then we're going to have a dictionary of roads. I'm sorry, not a dictionary, another list of roads with tuples inside of the list. So this is a tuple, this is a tuple, and this is a list, right, contained by the square brackets. So we're going to have a starting point and an ending point. We're going to pick home and park. These are just two things I came up with over here, home and park, okay? And the distance between them. So the distance can be assumed to be a weight, right? So how close or how far you are between different points. in this system that we're creating right here. So you have the start, you have the destination. So start and end is home and park. Okay, we're going to pick the shortest path, again, using Dijkstra's algorithm. This helps us to optimize the path or the route that we're going to take to get from point A to point B in the shortest distance possible and the shortest time possible as well. And those two aren't always equal, but a lot of times they're, right? If there's a lot of traffic between yourself and where you need to be, then maybe the shortest distance isn't the quickest distance. If there's a lot of traffic, the shortest distance might actually take longer. And if you travel further distance in terms of meters or miles, whatever your metric is for measuring the distance, it could actually be shorter even though you're traveling further, okay? So I'm going to go ahead and run this, Control Enter to run the data in the cell. You can see the asterisk is running right there. Okay, we'll get the hourglass at the top of the tab in this Jupyter notebook, and I think it's done now because the asterisk is gone and the hourglass is gone. So what did we do here? We're creating different distances in this network graph, and the distances are represented visually to reflect approximate edge weights. So weight here between home and school is 3, and the weight between school and park is 6. The weight between home and mall is 5. Okay, and this could be kilometers. Most likely it's kilometers. I don't think it's meters. And when we use Python, when we use Google Maps measures everything in terms of meters because most of the world uses meters. In the United States, we actually use miles, or they use kilometers and meters. It doesn't matter, right? One is 1,000 miles is 1 kilometer. So you can convert that into miles and feet, but I'm just going to leave this in the original form, which is meters, right? By default, Google Maps uses meters. So we can see between home and school and park, we have 6 and 3. So if you add those together, you'll get 9. And you can see that's exactly what happens here. So Google Maps uses Dijkstra's algorithm to solve this network graph problem. And it says from home to school is 3 units and school to park is 9 units. Okay, so it doesn't give us the in-between intermediate steps, but it gives us the sum total number of steps. We'll see in a minute how to get to intermediate steps. So hopefully that makes sense. We go from home to school to park, and that is 9, presumably kilometers. Now, it isn't actually defined for us as kilometers, but if you look at the graph, most likely it's kilometers. It's not 9 meters, okay? For the school and the park and the home to be 9 meters apart doesn't make any sense. So similar to this scenario that we just saw, we can also add in a randomly generated connection between roads and location. So like I said a few minutes ago, this could be considered to be a random problem that you have to solve because whenever you start using Google Maps is the initial input point, right? But like Google Maps doesn't know, are you going to start at your home? Are you going to start at your office? Or are you going to start at a hospital? It just doesn't know that, right? So the starting point is almost arbitrary, but the point is Google Maps has to figure out where you're going and be able to make that that determination and then find the shortest route to get there, right? So the starting point is arbitrary, but the route that Google Maps plans for you is anything but arbitrary, right? It's planned out using Dijkstra's algorithm, and you're going to find the shortest distance unless there's a lot of traffic or unless you have to create a stopover point, right? So there's a few different scenarios that we need to consider. The first one is very simple. We're going from home to school to park, right? Very straightforward, non-negotiable, nothing to really argue about there. But let's say we have a slightly more complex problem. We have different locations here and a different list, okay, a larger list. Originally we had what, just half dozen, give or take, maybe 8 or 9, whatever this is over here. Now at this point, we probably have close to a couple dozen. Okay, so with our couple dozen origins and destinations in the list, we have to pick where we're going from and where we're going to. Okay, so you can see that the algorithm is getting a little bit more complicated now, but that's totally fine. We're going to get from the origin to the destination using the shortest distance possible. Okay, so again, we're going to consider a bunch of different options over here in terms of the route to follow. We're going to look at the different edges with distances. Okay, so the distance shows the weight between the edges. So the edge can be considered as a circle, and the distance can be the can be the path here with a numeric value represented there. And you can see the path that's highlighted is the optimal route, right? So that is the setup here. And we have the start to end. So shortest path calculation. And we're going to loop through all these items in this shortest path -1. So if we go from shortest path to the end, it will take us all the way to the end. And we go back 1 just to get the last position, okay? So there's a city map. Start equals start and end equals end, or source equals start and target equals end, right? And these are defined actually in the previous problem, right? So start and end over here. I can transfer that down here just so everything is contained in spot, right? Maybe it's a little bit easier to read, but it's going to carry forward because it's preserved in Python's memory. Okay, let me get rid of this Control F thing over here. I don't need that. Okay, so let's go ahead and run it. We have the start to the end, and was there any kind of gotcha or catch over here? I think we're going to visualize this, right? And I like the shortest path. Okay, so we have that, and then use network analysis to solve the problem, and the shortest path from start to end, and we plot it. Okay, so kind of straightforward, a little bit more complex than the previous problem, but nevertheless, it's the same concept to go ahead and solve the problem. Really, instead of just using like 8 or 9 different locations over here, we've increased that to about, what is this, 20, give or take, about 20. Oh, wait, I think 15. I think it's actually 15. And the random point, the random starting point, or the starting point, the origin is going to be random. Okay, so over here, we have this start and end. Okay, start and end. Let me delete that. I don't think we actually need that over here. Let me get rid of that. So the start and end is defined here. Okay, Control Enter. So this is the simplest example from home to school and then the park. That's 9 kilometers, right? But let's say again, when we turn on the Google algorithm, it doesn't know if we're closer to park, supermarket, school, hospital, mall, home, and where do we need to go to the destination, okay? So this is a little bit more arbitrary random, but again, the solution is anything but random. The solution is going to be the optimal distance to travel, right? So you have to go from the airport to the office. That is a distance of 4 kilometers. If we look here, airport to office, I'm going to have to zoom in a little bit because this is kind of tiny, but you can see that small red line between airport and office. That's 4. Cumulative distance is 4, so cumulative distance traveled is 4 at this point. We go from the office to the park, that is another 4. Okay, so 4 plus 4 is 8. And then park to mall, we can see park to mall is 6, so 8 plus 6 is 14, and we have the shortest destination here from the airport to the office to the park to the mall. That is going to be the shortest distance that we travel. If I hit Control Enter again, we're going to see a different scenario played out here. Okay, now we go from shortest path from museum to cafe. Okay, so we go from museum to bakery. So over here, museum to bakery, that's 5. Bakery to home, that is another 5. So we have 10. Cumulative distance is 10. So museum to bakery, bakery to home is 5. Home to cafe is 10. So we have 10 plus 10, that's 20. Total distance traveled, 20 kilometers. Okay, and again, this is kind of a randomized scenario because when you turn on Google Maps, Google doesn't know where you are, right? Until you log in and you get oriented and they say, okay, you're closer to the museum, or you're closer to the bakery, or you're closer to home, or you're closer to the cafe. But a priori, or before you log into Google Maps, they don't know where you are, right? Like you have to initiate the request to Google Maps, then it's going to start to plan your route once it has the origin and destination. So that's what this scenario represents. Rather than you playing out everything at the beginning, where am I now and where do I need to go? This is kind of like a random scenario where Google Maps has to figure out where you are and has to plan the route based on the optimal shortest distance to get there, right? Okay, so now we can look at a few more scenarios. Hopefully that makes sense. If not, spend a little time with the code. I'm going to share all this code with you so you can use it at your leisure. You'll have it as long as you need it. You don't have to take notes and try to copy this down. Use a pencil or paper. Okay, I'm going to give all this stuff to you. So just take a little time, immerse yourself in the problem, and try to figure out what's going on. And then, of course, change some of these inputs, change the weights, change the parameters for each of these simulations that we're running through, and you're going to see what the impact is or what the outcome is, either one, right? So the first one was pretty straightforward. That's about as simple as it gets. This one is a little bit more random starting, so a little bit more arbitrary, but once you start the service, the Google Maps service, it's going to become oriented, figure out where you are, and help you get to where you need to be. So, and there's more nodes and there's more weight. So it's a little bit more complex, but same exact concept, right? So let's add a stopover point, and this is going to come from a user input. So again, we have the list of origins and destinations or whatever, like beginning, end, latitude, longitude, coordinates. I'm not actually using lat and long coordinates in this example, but that would be a little bit more complicated. We're going to keep it as simple as we can, right? This is a simplified example of how to use Google Maps, so let's keep it simple at this point. But if you're into all that latitude, longitude, coordinate calculation or analysis, by all means, check out some of my other videos on this channel. I've got a bunch that speak specifically to those topics, okay? So let me go ahead and hit Control-Enter here and run the code. Control-Enter runs it. And again, we're going to create a stopover point, and this is going to come from the user. So we have stop options right here. Okay, so it could be a bunch of different places where we're stopping. And this is going to be pulled in from the user right here. So we have mall, school, park, supermarket, coffee shop, pizza place, and gym. That's what these represent right here. Okay, and you can see these stopover choices represented down here too. So we can pick up a stopover point, and these are going to be represented by numbers. So it's very easy to enter 1 through 7. Just input the number and hit enter. If you had to spell out coffee and you misspell it, COOFFEE shop, or if you put a space between there, it's not going to identify that, right? So like Google Maps will take the input where you just click something, or they simplify it so you just have to input one item on the phone. I'm trying to represent that same thing too, so I'm going to just enter a number rather than spell it out. A number is a number. If you start spelling park, you could fat finger key, and it's just a lot easier to make a mistake. And then the algorithm is probably going to crash. You can handle a mistake gracefully, of course, but it's not going to help you get from the origin to the destination, right? So we're going to try to keep this as simple as possible and just add an identifier rather than ask the user to input something on the keyboard by typing out or spelling out the whole word, right? Or the combination of words, whatever this is. So I'm going to hit enter. So we're going from the start to the end, and we're going to stop at the park. So I hit enter, and it goes ahead and plans the route for us. So we're going, let's see, we're going from the office to school. Okay, so from office to school, that is 2 units or 2 meters, 2 kilometers, office to school. Then we have to go from the school to the park. So that's another 6. So 6 plus 2 is 8. From the park back to school, that's another 6. So we travel a total of 14 kilometers. And then from the school to the home, that's 3. So 17 kilometers have been traveled on this path. Okay, and this is the optimal solution. And if you need to go from office to school to park, and then you go from park to stadium, that's 8. So already that's longer. That's not going to meet the request or meet the constraint for the shortest route. If you go from park to stadium, you actually only have 2 choices, from park to school or park to stadium. Stadium is 2 units longer, or 2 kilometers longer. So clearly that's not a solution. Office to school, school to park, park back to school, and park to home is the best solution. And notice you can't go from park to home. The roads just don't go that way, right? So you can't go there if the roads don't go there. We're not flying, we're driving a car, or this could be a bike, this could even be walking, but we have to follow a predefined route, which is going to be a road or a sidewalk or something like that, right? So this is a minimal distance traveled to get from point A to point B with a couple intermediate stops on the way. And if we want to look at one more example, we can certainly do that. I can hit Control-Enter and rerun this. Control-Enter. Now let's say we're going to stop at a pizza place. So that's number 6. Again, we're not going to spell it. We're just going to identify it with an ID. So we're going to have 6. Go in there. We go from, let's say we begin at the office, go to pizza place. Okay, so office to pizza place, that's 5. Back to the office. Or no, straight to home. We don't have to go back to the office, right? So office to pizza place and pizza place to home. So that's even more efficient. So 5 plus 6 is 11. 11 kilometers to go from the office to the pizza place. Let's see, from office to home. If you look close from office to home, I think it's 2. No, I guess office to home isn't even an option, so we can't go there, right? The roads just don't go there. The car won't travel off the road unless we're in a 4x4 and we're going like on some back road or off road or something like that. But this scenario is following predefined routes or streets or highways or something like that, right? So you have to follow the street and the minimum path to get from point A to point B with one stopover is 11 kilometers, right? So let's look at another example here. Increased traffic weights. So if there's a lot of traffic in one area and the shortest distance by kilometers isn't feasible just because of the density of traffic, we can take an alternate route and get home quicker even though we travel further, okay? So that's what this scenario is looking at here. We can add the weight between school and office and add 50. Basically, we're multiplying by 50. So this is it's called a penalty. We're assigning a penalty to this optimal route, telling the algorithm, okay, there's a lot of traffic on this route. We can't take the route. Or maybe the street is closed down because of construction. There's some kind of impediment. There's a blocker here. We can't take the shortest route. We have to find an alternate route. So Google Maps is going to go ahead and do the lift for us and find an alternate route that is close to a shortest route, but obviously it's not going to be the absolute shortest route because there's a blocker or some kind of impediment, or there's a penalty assigned to this solution right here. So hit Control Enter. The shortest rerouted route due to traffic is office to coffee shop to home. So if we look at the map, office to coffee shop to home, so that is 6 units, and it didn't actually measure it for us. I didn't tell it to measure it, but if you look here, the school to office is looking here 2. It looks like 2, so it will be shorter, right? If you look at the distance between school and office, it does look a little bit shorter, but we're saying there's a penalty assigned here, right? So we can't really take that route. There's too much traffic. Maybe the road is totally shut down due to construction. Whatever the case is, we're going from office to coffee shop to home, and office to coffee shop to home looks like 6 units. I didn't calculate it here, but it looks like approximately 6 units. And school to office to home, I think, is also 6 units. But remember, you can't go between school and office. There is some kind of blocker over there or some type of impediment. So that is off the table. We have to take an alternate route. We're going from office to coffee shop to home. So that's it, guys. I think we have 2 more scenarios. Okay, let's keep at it here. We're doing good. Almost done. So we have scenic routes. We have a lake view where we have home park hospital, home school park hospital, home mall supermarket hospital. So 3 different routes. This is one scenic route. This is another scenic route, and then a third. Okay, so you have 3 options for scenic routes. I'm sure you've seen this in Google Maps. You can take a scenic route as one option. That's one thing you can choose, right? And if you choose River Road, it's going to assign this this sort of order of transactions into this dictionary. This is dictionary. You can tell with the curly brackets here, and you have the key and then the values. You always have a key separated by a colon. Here's the values. So it's a dictionary with a couple of lists, right? Anything with the square bracket is a list. So we're going to select River Road, Control Enter to print it, and we're going to go home, mall, supermarket, hospital. And that's exactly what you see here. Okay, so that's a scenic route. If you want a lake view, you can certainly do lake view. I will copy and paste that. I'm a big fan of copy and pasting. I don't like typing because that finger key is very easy. So if you copy and paste, it's harder to make a mistake. So if you pick this, home park hospital is the route. And again, like, you don't really see under the hood that this is happening on Google Maps. You would just click it on your phone. So take me to Lakeview, Forest Route, or River Road, and Google Maps does this behind the scenes, plans a route, and then gets you from point A to point B in the optimal time, probably, if there's not too much traffic, and the optimal distance, again, if there's not too much traffic. If there's a lot of traffic on the scenic route, then you'll probably be rerouted, right? So this type of scenario is going to come into play next, right? This would be step 1. This would be step 2, right? If you encounter traffic. And I think this is the final scenario here. Let's say we want a toll-free road, right? Because we're cheap and we don't want to pay for tolls. I've seen people do this, even though it's like whatever, 50 cents or a dollar for the toll. Some people just don't want to pay the toll and will take an alternate route, and it can be much longer. Maybe it's more scenic, but you can save 50 cents, right? So you're still better off somehow. That's some people's reasoning. I don't know if I subscribe to that, but anyways, so let's say we want the toll-free route, and these are items on the toll roads, right? Mall to office or supermarket to pizza place. So if we want to avoid those, we can take a toll-free route and hit Control Enter to run the logic. Toll roads has a penalty. Identify toll roads. Oh, okay, I think this is actually a comment here that was supposed to be commented out. Okay, so here's the toll-free route office to coffee shop to home. And I guess if we're going office to coffee shop to home, there is some kind of weight assigned to the toll roads. Oh, I see. Okay, yeah. So I did this code a couple days ago. I'm just doing the narrative for this whole thing today. So that's how it was set up. Toll roads have mall and office combinations. Okay, so that would be a tuple, and this would be the other tuple. So these are considered toll roads, supermarket, and pizza place, or mall and office or toll roads. We want to try to avoid that. So we're going to office, coffee shop, and home. We're avoiding the mall, the supermarket, and the pizza place, but we still have to get home, right? So that's still the destination. That is not negotiable, and we can't change that. But we don't have to go to the mall. We don't have to go to the supermarket, and we don't have to go to the pizza place if these are on the toll roads. And we're telling Google Maps, let's avoid the toll roads at all costs. It's only going to be 50 cents, but you know what? Maybe we're cheap, and for whatever reason, just don't want to pay. Bottom line, don't want to pay. This is an alternate way for you to get home, and you avoid the tolls. So that's it, guys. I'm going to wrap it up here. Hopefully this was insightful and informative and useful. I'm going to save the code for you and upload that when I save this file today. Look for the HTML file when I post a video, and you'll have everything you need. And again, go through the code at your leisure. Take your time, change a few items over here in these different scenarios. And when you make changes, see what the impact is, see what the outcome is. And that's the best way to learn. Really get your hands into it. Play around a little bit, make these changes. If you read the stuff in the book, that's one way to learn, but it's a little bit more passive. I like this way of learning. It's more active, it's more engaging. It really forces you to get into the code, make some changes, and see what kind of impact that has. Okay, so that's pretty much it. I'm going to wrap it up here, and I will see you guys in the next video. Take care. Bye. Hey there, everyone. Welcome to my channel. My name is Ryan Schul. So in the narrative today, I want to discuss about how we can build a generative RAG system, and we're going to use Python, of course, to do all the work. So what is RAG? You hear about this RAG here and there and everywhere. It's getting a lot of momentum. It's really showing up in the news a lot more these days than even like a few months ago or 6 months ago or whatever. Basically, it's an acronym for Retrieval Augmented Generation. So this is this system that works within an LLM framework that basically retrieves relevant facts from a knowledge store. This can be documents, tables, APIs, whatever source of data you have. It can be anything, right? Think about Excel spreadsheets, text files, CSV files, whatever it is. It can go ahead and fetch that data and pull it back, chunk the content. Okay, so it looks at this in chunks or in bits and like digestible pieces of information, almost like a person would look at it, right? You can't just dump a whole ton of data into a computer and expect it to understand everything. It feeds in chunk by chunk by chunk by chunk, just like a human reads it, right? If you give a person a book and say, okay, read the book, you're gonna have to read page by page, right? You can summarize, you can speed read, but you can't just like take the cover, take the book, flip it on its upside down so it's on its cover, and then say I read the book. Like that, that's not going to work, right? So you have to read chunk by chunk, and the computer has to do the same thing. So go through and just iteratively read all this data. You consume it, you can learn it. So there's queries that run, that fetches the data. They have to expand, rewrite the questions, retrieve the top number of passages that matches what you're looking for. It could be a summary, it could be a request. You could have some kind of, you could say, give me a recommendation for something, right? So it has to understand what is being done, and it returns the top K or N would be number, short for number, of passages, right? It packs those as snippets or chunks into a prompt, and then the LLM generates a response and creates citations for the most part, not always, but you see more and more citations just so the tool isn't just going back and saying, okay, this is my response to your request. Like it actually comes back and validates it too, right? So you can look up and make claims against these citations, right? So why do we even use that? Basically, it keeps answers current, right? So some LLMs actually become obsolete very quickly if new content comes out today or yesterday or 2 days ago. That might not necessarily be in an LLM system, and it probably won't be, right? Because the learning stops at a certain point, and then after a while they'll pick up the learning again, but it's not continuously learning like a person. It doesn't learn new things every single day, right? But with a RAG system, it is much more up to speed, much more real time based than these LLMs are, right? So for summaries, for comparisons, for decision making, right, it's very useful for that. For key design choices, again, chunking the data and digesting it and retrieving it, and running encoders and ranking and diversification of responses, making sure that the response is coherent and it makes sense, right? Generating those citations, so that's very important too. Fact checking. We set up guardrails for safety, right? So the LLM and the RAG doesn't go way off down some rabbit hole or something and come back with some weird response that's completely irrelevant, right? So guardrails help too. Common pitfalls are wrong chunks, wrong sizes of chunks. I've run into this problem before. Outdated indices, freshness of the response, right? Ungrounded or unfounded responses. So again, citations are key, right? And RAGs will help with those. So you'll get data that is current, that has citations for validation, right? And it tends to not hallucinate. With some of these LLMs, it seems to be very, very apologetic, and you can make any kind of request, and the LLM jumps up and says, "Oh, I'm going to help you with this. I'm going to help you with that." But sometimes the requests are really not very meaningful, and sometimes just very, very completely wrong, right? But the RAG tends not to do this. It tends to be very relevant, very fresh, and again, the citations are there, right? So you can validate what you're looking at. It's not just like, okay, it kind of feels right, it kind of looks right. Like, no, this is right, and this is why it's correct. So I'm not actually going to run this in most of my notebooks. I run these things. I had all these files sitting in this folder on my desktop. So here's my desktop right here. I had financial statements. I had these files right here, 2004 annual report, proxy statement, balance sheet example, management report, and then organization statement of financial income and expense.pdf. So I had these five. I wasn't even going to create this video. I kind of like did the whole thing and then put it on the back burner, forgot about it, and then deleted the files in the desktop. And then I just found this thing a couple of days ago. So I don't want to go back and research for these files, but let's just pretend it's on my desktop. I'm just not going to go ahead and run the whole thing. But if you copy and paste this code, I'm going to share all this code with you in your Jupyter notebook. You copy paste that, and you have this API key from ChatGPT. You need the API key. So you can get your key if you go to this link right here, Control C and Control V. And I'm not sure if I logged in through this browser or another browser. Yeah, I logged in through another browser. So it doesn't matter. I guarantee that is the link. You'll have to go ahead and get a key for yourself, download that, and put that onto your desktop or wherever you want to save it, okay? And name the file, right? So you have to have the key. Once the key is generated, it's going to be a long key. It's going to be at least 100 characters long. Put that into a text file. Name the text file whatever you want. Mine is called OpenAI_key.txt. Put that in a place that you can read it. It doesn't matter if it's on your desktop or somewhere else. I like to put these things on my desktop. Put these PDF files. Just go ahead and grab 4 or 5 from the web. Put those into a folder, again, on your desktop or wherever. It doesn't matter. And go ahead and run the code. You can see right here, we have PDF loader, recursive character text splitter. So this was going to open up these 5 PDFs on my desktop. Again, I'm not running this thing because it's going to crash. But because it's only going to crash because I don't have the files anymore because I deleted the files, right? I was not going to make this video, but just a half hour ago, I decided to make the video for you guys. So go ahead, download a couple PDFs, put this in a folder, get your API key, put it right here, and I guarantee this is going to work. It's going to open up all the PDF files, scan through each one, send that to ChatGPT, okay? And it's going to run a RAG process. So it's going to take the ChatGPT response and kind of refine it and just make it more into a RAG, retrieval augmented generation, and make sure that there's no hallucination, make sure that the data is current, make sure the data is relevant, and that any citations or any kind of like proof of the response has been generated as well. So you could say, okay, here's the response and it's correct because of this, okay? So here's the chunk size. Remember I said that this thing runs in chunks. If you have a bigger chunk size, it can take more information, but if the chunk size is too big, it's going to crash on you, right? So if the chunk size is smaller, an 800 should be completely fine for what you're doing. If it's smaller, it'll take longer to read because you just have more, you just have less data going through those pipes, right? If the chunk is smaller, if it's bigger, it's going to be a lot faster. But again, too big, it's just going to fall down because it can't handle the volume of data that's coming through. So that's it. We chunk the data. We have the text splitter. So that's taking everything in all 5 PDFs, splitting it up, chopping it, delivering that to the LLM, goes through the RAG, sort of gets cleaned up a little bit. Now we have a local searchable vector database that contains all the data for all the PDFs split into semantic chunks, okay? So the vector store is basically a searchable vector database, which is very fast, much faster than a standard SQL database. And it allows ChatGPT to go in and just almost instantaneously retrieve all the paragraphs from those PDFs, right? Feed those into the ChatGPT converter or system or whatever you want to call this thing. Get accurate, grounded answers with citations, right? So it just prints out a record of each PDF as it's being read into this chunk, this vector data store. So at this point, we are running ChatGPT 4. I found this one to be very affordable. Right? You do have to pay a small premium for these types of things, right? But it's just pennies. It's tinies of pennies for thousands of chunks. You'd have to look online. I don't know what the pricing is offhand. GPT, I see here. Pricing plans. You can just Google this. This is pretty simple, right? And it does change a little bit, but these things are pretty cheap. So here it says GPT Plus is $20 a month for advanced features, and ChatGPT for businesses is $20 to $25. There is a ChatGPT Pro for $200. I guarantee you don't need that. All you need is this $20 a month tool, and you can cancel anytime. They bill your credit card, right? So some of these things are totally free. If you use the free version of ChatGPT, there's no charge for that. But if you're using these RAG systems and if you're making requests to ChatGPT, you're going to have to pay a small fee for that. It's less than $1 a day, totally worth it. So that's it. So here's the question that I'm asking. Once all 5 PDF, all the contents of those 5 PDFs are sent into the vector database, right? What is the main risk clauses mentioned in the contracts? So I'm kind of trying to trick the system a little bit because these aren't actually contracts. This is an annual report. This is a proxy statement. This is a balance sheet, right? But it's smart enough to say, okay, no, it's not really a contract per se, but you're talking about main risk. So I can work with that. It's almost going to ignore this and mentioned is nice to have. You don't need that. You don't need in the, right? And all you need is like the main risk clauses, right? That's all you need. That's what it's going to focus on. And then it's going to print the answer and the source documents. So we go down here. Here's a little message that pops up. We can ignore that. So here's the answer right here. The main risk clauses mentioned in the contract include if the company fails to meet the customer's expectations or fixed milestones. So that sounds like risk, right? The customer could terminate their contract with the company or claim that the company breached their obligation. Sounds like a risk, right? So it basically just takes this main risk and it knows that this is a clause. So there's something here that's being mentioned that needs to be explored. It needs to be exposed, right? So it's focusing probably just on risk. You can probably just say main risk or just risk. What is risk? And it knows based on the content of that vector database that's been created, right? Which is consistent or which consists of those 5 PDF files. It knows what to do. It's a pretty smart thing. So the second risk here is legal risk exposure, such as class action, regulatory investigations, can impair the company's reputation. So that's a risk, right? And already knows that. The company's insurance policies may not cover losses incurred if their systems data are compromised. That sounds like a risk, right? It's pretty smart and knows what to do. This RAG is really performing pretty well at this point. There's a risk that the company's insurance policies may not continue to be available. Okay, so it's now the risk of the company's risk exposure related to changes in interest rates and foreign currency exchange. That's definitely a risk. The participant's willful failure to perform his or her responsibilities are a violation. The participant's commission of any act or fraud, investment dishonesty, or other willful misconduct sounds like a risk. Unauthorized use of disclosure by the participant of any proprietary information or trade secrets, that's definitely risky behavior right there, risky business. And the participant's material breach of any of his or her obligations under any agreement with the company, including restrictive covenants, right? So it printed out the sources for each one of these. That's nice too. And then optional here is summarize each document from each lang chain, summarize reports, load summary chain. So we have summary chain right here. And this is the summary right here. For all 5 of these PDFs, it comes up with 2004 PDF solution reported, strong performance, 179.5 million. So we're switching from risks to a summary report, right? So basically, it's summarizing the contents of those 5 files. And it goes on to say the company recently acquired SecureWise, a remote connection solution for semiconductor equipment. Okay. It's a summary and insert changes, including the declaration of Moore's Law, PDF solutions, and AI maintained robust data protection. The company also filed all necessary reports with the US SEC, complying with SEC Act 1934. Okay, so that is pretty cool. And I'm not going to do this for obvious reasons. The files are missing. But if you wanted to give it more information, you can just say, please give me 5 PA range. And so you can give it more instructions. It's going to follow the instructions because this RAG system is so smart. It's just going to understand what the ask is, and it's going to go ahead and deliver what you requested, right? And it just gets back to you with whatever you need. Okay, so that's it. That is pretty much what I wanted to demo here. Pretty short video today. It's not going to be a huge one. Thanks for future consideration here. Add multimodal intelligence, improve document Q&A. That's question answering. That's what I just did there. I added a little more context over here. So I think that is a step in the right direction. Visualization and reporting. Yeah, obviously I didn't do any here. That might be nice to have. I don't know if you really need it for a summary of 5 documents. Maybe not. Productionizing it. So this is taking this and putting it into an environment that's running 24/7. So some kind of web-based AWS, Azure, GCP, something like that, making it available to people on your team or people in your department. That's productionizing it and deploying the model, right? And then further recommendations, if you're ready to level this up to the next step, start with this roadmap. Summarize all PDFs side by side, add PDF tables extraction, deploy a basic chatbot in Streamlit. Maybe I'll create a video on that. That sounds pretty interesting. Use ChatGPT to simulate what-if questions and log queries and answers for a feedback loop. So that's it, guys. Let me save this short one today, just like I promised, right? And I will put that in an HTML file, and I will share all my code here with you guys so you have everything you need. The only thing you're going to have to do is go ahead and create an account right over here. So go to this link, create the account, go ahead and get a few PDFs, put that in a folder of your choosing. And when you get your account set up, you will have a big API key. This is going to be a monster, probably 100 characters, all kinds of random texts and alphanumeric characters and stuff like that. So take that, save it down. That is a good practice. You can actually put the API key directly into your Jupyter notebook, but then you can't share it with anybody, and you're exposing your specific key that is registered to you. Something that's personal and confidential, you're sharing that with other people. You don't want to do that, right? So that's pretty straightforward, I think. So that's it, guys. I'm going to wrap it up. I'll share the code when I share the video. I'll post that later today, and I'm going to end it here. So I'm under 18 minutes. This is a short one. I'm feeling good about this. Most of these drag on, and I like these short ones, to tell you the truth. I like these short ones. Okay, I'm gonna stop here. Thanks for your time. Thanks for sticking through to the end, and I will see you when I post the next video, which should be soon. Bye for now. Hey there, everyone. Welcome to my channel. My name is Ryan Schubel. So in the narrative today, I want to look at different types of plotly charts, and we are going to look at oil consumption of different countries. So I found this data online. Here's the link. I'll share the link with you guys. Okay, I'll put it in the Jupyter notebook. And of course, I'll share all the code with you too. So I saw this online. I thought it was kind of interesting. You have United States, right? Basically North America. Asia is over here. This is Europe, right? South America, and so on and so forth. So they break this down into different categories. Here's the data. You can copy and paste the data from this site. That's exactly what I did. And then you have the breakdown here of the ranking, the country millions of barrels per day. So I'm abbreviating that as MBPD, okay? And then share of global totals. So the United States is definitely number one, 18.7% of the total in 19 million barrels per day. And down here in last place is Taiwan, and that's 0.8 million barrels per day, and that's 8%. Okay, so that's the source of the data. So I went ahead and added in the standard libraries here to help me to do all the work, right? These libraries do most of the lift for everything. So we have all the rows. United States is first, Taiwan is last. Here's the 19 million barrels per day, MBPD, and this is 0.8 and 8%, right? So that is kind of the setup here. That's what we're looking at. And then we're looking at different regions. I plotted these into different regions. So United States of America, Brazil, America, Germany is Europe, and so on and so forth. So it's pretty straightforward. If I hit Control Enter to run this, you can see what the data frame looks like. Okay, so this is exactly what we saw in the original data set. We have the country name, MBPD, millions of barrels per day, share percentage, country, and region, right? And if we just do a quick sanity check, if the first and the last are the same, then I think everything else in between is going to be the same. So we see US 19, 18.7. Let me get rid of this thing. Not sure what that is. US 19, 18.7%. And then down here in last place, we have Iraq and then Taiwan. So 0.9, 0.9, 0.8, 0.8. And if we go over here, that's what we see in the original data, 0.9, 0.9, 0.8, 0.8. Okay, so I think everything is set up pretty nice. Control Enter to run this. The first thing I'm going to look at here is a tree map. So these tree maps come from Plotly. I think it's pretty cool. It shows you like the overall region and the breakdown, and then the percent of MBPD, millions of barrels per day, by the region, right? So here's Asia Pacific. So MBPD total is 35.3. That's nice. It aggregates everything for us right there, right? And then you can see the breakdown here. China is 16.4, and Taiwan is the smallest with 0.8. So America is the same thing. Total is 25. It's hard to read, 25.8 MBPD. I think that's what I'm looking at here. 19%. Mexico is ranked 12 and 1.9. And if we look over here, Mexico is, where is it? Oh yeah, 1.9, 0.8. Okay, so everything pretty much ties out. So I like these tree maps. Pretty nice how you can orchestrate everything and arrange everything by the grouping, by the region, and then see the details of the breakdown. Here's another view. If I hit Control Enter, you can add in all kinds of different shades of colors. This is greens. Everything is plural with this. Not sure why, but that's how they do that. Wait, GR, you have to spell it right? That was exactly what you tell it to. So here's greens. I had blues before. If I go back to blues, there's purples too. So Control Y. Wait, why doesn't it go back? Yellows, blues. Okay, so we have different shades of blues. So we saw before Asia Pacific is number one in terms of like overall use of oil. America is number two, but you can see how the square here, or the rectangle, whatever this thing is a little bit bigger because the United States is easily number one, China is number two, but by the region, Asia is actually number one, right? So it shows you like all the details, all the behind the scenes. The darker the color, the bigger the number. I like these these types of charts, it really like kind of pops off the screen, and it looks pretty nice here. Control Enter to run this. So this is called a sunburst chart. These are nice too. You can see easily here. Asia Pacific is number 1 in terms of overall utilization of oil, right? So 35.3. Americas is 25.8. If you go over here, 35.3, 25.8, right? That would be the total sum. And I like how these expand and contract. So you can click on the details and you can see all of the breakdown and how this kind of like flows down to each country, right? And then you can see per country here, 16.4 for China. India is 5.6. If you go back here, same thing, 16.4, 5.6. So you can see the same relative size. You can see kind of like the same details, the same size. That's why it's pretty nice. I like these a lot. So you can see all the details. You can click in and click out and see what's going on at multiple different levels here. So these sunburst charts are pretty nice for these types of things. Here is just a regular bar chart, horizontal bar chart. Again, darker is higher, right? So higher is more utilization. United States is easily number 1, China number 2, India number 3, Taiwan is in last place down here, or maybe first place if you're looking at it from a clean energy type of perspective, right? So these bar charts are pretty nice. This is another way to to represent the data here. So here is a cumulative consumption of petrol and oil, right? So MBPD, again, United States is easily number 1, China's 2, India's 3, Taiwan is down here. It's in last place or first place, depending on your perspective. And you can see cumulatively over time, this sums up to 100%. So of all the oil consumers in the whole world, this gives us 100%. So that is kind of nice here. You can even break this down by region, Control Enter to run this. So you have by regions, so country, US, Brazil, Canada, Mexico. That's exactly what you see up here too. US, Brazil, Canada, Mexico, right? And that's exactly what you see over here. So US, Brazil, Canada, Mexico. So the breakdown is nice. It really depends on your audience, the stakeholders that you're working with, who you're trying to communicate with in the story that you're trying to tell, right? So lots of different charts to communicate the message, right? Here is a global chart. And again, MBPD is million barrels per day. And this is just visually like the entire global chart. And it's very interactive because these are plotly. You can kind of like drag it and move it around. And it'll show you all the details behind this again. So China and US. And I think number 3 is India. I think 3 is India, right? So just a different way of sending a message. I always say a picture is worth 1,000 words. So I think this is a pretty powerful image. These all are, honestly, to tell you the truth. This works. It just depends on what you're trying to do, what you need to accomplish here, right? So we have lots of charts for our storytelling needs. This, again, is MBPD. Darker is more, so you can see United States is easily number 1, China's number 2, India's number 3, and then the smaller countries appear over here. And it's nice, you can click and drag this around and move it around. So very, very visual, very interactive. And I believe this is the last chart that I have in this series. And really, I would encourage you to use your imagination and just jump in and just experiment with this stuff and see what you can do. Try different ideas, like try to be innovative, try to be creative in how you tell your story and how you do your plotting and charting. And you can really do some pretty amazing things right here. So you have a circle chart with a bunch of circles inside of the chart, and everything is grouped by color by region, right? So we have the Americas, Europe is green, Europe, West Asia is brown, Middle East is red, Asia Pacific is orange, and then other is gray. I don't think we have any others over here, but I like how you can click on these plotly charts and interact with them, right? And see all the details behind all the charts here, right? So this is called the tooltip, and it pops up and shows you all the details behind the data here. So kind of cool, kind of neat what you can do with all this stuff. So that's it. Where are we with time now? About 10 minutes, just almost up to 10 minutes. So today's a pretty short one. I just wanted to like demo a few different plotly charts, show you what you can do just with some very basic data. Here is the source of the data, so you can copy and paste this into a web page here, and you can have all the data for yourself, right? You can copy and paste that and trace this back to the source. Okay, here's all the data, and I actually did all this for you right above. So you can put that in your own Jupyter notebook and run it and have everything you need. So that's it, guys. I'm going to wrap it up here. I thought I would just showcase some different plotly charts and show you how to interact with these and how to build these charts. This one right here, the last one, is definitely the most sophisticated, but a lot of these are pretty basic. If you look at it, you just have the data frame, locations, is coming from country. The location mode is country name. The color is MBPD. That's how we get the colors over here. The hover name is country, and reds and blues, right? Reds and blues, and you have different color schemes that you can try in there, like this. You can put reds in there if you want. Control Enter and rerun it. It's gonna be all red. Here's another color scheme. You really have to Google this stuff and see what all the different characteristics are. So I like this red and blue combination. That's kind of cool. I like that one personally. But yeah, the sky's the limit. You can do all kinds of stuff with this. So I would encourage you to jump in, experiment, see what you can do, try it. Um, copy paste the code into Jupyter, obviously run it, and then make some changes, make some modifications, and that's the best way to learn. It's very interactive, it's very dynamic, it's very meaningful, it's very purposeful, right? But you have to get in there and really kind of get your hands dirty and really play around with it if you're going to learn this stuff, right? So I create all my videos for people to learn and to just try different things, right? And see where you can go with it, see where you can take it to the next level. I've been doing Python programming for 12 years. At the beginning, I literally knew nothing, like not even the simplest thing. I couldn't even do the most basic thing. And now I can do quite a lot. And I'm sure there's other things I'll learn over time. I'm always learning new things every day. And I would encourage you to do the same. So just try to see where you can go with it. Run some experiments, see what the outcome is, and let me know in the comment section how far you can get with it. If you get stuck or something, let me know about that. Google it, try ChatGPT. That's a great resource as well. And just have fun with this stuff, right? It's all about learning, growing, and developing, guys. So that's it. I'm at 10 minutes. I'm at 12 minutes, and I'm up to 12. And I said this is going to be a short one. I'm going to keep my promise. So I'm going to wrap it up here. I'll share all the code with you in this Jupyter notebook. When I drop the video, I'll do that later today. And I will see you when I put out the next video, which should be pretty soon. Thanks, guys. Take care. See you soon. All right, y'all. Welcome to my channel. My name is Ryan Schewel. This is my analytics channel on YouTube. So in the topic today, I want to talk about New York City's congestion pricing plan and just break that down to show you guys how that works and to try to understand how effective this thing is in terms of making money for NYC, number one, and in terms of cutting down on congestion, right? Cars driving around New York City from about 60th Street south, right? That's how you get tagged and get billed. If you come in at 60th Street, it's actually 59th Street. It's the Queensboro Bridge, and south of that. And does it cut down on pollution emitted around New York City? Okay, so we're going to jump in. So there's a bunch of reasons we want to do this type of analysis. Most likely economic and fiscal impact. I just described that. Even things like revenue generation, right? I touched on that. Cost benefit trade-off, distribution of equity. Okay, that's the shift of money from one group of people to another. Transportation efficiency, reduced congestion, modal shift, environmental benefits. These go without saying, right? That's pretty obvious. Air quality improvements, climate targets, and so on and so forth. So let me try to explain how this thing works. Basically, NYC's congestion pricing plan charges drivers a fee, right? You have to pay a fee if you enter Manhattan below 60th Street on basically like Queensboro Bridge, or if you come through, I think, what is it, the Holland Tunnel or the Lincoln Tunnel, something like that, right? I think Brooklyn Bridge has this thing. I'm not exactly sure if it's on all the bridges. Manhattan Bridge, I think, has this. I don't know like all the details of everything. I'm just looking at the analytics behind this thing. But I think all these bridges south of 60th Street, and I think the two tunnels on the west side have this thing too. So the peak hours go from 5 a.m. to 9 p.m. and on weekends 9 a.m. to 9 p.m. Off peak hours are the rest of that, right? When tolls are 75% cheaper, but you pay a premium when you come in during the peak commute times, right? That's when people want to come into the city, either commuting or tourists coming into the city to check out stuff. So you pay a premium for that, right? So motorcycles pay a different rate, small trucks pay a different rate, and large trucks pay even a totally different rate, right? So it's all different pricing tiers or ladders or whatever they're called. So what else? I've got some notes over here. You can check this out. I don't have to spoon feed this to everybody, but basically I want to go ahead and get started with the analysis at this point. So looking at 5 a.m. to 9 p.m. for the weekdays and 9 a.m. to 9 p.m. for the weekends, right? And this is the congestion pricing spike. That's when the fees go up, and that's when people pay more money for this, okay? For the benefit of coming into New York City if you're driving. Now, if you take public transit, like subway, buses, I think there's no impact whatsoever to all these commuters, okay? So it's just this deterrent for people driving cars and motorcycles and small trucks and stuff like that, right? So we have different dates, before and after dates I'm looking at, and of course the time periods. Is this a weekday? Is this a weekend? Things like that, right? So we're going to consider all these different different like levels of criteria or whatever you want to call it, right? And if you are on the path to come into Manhattan during these hours and during these days, then you get pegged with this congestion pricing fee, right? You get kind of like hit with that, right? So we have the baseline entry level. I'm going to create a couple basic functions here for passenger vehicles, basically motorcycles, small trucks, large trucks, and taxi cabs, right? So I have a small function to handle all of these different types of vehicles, and I have another small function over here to track the toll amount, okay? So if you're in a passenger vehicle, like I just mentioned, you pay one fee, motorcycle pays another, small truck pays another, and so on and so forth. So we're trying to capture all these different criteria here. We're simulating the day. Again, is this weekday? Is this weekend? What time of the day? You're either going to get hit with the fee for the congestion pricing or not, right? If you bypass that because you come in at these off hours, and these are really off hours. I mean, if you look at this, what's the time range here? 5 a.m. to 9 p.m. So that's most of the day, right? If you're coming into New York City after 9 p.m., you avoid it. But honestly, how many people are going to fall into that bucket? Probably not too many. Maybe if you're going out for a late night meal or nightclub, right? People coming out for the nightclubs, but that's a pretty small overall clientele, right? So most of these people are getting slammed with this congestion pricing fee, and there's just no ways around it, right? So at this point, I've got a couple of different functions that help me customize which vehicles are coming in, which days, which hours, things like that. I create a list over here called rows. Control F will help me find out where the list goes down here, and this is pretty similar. If you've seen my other videos, I've done this probably at this point hundreds of times, right? Create a list, and then you append all the data that you collect from above. So above, I'm getting the day of the week, the day name, just so I don't have to look at 0, 1, 2, 3, 4, 5, 6. That's how Python interprets it. But that's helpful, but I also want to know the day name. Is this Monday, Tuesday, Wednesday, so on and so forth. Weekend, we have a flag for that. The period during the day, the hour of the day, is this peak, right? So it's a Boolean thing. Yes or no, it's one or the other. It can't be both, and it can't be neither. The toll charged, right? The speed of the vehicle coming into the city, and then the average speed. I'm going to calculate the average speeds of cars around the city to try to determine if there's fewer cars because of this congestion pricing, because it's a deterrent for people to drive in New York City. More people are going to take the bus and subways now because it's more expensive to drive your own car. Is the average vehicle speed around New York City actually faster after implementing this congestion pricing plan, or is it about the same, or is it actually slower? So we're going to take a look at that. And then the revenue collected, right? So all of this gets appended to that data frame, appended to the list. I create a list over here, right? With the square brackets, I have the list. I append all of the different elements to the list. These are the different data points I'm analyzing, and then I'm going to go ahead and convert the list into a data frame. So I have everything in a very structured way laid out before me, okay? So when I run the code, you can see what it's doing. It's going to create this nice looking data frame and capture all these different metrics or different features that I just described, right? So you can see that right here. So everything looks pretty good at this point. So let's go ahead and look at the revenue that this system is generating and any changes before implementation of the congestion pricing plan and after. Okay, I want to see what's going on before and after, and then make a comparison before or after what's changed here. So Control Enter to run this, and you can just see it's pretty basic over here. I'm looking at the average number of entries, so cars coming into the city before, after, right? Looking at averages, and honestly, like in the analytics world, you have a lot of different mathematical equations and different functions, and you can do hundreds of really cool different analytical exercises, right? But by and far, most of the time you're looking at counts, you're looking at averages, and you're looking at sums, okay? So you can go through all this data and analyze it to your heart's content. You can do as much as you want or as little as you want. But by and far, most of the time, we're just looking at an average, which is a mean, a count, counting number of cars, counting the cars or motorcycles coming to New York City, what have you, and looking at the sum, what is the total revenue collected for all these vehicles coming into New York City. So look, and just we have three metrics that we capture nearly everything. The mean is the average, the count is the number of cars, and the sum is the total number of dollars collected after this project was put in place. So here we have a basic breakdown here. So large trucks after and before, decrease of 13%. So across the board here, the numbers have declined, okay? Small trucks, those are fewer. These are probably delivery trucks for restaurants or, some kind of supplies, raw materials for some vendor or something. Passenger cars, 984 million. After, before, 1.12 million, 984,000. Here, motorcycles, 80,000, 84 before, and 746 taxis, 779 taxis before. So all over the place, the delta has decreased after the congestion pricing was put into place, and that's pretty telling right there. So you can see that's cutting down on traffic. So that was almost a given. I can tell it's going to cut down on traffic. It's not going to increase. That doesn't make any sense. You charge people more money and now more cars are driving. No, it's cutting down on traffic. We can see that, and I'll have a summary description at the end reiterating that same point. So it's going to cut down on parts per million of pollutions that are expelled into the atmosphere, right? So this is pollution coming from exhaust pipes. That is going to decrease. If the cars are fewer, then the pollution is going to be less, and it's going to generate more money for New York City. So we're only halfway through the analysis. I already know how this thing is going to go. So down here, I'm looking at month revenue US dollars, and then cumulative revenue over time. So this is January, 749K, 1.52 million, 2.36, 3.19, 4.05, 4.8 million. If I'm looking at that right, there's 3 and 3, 48 million. Okay, so it's making a lot of money in the first 6 months. This thing was implemented in 2025. The system generated almost $50 million in revenue, right? 48.7 million in revenue. Period. After and before is this peak time? Yes, no, and yes down here. So 320,000 cars, 458. I'm sorry, these are averages, right? So looking at the averages, 320 is peak true. This actually went up, so that's kind of interesting. This went up, but the speed miles, average speed miles per hour went down, so that makes sense, right? There's more cars driving around New York City. The average speed has to decrease here. You have fewer cars, more speed, right? And before, 340,000. So it did go down a little bit, right? Is this peak time? No, the number of cars went from 340 on average to 320 on average. And before, congestion pricing 513, before 458 after, and this is peak hours, and this is peak hours. So I think that was defined as 5 a.m. to 9 p.m. So it captures most of the cars for most of the day, or across all the days, all the weeks, right? Okay, so as we can see beyond a reasonable doubt that the the system is working, right? Cutting down on cars, we're going to see just a minute, cuts down on pollution, and it generates quite substantial revenue for New York City, right? So let's look at a quick plot over here just to see visually what's going on. Okay, so here we have the daily congestion Total revenue after implementation. Over here, you can see January 6th, 7th, 8th, 9th, 10th. Revenues are higher, dips on the weekend. Okay, this is January 11th and 12th, and it goes over here for about 6 months, right? We're looking at the first 6 months of 2025. And here we have, again, weekdays, so June 23rd to June 27th. There's a dip down here on June 28th and June 29th. So those must be Saturdays and Sundays. If I go over here, then June, here's the 28th and here's the 29th, just as I expected. So Saturday and Sunday dips down. You're still making pretty decent revenue, right? New York City is still getting 196K, 195K on Sunday. And the weekdays, it's probably a little bit more than 100,000 more weekdays, right? Because weekdays you have the wider gap. What was it, 5 a.m. to 9 p.m. And I think they actually charge slightly higher rates too on the weekdays, right? So that jives and that makes sense. So let's go down and look at these. These are called violin plots. It kind of looks a little bit like a violin. In this case, not really, but if you do have the right distribution of data, it looks very similar to a violin in some cases. So before congestion pricing, you had, what is this telling me? Maximum speeds 26 before congestion pricing and minimum 11.14 over here after maximum, or is it 28? So you go from 26 to 28. So the average is a little bit higher after congestion pricing is implemented, and the minimum is a little bit faster too, right? This is just common sense. Fewer cars in New York City, and the average speed overall is faster, right? So you can see the distribution. That's kind of like on the x-axis, that's the width, and then the height is the more like the y-axis, right? So you can see the max and the min over there. So that makes sense. Here's the PM trend before and after. So after is in blue, before is in red. And this is showing me basically, parts per million in terms of particles per million in terms of exhaust fumes, right? So exhaust from the tailpipe getting into the atmosphere in New York City. So it does go down, not huge, but it does go down a little bit. Before is in red. So I'm guessing this is, let's see, June 3rd, 11th, July 1st, and then it dips down. So what happens on September 1st over here? This dips down. Oh, that's 2024. Okay, so that's 2024 after congestion pricing, right? So that's 2025, right? This is before and this is the after over here. And it is lower, right? So the part per million in terms of pollution being emitted from people's exhaust pipes is lower, right? I'll expect a little bit lower than that, but it's a little bit lower, not substantially, but probably enough to make a difference. Okay, so here we're looking at before and after weekday peak category and period. Again, parts per million of pollution. So before pollution, 7.24 parts per million, 7.08 on the weekend. So weekdays a little bit higher. This is more business people commuting into the offices, presumably. Weekends drops down a little bit, 7.08. After congestion pricing drops to 6.95 and 6.82 on the weekend. Again, not a massive change, but you can still see a change in terms of the pollution emitted all across New York City, and it is decreasing. So that's a win. Faster traffic on average, fewer cars, and $48 million in the first 6 months since this system was implemented. So that's good for New York City. It's not necessarily great for yourself and myself as commuters driving in, but it's helping the city. They got a almost $50 million windfall. So here's pollution again, parts per million. So before maximum 12.85, minimum 3.5. Over here it's down a little bit, so about 12.15 and 3.67. And that is before implementation. This is a weekday is on the left, weekend is on the right. So after implementation of the congestion pricing plan, it's down a little bit, 11.92 from 12.85, and then weekends 12.15 to 12.13. So just incrementally lower, not huge, but definitely less pollution flying around New York City. So that is good. Okay, so down here, we're getting kind of towards the end here. We're looking at different vehicles. So passenger, motorcycle, small truck, large truck, and taxi. And then the different rates that they have to pay if this is weekday or weekend. So we're going to try to aggregate all of this together and see what comes out in the mix. And then looking at things like traffic intensity. This again is the pollution, parts per million, 25 being the base case, the most likely case, and um, noise. So this is pollution and this is noise. Okay, so we're going to mix all of this together. Again, put this into a data frame and look at total revenue before and after, revenue boost, minimum daily, after, average daily, and max daily. So like I said before, a lot of these metrics, even if you get into very advanced analytics, a lot of the times it's a sum, it's a count, it's an average, right? So we're going to get the means, min, and max. You can do like 90 to 95% of your work with these. Was it's just 5, right? Sum, count, min, max, um, and some count, min, max, and mean, right? That was the average. With these 5, you can do 95% of your work. Okay, so we end up before revenue, $0. That makes sense. There was nothing coming in. Right after revenue, 48 million in the first 6 months of 2025. So that is a huge windfall. Now we're through October 31st. Today is Halloween 2025. So 10/31/2025. So we're about 10 months into this thing, and I'm going to guess at the end of June, it was up to almost 50 million, probably 75 to 80 million now, maybe closer to 85 million at this point. So at the end of this year, if the middle of the summer was any indicator, at the end of this year, we're going to have about 96 million, close to 100 million in revenue from this congestion pricing. So huge windfall for New York City, less pollution, less traffic, faster, less cars driving around, right? So it's like win, win, win all over the place for NYC. Okay, so again, residents have to bear a brunt of the cost of this thing, right? The 48 million just doesn't come from thin air, like it's coming from people's pockets. But overall, I would say it does motivate me to drive my car less in New York City. I'm very cognizant of that now. Before I wasn't too kind of carefree about it, just driving around wherever. Now I plan my trips a lot more carefully, and I'm taking the subway a lot more. So I think this is basically a good thing. I think it's win-win-win everywhere you look at it. Yes, there's a cost associated with this thing. Of course, it's coming from people's wallets, but I think the overall outcome is positive, and I think New York City is doing the right thing in this case. And I think other cities, I don't even know what offhand I would say. Maybe Boston, San Francisco, Los Angeles, San Francisco, other cities are going to look to NYC as a model for how effective this plan can be. And I think they eventually will implement their own um, pricing mechanisms to reduce congestion. And this is very elastic too, right? Like people just aren't going to spend as much money and not going to drive as much and not going to take their cars into the city. That's the elasticity part of this model here. So you can see that the utilization is decreasing. Number of cars is lower. Pollution is lower. Average speed around New York City is higher, right? So that's win-win-win everywhere you look at it. I think other cities are going to copy this model and implement that in their own backyards, probably in Boston, Chicago, maybe Dallas, LA, San Francisco. I'm just guessing here. I don't know for sure what these guys are doing, but that would be my guess that they're going to take a close look at this and copy the model. I think it's very successful. And that's it, guys. So that's congestion pricing in NYC. And we looked at the elasticity of the model and how people will, follow suit with what the government is telling them to do by means of their pocketbooks, by means of their wallets, right? That's the elasticity part of the model too. So, okay, I think that's good summarization here. I think I covered all the topics I wanted to get to. So that's it. I'm going to wrap it up here. Thanks for your time. I appreciate you guys sticking through to the end. I'm going to drop the video later. I'll share all this code with you so you can copy and paste that into your own environment and run it as is. And you'll have everything you need to do your own analysis. Okay, so there you go, guys. That's my take on it. Let me know what you think in the comments. Go ahead and subscribe to the channel. Helps a lot. Really appreciate that too. Thank you so much. And I will see you guys soon when I drop the next one, which should be probably a couple of days, maybe even later today. Let's see how it goes. Okay, thanks and goodbye. Hey there, everyone. My name is Ryan Schewel. Welcome to my channel. This is all about predictive analytics, data science, machine learning, and things of this nature. Okay, so hopefully you've turned into some of the other topics that I've posted here. I'm coming up to about 200 really soon here. I think I'll hit that mark today. That's what I'm aiming for. So if you've seen any of the others, you know kind of what to expect, right? It's all about predictive analytics. A lot of it is focused on finance, machine learning, deep learning, data science, things like this, right? So I've got a really cool lesson for you today. This is how to understand changes in prices and how that will either stimulate people to make purchases, additional purchases, and increased frequencies of purchases, or discourage people from making purchases if the price is too high. Okay, so this is basic economics, and we're going to look at the elasticity of demand and see how demand changes as price changes. Okay, so if prices are lowered, people buy more items. Okay, this is pretty much common sense. And as the price goes higher and higher, people purchase fewer and fewer of the same items, right? But if you have an item that is being offered at a lower price, you can raise the price to a certain amount, right, and expect people to buy more of that, and it will increase your profit margins. But if you raise the price too much, people are just going to stop purchasing it, right? Now, you see a lot of this today in this high inflationary environment that we're living in. So some of this stuff is pretty painful. Honestly, I go to the grocery store and I'm kind of shocked at some of the prices that I see. And literally, some of these things are going up almost weekly, if not monthly. And I tend to buy the same things in the grocery store, so I see this all the time. It's very obvious to me. It's very apparent that prices are spiraling out of control, right? And I think some of it is due to either grocery stores or maybe suppliers or producers of these goods that we buy in grocery stores. Maybe they are somewhat ignorant. Maybe they have to cover their fixed costs, right? They have fixed costs and operating costs that need to be covered, or they won't even be in business, right? 6 months or 12 months from now. So they have to cover their costs. But are they actually charging too much? And how much is too much? That's what we're going to look at today. Okay, so I'll show you some real world examples here about how we can change the prices of different items and how we can expect to make more profit and do that intelligently. But again, if it gets to be too high, people are just going to stop buying the stuff, right? And they're going to look for alternatives or for a different product altogether. If you're brand loyal to, I don't know, just take your pick, whatever, Hershey's chocolate or something, and it gets too high, you can easily find chocolate alternatives. You don't have to buy Hershey's. You can buy Reese's or something else, or vice versa, right? If Reese's is getting too expensive, you can buy Hershey's, right? So let's take an example. Now, I did make up this data. I wish I had access to grocery store data prices and what is the demand for these different items. And as demand changes over time, as you increase the price, what is kind of shrinking impact is that going to have on demand? And as you reduce price, how is demand going to expand, right? That's the elasticity of demand. So that's what we're going to look at. And again, I apologize, I don't have these actual prices. I looked into this. I found the guy that was willing to sell me real-time grocery store prices, and I think he had 1 million items, but he wanted to charge something like $1,000 per week, and I don't feel like paying $1,000 for something that I can basically get for free doing myself. So this isn't real-world, real-time data, but I think it's pretty close, and all of these prices should realistically simulate what you would see in a grocery store today. At least where I live in New York City, so these prices are pretty realistic. If you live in the Midwest, I don't even know, Kansas or Oklahoma, maybe the prices are a little different over there, but New York City, I think this is pretty realistic. Again, it's not real-time grocery prices. That would be ideal, but I don't have access to that. So we're going to make do with what we have here. So I'm going to go ahead and run this to create a list of prices, or actually this is a dictionary. This is dictionary because we have your key over here and your value over here, right? We have key value pairs, and everything is contained in these curly brackets right here. And that's why we have a dictionary. It doesn't matter if it's a dictionary, if it's a list, if it's a tuple, if it's a data frame. It doesn't even matter, guys. It could be any kind of container or data structure just to hold the data while we work with it, right? So I just put this into a dictionary. That's pretty easy to work with, pretty straightforward. So here is what the dictionary looks like. We have milk, eggs, bread, butter, Okay, and so on and so forth, juice and coffee. So take your pick right here. I think you can find what you're looking for. D0 is the initial demand at time zero. This is just basically what we're going to start with today, given a certain price. And there is a base cost too, right? That costs, like I said, there's a fixed cost and a variable cost. There's a fixed cost if you turn the lights on, turn the heat on, turn on the manufacturing equipment. There's a fixed cost to doing that. As you produce more and more goods, your prices are going to increase because your raw materials will increase. You'll have to turn on more machines instead of one or two. You might need three or four, and you're probably going to have to hire more people if you want to produce more stuff, right? You have to hire people to manufacture the goods that you're selling and operate the machinery, right? So there's certain fixed costs, there's certain variable costs, and the demand, we're going to just start at the beginning here. That's the assumption here. So we have a decay factor. K equals 0.15. This means as prices increase more and more and more and more and more, the demand is going to decrease, right? There has to be some kind of decay factor. Otherwise, producers can just increase the costs that they want to sell the product at, or increase the price that they're charging, and it can go on into infinity, or it's called what is that? I forgot, in perpetuity or something. Yeah, something like that. So it just goes on and never ends, right? But realistically, you know, as something gets more and more expensive, fewer and fewer people are going to be able to afford that, and eventually people are just going to pass by your product and not even buy it at all, right? So that is the setup here. Here's the dictionary, like I said, with the key value pairs. We have the K factor as the thing gets more and more expensive, whatever it is, grapes, yogurt, cereal, juice, coffee, take your pick there. Fewer and fewer people are going to buy the item and either look for alternatives or give it up altogether, right? So we have a decay factor. We have the initial cost right here, the initial demand, and I'm going to go ahead and try to understand how prices are affected by, or how demand is affected by prices. I'm sorry, I said that backwards. How demand is affected by prices, right? And we're going to look at the demand curve, and we're going to take a look at the profit curve as well, right? And then try to understand where is the maximum profit that we can charge for this item, and at what point is demand going to decrease so much that nobody is going to buy the item anymore, right? Or people will just buy it less frequently. So if you pass the optimal point, or the optimal price, let's call it the optimal price, nobody is going to be able to buy this because they simply can't afford it anymore, right? So that's what this code does right here. That's what the logic does. I set up an input box where you can select different items here, right? And the chart is going to update according to what you buy, or according to what you pick here, right? Which is basically what you're going to buy. And we will see the demand curve changing and the price maximization point changing too. So if we look here, the maximum profit of bread, we can charge $8.12. And again, this data is a little bit made up, so forgive me, you know, if it seems a little bit high, but again, this is New York City and I don't have actual prices, right? So I'm looking at bread over here, coming in here, initial cost is 1.5 and 550 units of bread, or items, loaves of bread, I guess you can call them loaves, will be sold. But again, we're looking at over time, you know, what's the optimal price, and then how many items can we expect to sell right here? So if you look down here, we see the price is actually negative, right? You can actually go zero. It has to be at least zero at $1.52. The bread profit is going to be $11, right? And then if we increase over here, for all the items sold, by the way, for all the items, if we increase the price over here, we increase it more and more and more. We get up to 2, 3, 4. Here's the maximum price that we could charge for bread right here, $8.12. And as we charge more and more and more, the profit is actually shrinking, right? Because demand is shrinking, and it will actually converge. If we go further out to the side of the curve, over to the right, we'll see these two converging, and it just doesn't make any sense, even at this point, way before they converge, to keep selling bread at a higher and higher price, because demand is going to decrease so fast, you're actually losing money as you sell more and more loaves of bread, right? It doesn't make any sense. So the bread optimal price is $8.12. Maximum profit is $177. And we will sell 102 units of bread. Now, there's no real time duration set here. I'm going to assume it's 1 week. We're not going to sell 162 loaves of bread in one day, at least not in my grocery store, right? There's a certain number of people that go in there, but the customer base is kind of limited. So we're going to say this is 1 week. And again, the optimal price is $8 for bread. Sounds a little high, but just stick with me here. It makes sense. And the maximum profit is 177. So if we go down here and run the next cell here in my Jupyter notebook, we can see bread at $8.12 right here. We'll see the peak. So it's just between 7.9 and 8.26. So I don't see the exact dollars and cents change over here. But you can see as the price exceeds the 7.96, it kind of decreases demand right here and decreases the profit too. So we went from $176 to 177, 176. Now it's decreasing, right? The profit's decreasing. It doesn't make any sense to raise the price anymore because you're just going to cause more and more people to pass by your bread. They're not going to buy it because either they can't afford it or it's just not worth it for them to spend their hard-earned money on this bread, right? So the crossover point is about, we calculate right here, 8.12, and it's about between 166 and 159 loaves of bread, and the profit goes from 176.32 to 177, up just a little bit, then it goes down again. So 8.2 to 8.4 is just about the maximum price that we can sell right here. And let me look at another, just to reset that. Rice goes 7.68 if we go back to bread, 8.12, and you'll see that it's kind of buried in here, right? So it's a little bit closer to, oh, whatever, I guess it's between these. 7.96 and 8.26 would be the price. Again, demand is constantly decreasing here, right here, right? As you charge more and more price, fewer and fewer people are going to be able to buy that, and your profit is going to shrink, right? So it goes from 177, 176, 175, 73, 71. Profit shrinking. It doesn't make any sense to charge more for the bread, right? So let's look at a couple more examples. Hopefully that makes sense, by the way. Hopefully that makes sense. So let's go over here and look at beef. So I reset, I choose a new item over here, and the graph is replotted dynamically, right? And we see the maximum profit for beef is just about 1301. Is that right? 1310. Yep, that's what I got, 1310. And the maximum profit is 416.26, and we'll sell 63 beef, whatever this is, beef patties. Like, I don't have the exact grocery store items, right? So you'd have to kind of use your imagination a little bit here, but containers of beef, beef patty, beef beef package, whatever you want to call this thing, right? But it goes up to 1310, and then the demand starts to decrease after we exceed that, right? So we say 1295, 1294.9, basically $12.95. We'll sell 64 items of beef. Then it goes down to 61, 60, 59. The price maximization point right here is about 416.26, right? And you can see that the demand increases just a little bit. I'm sorry, the profit increases just a little bit there, then starts to shrink and shrinking all the way down here, right? So the maximum price we can get is 1310, and then the demand falls off more and more, so the profit shrinks. So it doesn't make any sense to send more beef, to send more package items, bread, beef, whatever it is. You might sell a little bit more, but your profit is decreasing. It makes no sense, right? Or reduce the price to under $13.10, and you'll sell more. Your profit will go down a little bit, but you might build rapport with your customers and have some goodwill that you would not have if you charge too much for your bread, right? So that's another consideration. If we look at apples, so here is the apples, the maximum price at 8.70, and we see that just about over here, right? So profit goes from 1.8997 to 1.8972. It's already decreasing, right? Once we get over 8.70. Let's look at one more. Peanut butter. I happen to love peanut butter. Let's look at this example. So 10.17 for a jar of peanut butter, and the maximum profit is $500 per week. That's the time frequency that we're dealing with here. And the demand is 76 units sold. So we'll sell 76 containers of peanut butter, or jars of peanut butter, whatever you want to call it. And this is the maximum price that we can expect to maximize the profit. If we look over here, 10.17 is right between here and here, right? And we have 77 for demand, goes down to 74, 76 units are sold, right? Because that's right between here and here, 10.17. And you can see the demand is already shrinking. It goes from 5.0765 to 5.766, right? So I think it's a little bit closer to here, right? And then it shrinks 5.730, 5.6, 5.5, 5.4, right? So that's it, guys. That's how you can understand the elasticity of demand and maximize the profit that you earn, right? While not taking off your customers because you're charging too much. I see this all the time in the grocery store, and it is frustrating, by the way. It is frustrating. So, manufacturers and suppliers and producers, hopefully you're watching this and you're taking notes on this thing because I think it's important for the end consumer, right? You can probably charge a little bit less and make more money, charge slightly more and increase your profits without irritating the customers. But if you charge too much, customers are just going to walk away. Okay, and you can see that in this chart right here, right, and down here as well. And you can see that plotted visually right here, right? If I look at one more just for fun, just to beat this horse to death right here. What was the last item listed here? Honey. Okay, I like honey. I like peanut butter. I like both. Optimal price is 11.19. So if I charge 11.19, I should see that right about right there, 11.19 maximizing profit. The demand right here is about 55.98. If I go over here, 11.19, it's about 55. What is that thing? 55.9, 56. We're going on to 54. 11.19. Yeah, it's going down to 54. So it's in between these two. You can tell it's in between these two. This is 11.19. The 54 is a little bit closer to here. Just over that, and the profit is 37.49. Profit over here, if I put the mouse over it, 37.61. It's off a little tiny bit because we have a lot of decimal places, a lot of items being plotted here. There's thousands of them. So if I move a little bit to the left or right, you'll see those digits update, but that's why we have this chart here. All right, here's the optimal price, and here's a sensitivity analysis. This is called a sensitivity analysis. So as you change the price, the demand becomes more sensitive, and then the profit becomes more sensitive too, right? So the sensitivity analysis drives everything. You can see the exact point that we need to maximize our profit to sell this jar of honey. And again, this is based on these assumptions, these demands, which I don't have, but I did create these to be fairly realistic. So hopefully that makes sense. So that's it. Elasticity of demand given price changes and profit margins, right? So that's it, guys. I'm going to wrap it up, and I will see you soon in the next video. Keep your eyes out for that. Thanks. Bye. Hey there, everybody. My name is Ryan Schewel. Welcome to my data science channel. If you've been here before, welcome back. If you haven't been here, then welcome for the first time. Okay. So what is this about? It's all about data science, machine learning, deep learning, and topics related to these. Now, today I want to show you how to use OpenAI to fetch data from a bunch of PDF files. We're going to combine everything into one comprehensive body of text or corpus of text. And then we're going to ask the model some questions. We're going to ask the model to make some summary comments about the model. And then we're going to ask some specific questions pertaining to the contents of this text file that we created. Okay, so the benefit is pretty obvious. If you have a bunch of PDFs and they're pretty substantial in size, here's my PDFs right here. This is the biggest one. Let me see what this looks like. Yeah, it's kind of a lot. Kind of a lot right there. And does it give me the page number? 57. I think we're up to 57, 58 pages. Okay, so this is going to be pretty big. This is the biggest one. The others are a little bit smaller. But let's say there's maybe, if that's maybe that has half of the text. I'm just guessing here. Maybe based on the size of the file, maybe the other two have like about 25 pages each. We could say that the total number of pages is maybe around 120, 125, something like that. So if you don't want to read through 125 pages of PDF files and just want a quick summarization, this tool is perfect for that. Okay, so I'm going to go ahead and hit Control Enter to run the process. Okay, and down here it's going to ask me for an input as a path, a network path, or some type of UNC. It's also called UNC that gets me to where all these files are. So if I go over here, you can just copy and paste it. I'm a little bit lazy. I don't want to type it out. Okay, so there's my network path, and I want to save this file with a file name. This can be named anything. I'm going to put the network path again so it knows where to go, and I'll do body of text, text, right? Because this is a text file. Because and I misspelled body. Nice. All we really care about is the text. I don't care about all the formatting, all of the all the stuff that's coming from the PDFs. It looks nice. It's very appealing. It has a lot of nice charts and graphs, but I just want to go ahead and extract all the text from that and then summarize it and do some basic analysis on the text. Okay, so that's what these user-defined functions are for, to help me with the input files, to help me with one single output file. Again, we're going through 4 PDFs, extracting the text from every single one, concatenating everything together, and then saving the file. Now, whether or not you save the file is really up to you. If you work with the file over and over, especially if you have a slow network, you might want to save it so you don't have to do this process over and over. If the objective is to just do the analysis once, you don't have to save it down. I'm thinking I might have to go back and use this file again, so I'm going to save it just so I don't have to run through this process again. Okay, so everything is done over here, body of text, and we can see that this is fairly substantial in size. If I paste that into a Word document, we can get some basic stats about all the text over here. So let me try to do that. Apply, Control Enter to paste, Control V to paste, and then we have word counts down here. So I have 118 pages. Okay, I think I said 120 to 125. It's 118, so pretty close. 19,000 words and 103,000 characters with no spaces, and then it gives me spaces too. I don't really care about that, but that's good to know. Okay, so the file is pretty large, almost 120 pages, and now that everything has been concatenated or combined into one single text file, I can go ahead and read this text file into a model and have the model trained and tested on that text file, and then I can ask it questions, right? So this is pretty powerful stuff. So that's what OpenAI is for. And this is not free. I set up an account a few days ago. It cost me about 19 cents to do this analysis. Okay, so you start with $10 and you have, I think after that, you can add $5 to $100 increments for more tokens. Every time you send a token back and forth to this Open API tool, it's going to charge you a little bit, but it's pretty minimal. I mean, it's very, very minimal for what you get. All right, so there's quite a bit of bang for the buck. So you just have to go to this API, openapi.com, and set this up for yourself. And when you do that, you'll get an API key. Okay, you pop in your API key right there. So if I go over here, I have billing. You have a couple little controls on the side. API keys. Here's my API keys. These are all blocked out, right? And I chopped mine off of here, right? Because I can't share that with you guys. This is personal and confidential, so I can't actually run this next part. So you can see right here, it scanned through the 4 PDFs, and then it created the body of text. I just showed you that, right? So that goes into the same folder. So for this next part, I'm just going to show you what I did a couple of days ago. I set this up and trained and tested the model, and it worked totally fine. To get this to work, again, you will have to get your own API. And it's not free, but it is very, very, very cheap. For what you get, you really getting quite a lot here, quite a lot of value add. So plug in your API key when you get that set up, and then you would change this path that goes to your corpus of text. Okay, so that is going to, wait a minute, I think I actually renamed it, but it doesn't matter because I'm not even going to run this thing at this point. Trust me, it works. It works totally fine. If you have some questions, you can post those in the comment section, and I can try to help people. The only thing you really have to be aware of, and I tested the code pretty extensively, so everything is fine. The input file, and again, that's dynamic. I made that dynamic so that can go anywhere. You can see where it's going here. Okay, it's going to this folder on my desktop. You would have to change your API key, and you would have to change the text file that contains the whole summary of all the text, not the summary, I'm sorry, the whole corpus of text from those 4 PDF files, right? So you would have to update that, but that's the only thing you have to do. Once that is all done, hit Control Enter to run the contents of the cell, right? And it's going to spit out a little message over here. So summarizing chunk 1 of 7, 2 of 7, 4, 5, 6, and 7. And they break these into chunks because the computer is a little bit like a human. You can't just dump in every single thing and hope for the best, right? That would be, I don't even know what that would be. Maybe magic or something. It doesn't work like that, right? You have to read in one chunk and then another and then another and another. And a person is the same way. We speak in sentences or maybe in paragraphs, right? But they're chunks. They're all chunks of data. It's not like just blasting a fire hose volume of data at a model or at a person is going to be effective. It's not, right? You have to take just a brief moment to interpret chunk number 1, chunk number 2, number 3, number 4, and so on and so forth. So computers and humans are similar in that respect, right? The learning isn't infinite, but it is pretty impressive though. right? So here's the summary. I just put, can you summarize the text into 3 sentences? The text summarizes the risk of and conditions of the banking industry in 2023, highlighting economic, so on and so forth, agricultural sector, small business conditions, and finishes with an asset quality of community banks in energy producing states in 2023. And if you want to ask it another summary question, you can ask another one. If you want to type exit or quit, that will end the program. Okay, so it ends gracefully. You don't want crashes and weird error message coming up, right? So you type an enter to exit or quit, and it will quit the program. Okay, so that's pretty cool. The only limitation, though, is that you have to have the word summarize to get a response from this model. So when you type in, please summarize this text or summarize this, whatever, I mean, it's pretty straightforward. Just summarize the text for me. That will trigger the model to run, but you can't ask it specific questions about the body of text. All this does is a basic summarization. So I leveled up for this next one and made it a little bit more dynamic and a little bit more interactive. So you can ask questions in a very like question response interactive type of environment, right? So this is a little bit more dynamic than the first example where you can only summarize the text. This you can say, summarize the text for me, or ask it specific questions about the body of text, right? So it's a little bit more evolved than the first script, which was still pretty impressive. It's taking 118 pages of text and summarizing it for you. So that's still very impressive. But if you want to make it just a notch better, you can refactor the code to make it more interactive again, so you can ask it different questions. So in this example, all you have to do is pass in your API key. This is the type of model that we're using. If you want to learn more about this, you can look at this too. And there's all kinds of models out there these days. Let me see. I'll just Google this thing quick. Model sentence transformer. Of course, this comes from Hugging Face, and you get over here on their website, and they'll have all kinds of examples of different models that you can use, right? And sentence transformers, that's what we're looking at here. And here's all the different models, right? So 13,625 models as of April 3, 2025. So 13,000, you've got to be able to find something here that's going to fit your needs and help you do whatever it is you're trying to do. So I have a sentence transformer. I think that was very appropriate in this case. If that doesn't work well for you, then you have 13,000 plus other models that you can pick and choose from and play around with. And again, this is not free, right? There is a small charge for this, but there's my bill, 19 cents. That's what I paid to put together this video. But again, like if you need to do this, it is absolutely worth it in terms of time savings. And most likely, if you're doing this in a professional environment, your boss or your manager or something is probably going to pick up the bill, right? Or the company will pay for this thing. So that's not really a huge concern, I think. So again, generate your API key, pop that in there. And we're going to go ahead and run the analysis again on that same corpus of text. So you would have to change the path to the text. And you can make this dynamic. I think once the 4 files are read in, you read in those 4, you get one text file from that. I don't think this part has to be dynamic. If you want to do that, you can do that. It's really up to you. These things are pretty flexible in so many different ways. So now with this model, again, it's a little bit more evolved than the first one where we could only summarize text. That's the only thing that is going to do. You can actually summarize text with this or ask this specific questions about the contents of that text file. So here's my first question. Can you summarize this text into 4 sentences? And again, it reads in all the chunks. The text provides an extensive analysis of economic financial conditions in 2023. Key risks include market and credit risk. So I can already see there's a small mistake here. This isn't just 4 sentences. There's, I think I'm looking at 1. Oh, these are 2 right here. My eyes are not great these days. It's getting older and getting myopic. So there's sentence 3, there's sentence 4. I think it gave me probably 8 sentences, maybe 7, maybe 8. Or 9 sentences, okay? So it gave me a total of 9. I asked for 4, so it's off a little bit. But that's okay. I asked a second question. Can you summarize this into 4 sentences? And again, it gave me a summary over here. And then the response was, what? 2023, it's talking about economic growth, inflation and monetary policy, labor markets, financial markets, banking sectors, key risks, and in summary, there's market volatility, there's resilience in the banking sector, and the rebound in financial markets towards the end of the year highlights this adaptive nature of the economy amid persistent external pressures. So I think it kind of struggled a little bit with this direction. 4 sentences, it just didn't get that. The first time it gave me 9. But you know what? Still, overall, it's very impressive what you can do with this. And who cares if you get 4 sentences or 5? It probably doesn't matter too much. If you have a nice summary, you pay 19 cents for that. I mean, it's still a huge value add. It's still very, very, very cool what some of these models are available to do these days, right? And I think it's only going to get better and better. So the obvious takeaway here is faster, better decision making, time and cost savings, synthesizing data, improved knowledge and retention, personalized question answering interactivities, right? Efficient research workflows, complex report generation, multilingual understanding, and compliance and audit support. So if you work in a highly regulated industry like banking is, then there's going to be compliance requirements around that, around basically everything that you do. So if you need this for compliance purposes, you can add in a couple statements to your question over here. Give me a summary and make this compliance worthy or whatever the term is. I'm not sure. Okay, so the PDFs came from this website. You can take a look at those. If you want to combine any PDFs, clearly this does not work just on these, right? You can dump in anything you want. It can be a Word document or a PDF. Or a bunch of text files. In this case, I'm just looking at PDFs. That's it. You can do Word or PDF. Anything that has any kind of text embedded in it, you can analyze that. And then again, you have to get your API key. You can get it from this URL right here. And then you would simply update your comprehensive body of text that you created and put in your API key right here. And that is literally it. That's literally it. Okay. You have a couple different chat GPT models that you can play around with over here. If you want to experiment with the resiliency or maybe not resiliency, the capability of the model to make more and more impressive types of responses, there's several models that you can pick from. This is the cheapest one. That's why I'm picking this. That's probably why it kind of didn't really understand this direction down here. It said 4 sentences and it gave me 9. There are 2 others. I think there's Chat GPT Turbo. You have to go on the website and see what these things look like. There's a couple others. Oh wait, I got that. I didn't even copy the thing. I think there is a couple others. Oh yeah, here. Right. Versus. Let's try this. Versus. Oh, that's not what I was looking for. Oh, maybe. Pricing. I just want to see the pricing here. Cost comparison. Okay, we're good. Yeah, so here's the different models. So you just copy and paste that in there. GPT 3.5 Turbo, that's what I have here. So that is the cheapest one. That's probably why it got screwed up a little tiny bit there. But only 0.002 cents dollars for 1,000 tokens. And again, the token is like the bits of data that go back and forth between your computer and the model. So to send 1 million tokens is only $4 here. It's a little bit more expensive, 1,200, and this is 1,200. But again, these responses are going to be much more accurate. So if accuracy or precision is a non-negotiable for you, then you probably have to go with the more expensive model. And, you get what you pay for. You pay a little bit more, you get a little bit more, pay a little bit less over here, you get a little bit less. I think that's why it kind of didn't give me exactly what I was asking for down here, right? Because I went the cheap model. But you know what? I'm just a cheap guy, and that's it. So that's how you build the tool to analyze a bunch of text files or PDF files, convert that into text, and feed it into a trained and tested model and interact with it. So I will share all this code with you when I post a video later today. You can copy and paste it. Again, the only kind of updates you're going to have to make is this over here and this over here, and I can pretty much guarantee everything else will work. If you have questions, post those in the question section or comment section, whatever it's called. I think comment section. on YouTube. And if you have questions or requests for additional videos that you want to see in the future, post those and I'll see if I can get around to it. I try to read all those comments and follow up with all those comments too, to the greatest extent possible. So that's it. I'm going to wrap it up here, guys. Thanks for your time. Enjoy the rest of your day. Goodbye. Hello, everyone. My name is Ryan Schewel. Welcome to my data science channel. So today I want to talk about the topic of hospital treatment searching and price prediction modeling. Okay, so I got this idea originally a few months ago. I actually created a YouTube video on this. This is the original video right here, Save Money on Common Medical Procedures. And what you do is go through this website and you select the procedure that you need, all right? You choose from a drop-down menu here. You pick your medical care provider or your insurance, whatever this thing is, your insurance, I guess, and then you pick your zip code. So here's the original website right here. It's pretty easy to use. I have this in the link of this original video that I put together a few months ago, and I'll share this with you too. I'll put that link right here at the bottom of this page. I'm going to share this these ideas with you later today. This is all the source code that I'm going to go through today in the video, all the Python code, and then you can copy and paste that into your own Jupyter Notebook environment and run that whenever you need to. Basically, here's the concept, right? You would go to this web page, go here, and select the item that interests you, right? What kind of medical procedure you need. Here's cataract eye surgery. Okay, you put in your insurance company. I'm going to put Aetna. That's what I have. And then my zip code is 11101. Okay, this is Queens, New York. And it pops up a price range. Cataract surgery costs about $850 up to $2,700. And this is pretty consistent. You have 700 to 2250, 850 to 2700, 1,300 to 4,000 for these guys, right? So they give you different hospitals and then location for each hospital, the city, and so on and so forth, and a price range. And they give you a nice little map that you can get an approximate idea of where these hospitals are located, right? So that is the concept here. And here's the overall comparison. Great price, 1,200. Fair is 1,900, and expensive. This is on the higher range of things, $3,300, right? So my concept basically creates a screen scraping process that goes through the website, goes ahead and selects every single possible procedure type, okay, and puts in your insurance costs and everything, and then it gets the information from right here, right? It copies and pastes that into a data frame. So I'm not going to run this process because it takes quite a while, probably at least 30 to 40 minutes to finish off. When you finish the entire thing, though, you will have a data frame which you can download and export. I put it on my desktop right here. I did this yesterday to prepare for this lecture right here. I did this last night. And you can see here, when I open up the CSV file, it's going to have all of the medical information that I just showed you and basically everything from the entire website, right? So what you just saw was one page. This goes through thousands of pages and goes ahead and grabs all that information from those 1,000 pages, right? So if you go down here, I think you end up with about 43,323 minus one for the header. So 43,322 different types of medical procedures, the facility name, and the hospital, and then the price range. Okay, so that's what that does. I'm not going to go ahead and recreate the whole thing because this video does that for you, and this code will also do the same thing. But again, it takes probably about 30 to 40 minutes, so I'm not going to run through that. But I do have a sample that I can load. This is all the health data that I just showed you. That is about 4,200 records. I'm going to take just the top 500, okay, and just work with that. So I have a small subset of the entire population. Instead of 42,000 records, I'm going to work with about 500, give or so, okay? And when this information comes in, it looks just like this. So you have the procedure type, facility name, the city name, and then the price range, because that's really all they give you. They don't give you a ton of data, but it is pretty useful data, right? Because you have the prices here, and to get this cost information for medical processes is actually very hard. So I was pretty fortunate to find this website that gives you a ton of stuff here. It doesn't have the hospital information other than the name, but by using some Google tricks right over here, some Google technology, specifically, we can use the Google Places API key, and we can actually derive the latitude and longitude coordinates for all of these hospitals right here. So I have the facility name, okay, Bayshore Medical Center, Bellevue Hospital, Bronx Health, and Brookdale Hospital Center, and I have the latitude, longitude coordinates for each of these hospitals. So that comes from Google Places, and if you go over to Google, you can find this key for yourself. I can't give you mine, of course, this is private and confidential, but you can get your own quickly and easily. Let's see, Google Places, yes, API key, Google Places API key. You can go to Google console. Let's see, Google Places key API. This is what you want, I think. Except I want the Google console. Wait. Where's this? Google console, GCP. Oh, did you try GCP? GCP, Google Cloud Platform. Um, might be here, or is that the one I just saw? That's probably the one I just saw. Let me see. Manage API keys. I think this is it. I see Google Cloud Key Authentication console. Oh, here it is. Console. It's in the upper right-hand corner, right? So there's some documentation on how the console works, and you can go here and API service. So it's pretty easy to get to. You can go ahead and apply for your own Google Places API key. It's free and it's pretty quick to get started. Okay, all the keys are over here. Some of these I have, most of them I don't have. BigQuery, that's for the database. And yeah, I don't have that one. Okay, that's fine. But you can just look for Places over here in this list. Go ahead and apply for that, and you're going to get your key right here. So you put in your key, and then you can go ahead and get all of the longitude, latitude coordinates for yourself. Again, this is personal and confidential, so you have to get your own. I can't get that for you or share that with you, right? But once you do that, you have the procedure type, facility name, city, price range, and then the lat and long coordinates. Okay, we have three different types of procedures. I'm doing DF sample procedure type value count, and it's giving me ankle replacement surgery and angioplasty PTCA. That's what you see right here. Here's the price ranges, 26K to 83, so it's quite a range. And ACL, this is, I think, in your, what was that, like lower foot area, ankle or calf area of your leg, something like that. I think those are the ACLs. So anyways, it prints out all of the information. And again, I'm taking a subset of all the data. I have 500 records just to make this faster. If I had to do the Google Place API of 42,000 records, that's going to take quite a while. It's going to take probably a good, decent hour, maybe hour and a half, maybe even more. I'm not going to do that right, but I can get 500. That's what I'm taking the head here. I'm getting 500 pretty quick and pretty easy. But to get the full 42,000 is going to take a big lift, and they just don't want to spend that much time and that much effort on it. The labor cost is just too much for me, so I'm just going to go with 500 just to illustrate the point of what we're doing here. 500 is sufficient, right? So you can see 354 ankle replacements, angioplasty is PTCA, and ACL reconstructive surgery. We have 16 records for that. There might be more. Again, this cuts off at 500, right? That is the limit here, just to get the Google Places to run and finish off faster. Again, if I did that all, that would take quite a while, right? So I'm not going to do everything, but I do have a file saved on my desktop where I have all this information filled out, the latitude, longitude. I got this last night, saved the file, so this is going to run pretty fast, okay? So now the nice thing is when I run this code down here, and don't worry about all the details, it gets a little bit convoluted, but it's really not too bad. You can grasp this if you spend a little time looking at the code and playing around with it. Basically, we're going to get some inputs from the user based on where the person lives. We're going to find hospitals close to this person, and then ask the person for the type of surgery that they need from their healthcare profession, right? So here's angioplasty, ankle replacement surgery, and ACL reconstructive surgery. These are only three. There is a whole bunch here. If you run the first script, you can get hundreds and hundreds of different types of surgeries and the prices for each one, right? If you go over here, you see the list, shoulder, knee, surgery, cataract, all these down here, and so on and so forth. MRI, if we need just general MRI, we can say Aetna, put in my zip code. Whoops, I didn't put in the zip code, 111. And then you'll get the prices for each one. And this one actually has none. That's kind of weird. Let me try a different one. Pacemaker, You know, MRI, MRA. Let me do an MRA pelvis. That sounds kind of cool. Not even sure what that is. Okay, New York, and we can click the next button, and there's the details, like I showed you before. So pretty similar, right? And you have 12 pages here. So quite an extensive list of hospitals in the New York City area. That's where I live. So we're going to take a lot of information and distill it down into a useful format that a person can interact with and derive some value from. So when I hit Control Enter, the first thing it does is ask me for what type of procedure are you looking for. I can put in neck. Okay, let me just say neck or ankle, or let's see, lower leg. Okay, let's see what it says. Did you mean one of these ankle replacement surgery? Actually, yes, that's what I was looking for. I want ankle replacement surgery. I typed in lower leg, but this code is smart enough to direct me to the type of surgery that I actually need, right? There's no lower leg surgery per se, but there's ankle replacement surgery. That's what I need. I can put in my zip code 101 and hit enter, and then it says 111 San Pedro Quintan, San Jose, Costa Rica. Okay, that's definitely not me. So it needs a little more information. Let me put in Queens, NYC, or Queens, New York. I think that's fine. Queens, New York, hit enter. It says, found this, Queens, New York. Is this your address? Yes or no? I'm going to put in yes, Y-E-S. Okay, and it's going to move to the next question here. Is this correct? Umbria, Italy. Italy. No, this is not correct. Let me try this one more time. Queens, New York, 11101. Let me put that. Okay, it's pretty smart. Sometimes you have to give it a little guidance. So, no, no. Oh, Queens, New York. Yes, that's what I want. This is right. Now it's got it. Queens, New York. Let me put in yes. I hit enter, and found Extrovia. Oh, it did the same thing again. Is this correct? No, let me put no. Let me start this again. I think it got confused or something. Enter full address. Okay, this is my address, 4705 Center, the one City, New York, 11101. Enter. Okay, let me see if this is correct. Skinny's Cantina. You know what? That's pretty close. That's right down the street. Yes, that is correct. So let me put yes. And I want all of these hospitals that can do ankle replacement surgery within a 5 mile radius. So let me do 5 mile radius and enter. And it's going to pop open a map for me and show me where my home is. This is my house. This is very close to where I live right here. Okay, so there's my home, your location. And you can see all the hospitals here, and we've got a bunch. So the nice thing is that it plots all of these hospital locations on the map. And if I zoom in, I can see the details there. So Gregory Surgery, Surgical Services. This looks like a pretty small shop. I see International Financial Center and Delicatessen. I hope they're not sending me to a deli for my ankle surgery. Let's see, CarPoint Health Brooklyn, Hoboken. Okay, there it is, Hoboken University Medical Center. Okay, so this one, it shows me the distance, 4.0 miles from where I live. Okay, and here it's showing me, again, the price, 15.3 to 47,800, 4.96 miles from where I live. That's very helpful. Here's one right in New York City, 78,000 to 24.3, 1.96 miles. That is good to know. Here's one that's pretty close to me, Murray Hill Care, 7,800 to 24,000, 0.97 miles. That might be where I'm going to go. I could negotiate a lower price, 7,800. And let me look at one in Queens. This is the Sora Orthopedic, 8,000, 24,000, and that's 2 miles away. Okay, and if I zoom in, it's a little bit hard to see that. This might be like a small private practice or something. Let me just look for one that just gives me some kind of assurance that this is a hospital. I see the white cross there with the red indicator, 2.5 miles away. That looks like it could be an option. And here's one more, orthopedic and sports medicine, 8,000 to 24,900, 2.38 miles away. If I zoom in, looks like another small family practice, right? So anyways, it gives you good insight into what the healthcare costs are for this particular surgery for ankles, and shows you on the map where all of these things are located. Now, if I go back and redo this and let me hit Control Enter to rerun it and just get a bigger radius instead of, what did I pick, 5 miles? Let's say I want to look for 50 or 100 miles type of surgery. I'm going to say ankle, K-L-E, ankle. And yes, I want that 1, so I'm going to put in 1. Okay, it's asking me to confirm with a number instead of typing. Numbers are easier for the computer to understand. And if you type this out, okay, let's say Long Island City, New York, 11101. And is it going to find it on the first try? This is correct. Yes, yes, yes for that. And that's asking me for the radius. Let me say I want more hospitals. I'm going to go to 200-mile radius here, and it is going to find 346 hospitals and plot everything on the map. So now, if I look at this, this hospital is 86 miles away, still less than 200, and the cost is 15,300 to 47,800. This is 82 miles away, 15,000 to 4,700. And if I zoom out even more, these hospitals are further away, but still within the 200-mile radius, 176 miles away. The cost is 27,000 to 24,300. This is 161 miles, and the cost is 8,000 to 24,900. Okay, so the nice thing is it gives you the overall range of costs like you can get from here, but it gives you everything comprehensively, right, all in one spot. So you can do these queries, look for the specific medical procedure that you want or that you need. Maybe this is not elective surgery, it's necessary, mandatory surgery for your health and wellness, right? So that is pretty cool. You can search through a whole bunch of records quickly and easily, and everything is plotted on the map for you. Let me show you one more thing, because this has the dual functions of hospital treatment search. That's what we just did, and price prediction modeling. So that is the next step here. We're going to take that same data, the health mapping CSV, read that into a data frame, and go ahead and consume that data by 2 different models. We're going to look at a random forest regressor, okay, and an XGB boost regressor, so extreme gradient boosting regressor and random forest regressor. And we can see that the R-squared of both of these is pretty high. The higher, the better. We want this to be close to 1.0. 0.87 is pretty decent, 0.87 pretty decent. So these are pretty close. The random forest is just slightly better at making predictions, right? And again, this is taking the historical prices right here and making predictions into the future for what specific type of procedure you need. But let's say that you have a very, this is just generally looking at all the procedures. Let's say the procedure type is very special and you need ankle replacement surgery, right? So we're going to take the trained model. It's been trained and tested over here. The model is literally fit right here. This model is fit right here. So the random forest is fit, the XG boost is fit, and then we're using this to make predictions, okay? And we're looking at the predicted values versus the Y test, okay? And here's XGB predicted versus Y test. And that's how we're getting these R-squareds. Now with the model tested and trained, we're going to make predictions. How much does it cost to get this type of surgery in New York City? And these are my local coordinates. This is my local longitude, latitude. Now, if you do this in a professional way, and I'll admit this is a bit of a hack, if you do this professionally, you'd probably have a couple drop-down menus and let people choose items, kind of like this website is doing over here, right? I'm not a web developer by any means, so I don't know how to create these types of interactive controls. But if you're doing this professionally, 11109, you would have a web developer working for you, and they would take care of that. Or if that's your skill, if you're a web developer, then I suppose you already know what to do, right? Wait, spinal fusion, ultrasound. Let me try that. Oh, there's a couple here, right? Abdominal ultrasound, and hit next, and like that. Okay, so you'd have some drop-down controls. It's easy for the user. I'm not a web developer, so I just created this tool right here. So again, the model is trained and fit and tested, and we can make a prediction. This procedure is going to cost about $10,454 or $9,400, so it's about a $1,000 difference, and the difference comes from the 2 models, right? We have a random forest model and the XG boost model making these predictions. That's really the only difference. Otherwise, the data that these 2 models has seen is exactly the same. The random forest is fit here, XG boost is fit here. So trained, tested, and ready to make predictions right here. That's it, guys. That's pretty much it. I've had some feedback that my videos get a little bit too long and they kind of drag on, so I'm not going to make a filibuster here and go on ad nauseum. I'm just going to make it pretty crisp and tight and keep it pretty clean for the rest of my videos here. So you have all the code you need from the beginning to the end. This is the if I go up to the top, here's the screen scraper over here. Okay, so you can put that into a Jupyter notebook, or even run this in Anaconda Spider. IDE, and that will work fine. You'll screen scrape everything, save it down as a CSV file. Then you can go ahead and load the CSV once it's done, because again, this does take a while. It probably takes half an hour, maybe 40 to 45 minutes. Once that's saved down, you don't want to redo it. You want to save it as a CSV file or maybe in a database so you can access the data very quickly and easily. You go ahead and get your longitude, latitude coordinates right here. Okay, once you get your Google Places, or I'm sorry, Google, what was this thing called? Google, Google Places API key. I showed you how to do that. You can get the lats, longs over here, and then you can predict how far away each of these hospitals are from your local place of residence. And for me, it's right down here. So the blue house represents my location, right? And all of these red crosses, or I guess it's a white cross with a red push pin or whatever that thing is called, that represents the background of all these hospitals. And then it shows you, right, the price for that surgery at the hospital and then the distance from your location. So that's it, guys. I'm going to wrap it up, and I will see you in the next one. Thanks for your time. Bye. Hey there, everyone. My name is Ryan Schewel. Welcome to my data science channel, where I talk about all kinds of different data science topics and try to make everything interesting and relevant too. But I don't just look at data science. If I have some innovative ideas I think are somewhat interesting and digging into and just analyzing the practicality of that, then I'll take a look at some other things too. So that's what I want to talk to you today. I was thinking just a few days ago, how many calories would a person burn if you walk from one side of the United States to the other? Okay, so if you walk coast to coast, how many calories will you burn? And this is my analysis, and I'll show you how I came up with this. Okay, so we're just making some basic assumptions. People are different heights, right? They'll take different number of steps in any given distance, but I think this is a pretty decent approximation. Okay, we're saying it's going to be around 2,800 to 3,000 miles, or 4,587 kilometers to go from New York City to San Francisco. So I put this into Google Maps. This is what they came up with: 2,962. Okay, and this is the path. They actually give you all kinds of very interesting details over here. So this is very useful. So this was kind of like the basis for the analysis I did. So we're going from New York to San Francisco. It's going to take about 1,069 hours, and we go 2,962 steps. So I'm thinking that's in line with this, right? So that is pretty accurate. Calories burnt per mile is about 100 kilocalories per mile walking. I'm looking at biking too, okay? So I'm looking at two different analyses here just to compare the biking and walking together. And the assumption is that you would weigh about 160 to 180 pounds. Now, obviously, I'm a guy, so I'm probably going to be closer to the 160, 180 for some women. Obviously, they're going to be smaller, right, and probably walk slightly slower, right, or at least take more steps per mile, okay? But again, just making some general assumptions here. So I think so far things line up. I got, what's this come up with? 2,962 for miles. Okay, so that's definitely between that and that. And I'm putting down 2,962. It's exactly right here because that's what Google is giving me. And I want to see the calories. Per mile walking is about 100, and per biking is 50. Obviously, biking is going to burn way fewer calories than walking. Biking is actually the most efficient way to move from point A to point B, okay? Because you put in very little effort, and when you're going downhill, you probably put in no effort. Gravity just pulls you down, right? So walking, you're definitely burning more calories. To go from New York to San Francisco, it's about 200, okay? 296,000, so close to 296,000, close to 300,000 miles, calories. I don't know why I keep saying miles. And almost 150,000 calories if you're biking, right? So, so these line up pretty consistently. But that is, that's a standard calorie. So a calorie is defined something like how much energy it takes to heat up, what is it, a liter of water or something like that. I studied that a long time in school, but that's not really a metric, metabolic calorie, right? So that's more of a kind of scientific metric, but metabolic calories are more like actual energy that your body uses, right, when you metabolize food. So these are more usable calories, right? So the calculation is going to be somewhat similar, but just slightly different. So metabolic walking, metabolic biking, these are the two variables I defined, and I came up with about 281,000 metabolic calories. This is going to be MET, M-E-T, and for biking about 148,000 MET. Okay, so underscore there. So for biking, it's pretty much almost exactly the same because you put in the same amount of effort between a calorie and a metabolic calorie, right? For walking here, it's going to be almost double of biking, right? But the metabolic calories are going to be slightly less than the kilocalories over here, okay? And these are just assumptions I'm making. I think, again, it's pretty accurate, pretty practical. Is this exactly going to be precise right down to the metabolic calorie? I can't say for sure, but I think it's a pretty good baseline for our analysis here. And then time to walk across the United States. If the average speed is 3 miles per hour and the average hours per day is about 8 hours of walking, because you have to sleep, you have to rest, you're going to have to eat at some point too, take a shower. Hopefully you don't go the entire distance with no shower, right? And the daily distance would be about 24 miles. So 2962 divided by 24 is about 124 days, practically speaking. Now, in Google Maps, they say 1,069 hours. So I put this into Excel. So I got 2962, or 124 times 24 is number of hours, right? So this is number of hours, 2976. Google says 1069, right? But that's, again, making the assumption that you do this continuously, and that is not realistic at all. At some point, you're going to have to stop and rest, right? You're not going to be walking 24 hours straight through. But I think this number, the 1069, is about a third of the 2976, and we came up with, 124 days. So I think this is pretty approximate in terms of number of days, because, again, you're not going to be walking straight through. You're going to have to stop and rest, right? But the 1096 is about one third of this 2962. And if you're going 8 hours a day with about 16 hours of rest, I think this totally lines up. Okay, so about one third of your day is spent walking, and about 2/3 of your day is spent doing other things. Again, shower, eating, resting. You're going to have to rest at some point. Did the same analysis for biking. So the daily range is about 50 to 70 miles, moderate. Now you can do more, okay? This is just making some assumptions. 2962 divided by 60 should take about 50 days, okay? Realistically, like, you're not going to be biking constantly straight through the whole thing. You're going to have to stop and rest. So this was the biking. What I'm just curious to see what they come up with. Oh, 12 days. Okay, so 12. If we look at my analysis over here, okay, 281 hours or 12 days, right? No, 281 hours. So how many, let me see how many days did we come up with here? 50 days, 281 hours, all right, 281, 50 days, 50 days. And what was this again? Times 24, 24 times 281. This is, whoops, need the equal sign over here. Or wait a second, this is already in days. Let me see what's going on here. This is already, in hours. This is already in hours, so I don't have to convert that, right? So 281, this is already hours, okay? So we're good there. And if I do this, divided by this, so 17, close to 20, so maybe 20% of your day is spent biking, and the other 80% is spent doing other things. You're going to have to relax again, take a rest, eat at some point. So I think this is pretty accurate, right? So about 50 days to bike, and what did you come up with? 124? Yeah, 124 if you're walking. Okay, so I think that's pretty interesting. I want to take this analysis a little bit further with Google Maps. we can go ahead and get a free Google Maps API key. If you go to your Google Cloud Console, let me see if I can get to mine. Google. It's totally free to sign up. You do have to pay if you use it a lot. I just started getting charged by Google because I use this quite extensively recently. I don't use it too much, but it is free to sign up and get these API keys, right? But if you use it quite frequently, they will bill you for this, and you have to put in your credit card to be eligible. But anyways, here's all your API keys over here. Enabled API services. This is what it looks like. So you can go ahead and sign up for your own free Google Maps API key. I can't show you mine, right, because it's personal and confidential. But once you get this Google Maps key, you can do some very interesting analysis, right? So here I'm looking at New York to Los Angeles, so a slightly different endpoint. Again, we're going from coast to coast. And when you run this, you can actually get the elevation gain and then all the latitude, longitude coordinates for your entire trip. So I took a look at that. I thought that was kind of interesting. And then I went over here on Folia Maps and plotted it out, and we get somewhat of a similar map here. So this is New York City to LA, right? And we see all the details of the map. If I zoom in, something looks a little bit off here, right? Because the map doesn't really follow the lines of any kind of discernible path or US highway or anything like that, right? So we're kind of crisscrossing. So I think this is kind of close, but something's off here because you're not going to walk through somebody's backyard. This looks like you run right through the middle of a hospital or business here. That's not super realistic, right? So I think we have to enhance the analysis a little bit by giving this Folia map tool a little bit more information here, right? So we can embellish this. Again, you'll need your own Google Maps API key. I can't rerun this because the key's not in there, because I would have to show the key, right, to do the analysis, but I can't show that. So here, if we zoom in, we did the analysis again. It looks, again, pretty decent. We're following the path of these roads here, right? Which is plausible, because I don't think you're going to go switch back across the road back and forth. I think you're going to follow the path of the road. Here we go straight through the middle of an airport, right? I don't think that is super realistic. So I think we can actually improve this analysis a little bit, right? If we use haversine distance, this is the way to get different distances between coordinates, right? So you have a latitude 1 and a longitude 1 and a latitude 2 and a longitude 2, and this becomes coordinate 1 and coordinate 2. Then you can apply some haversine math, and we can do I think a more accurate type of analysis here. So here the total distance is 4181 kilometers. What did we have at the beginning here? I think I had kilometers, 4181, 4587. Okay, so it's pretty close. It's off a little bit. But again, there's many paths you can follow. You can see all the roads over here, right? We can follow this road to the north. We can take a different path to the south. So there are more assumptions going on here. But again, I think it's pretty accurate. I think it's good enough for our purposes here. Okay. So we're going to go from New York to San Francisco. Again, you need your Google Maps API key. And by the way, I'm going to share all this code with you. So all you're going to have to do is apply for the API key and then pop it in here, and you can simulate all the analysis that I've already done. Okay. So here I'm looking at different elevation gains. Okay. And then total distance traveled. So again, we get the, what's this, 4181 kilometers. So that kind of pretty much syncs up exactly with this over here. Okay, so we have the number of kilometers, so that looks feasible. And we have the elevation gains plotted out here on this Plotly map. I like these Plotly maps because they're interactive. You can zoom in, you can zoom out, right? So it's a pretty cool way of interacting with your data in a Jupyter notebook. That's the environment that I'm in right here. Now, to make this a little bit more realistic, I'm applying some waypoints or some stopover points that we would likely go through during the entire trip over here, okay? So you have to kind of give it some guidance and coax it and sort of cajole the tool a little bit. Otherwise, it's just going to kind of run wild and try to do some analysis, but is it going to be super accurate? It may, but it may not, right? So you have to give it some guidance along the way. So again, we're going from New York to San Francisco, walking. That is the type of analysis here. If I zoom out, okay, that looks pretty accurate. Okay, now if I zoom in, are we following the street lines here. Kind of, but not really, right? So I think something's still off because we're not really getting the details of all these roads, right? So we have to take into account a little bit more accuracy, right? So again, we're going back to the Google Maps API key. Again, I'm going to share all this code with you, right? And we're going to give this a little bit more guidance on how to do the lines. We want a polyline, okay? And we want to hit certain points across the trip here. So we're going through these major cities over here, right? And we're assuming this person is doing the walk from New York to San Francisco. So if I zoom in, now we have an excellent map. So the assumption here, my take on this is we're starting basically at City Hall. That's interesting. Okay, so this is a good place though. I think for New York City, this is kind of like the epicenter of New York City. So we start at City Hall. We take a ferry down here. We get down to Jersey. Okay, so the terminal is this ferry. Bedford Harbor, so this is the ferry terminal right here. Okay, so that looks pretty accurate to me. So we get out, walk down the street, and this looks very good. So we're following the path of the street now. Okay, that's what this polyline is doing for us. So it's making the analysis very, very accurate, or the trip that we're taking very, very accurate. So we're not walking through hospitals and airports and going through people's backyards. So this looks good. We're following this route over here. So this looks pretty good. Let's go to further out in the trip. Couple more points. Okay, we're going through Pittsburgh over here. Are we following the path of the street? And it looks like we are. I think we're crossing over the bridge here, crossing over another bridge. That looks good to me. This looks very, 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 very good over here. Okay, if I go over here, I think it is following all the streets. This looks good. Looks very good. We're following all the streets. Here we took a little deviation to, oh, no. It's just going on a different road close to that airport. So I think this is highly accurate type of analysis in terms of what paths or streets we're going to follow. Right, we're not going through the middle of buildings. Denver, how's it go through Denver? Pretty much through the downtown. Okay, again, following all the streets. That was the order that I gave to this thing. Okay, that's the instruction that I gave. So we get over here to Reno, Nevada. And this looks good. Again, we're following the streets. I think this is looking pretty accurate down here. It looks like we take another ferry. We go over here to another ferry terminal, okay? And then that is going to take us over to San Francisco. And where does this end up? We go down here, follow the path a little bit more, and we go to San Francisco, Van Ness, and Market Street. And I used to live in San Francisco many years ago. This is pretty much the epicenter of SF, and that's it. So mission accomplished, guys. We got from New York to California to San Francisco, followed the path of least resistance, followed the street maps, right? So we have to follow some kind of like pre-ordered or preset path. It can be a hiking path, it can be a walking path, it doesn't matter, but I don't think you can go through a physical building, right? That's what the first map had it looking like. So I think this looks pretty good. I'm going to wrap it up here. Again, I'm going to share all the code with you guys. I thought this type of project was pretty interesting. I learned a lot by doing this, and I'll share the code with you, and hopefully you find it particularly interesting as well. So that's it. I'm going to wrap it up here. Thanks for your time today, and enjoy the rest of your day. Goodbye. Hey there, everyone. My name is Ryan Schewel. Welcome to my data channel. So in the in the case study today, I want to take a look at an event that was very catastrophic called the Palisades Wildfire. It started back in January 1st, 2025 near Piedra Morada Drive. Hope I'm pronouncing that right. In the Pacific Palisades neighborhood. So basically, is a horrible fire, wiped out many thousands of acres of homes and pristine wildlife, and just a very, very unfortunate event. And police just recently discovered who committed this atrocity. I read this article, this just came up on my radar like a couple of days ago. Florida man arrested on federal crime complaint alleging he maliciously started what became the Palisades Fire. So if you read into the article a little bit, they're talking about well, what was it? Cell phones, yellow, cell phone. Okay, so this is what really caught my interest. So, law enforcement determined using witness statements, video surveillance, cell phone data, and analysis of fire dynamics and patterns at the scene, among other things, that this guy, Render Schnatt, maliciously set the fire just after midnight on January 1st on land owned by the Mountain Recreation and Conservation Authority. Okay, so what that might not mean a whole lot to some people, but what I thought was really fascinating is that somehow law enforcement officials, maybe the FBI, I'm not sure, actually acquired cell phone data probably from a bunch of different people. Maybe they just pinpointed to this one guy and they kind of like triangulated everything together. I'm not sure what the whole process was, but there's two things that really struck stuck out at me. So the cell phone data I thought was very fascinating because any cell phone company, the big three, I believe, is Verizon, AT&T, and Sprint, and there's smaller cell phone providers. But I started to think if you could procure data. Now, when I'm talking about this is very highly confidential, sensitive data. Even I just can't go out and look at people's cell phone data, right? But if you're a high up law enforcement official or a member of the FBI, I would think that you could probably do this pretty easily. So I started to think like, now today is 10, what is it? My eyes are getting worse and worse by the minute here. 10/12/2025. Okay, and the incident occurred on January 1st, 2025. So it took them almost 9 months. And this article came out, when was this? October 8th. So just over 9 months to track this guy down. But I was thinking, like, can't they do that much faster? And, I have nothing to do with law enforcement. I certainly don't work for the FBI. So I don't know the processes and the procedures behind that. But I thought, if you know the longitude, latitude coordinates of the epicenter of where this fire started, and you know people who were in that vicinity, that general area, and you know the people that were at that spot at that point in time, can you pick out the 10 most likely suspects that might have triggered this fire or might have initiated this fire, right? So I looked this up online. Apparently the latitude is here and the longitude is this, right? So we have 34 north and 118 degrees west. Now, like I said, we can't just obtain people's cell phone data. That's obviously a violation of people's privacy, right? But we can simulate using a realistic data set and 10,000 synthetic cell phones, right? I'm going to create data for cell phones and then look at the GPS coordinates of how these cell phones move over time. How are they moving up and down, left and right, north, south, east, and west, right? So I want to go ahead and dive into this case study and see what we can find. Because again, like, I don't know what law enforcement officials were doing. I can only speculate. I don't know why it took 9 months, but I came across this article, I think like 2 days ago. I wrote the code in about a half of a day. I would think that there was just an easier way to go ahead and, like, somehow track down this perpetrator, and it wouldn't take 9 months to do that. But again, I don't know all the stuff that goes into that, okay? But this is what I came up with. So NumPy and Pandas, I'm going to set a seed. Number of devices is going to be 10,000 simulated cell phones. Now, again, I, myself, and you, I can guarantee you and me don't have access to people's cell phones. The cell phone carriers, Verizon, Sprint, AT&T, will have access to this, right? Like, if you're the FBI, you would probably have to make a request or maybe even have a warrant or something. But I'm sure it can be done, and I'm sure it can be done fairly quickly, given the severity of the incident here, right? Again, it was catastrophic. Many people lost their homes. I don't know how many hundreds, several hundreds, maybe 1,000 people, and thousands of acres were burned. So this is a pretty serious thing here, and I think we can analyze this a little bit and try to find out how to streamline the process of figuring out where the top most likely suspects are, given the lat-long coordinates of the event and how all these people were tracked using their cell phone devices over a period of time. So I set the start time as 12:31, and this is 12:31, basically the beginning of the day, and we're going to go to the end of the day, 2025-01, and this is midnight. So we have like 2 days of data here. Okay, so 48 hours of data, and I want frequencies to be 15 minutes. We can look at 1 minute intervals. I don't know if that's going to help us make a more accurate prediction as to which device is associated with the person that caused the fire. I think 15 minutes is sufficient here. We can run the analysis pretty quick and pretty efficient. And again, I think this is sufficient to get to the granular detail that we need to get here. But of course, you can change this. You can make this to 5 minutes, right? You can set this to 5 minutes. If you need 1 minute, you can set this to 1 minute. You'll have a lot more records generated, and it'll take a little bit longer to do the analysis. So that's the trade-off there, right? You can probably get a little bit more precision in terms of how the analysis is worked out. But is that going, and it's definitely going to cost you more in terms of compute time, right? And time just to wait to see what the final results look like. I think 15 minutes is totally fine in this case. So just to isolate things even more, I'm setting up like a 48-hour window and saying that the event occurred within this time period, but we can actually start an event start date, and we can set an event end date and see if that can help us even make a more precise determination about what happened here. So I'm going to use Haversine distance to look at the overall distance from the incident to all the cell phone users and tracking their devices, and then try to see what the distance is. I'm going to try to minimize this distance, right? And then by doing that, pick the top 10 people that are most likely associated with this incident, right? And we know now it was just one. It could have been two. I think if you go for 10, I think that makes sense. Again, you can set that number to whatever you want. You can say, I want to look at the top 100 cell phones that were closest in proximity, but then you would have to track down 100 people, do 100 investigations, go to 100 persons or people's houses, right? And again, this is just an assumption. These are all assumptions I'm making, guys. This is not absolute guaranteed concrete truth, but I think the assumption of 10 cell phones moving around all over the place, right, close to the proximity of the epicenter of this horrible event, I think this is fine. So that is the setup there. Haversine distance is going to show us the distances from the cell phones to the site. And we are going to go ahead and create simulated cell phone. Let me kick this off because this will take a couple minutes to run. Control Enter. So we're going to simulate cell phone users and the tracking. We're going to assume that they are moving around and tracking. And again, like I don't have access to this data, and and nobody does unless you're a cell phone company. The FBI would have to go ahead and make that request. But you could easily dump that into this model. You won't have to create your own simulation, right? You would just load the data that you have, actual cell phone data, with the actual lat-long coordinates, and you get the output that you need, right? So that's the point here. So we're going to go ahead and look at the tracks or the movement of all these cell phone users, right? And it has to be greater than or equal to the start event and less than or equal to the end event. Okay, and I'm copying everything into data frame event. So if you look at my code, I do this a lot. So I create a data frame, do whatever I need to do in it, and then create a copy of that, and then move on to the next stage of the analysis. I think that's better to do. I think that's good practice, because if you make a change in the data frame, which is like the original source code, and it takes a while to run that analysis, because these easily could take hours, maybe even days if the data set is massive. But if you take a copy and you make a change to the copy, and it's actually a mistake, it's a accidental change, then you only have to go back to this step right here, right? Like just saying, if it took a half a day or a day to run this, and this DF event has an issue down here on the next line, you only have to go back one line of code to reinitiate this data frame. You don't have to go back to the beginning and redo all of this from the top. So the point of taking a copy, right, I don't have to go through this again. I'd like to take a copy, because if there's a mistake, I only have to go back one step. I don't have to go back to the beginning. So hopefully that makes sense, right? That is the expectation here. So we have the device ID, we have 10,000 IDs, we have the timestamp, right? Because we have to look at this in 15-minute intervals, and we know the event occurred pretty close to midnight on December 31st, 2024, right? Or yeah, and then, or maybe early 2025, like right at January 1st, the first few minutes, maybe 5-10 minutes into the new year. We don't know exactly what time, but we know pretty close. It was right at the end of 2024 or right at the beginning of 2025. And people think that was probably right at the end of 2024 in the last few minutes, like close to midnight. So we have the event here, and I'm going to go ahead and print the shape. So this is going to show us 4 columns. These are all the simulated cell phones, 10,000 times 2 days. So it's 24 hours times 60 minutes times 15, right? So we have to get this into 15-minute interval. So where was that? I'm just looking for the math here. Yeah, I think it's kind of like built in. We have the number of devices here, 10,000. Let me just see where that goes quick. Yeah, it's fine. 10,000, we have the 15-minute interval, right? That comes from over here. So 10,000 times 15 minutes times 2 days, right? So that's how we get this number here. Then we're just looking for a subset, right? So we get down to 10,000, and then we're going to look for the device ID and the minimum event. So this is the minimum distance from that cell phone, and essentially the user of the cell phone, right? And the original lat-long coordinates that we had defined when the event occurred. And we get the distance event right here. This comes from the Haversine distance, UDF over here. So that is right here, Haversine and kilometers. And you always use lat one, long one, lat 2, long 2, right? So you always have to have like a beginning and end of lat and beginning and end of longitude, right? It's a pretty simple concept down here. The radius right here is 6371, and then we're looking at different degrees right here. So you can just Google it, and this would be a great learning opportunity. Haversine distance. So Google for that, okay? And these first couple ones are probably going to be ads over here. So here's sklearn. I use this a lot in my work. So Haversine distances. This is pretty basic. This is a formula right here. What else? Haversine formula. Yeah, the whole point is that it shows you the distance on a curved surface, right? Because the surface of the Earth is curved. So you have to use some trigonometry over here, right? So you have sine, cosine, what else? Arc sine. I used to have all these memorized when I took calc, but that was years ago. So I would just go ahead and plug in the formula, and you can get that easily if you do calculate Haversine distance Python, and you'll have at least a couple different ways to derive this, right? I mean, there's one true way to do that, but there's built-in libraries that will do this for you very easy. If you want a really cool exercise, you can actually build this from scratch and then compare that to the libraries that are built into Python, right? So here's a good example if you want that. So that would be pip install Haversine and then run this right here, and it'll give you the distance. But again, if you wanted to find the whole thing from scratch and build it from the ground up, you can do that. So that's where we are. So we get the device ID. These are the top 10 most suspicious potential culprits, perpetrators, right? And then the distance from the cell phone device to the actual lat-long coordinates where the event was triggered, right? So let's map the event point and look at the top 10 closest samples. First, we need to make sure that the top 10 table includes the lat-long coordinates by the minute where each device hit its event day minimum, okay? So that is what we're gonna do in the next step here. So we have the data frame event that comes from back over here, right? If you go back a couple steps, you'll see that data frame event. We're adding in the kilometers, the timestamp, the device ID timestamp, minimizing the distance, right, to find out who's closest to the what's it called, the origin of the disaster. And then we're going to group by the device ID and the kilometers kilometer distance, that's the haversine distance, and look at the minimum distance. And we'll use that to create the top 10 points, and we can display the top 10 points. I also want to plot this on a Folium map. So I do a lot of work with Folium maps and Plotly maps. I like Plotly, I like Folium. They're both great tools. You can pick and choose which one you have a preference for. I like both. Sometimes I'll switch back and forth between them depending on what I'm trying to accomplish. And I think they're both great. They probably have their pros and they probably have their cons. Usually I'll try both and see what the outcome is and see which one makes more sense. You really have to pick the right tool for the job. You can pick Plotly and do it that way. You can pick Folium and do it that way. I went with Folium, right? And I'm adding in a couple of different parameters, the center of the latitude, center of the longitude, and I'm building up the map. So this is going to be a Folium map right here. So it's interesting with Folium and Plotly is different code and kind of different look and feel of the code. But in terms of how the charts are built, it's exactly the same. You take different layers, you start building in different events or different lat-long coordinates or different items from your data frame if you want pop-ups when you mouse over the chart or the plot that you create. So there's all these different markers that you can set to, right? So we have here the location is going to be the latitude and the longitude. The pop-up is going to be the event. The tooltip is going to be event location, and the icon is going to be colored red, and we add this to M. So this is what I was referring to a couple of minutes ago. You build these different layers, you keep adding layer onto layer onto layer onto layer onto layer, and everything is called M, and everything gets appended onto M, and then right at the end, you display the results of M. So here I'm creating a circle with a radius of 100 meters right here to make sure we capture everything. The location, the color is going to be red, fill-in will be true, and all this gets added to M. So you can see how this goes incrementally, step by step, piece by piece, brick by brick, right? So we go in the next step to location. The radius is going to be 6 meters now, 6 meters. And this is all metric. I'm in the US. Everyone in the US uses the US standard system. I wish we could get off of that and use meters, but I think I know most of the people in the world are in the metric system, so they'll use meters, so I'll go with that. If you want to do the conversion, totally fine. I think if the audience is only US and you're only staying in US, it might make more sense to use the US standard system. I know YouTube is broadcast all over the world, and I will pretty much guarantee most of the people that see this video are not in the US. So I'm going to cater to that audience and just make everything metric. So we get down to the end again, add to M down here. The last step is for location. This is the row of the data frame. We're looking in the latitude and the longitude. Again, row, lat, long, target latitude, target longitude, and plot this, right? So that is the breakdown of this script. So over here we have the top 10 devices, the timing of the event. You can see that all of this is late in the day, 2024, right? That's when it's assumed that the incident occurred, right? So this is like 4 p.m., this is 11 p.m., this is 12:15 p.m., 12:45, and then we have the distances, right? So in the next step, I want to take all of that information, again, true that up, make sure everything's fine. We have the device ID, the minimum time, again, it's end of the day, 2024, the lat, long coordinates, and distance to the event. So here's my Plotly chart. If I zoom out, you can see the whole United States, right? But I'm going to zoom in here, and you can see basically based on the lat, long coordinates where officials predicted that this event was initiated, this horrible catastrophe started, was right here. So this is the lat, long coordinates of the event location. These are the top 10 cell phone users. So we don't have people's names. That's totally to be expected. This is anonymous data. We can convert anonymous data to like a name recognition. So we have a person's name and address and contact information. We certainly have the cell phone because they're carrying their device on them when they committed this crime. So these two are within the area of we defined it as 100 meters, right? So 100 comes from over here, radius of 100, and we're looking at all of these people and who's closest to this. So we have device, that person, that person, that person, that person, that person. So we have the top 10. We can go ahead and reach out to those top 10 people, start the investigation. But these top two right here are the most suspicious ones, right? They're close to the event at that time, at that date. So those two would be the primary um, initiation, investigation. I don't know what it's called because I don't work for the FBI or any kind of law enforcement agency. But those two really jump out at me. And if we contact those two and get no traction whatsoever, we have 8 more because we have the entire top 10 list right here. And if none of these top 10 work out, we can broaden the parameters for the search even more. I can pretty much guarantee it's going to be one of these top 10, most likely these top 2, this person right here, right? Device 08657, it looks like, and this 07134 doesn't work out. Look at the other 8 that doesn't work out. Broaden the parameters of the search, and I think you would have a shakedown at that point. So that was my take. Again, I don't know why it took 9 months to get the guy. I'm glad they did it. And I don't know what goes into all these investigations. Maybe you need warrants. Maybe you have to, there's some precedent or some what is the thing? Precedent or legal requirement or something. So I don't know what goes into it. What was I trying to think of? What's the word? Standardization, cosmopolitan, I forgot. I don't know. Anyways, maybe there's some precedence required. It takes 9 months, but if you want to do a quick and dirty analysis of cell phone data, who's closest to what lat long coordinate at a specific time, on a specific date, this is how you can do it. Okay, so I just thought about the exercise yesterday, put the code together, took about a half a day. There some really nice results here that I think that we can get in front of the higher ups and start making some informed, intelligent decisions based on this data. So that's it, guys. That's all I wanted to show. Those are my findings with this analysis, this case study about how to catch a perpetrator using cell phone signals and latitude plus longitude coordinates. Hopefully this was interesting and insightful for you. I learned a couple new things when I put this together. So I'm going to save this file in HTML format, and I'll share the code with you so you have all this source code over here. You can run the analysis for yourself, and I will post the code when I post the video a little bit later today. So thanks for your time, guys, and I'll see you next one. Bye for now. All right, everyone, I've got a great lesson for you today. We are going to explore the ins and outs and nuts and bolts of how to find a great deal on a car using Python and some data science analytics. So I found this website just a couple of days ago. Let me show you this thing. It's kind of cool. I looked at a couple different car websites. This one looks pretty interesting and pretty straightforward because they expose a lot of the data on the landing page here. On some of the websites I looked at, you had to go ahead and click into the hyperlink to get more information about the car. Let me look at this, C-A-R-S. I think cars.com was one, right? Pretty obvious, cars.com. You really can't mistake that for anything else. Let's look at electric. Oh, so here's a good example. So here's the landing page for the website, right? You have some cars over here, some cars over here, all new EVs. If I scroll down here, Volvo certified, you have the price and the mileage and the make of the car, but that's it. You don't have a whole lot of detail here. If you click on the link, you can get extra details like color, interior color, MPG, fuel type, VIN, mileage, extra features, entertaining, which is great, but I didn't want to do that much work. I'm a little bit lazy. I wanted most of the details of the car exposed in this page, so you can see that here. So you have 2023 Ford Edge, and I can't click on it. I can't select it for whatever reason. That's fine if I could, but whatever. Maybe I can do this. Okay, so you have 2023 Ford Edge. You have the price over here. Below market, 5,456 below market, miles, no accidents, 4-cylinder, all-wheel drive backup camera. I just like this site because it's exposed here. I don't have to drill in. If I go to this site, I'm gonna have to click on all these links over here and then down here and then down here, and then I can get more details. So you could do that, and I have other videos I created. It's called Parent-Child Relationships. This is the child. If you go back here, this is the parent. So you have the upper level and lower level. You have to click into the lower level, go back to the parent level to go to the next car and do that over and over. You can totally do that. That's fine. Takes a while for it to run, and it takes a little bit more effort to set the code. I didn't want to do it, so I just created this version that's pretty simple and pretty straightforward. You can see all the data on this main landing page. Okay, so that was my motivation for that. So I'm not actually going to run the code. You can see down here, I ran it, and I did my screen scraping. I got page 1, 2, 3, 4, 11 scraped. There was one issue over here. I looked into it. It's one record, and we have um, about 419 or 420 records here. So I missed one, and there was some little disconnect with the web. I'm on Wi-Fi now. Maybe it had a glitch or something. Who knows what happened? So we missed one record. It looks a little bit ugly, but it's just one. We have like 420 records that we can use, and that's enough for the analysis. Okay, so I'm not too concerned about one. When you run it, you can have everything perfectly scraped. If you get this message, don't worry about one record that's dropping out. It's no biggie. So what we're doing is going to this website, looking in this website. If I go over here and right click, and I'm not going to get too far into it today because this is not a lesson about screen scraping. But I do have several videos on how to do screen scraping. But I just wanted to take you through this just so you have like a basic understanding. So if you right click on this and go to inspect, you can see where the source comes from. It comes from this A class. If I put the mouse over it, that 2023 Ford Edge gets highlighted. And if you look closely in here, you can copy this, let's say outer HTML. If I put this into a text file, you can go over here and you'll see all the HTML rendering for that link. And if you look close, you'll see that right here. I think 2023, yep, Ford Edge. So we would look for that tag in here, div tag, and this should have some class. Like if I stretch this out, what does the class say? Class looks like size 16, text gray, bold. So everything with that div class is associated with this detail about the car. 2023 Ford Edge, and if you go over here, 20,688, go to inspect. And why is it not taking me there? Now there should. Did I also get that from there? Oh, here it is. It's the next one. Okay. So if you go over here, expand that div class and this, there's the price right there. If you look real close, 2,688. See my mouse like kind of in the middle there? And you can go down here, see 5456 below market, great price. So that's how you get the HTML behind the website, right? So I told Selenium is an interactive web driver right here. Go ahead, navigate to this website right here, extract that URL, and create a vehicle list right here. I'm going to append everything to vehicle list. So if I do Control F, vehicle list gets everything appended here. The dot append is the property that takes the price, year, make, model, mileage, engine, dealer location, features, and so on and so forth. So I'm parsing that by this. Heading 3 is the price. FW normal, size 12, that's the class name. So you have to look very carefully at these HTML elements. And once you find that, you know how to assign those HTML variables to that, right? I go over here and I can get the price. We just saw that. There's the price, 19,299, and this one has, what is it going? It has that 6,400 below market. Okay, so that's how you get everything. You assign it to these variables and take these variables and append it to the list and take the list and then convert that to a data frame down here. So we have a nice, neat, orderly data frame structured in a way that we can see all the rows and all the columns here, and everything is organized, very neat and very clean. So we have nice, clean price, year, make, model, car details, price below market, and so on and so forth. These are the features here. Everything actually came in together, like all-wheel drive backup. That comes down here. All-wheel drive backup, Bluetooth, keyless entry, upgrade headlights. That is that. And I just told Python to go ahead and explode those features. I have df column name is features. The first data frame had features, and I said go ahead and explode that into features 1, 2, 3, 4, and I think 5. Yep, they have 5 features. So we're splitting that string on the comma delimitation. You can see very closely there's a comma delimited after the all-wheel drive. forward round is a comma. So we split that and expand that to feature split, and we call this I plus 1 increment plus 1. So we get features into features 1 through 5. Right. So we've got that done. That's pretty cool. I saved everything to a CSV on my desktop just because it does take a while to do the screen scraping. This could take 5-6 minutes, could take maybe 10 minutes if you have a slow connection. And if you make a mistake on the data frame, you'd have to go back and get it again. If you make another mistake, get it again, make another mistake and get it yet again. Okay, so it takes 10 minutes to do the screen scraping. You probably just want to do it once, save it to your desktop. And if you make a mistake in the data frame, just reload it from your desktop. This will take a fraction of a second, maybe half a second, and you can continue. If you have to wait 10 minutes for this whole screen scraping job to finish off, you're really doing yourself a disservice because you're going to sit there and wait for something that you didn't have to wait for if you put it into a CSV on your desktop. Okay, so so we go ahead and clean this up a little bit. We have $sign here, and we have a comma over here. So machine learning algorithms and anything in the data science world, most things in the realm of computers don't like $signs, and they don't like commas and things like that. So we're just going to go ahead and do find and replace anything that has a $sign. We're going to replace a column, I'm sorry, a comma with nothing. Okay, that's it. So we're just cleaning up the data frame and then aggregating prices to get a grouped price based on year, make, and model. So if we have the year, make, and model all the same, we can consolidate that into one vehicle. Okay, we don't need 3 different vehicles because then we're creating duplicates. Now you can have slightly different features over here, and of course the mileage is going to be similar, but probably different for different vehicles produced in the same year that have the same make and the same model, and the prices are going to be slightly different, right? But you can take the mean of the price and the mean of the mileage and then consolidate these 3 columns over here. You see this all the time in the SQL world. You see it now in the Python pandas data frame world. Okay, we just want to go ahead and create a mean price down here and then a mean mileage down here if these features are the same. So if year, make, and model are all the same, let's get an average for everything, and then we can compare this price and this mileage to the average of other cars that have the same year, make, and model. Okay, so that's what we're doing there. And I used kind of a little trick. Instead of merging 2 data frames together, I'm going to merge on the left. So if you do a left merge, you take everything on the left-hand side here and take only the matches on the right. If you do a right merge, you take everything on the right and match it with only the matches on the left. Inner merge takes everything it matches, and outer merge takes everything in the whole universe and then merges out together, right? So those are the ways to do that. For my purpose here, I think left is the most appropriate. Then we have our final data frame like this. So we started off with 420 records. One got dropped off. Remember, we had an issue over here with this guy. Where is that? Over here. Sorry. Yeah, if I go up here. So this thing didn't get scraped for whatever reason. I don't know what it is. We lost 1 record. So we have 419 out of 420. I'm not going to lose any sleep over that. That's 1 record that got dumped or got spit out or chucked out for whatever reason. But we still have a decent data set, 419. And honestly, like, more is better. If we had just over 400 cars here, if we had 4,000 or 40,000, 400,000, we could do a much more comprehensive analysis. It'd be more robust and more meaningful. We only have 400, basically because I don't want to sit here and wait all day for all of these screen scraping tasks to finish off. And this would take a long time. We have quite a few pages here. What does it go up to? Let me see. So if we go up to 6, it goes way beyond 6 because I got 20 pages. And keeps going and going. Oh, 126 out of 19,972. So now I'm curious. Now if you have 19,972, so you have 20 out of 19,272. So, okay, so how many pages do they actually have here? You divide that by 20, 1920 divided by 20, like 20,000 cars, I think. And you have 20 on each page. Let's see this quick. Enter equal that divided by 20. Okay, this has some thing over here. Oh, it has a space at the end. Okay. Yeah, almost 10,000 pages. Okay, so I'm not going to screen scrape 10,000 pages. There's no way. And the system would probably shut me down if it saw that kind of activity. It would probably have some denial of service flag popping up or something. So I got the first 20 pages and has 10,000. So we just got a small fraction. So what is that? Calculate. Let me see what this is. We got 20,000, 9,500 pages divided by 20 cars, right? Oh, that divided by, yeah, 20 per page. Yeah, 475. I'm not doing that, okay? I did 20 loops. I'm not doing 400 loops. So anyways, we have all of our data frame assembled nicely here. So we have price here, make, model, car details, price below market, vehicle history, engine type, vehicle location, and then the features over here. Then I created some feature engineering um, features over here. I ran a feature engineering exercise to create price mean, mileage mean, price deviation. That is the price minus the mean. Mileage deviation is the mileage minus the mean, and price rank. So now this gets pretty interesting, right? So we have price deviation, price minus price mean, mileage deviation, mileage minus mileage mean. So that's how we get these two. Price rank comes from here. This is the price deviation. We're assigning a ranking, ascending equals true. So we're saying lower is cheaper. So lower cost price is cheaper car, and that's true, right? That's non-negotiable. Can't argue with that. Lower is cheaper mileage deviation. So we have a mileage rank. So we have a price rank, mileage rank. Lower is cheaper. Feature count. This is the number of features um, plus one. So the feature count is 5 because we have 5 features. 1, 2, 3, 4, 5. Okay, comma separated. That's how we get the feature count. And final rank is price rank, mileage rank, and feature rank. And we're taking the average of these three, right? So we're ranking feature count, ranking mileage deviation, ranking price deviation. So those two and feature rank. Wait, sorry. Feature count is a rank. Feature rank. Oh, here. That we're taking the mean of this and this and this and assigning a final rank to that. So that's how we're assigning a ranking to the cars. We're saying which car is better, which car is not quite as good, which is the worst car. I'm going to get to the top 10 best cars at the end of this. You'll see that in a couple of minutes. And we'll see the top 10 worst cars based on, again, these features. So mileage mean, oh, sorry, price deviation, mileage deviation, and then feature rank, right, to get the final rank. That's how we got that, right? So if you forget, just look at the code. It's all right here. It's all exposed. It's given to you right there. So we are grouping all the features here now and calculating price deviation. I think we did this, right? Oh, no, sorry. We did the price mean and the price and the mileage mean. So it's slightly different, okay? So price deviation here and mileage deviation before. I'm sorry, we did do that. We did that. Okay, so we don't have to repeat this again. We had 2 new features over here. The price mean grouped and the mileage mean grouped. Okay, we still have the same. This is rows and columns. 419 rows. We missed one because there was some weird glitch during the web scraping process. And we created 2 new columns over here. So 419 rows, 22 columns. These are the 2 new columns. Price mean grouped, mileage mean grouped. So we can move on. We are going to group everything together and assign the order that this data frame is displayed in based on the rank. We want ascending equals true, rank ascending equals true, and rank ascending equals false for the feature count. Okay, so higher is better here. Lower is better. So feature count lower is better. And we're going to do everything or sort everything in ascending order by the final rank. Okay, so I hope you're sticking with me. It does get a little convoluted here, but don't worry about it. You'll have all this code. I'll share all the code with you when I share the video just a little bit later today. And I've got my notes in here too. Okay, so rank cars based on cheap or expensive, normalize the features for easy comparison, and then sort the final rank by cheapest to most expensive. So we're looking at value vehicles here. We're looking at cheaper cars with relatively lower miles and relatively lower price. This is going to get a higher ranking in our ranking order system hierarchy here, and more expensive cars are going to get a lower ranking. Okay, if you're Mark Zuckerberg or Jeff Bezos or Bill Gates, congratulations. Most people are not like that, so we're looking for value. We're looking for deals here. That's how we're assigning our ranking. Okay, so I'm going to go ahead and create a k-means clustering experiment here. I don't know what the actual number of ideal or optimal number of clusters is. So I'm going to loop through a range of 1 to 11 and let k-means uh, k-means algorithm tell me what the number is, the maximum number. You could say 4 or 5. It's where the elbow bends. If you bend your elbow where the curve bends, the most is probably the optimal number of clusters. It's really getting flat by 7, 8, 9, 10. That you really can't argue with. And it decreases quite a bit from the number of clusters starting at 1200, right? There's no way we need 1200 clusters. We get down to 6, or sorry, inertia is the sum of square distance. Number of clusters, 1, no, because we'll never have number 1 cluster, right? There's no point in doing clustering if you just have 1. 2, 3, 4, 5, 6, I think is optimal. That's what I use over here. So I said, give me a cluster of 6. Where's my 6 here? I think I said 6. What? I don't see a 6. A second here, 6. Oh, yeah, okay, okay. That's it. So, yeah, you don't see it over here. It's telling you to loop through 1 to 11. Right, that's what we're doing. I'm saying it's 6. You could argue 5, maybe 4. I think 6 is okay. You can do 4 or 5. Doesn't really matter. I'm picking 6 here, and I'm saying give me 6 clusters based on car details, price, mileage, and assign a cluster. So assign a cluster to the data frame right here, and then displaying the results based on car details, price, mileage, and cluster, which we just created. Created a new feature here called cluster. Then we're going to go ahead and create a scatter plot of all the clusters. So we have the if group, that's our data frame, price and mileage. It's going to be the X and Y. The color is going to be the cluster. That's normally how you do it. You can pick another color if you want. I think cluster makes the most sense. So you can see here, these are all 0 clusters. Go down here, you have cluster number 4. This is cluster number 1. You can see obviously the bubble pops out from the chart. This is cluster 2. And down here in yellow, we have cluster 5. So everything that is assigned by proximity to its neighbors here is the same cluster, and everything that's homogeneous will go into the same cluster. Everything that's heterogeneous goes into different separate clusters, right? So I just zoomed in here. That's why I like these plotly charts. You can mouse over, you have the animation here, you have the pop-ups, so on and so forth. So we have all our clusters. That looks nice. And we have a couple cars over here. This is a P400 SC four-wheel drive. Price is 104,000. Mileage is 12,000. You can see it's a lower mileage here. The prices tend to be more expensive. Although if you get to, you can buy some cheaper cars over here for under 20K, right? And the mileage is pretty low. Here we have 8,900 miles, 12,000 miles. Here the price really drops as you get more and more mileage. Here you have 157 miles, 150 miles, 150,000 miles. This is for a cargo van. Another cargo van, low roof cargo vans. Cargo vans are pretty popular, I guess. Here's a LX four-wheel drive SUV. Price, oh, here's a GT Quattro sedan. Price is 10,000, mileage 74,000. So everything is working like it should with the clustering, with the pricing, the mean price, mean number of miles. But actually, what is the best car here? We still haven't answered that question, right? So we're going to try to derive that in just a minute. We have, again, the car details. That's important. Price, mileage, P-score, and mileage score. So now we're looking at extreme examples. Anything that has a Z-score greater than 3, absolute value of 3, so greater or less than -3, right? And greater than +3 or less than -3, absolute value. Anything is greater. This is going to be an outlier, okay? So we're going to have price Z-score and mileage Z-score. So these have higher mileage, right, for the category, and higher prices for the category. That's how they're getting these high Z-scores, right? These are outliers. So we'll use that in our final analysis to determine what are the top 10 best cars and top 10 worst cars. Now we have, again, the price and the mileage scatter plot. So over here, you can see the type of car again. You can see all the car details, the Z-scores. So before we had just, remember in this plot, the price and the mileage, right? Everything is plotted out there, and you have the the color bar plot on the right. Um, that's called the legend. The color ranges over here on the right is a legend, and over here again you have a similar legend. Here you have one car. The price is 104,995, and this is an outlier for both the price and the mileage, right? So that one gets kicked into the C score bucket over here. So the final thing we need to do is take the price Z score, right, and look at the minimum, look at the maximum, divide the min by the max rate, and we're doing this a few different times by the mileage, price deviation, feature count, feature rank, to try to get the top 10 recommended cars and all of the cars. Remember, we had 419 cars. Of the 419, these are the top 10 recommended, and these are the reasons why. You have the car details: sedan, four-door hatchback, Model Leaf. Price is 11,000, so relatively cheap compared to the others in the group. This is 15,000. This is 21,000, 19,000, so pretty cheap. Pretty low mileage, only 12,000. This guy has 13,000. The scores are very similar. This is just probably slightly more because this has slightly less mileage. Otherwise, these cars are almost identical, right? This one just has like 400 miles, 400 miles more. This has 400 miles less, right? The price mean is the same as it should be, and the mean mileage mean is the same. Price deviation is basically nothing, and the mileage deviation is 194. Okay, so these are the top 10 cars, okay, and the whole universe of cars that we looked at, these are the top 10, and we can sort the final score in ascending order, okay, with this Range Rover. Oh, and yeah, top 10, I lost track for a second there. This is the top 10 recommendations as being the best cars, right? And you can see why. Pretty affordable, 19K, low mileage, 15K, not too bad, pretty low mileage, 20K, that's probably the highest one, but again, low mileage, 5,300 miles. These are the worst cars based on these metrics: price, mileage, score. Okay, so this is 104,000. I don't have over 100,000 sitting around my bank account, so this is off the table for me, probably for most of the people here. 95K, 100 and uh, oh wait, 9,500, but this has a lot of miles, 157,000 miles. This is relatively affordable, 11.6, but high mileage, 68,000. It's a lot. Now high mileage, but 37,000, almost 40, getting up there, right? 12,300, lots of mileage, lots of mileage, lots of mileage, lots of mileage, right? So these prices a little bit lower, but the miles are up there, right? Like, is this thing going to last too much longer? Who knows? Might be near the end of its life, but these are the 10 worst. Okay, worst 10, and these are the top 10. You could call this the best 10, top 10, whatever you want. So in summary, I think I had one more chart. Yes, this is the top 10. That's what I'm looking to plot here. If you want the bottom 10, you could certainly get that. This would probably be one of the cars recommended. About 11,000 for the car. Mileage is about just about the same. About 11,000 mileage, 11,000 price. No, 13,000 mileage, 11,000 price. Here the mileage is 8,000. Price is 13K. Over here you see the price of mileage, price of mileage, price of mileage. Here, preload miles 2,300, and the price is 22,000, basically 21,000, right? You can round up by a dollar, $22,000, 22,000. Sorry. So that's it. So that's how to find the best cars and the worst cars in a data set of cars using a few techniques: average price, average mileage, ranking, methodologies, and everything coalesces or arrives in some type of confluence arrangement in the final analysis here in the final data frame. So that's it, how to find the best cars and the worst cars. If you're into that kind of thing too, I just show the worst just to be comprehensive there. Really, you probably can ignore this. You should really focus on the top 10 best cars, which is right here. So that's it, guys. Hopefully that was informative and enlightening and useful to you. I learned a little bit putting this stuff together, but I knew most of this stuff, so it's pretty straightforward for me. So I just wanted to share that knowledge with you, drop some nuggets of wisdom. Hopefully that helps with your learning experience as you, complete your journey through learning Python and data science and machine learning and all that good stuff. Okay, so I'm going to wrap it up. Thanks for your time. Enjoy the rest of your day. Bye. Hey there, everyone. Ryan Schul, Straight Data Science. Welcome to my channel. So, for the topic today, I want to talk about creating a carbon footprint tracker, and we are going to base everything on zip codes around the United States. Okay, and at the end, I'm going to aggregate everything up to a state level so you can see what the total state carbon footprint is. Okay, so why do we even want to do this type of analysis? This is a multifaceted type of answer. Basically, for targeted climate action, okay, we can look at zip code level data and understand the emissions, and are they increasing, are they decreasing, what are the emissions by zip code, and how dense or how non-dense are the emission patterns in certain zip codes, right? And with this data, we can understand behavioral and socioeconomic drivers, income, commute times, home sizes, household behavior, how much waste does a household create, things like this. That's what we're going to look at. We can promote climate equality, right? This helps identify communities with high emissions, but low access to clean technology like solar power, wind power, hydropower, things like this. We can inform policy decision makers, urban planning, architects, utility strategy, concepts, and any kind of legislation related to that. Okay, we can do city planning and utility production and the modeling and the utilization of those. We can make that more optimized and more efficient. We can track progress over time. We can look at local governments and understand, based on the zip codes, how to set emission targets or how to try to cap emissions from different zip codes, right? And also to engage citizens with localized data, because this is specifically pertaining to them. This is directly relevant to the people that live inside of these zip code borders, right? People are more likely to care about what they can see and have a direct impact on. Okay, and if my zip code emits 22 tons of carbon per year, and this is higher than my neighbor's zip code, how can we correct this action, right? So we can almost create like a competitive sort of vibe to this type of thing, and how people ultimately to lower their carbon emissions. Okay, so on average, there are about 33,000 zip codes in the United States, just over 33,000. Basically, you have the 5-digit zip code that can start with a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? It has 5 digits. Some of the more specific areas or delivery locations actually have an extra 4 digits on the zip code. We don't really get into that, but I guess that's good to know. Zip codes are used for more than just mail. They're also used for statistics, marketing, and even internet applications. Okay, so that's important to know. And we're going to create a choropleth map similar to this one. So this was the motivation for my analysis. I found this about 2 days ago, and I thought this was kind of cool. And I said, okay, I'd like to be able to reproduce this map. How can I do that, right? So that's what I undertook, right, on my own initiative. If I zoom in here, I can see New York City. This is where I live, and I can see my exact zip code, 11101. Sounds like the first zip code ever, 11101, and we have 31.6 carbon tons of emissions output per year. Okay, so basically, if we zoom out here, we can see the entire United States. I'm not an expert here, but I think the zip codes start in the Northeast. If we go over here, I see some low numbers over here, 04, 07. This one's a little bit redder, so they have a little bit higher carbon emission, 48.8, 04, 745, 04756, and 04746. These guys are a little bit lower. Okay, so anyways, zip codes start in the Northeast, and I think they continue down the East Coast, and they wrap around Florida or something like that. And I think they end in the Pacific Northwest, because you see some high numbers over here. We start with the 04s on the East Coast, then we get to 98357, 38.3 emission. This is higher emission over here, 67.9. So this is more of an urban area, I believe, and maybe an industrial area. And then you have some higher emission zip codes over here, 54.2, 54.1, 52.4. So anyways, that was the motivation for the analysis that I undertook. So if we jump into it, I can actually download some historical ZCAT5 data, which comes from over here. Okay, if I hit enter, I can download this right here. I'm going to not download it because it's actually already downloaded. This is in my desktop, and it is called All Files. So I put all the files into this folder called All Files. So the interesting thing about this is it has a SHAP file. So this has all the shapes of all of the geometric patterns for all the zip codes throughout the United States. That's what the SHAP file is. And apparently there's some dependencies over here with some of these XML files, PRJ, DBF, and CPG, I guess, because I tried to run this just on the SHAP file and it didn't work. It's giving me an error message saying that it needs all the other files as well. So as long as all the files are in the folder, you can go ahead and run this. You can put some padding on these zip codes because some of these will actually come with the leading zeros truncated. So if you start with a 0, like we saw in the Northeast, you would actually have 4 digits, right? They append the 0 onto the beginning just to create a 5-digit zip code, right? So we have to pad this and force these zip codes to be 5 digits if they're not. And this is what it looks like when it's printed out. Okay, so now we have all the zip codes and I can go ahead and print the number of rows, and we have about 33,144 zip codes in the United States. So I got one more source of zip codes. This came to me from here. So I put the URL in here, put the other URL too. So you have that. That's where you can get the SHAP file and all the dependencies. This is where you can get all the zip codes. And I see here we have 33,782. So slightly more than this 33,144, slightly more granular perspective, I guess. And it is what it is. It's about 33,000. I have 33,100 here, 33,700 here. As long as we have good coverage, I think it's fine. These are the zeros I was talking about before. You have to pen these on to the beginning of the zip if it doesn't exist, okay, because the leading zeros will be dropped off. And if we just do a quick sanity check here and Google it, zip code, it says Adjunitas, Puerto Rico. And if I go over here, I see Adjunitas, Puerto Rico. So I think everything's fine. So we have the zip codes. We have 33,700, 33,100. I don't think it really matters how many zip codes we get. As long as it's over 33,000, we have good coverage here. So I want to go ahead and look at zip codes, income, commute minutes. Now this is synthetic data that I created. I couldn't find the actual data I was looking for. I was looking for data related to zip codes and showing me commutes and household sizes and regional factors. I couldn't find it, so I created it, okay? So this is pretty realistic, but it is, why is that MP? Okay. Okay, it's complaining about this. All right, now you're happy, right? So we have the zip codes. Now I just want to get a quick visual understanding of what we have here. So here's the zip code. It's repeated. I'm not sure why. Then we have a classifier. This is some kind of geocode over here. I'm not sure what that is. This looks like geographical, long coordinates, right? So it's -83, 615, 41, 318. And I can prove that if I go to Puerto Rico, maps, just generally speaking, okay, Puerto Rico. And let's see what kind of zip codes they come back with. Okay. Here, I'm not even sure. I'm not even sure what this looks like. Oh, wait, maybe, what was that thing called? What was that? Adjunitas. Okay, let me just look at this thing on the map just to see what we're dealing with here. Okay, Adjunitas. It's there. It's definitely there. So, okay, it's not giving me any zip codes there, but that's fine. It's part of Puerto Rico, and it's called Adjunitas. So anyway, so we go back to the data set. I think I just ran this. Let me just do it again just to make sure. And here's the GDF data frame. If I look for this, this actually comes from here. So this is the SHAP file that I originally imported. This is global data frame. I think that's what the abbreviation was. I forgot what I named that for, GDF. And then we have another DF zip, and DF zip comes from over here. Put that in there. Then we have the DF, and that comes from this data frame that I created over here. Okay, so everything looks fine. I'm going to go ahead and merge these two right here. So GDF is merged with data frame on zip. So we blend these two together, and we are creating the join right here, left join. If I go enter, oops, I need to hit that, control enter, 33144. So in this case, it doesn't matter. All these zip codes match. If I did a left, right, or enter, probably get the same amount, 33144. Yeah, so everything is exactly the same. So left, right, or enter, it doesn't matter. I like to use enter. Everything that matches shows up. Left is going to show you everything on the left and all the rights that match up, and right will do all the rights and all the lefts that match up. Okay, so pretty standard stuff. So now I'm going to go ahead and create a Folium map. Folium maps are very useful for all kinds of different things, for plotting, charting, geographical, latitude, longitude coordinates, all kinds of different stuff, right? So I want to go ahead and create a simplified map, simplified, and this is going to be based on geometry. If I show you where this goes, it goes to map df sample, right? Simple or sample, basically same thing. So that's going to be the source data for this. And we're looking at 10,000 different zip codes. So the point of this is to make the map render faster and generate faster than if I used all 33,000 zip codes. That's going to take a little bit longer. If you need all 33,000, and I'll actually do that a little bit later, I'll get all 33,000. That's totally fine and well and good. If you just needed a subset of this, this whole population, this whole geographical layout of all the zip codes, then you could get it this way, right? Just taking a random sample, and we'll see how the map is rendered down here. We'll see that this uses GeoJSON data. So JSON is short for JavaScript Object Notation. This is just the way that all the data is rendered, right? So it's rendered as JavaScript, and it looks a little bit funky if you look at it, but it's actually a very efficient way to store and to retrieve data, and computers can process this JSON data seamlessly and very quickly and effortlessly, right? So even though it looks kind of weird, when a person reads it, it's a very efficient storage medium. So it's pretty popular to use this data format. Okay, so this is going to load up into geo data, and the map comes from df sample. Okay, so that comes from here. You can see the df sample is right here, and that is the first 10,000, or not first 10,000, but a random sample of zip codes across the country, 10,000 zip codes. Okay, so I think the map is rendering. This does take a little bit of time. I did this yesterday, and it showed up in a couple of minutes. It does take a couple of minutes, however, though. And I had to redo this video, by the way, because there's no sound. I don't know what happened yesterday. The sound bar was bouncing up and down. I'm looking at it right now, it's going up and down, up and down. So it indicates to me that it's working fine. However, when I posted the video, there was no sound. So I don't know what happened between recording the sound and posting the video, but somehow the sound got stripped. So I had to redo this. So that's how we got here. So just waiting for this thing to render, and then I think I'm going to go ahead and actually get all the zip codes and put everything into this this whole package here. So if I do Control F, I can see map simplified to JSON. I want to put that into GeoJSON, and map df sample. I want to map that. And then of course the two columns I'm looking at is zip and total carbon footprint. And if you look closely, that comes from over here. Here's the zip code, right? Actually, it matches that. So you can use any one of these columns. That's the ZCTA code, which matches that, and it matches that. So you can use the zip code. We have income, community, commute minutes. This is the time, the average time to commute to work for the people that live in this zip code, and the average is just an average. Some people will be more, some will be less, right? Household size, based on the household size, the regional factor, and the noise that is emitted in this area, we can calculate total emissions. So we have transportation emissions. This is going and coming back from work, going to work and coming back. Home energy emissions, this is directly related to the size of the house, right? The bigger the house, the more the emissions, presumably, not always, but pretty much that's the rule. And then waste emissions. So this could be like garbage, recyclable, non-recyclable waste, things like even was it fertilizer or compost, things like this. That's not going to create a whole bunch of CO2 emissions, but there will be some, right? So we can sum all these together and get the total carbon footprint. And again, that's the sum of this, this, and this. So transportation emissions, home energy emissions, and waste emissions. Okay, so let's see how the map is doing. Still working. So that is running, presumably, hopefully. Okay, we'll give that another one more time here, another few seconds or whatever. Hopefully this finishes off pretty quick, and then we can move on. I was hesitating to even run this thing, just use the previous run. I wanted to show you that the code actually works and that doesn't just look pretty, that it actually does something too. So that was my intention here. Let's give it a minute. Hopefully it responds something favorable. Okay. And again, if you look at this, we're just putting in the inputs into geographical data. This is the GeoJSON. This is the data. That's the sample data that we came up with. The columns are zip and total carbon footprint. Key is the feature properties with the zip code. The fill color is yellow, orange, and red. Okay, so you'll see like some brown tint in there too, yellow, orange, and red are the main ones. Fill opacity is 0.07, so somewhat opaque. Line opacity is 0.02, so more opaque, the more translucent it is, right? And the darker the color, the more filled in it is. Okay, so there's the 10,000. And the next one is running with all the records. Okay, so instead of just 10,000, we can see everything. And if I put my mouse over the FIPS data, this is, I'm sorry, zip data, this is not FIPS. FIPS is something different. If I put my mouse over the zip code data, you can see the details here and then the carbon emissions from each zip code. So I see 10075, this is Manhattan. These are my neighbors over here, 10.2, 13.74 for 10021. If we go down here, 10009, 12.17. This is metric tons emitted. Carbon footprint, metric tons. This is a little bit higher, 15.9. These guys are dark red, so this is even higher, 17.7. This is probably the Bronx, 10471. If I Google that, let's see, Google 471, right? Zip code Riverdale, neighborhood of the Bronx. That's what I thought. 10471. That's what it looks like. And this is what it looks like on the map. And the neighbors over here are doing about 13.37 metric tons and 12.03, 10470. So it should be right next door, right? 470. And indeed it is 10470. This is Bronx, New York. So it's just called Bronx. The other one was called Riverdale. Okay. So the main point is we have 10,000 different zip codes rendered and displayed in this geographical map, this folium map right here. We have a few things down in Cuba because we have some zip codes down there, right? And Hawaii actually got picked up too, and they have carbon footprint about equal to New York. So that's interesting, 13.6. Even these guys over here have 13.12, right? So we have pretty much the entire United States covered, even Alaska, but there are some gaps in here you can see because we only got the 10,000. I wanted the map to be displayed pretty quick, but I had a change of heart here and I actually want to see the full display with all the zip codes filled in. Okay, so that's what we're getting here. And again, this data comes to us in the form of JSON strings, right? If I put that in here and show it, this is what it looks like. So that's what I said before. It kind of looks funky. You have all the lat long coordinates right here, and then all the relevant zip codes. Not fun to look at, but again, if you feed this into the computer, it is going to interpret this very quickly, very easily, and decipher that effortlessly. So you can see all of the lat long coordinates and all the zip codes rendered perfectly on your map, right? So JSON data is great for storing and retrieving data, not great for reading for a person, but it's great for the computer. So as I move down here, I'll move down to the next cell. We can come back. I can discuss this in a minute. I have another file called US zips over here. So this is saved on my desktop. This is what the file looks like. If I open it, you will see, what is this? The state and the state ID and the zip code. I believe that's what this is. And it's opening right now. Okay, so we got a bunch of stuff here. So the zip code, and you can see this leading zip codes, the zeros are truncated. That's just the way it comes in. Also, that's the way it's displayed in Excel too. Like if I do, let's see, left. how do we do this mid left? I forgot how to do padding in here. When something like this, give me a second because I know that code is going to run too. Plus two. If when less than 5, comma, and that I think I can add on the zip code like that. Does that work? No, it doesn't like it. Oh, 00061. Okay, so I got something there. And I think I can put that there and then fill in. Okay, so see, it should have six, I should have five letters in the zip code. And these are letters, by the way, these are not numbers. Even though this looks like a number, it's not a number. And you can't do any kind of math on zip codes, right? It's absolutely meaningless to try to do math on the zip code. It's just a designation for one region of the country, right? So what do we have? Lat's long, city, state ID, state name, and so on and so forth. So that's what comes to us from this data right here, the DF zips. You can download that from this website I gave you at the beginning. All right, if you look over here, DF, that gives you all the SHAP files, and this will give you the DF zips, right? So these are the zips over here. So you can get that and then load that. And this thing just disappeared on me. Oh, it's back. Nice. Okay. So that will give us all the zip codes. And if I go ahead and run that, I can see what this looks like. It says merge with emissions data error. Name cool climate data is not defined. Let me see what is going on here. And then I'm going to go back. I don't like these things that kind of just skip around like this. This was totally working yesterday when I recorded the video, and then there's no noise. And then today it's giving me a weird error. Something doesn't exist. And yesterday it did exist. So I don't know why these things are missing, although I did have to regenerate all this code because I actually deleted it yesterday. I thought the audio was working. It's not working. I don't know what's going on with that. Okay. So anyways, here's all the zip codes, 33,000, right? When we put the mouse over it, we get the pop-up or the tooltip that comes up, right? And if I zoom in, this is going to be a little bit slower because now we're working with 33,000 zip codes instead of just 10,000. Well, you can see it's pretty comprehensive, right? And most of these zip codes are filled in. Now I zoomed in too much. So let me go out a little bit more. And that looks like Connecticut and Long Island to me. If I go down here, we'll get to New York City. That's where I am. Okay, if I zoom in a little bit, we can see all the details for all these zip codes. And you can see how this pretty much matches the sample I showed you at the beginning of the video here when I showed you my motivation for creating this kind of demo here. And if I go down here, I can find my zip code 11101. That's where I am. We have 16.6 metric tons of CO2 emissions. The neighbors 11106 have just about the same. And down here in Greenpoint, they have just about the same over here. A little bit less. No, a little bit more. No less. 12.79. We have 16.61. So we have to kind of get our act together, guys. So that's motivation to clean up your act, literally, to clean up your carbon emissions act. So it's nice how you can zoom in and zoom out on all these different zip codes throughout the United States. Let me see if I have something. Okay. So I'm saying cool climate data. Oh, but I don't need that. Let me see. Let me see where this is coming from, because just give me a minute, because I had to rebuild this whole thing from yesterday. A mess. I mean, like everything is totally working and the audio doesn't work and then nothing works, right? So let me go back here. Okay, so carbon footprint. Let me look at the other file I had, and now it wants to go slow too. Man, I'm telling you, man, this is like just never ending nightmare stuff. So if I go over here, where is my cool climate data, right? Because it literally worked yesterday. So, and what changed here? If I do Control F, and go over here. Okay, so we have that. Oh, and that's exactly the same thing. So that's why I understand why it would work and then it doesn't work. And do we even need that? I'm thinking maybe we don't need that because look at this. If I do this and then this, and then state total carbon footprint. So okay, let me go over here. And this is map DF. Okay, so I think I can just merge these two. I don't even know I had a cool map DF over there. I don't know what that's about. Anyways, let's get this cleaned up. So I think I can get this out and let me just give this a go and see if this will work. And it does. Okay, so I didn't even need the other thing. This is superfluous, extra, and unnecessary. I don't know what that's doing there. I don't know why it would work yesterday and it doesn't work today, but okay. So we have the total carbon footprint. Texas, Pennsylvania, New York, California, and Illinois, presumably from Chicago. That's the biggest city in Illinois, and I think the top three in the United States in terms of population. So that's how they make it to the top 5 list there. And if I look over here, we are just basically grouping by state and then summing the total carbon footprint, right? So all the total carbon footprints come from over here. Okay, total carbon footprints, and we're taking everything by the state, merging those together, and then summing all the carbon footprints. Okay, so hopefully that makes sense. It's pretty basic aggregation. And Python in the bottom 5, we have Delaware, DC, which is a district of Columbia. It's not even a state, it's a district. I think they did that. So no state would have superior influence or power over the governments, the legislative, judicial, and what is the other one? Executive branch of the government, right? So it's not a state, it's a district. And then you have, I think this is Guam, Virgin Islands, MP. I'm not even sure what that is. Sure what that is. What is MP? It's some kind of U.S. territory. That. Northern Marina Islands. I've heard of that. Never been there. I don't know anything about that. And AS is the smallest carbon emitting U.S. territory. And what is that? AS is it U.S. territory? Oh, American Samoa. Okay. Gotta love it. So American Samoa makes it to the list, and they emit the least carbon emissions here. So we can go ahead and plot this on a chart and see what this looks like in a basic bar chart. Okay, and then I can go ahead and plot this on a regular geographical map, and we can look again at the what's it called, choropleth map. We can look at the choropleth and see how that looks relative to all the other maps that we saw before we saw all of the zip codes, all of the United States, right? When we look at this big picture, this is macro picture, we're going to see the United States map in all the states around the United States. Here we can see Texas has 26, right? If we go over here, 26,000 metric tons, PA 24, New York 24, California 23, and Illinois 18. And we see the same thing down here. So PA, New York, California, 24, 23.8, and then Illinois rounding up the top 5, 18.82, and that matches exactly with what you see over here, 18.82. Okay, so that makes sense. If we look here at the choropleth map, EF states, now I'm getting this error. So this is great, guys. I don't know why it keeps doing this. Literally, yesterday it's working, the audio doesn't work, and today this thing doesn't work. So I have to look at this DF states and see what is going on here. I'm telling you, man, if it's not one thing, it's another thing over here. I don't know why these things just can't work ever. Guess that would just be too easy. And then My job would get boring really quick, I guess. Let me try to fix this up. Okay. um, DF states is a geodata frame, contains state boundaries. So I get it, but why was it working yesterday and now it's not working today? So if I go here, GDF states, was that over here? Because this was my original code yesterday. They have GF states. Oh, and I did GF states merge. But I have just GDF states because it doesn't look like it. GIF total. So it's coming from there, right? So let me try this. Oh, I have the states and the abbreviations, all the names there. So I could have dropped that. Let me make this a little more easier to read and pull that up. That. And voila, we got our states. Okay, so this is good. We have the top 5. The darker colors represent more intense emissions, carbon emissions, right, in metric tons. New York has 24,000, 24 for Pennsylvania. Texas has the most, right, 26,180. California is 23,820. We go over here, 26,180, 24,192. 23,280. That's it. 23,280. 23820, 26,180. 26180, 23820. Okay, so I think we're fine here. So now we have the chloropleth map of the United States. You can see the high state emissions over here. All the states are filled in, including now I think we lost Puerto Rico, but that's okay. We have Hawaii. We do have Hawaii, so that's nice. So that's filled in. Carbon footprint 1,2,8,5, right? And Alaska is pretty low, 3,218. Based on size of the state, like Alaska is easily the lowest, and Texas is the number 1 in terms of emissions, I think, because they have all the oil, all the gas. You can drive through Texas and you see all the refineries billowing up all that nasty stuff into the atmosphere. So that's what they do down there, I guess. So that's it. So we have the chloropleth map. Everything is rolled up and aggregated and summed up in terms of metric tons of emissions. And over here we see the breakdown based on the whoops, let me get the map back, based on the zip code of all of the zips in all the states in the entire United States of America. Okay, so you can zoom in, you can zoom out. This is very dynamic, interactive. I love these plotly charts. I love these chloropleth maps. This is perfectly designed for these types of things, right? You can see all the detail and all the nuances here. And all the in-between stuff. This is Connecticut coast, Long Island. You can see New York City over there. So mission accomplished, guys. We did what we needed to do, measuring all the carbon footprints and creating a tracker based on zip codes all across the United States. So that's it. I'm going to wrap it up here. Thank you so much for your time. I appreciate it. I like the way that you guys watch these to the end of the video. It helps my utilization, my overall watch time, and hopefully I can monetize this channel pretty soon. I'm trying to get close to monetization, so I haven't earned 1 penny from this YouTube channel, but I'm still trying. I've been doing this for about 1 year, devoted 1 year of my life to this. Still haven't made a penny off it, but hopefully soon. I need more people watching more videos. I have to get to 3,000 total hours of video watched. Getting kind of close, but still haven't hit that mark yet. But I do have enough subscribers, so that's nice. That's one of the 2 criteria that I can check off the box. So that's it. I'm gonna wrap it up. I am going to turn off the recorder right now and post this video in just a bit, and hopefully the sound works this time. You have the all the source code. I'm going to upload that in the what do you call this, in this HTML file, and I'm going to upload the video, so you have the video and hopefully the audio this time if everything goes as planned. So yeah, that's it. I'm going to wrap it up here. Thanks for your time, and I'll talk to you guys soon. Take care. Goodbye for now. Hey there, everyone. My name is Ryan Schewel. Welcome to my data science channel. So, in the topic today, I think this is very, very interesting. I want to talk about how to predict which NBA team will win when they face off in the next game that they're going to play. Okay, so whether you're a fan or not, data science is one way to get more insights into sports analytics and understand sports management and predicting certain outcomes, right? What's going to happen at the end of this game and which team is going to win. So, this is interesting from many different levels: betting and fantasy sports, team strategy and coaching, front office decision making, fan engagement and broadcast, risk assessment and lead management, as well as just understanding some of the key tenets and key principles of data science and machine learning practice, right? And how to implement this in a real world scenario. That's exactly what we're going to do, okay? And real world gives us real value. This is basically prediction plus insights, right, to make these types of decisions. So that's what we're going to look at. Let's get into it. So I'm going to share all this code with you. It gets a little bit complicated, but it's not too bad. Just stick with me. You don't have to make notes and understand all the nuances and all the details of every single line of all these scripts, right? I'm going to share this with you in HTML format so you can download this, copy and paste it into a Jupyter notebook and run it for yourself, or just view it in the HTML file and understand what's going on from that perspective. Okay, so we're going to import a couple of libraries that we're going to use below. This is pretty common. We always do this for everything, right? So Python has, at this point, probably over 10,000 libraries. Let me Google this. I'm a little bit curious. Google, okay. How many Python libraries? Are there? Okay, it's the first one. Nice. Whoa, was way off. Oh my goodness. 137,000. Jeez. That's kind of shocking. I had no idea. 137,000 libraries. Okay. I thought it was 10,000. I was way off. But anyways, the point is, like, we import these libraries at the beginning so we can use all these scripts that, or so we can use all these lines of code that show up in the script down below, okay? So I'm going to create a list here and append everything to the list. You can see the name is all teams log. Control F is right here, and here's the append, okay? And I'm also going to convert this into a data frame and append all of these items that I'm getting from calls that I'm making to an endpoint, okay? And this is going to be all the NBA teams, and the data basically is stored in JSON format. We go fetch it as JSON and convert it into a data frame so it's easy for a person to read and append everything right here. Okay, so that's what that is doing. And when we are all done, we can go ahead and view the data frame set. So where is this data coming from? Basically, it comes from right here, okay? And I did a little research on this. So the NBA has several API endpoints where they store and load all of the team's data. So for every team, they'll have, okay, who won, who lost, basic information like this, right? And some of the conditions of the players. They don't have all the players' stats and all the details of all the players. Okay, when I run this, I get, what is this thing now? Let me take a quick look. Let me actually see how much is collected here. Sorry, should have done this before. I didn't even think about it. Print. Oh, I want the shape. Okay. Oh, I don't need that. Sorry. Why stick with it? Okay, so we have 2,460 rows in this whole data frame, and basically these are all the games that were played for the 30 NBA teams. Right now it is mid-May, or kind of the end of May 2025, and there's 30 NBA teams. That could change over time. There could be new teams added to the list, maybe some dropping out eventually. Who knows? But at this point in time, we have 30 different teams, and these are all the games that they play. So we have some details over here: team ID, matchup, who won, winning, lost, win percent, minimum, field goal average, 3-pointers, what is this over here? Rebounds, assists, steals, things like this, right? So this is the stats for the entire team. and then you have the team name over here. So that is essentially the data set that we're looking at. And I'm going to do some basic statistics on this data so I can train the machine learning model and try to make predictions into the future, which team is going to meet, and predict the probability of one team winning over the other based on historical events, right? What happened in the past is a pretty good indicator of what's going to happen into the future. But we're going to make all these predictions because you don't know for sure what the outcome is going to be, right? So with the team name, you saw that as the last column over here. Okay, so I'm taking some new data that I just created. This is called feature engineering and appending it onto the same data frame. So I have points rolling average. That's points rolling average, assistance rolling average, and rebounds rolling average. Okay, then I have the win streak, and whether or not this is a home game or an away game. So basically, the concept here is if you're on a streak and you have several wins, you're more likely to have another win, right? And if you're playing at home, you're more likely to win the game. So a winning streak based on points rolling average, assists rolling average, and rebounds rolling average, and the win streak, and whether or not it's a home game, we can use this information to feed into a machine learning model. I'm going to use log regression because I want to predict the likelihood of a certain outcome. Okay, so this is actually a classifier. A log regression model is actually a classifier. I have an XGBoost classifier. So XGBoost is sort of an ensemble learning model where you take one action and then you boost it up to another level. You do an analysis and then you take the result of that, boost up to another level. You do the analysis again, take the result, boost that up to another level, right? So this works sequentially. It's a little bit different from a random forest type of classifier where random forest, everything works in parallel and you're looking at all these different branches, and you go down to the leaf level. You start kind of at the trunk, right? And you go down to all these different leaves and look at every possible combination of every outcome and then make a prediction into the future and see how accurate that prediction is. Okay, so I'm actually looking at 3 different models: XGBoost, random forest, and this is a classifier, and then log regression. I have to look this up because I'm always confused. I know it's a classifier, but it sounds like a regressor because it's called log regression, but it's actually a classifier. Okay, so these are the 3 models we're using right here. You can see that, and I put that into a dictionary. When you see these curly braces, that's a dictionary. When you see the key value pair, this is the key over here. This is the value pair. So when they have a separator, that's a colon. And that's a dictionary. It's a little bit different from that list object that we saw before. A list has square brackets, and you'll take all your data and then append it into a list, and then you can do a bunch of things. You can print the list, convert the list into a data frame, all kinds of stuff, right? So that's where we are. So now I'm going to create abbreviations. Again, I'm going to use a dictionary, and we have these key value pairs. I want to create abbreviations because that's how the data comes to us from this endpoint over here, right? This NBA endpoint I showed you initially. So all the value comes in a certain format. I'm going to just reformat that data and reconstruct it so it's a little bit easier to work with. So I have abbreviation to name because I want the full name. I think that's a little bit easier to work with. So Oklahoma City Thunder. So I know what that is. I didn't know OKC is the abbreviation. I knew this one. Utah Jazz. I know that. So some of these you can kind of figure out. Golden State Warriors, I think you can figure it out. But some of these, like that one, I wouldn't know. So I want to convert this to something that's just a little bit more consumable, a little bit more user-friendly. So so it's easier to interact with too, okay? So I think I just ran this. Did I get an output down here? Yes, okay. So I'm saying it ran. I'm doing the abbreviations, taking all these abbreviations, getting the actual name from that, and then I'm going to go ahead and do rolling averages over here, rolling assists, rolling rebounds, win streaks, points rolling, assists rolling, rebounds rolling, win streaks, and then whether or not it's a home game and whether or not it's a win, right? So these are the feature engineering exercises that we did over here above. I wanted to take all of that, feed that into the model, take all these teams' names, and then jam that into the model too. And then down here, I can start to make predictions. So here's the actual train test split. So you always have to train the model on a portion of the data, not the entire data set, right? You usually use 70 to 80%, could be 75%, could be a little more or less. Usually it's 70 or 80% for the training, and the testing is the holdout. So that's remaining 30 or 20% that you didn't use to train the model, because if you use everything to train the model, it's simply going to memorize everything. Computers are very good at memorizing, right? But you don't want it to just memorize it because you don't know if the model can make decent predictions on unseen data, right? So you want to test it in a simulated fashion. Okay, I'm going to give you 70 or 80%, hold out the rest of it, the other 20 or 30, and then I want you to make a prediction, and I want you to check your prediction against what that value actually was. That's the whole point of this whole experiment, right? So here we're using XGBoost classifier, and we have our results. So this looks pretty nice right here. So we have Boston Celtics and Atlanta Hawks. Okay, so I put together a couple lines of notes over here. So in the script, we're doing the following: loading the data set, grouping and averaging, looping through all team matches, building the matrix, and then displaying the results using pandas. Okay, so here's the final matrix. Here's all the teams facing off against each other over the course of time, because we have that historical data. And again, I want to make predictions and understand the probability of a certain outcome or a certain team winning the next game when these two teams match off against each other, right? Or match up against each other, whatever it is. So the row is always the home team, and the column is the away team. The value is the probability of the home team winning. So if the row is the home team, the row is going to be Atlanta Hawks. That's the home team. This is the away team, Boston Celtics. So when the Atlanta Hawks meet the Boston Celtics next time, the Hawks have a 91% chance of winning the game. Now, when the Atlanta Hawks meet Brooklyn Nets, they have a 14% chance of beating the Nets. Okay, when the Hawks face off against the Hornets, they have a 38% chance of beating the Hornets. Okay, that's how you have to interpret this. And I know it's a little bit confusing. I tried to come up with a few different ways. This ultimately made the most sense. It was the least confusing, but remember, it's always the team and the row that has the probability of winning. And I have that in my notes on here. So the row is the home team, column is the away team, and the value is probability of home team winning. So when the Washington Wizards face off against the Hawks, the Wizards have a 31% chance of winning that game. Okay, so I took this one more step and created a heat map down here so we can visualize what the outcome is for all these potential wins and losses. So Wizards, we just saw, was 31.729% chance of winning, right? And if we saw over here, the first two we looked at was the Hawks and the Celtics, Hawks and the Nets, and we have 91 and 14, and that's what we'll see down here. Put my mouse out, there's the 91, and that is the 14. And the way, again, remember, it's always the home team that's on the row, and it's the home team's probability of winning. So if the Hawks face off against Boston Celtics, they have a 91% chance of winning. Hawks versus the Nets, the Hawks have a 14% chance of winning. Okay, so that's how you interpret it. So I thought this was a pretty cool exercise. I'm not a sports gambler, so I know the statistics are solid. I know the machine learning and data science is very solid here. I don't really know that much about sports gambling or betting or anything like that, so I don't know how to cater to that. And I wouldn't say use this as the gospel truth and bet a ton of money. That's not my intention here. And if you do bet some money and lose, don't come after me. I don't have any money. I literally have been unemployed for 18 months. So that's why I'm creating these videos, to give me something to do during the day. But yeah, don't try to sue me. I don't have any money, all right? It's a fun exercise, and you can test it. You can test the strategy, and you can see how it works if you are into sports betting or if you're into gambling or whatever. I think it's a very interesting exercise. I know the math, the stats, all the computer science, machine learning is tight. I don't know about sports betting, so I can't say, I can't speak to that, okay? So we're simulating matchups in conclusion here, and the home team and the away team are plotted ultimately with the probabilities when these two teams face off against each other. The home game, one means the model interprets the row the home team as being at home. I explained that, and we're predicting the probability that the home team wins because the target variable, when equals 1, corresponds to the team that is being modeled. The home team in this example is the row team. Okay, so that's how you interpret it. So that's it. If you do have comments or questions or suggestions, put that in the comment section. And if you were into sports betting, I'd love to hear something about that. And give me your thoughts on that. And if you test this model and try to understand, how well it performs in the real world, that's great. I would encourage you to do that. But remember, there's always probabilities here, right? There's no guarantee. So here, the Hawks should be the Celtics, right, with a 91% chance of probability. But the Celtics could win, right? If a key player fouls out and doesn't even make it into the fourth quarter, then you have a big handicap right there. If a key player sprains an ankle or has a serious injury and they're out of the game, then it's going to be a potentially very different outcome, right? So during these games, anything can happen. I'm just showing you like historically what has happened in the past and then how to make predictions into the future. That's what this exercise is for. So hopefully that was informative and enlightening. I try to make these things very practical and very realistic, and helps me to learn new things and to refine my skill set. All right. So that's why I put this stuff together. So that's it. I'm going to save this and I will share the file with you guys later today. Thanks for your time. And I'll see you guys soon in the next video for sure. Okay. Thanks. Bye. All right, everyone. I've got a really cool Python use case for you today. Okay. I researched this yesterday. I found some crime data about New York City, and this is near and dear to me, literally and figuratively. I live right by New York City, one stop away on the 7 train from Grand Central Station. For all intents and purposes, this is New York City. We certainly pay New York City taxes. Hooray! Wait for that. And we're right by New York City, right? You can be in Grand Central in 5 minutes on my local train. I live close to the 7 train stop on Vernon Jackson. So I see this all the time in the news, in the newspapers, on Good Morning America, Fox, uh, Today Show, all these things, right? Like this is right in your face. You can't avoid it. So crime is running rampant in New York City post-pandemic. Before the pandemic, actually, it was kind of under control. I think Giuliani did a fantastic job decades ago when he was mayor. Bloomberg was mayor for 12 years. He did a great job. De Blasio, not so much in many people's opinions. I won't really get into all the politics and all the bureaucracy behind that. I think de Blasio probably dropped the ball, and I think a lot of people would agree with that statement. Anyways, Mayor Adams came into office a couple of years ago, and he's been trying to clean up the mess from de Blasio ever since. I tip my hat to him. I think he's done um, a decent job, kind of suitable, but there's a long way to go between de Blasio and the pandemic. Things really unraveled, and we're really in a dire state right now. Although for the size of the city, crime is relatively low compared to some other cities around the U.S., where the population sizes are much smaller. So relative to the size of New York City, crime I think is still somewhat de minimis, but it's way worse than it was 5 and 6 years ago before the pandemic hit us like a ton of bricks. Okay, so I decided to do a quick analysis on the crime rate across the 5 boroughs and see what I can come up with, see what kind of results I can produce, and see what kind of recommendation I can offer. Um, so let's jump into it and stick with me to the end here. I think you're going to learn a lot, and I think the insights are going to be um, very interesting, eye-opening, and very quite fascinating too. Okay, so why would we even analyze crime rates around the 5 boroughs of New York City? Obviously, to try to prevent crime, right? To understand it and try to prevent it. If you can't understand anything, you can't solve the problem. If you can understand the problem, you can start to come up with solutions. So identify crime hotspots. We're definitely going to do that. Predict crime trends. We'll try to do that. Support policy decisions. Optimize patrol routes. Yes. Resource allocation. Absolutely. Public awareness. Urban crime mapping. Yep. We're going to do all of these things. So sit tight and let's get into it. I downloaded a file called Crime Map. You can see it here. I have a reference to it right at the bottom of my Jupyter notebook here. And this is a source right here. If you go here, I'll just show you here. I'm not going to spend a whole lot of time on this. But if you go here and download the CSV file, you will have all the data that you need to reproduce the analysis I'm doing right here. So let me take a quick look at this thing. Loading. Okay, I think where did this even come from? Filter, visualize, embed, about, export. I think export. Here it is. Okay, so export CSV. That's where I got the file from. Okay, so that reference point is right here. You can get that at the end of the analysis here. So I download the file. I'm reading it into my data frame, and this is what it looks like. I'm printing all the columns here, and then this is the head of the data frame. So we have some data over here. This is the borough, the date of the complaint, complaint filed, maybe FR is filed, I'm not sure. Complaint is it the timestamp, okay? And then what was the action taken? This is completed, jurisdiction, description. Okay, this is a description of the crime. And then we have over here PD, I think this is police department description. We'll look at these. Type of description. I'm not so concerned about street or residence. Things like that don't really bother me. Latitude and longitude, that's very important. Okay, so we'll take a look at that. So we are going to go ahead and load the data. And as I recall, this load's kind of slow because I have a T14 laptop. It is a solid state hard drive, so it's kind of fast. But when you get into now analyzing some of these big data sets, it's actually not that fast. So I'm not going to run the code, but you can see I ran it earlier today. It probably took maybe 35 or 40 minutes to crank through everything here. So I'm not going to rerun it because I don't want this video to drag it on, and I don't think you want that either. I'll take you through the steps, and I'll share all this code source with you, like I do with all my videos. I'll share all the source code so you can copy and paste it and run it in your own Jupyter environment, or copy and paste it and put it into Spider. You can run a Spider. There's a few IDEs you can run all this Python code in, so just take your pick. Go with your favorite one. I'll give you all the code. So all you have to do is copy and paste. That's it. Okay, pretty simple. So we are going to create some feature engineering columns here, or new features from existing feature. We have this feature right over here. I showed you this is a timestamp, I think. Where'd it go? Yeah, okay. So we have timestamp here and the date over here. So I want to create 3 new features: hour, the day of the week, and the month of the year. So I'm going to go ahead and get the DF complaint FNTM. That is this right here. And I'm going to convert that into hour, and then day of the week comes from FRDT, and then FRDT, month, day of the week. So we see that the date, okay, and here's the time. So we're going to get hours from this, hours of the day of the week, and the month of the year from that. So I'm not going to run it, but you can see down here, when I run the code, I get exactly what I just described. So we had the latitude, longitude combined. Then we get the hour from this guy right here, okay? The day of the week, Monday, Tuesday, Wednesday, Thursday, Friday, so on and so forth there. And then the month comes over here. And you'll see why in a moment. That's important. We are going to value count all the hours and count up those hours, and make sure we pick up Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So all the days of the week. These are all the months of the year, and we're going to count the day of the week. That's why we're doing this, and count the month. That's why we're doing that. And we are going to have, so we have the month and the day of the week. Oh, and the hours. So we're counting these 3. We're counting hours, counting days of the week, Monday through Sunday, and then months of the year, January through December. And we're going to print a nice little chart. So what does this mean? We have this number of crimes, and this data, like, let me take a look at this quickly. I think this is what, 2023, 24. I can go up and look at this quick. This is 24. Okay, so it looks like 24 data, and I'll tell you that the data looks a little bit wackadoodle. At one point, we're going to see why in just a minute here. This is 11% loaded, a little bit slow. That's why I told you. See, tell you guys the truth. I give you straight up what's happening here. This thing is slow. So let's count by hour. We can see by midnight, this is 0 hours. This is 1 o'clock in the morning, 2, 3. This is 24 hours. So it dips down here by 3, 4, 5. So this totally makes sense to me. We have 6,281 crimes throughout 2024. The lowest at 5 o'clock in the morning, presumably because most people are sleeping. Most normal people are out, not carousing around. They're sleeping. They're not committing crimes. As the day breaks and we get into 6, 7, 8, 9, 10, 11 is a big spike around 12. There's some crime here. It dips down a little bit. I guess people get hungry for lunch, so they're not committing crimes. Then they're done with lunch. They're back to their criminal escapades. 15, that's 3 p.m. 16, 17, okay, and then people are getting hungry again, so they go home for dinner and they stop committing crimes, okay? So that's kind of trying to be a little bit humorous here, but that's basically what happens, right? In the middle of the night, not middle of the night, but 5 o'clock in the morning, people are sleeping, they're not committing crimes. This finally loaded up. I actually forgot. I even Made that request to load. Let me look at some of these dates over here. I think it goes throughout 2004. If I put a filter on, let's look at the minimum. And of course, we could do this in Python too. Oh, this is interesting. So this goes back in time. Oh, years and years. Okay. Okay. Got it. So years and years worth of data. Um, and we have a total of about 433,000 records. If I go down here, we have 433,000 crimes going back to the 1960s. Okay, so it's pretty comprehensive. I didn't even know it went back that far. But anyways, here's the hour of the day plotted in our chart. So this makes sense. Early in the morning, there's not too many crimes. Later in the morning, there's more crimes. Mid-afternoon, early evening, there's more crimes. And then people get tired. They have to go to sleep. So the crime spree winds down. Now we have crimes by day of the week. This is exactly what I would expect here. So the hour of the day has a big impact on whether or not people are committing crimes. The day of the week has no impact. It's like this a little bit on the weekends, just to be a little humorous. Maybe people need some walking around money for Saturday and Sunday, so they're committing more crimes. I don't know exactly where it's up a little bit on Friday, but you can see it's pretty consistent across the days of the week, very inconsistent across the hours of the day, right? So people are tired, they're sleeping at 5 o'clock in the morning. That makes sense. Here, people are up and about 7 days a week, and crime is being committed like any day of the week. There's no preference for any given day for crime. Maybe Sunday is down a little bit. Maybe a few more people are going to church, but Friday, there's a little bit spike up to offset the decrease on Sunday. Okay, so that's pretty even. Now this is interesting. I think this is a data quality issue. There's no reason whatsoever that the counts of crimes would fall off a cliff from September to October. I think it's a data quality issue, or um, NYPD just wasn't recording crimes by the time they got to October. I'm not sure why. I can almost guarantee in October and November there's more crime than in September, because over here we're heading into daylight savings time, and it's a known fact. The day after daylight savings, when it gets darker earlier in the fall, when we put the clocks back, remember, fall is back and spring is forward. The day that we set the clocks back, that Sunday, there's always more crime because it gets darker earlier and people commit more crimes when it's dark. Okay, that's a fact. That's a given. So I don't know why these numbers fall off October, November, December. It looks very bizarre. I would say there's a data quality issue. I'm just using what I've got here. I didn't create the data. I just downloaded it from that site that I showed you, and I was saying crime is way down for October. This must be a mistake. That's all I can make of it. I don't know why it would be down for October. It makes no sense. So let's look at plotting again. We're going to do these bar charts, but this time we're going to add in the category of the crime. Okay, so the law CAT means category, CD charge or something like that. I don't have the data dictionary, so I don't know what law CD is. I think it's the law category and some classifier or whatever it is. So we're going to look at some stacked bar charts again by the day of the week, by the month, okay, and by, I think we have the, do we have hour of the day? Maybe we don't. Maybe we just have those two. Okay, so by category stacked here, we have FE, MI, and VP, right? This is a plotly chart, so it's interactive. If I click on any one of these, it disappears, and I click again, it comes back. So these show us the categories of um, of legal infractions here. So red is felony, blue is misdemeanor, and green is a violation. These are kind of broad categories. You can see again, 5 o'clock in the morning dips down. Rest of the day, it's pretty flat, pretty normal. Day of the week again has no effect. That's exactly what I'd expect. Now these should be pretty normal and pretty linear. There's no reason why in October it would drop off unless we have a data quality issue. That's the only thing that makes some sense to me. Otherwise, I have no idea why we're not picking up October, November, December. It looks like a total mistake, but the first 9 months of the year look pretty normalized to me. So here we have the offense description. So this is a little bit more detailed than what we see over here. We have felony, we have misdemeanor, and we have violation. But what do those mean, right? There's a lot of descriptive categories within those parent categories. So these are sort of like the child categories. These are the parent categories over here, right? So if you drill into one parent, we should be able to see the children. We scroll down here and we can see the descriptions over here. So we see here, this is other offense related theft. This is miscellaneous penal law, public ordinance, this is petty larceny. Go down here, harassment 2, robbery. So you can see these color bands correspond to the type of the description of offense here, right? So here's offense and description, OFSN, OFNS, and description, and we have the key to all these on the right. Again, if I click on that and then it's going to disappear, I click again, it comes back, and dangerous drugs. Where's that gray one? I was looking for a big gray bar over here. Maybe escape 3? No, it's tiny. Okay, so anyways, you have all the details of the offense stacked up here. So the days of the week totally makes sense. The month of the year makes sense for the first 9. The last 3 don't make any sense. I think there's a data quality issue. That's fine. So let's get into plotting a scatter plot map using the latitude and longitude coordinates, okay? And we're looking at the broader category, the parent category, like I said before, misdemeanor, felony, or violation. And again, if you click any of these, it drops off the map, and you click it, and then it comes back onto the map. If you want to see only misdemeanors, that's what you have here. These are felonies, and then these are all the violations. And it's a slight lag there because the computer is a little bit old and slow. It's just getting tired now. It's probably time for an upgrade pretty soon. So there is lat longitude plotting of all the crimes. So let's move down a little bit more and look at clusters of crimes. Again, plotting based on the data frame, the latitude and longitude coordinates, and we are going to take all those coordinates and cluster those into k number of coordinates. We're going to say, give me 1,500 different types of categories of crime, right? And that's what we see over here. So if let me see if I can zoom into the map. Yeah, here we go. Okay. So here's my zoom. And if I zoom in a little bit, I love these plotly charts because they're very interactive. You can zoom in, you can zoom out, put your mouse over the top, and you can see all the details. So there's 426 crimes, 170, 245, 80, and 69. And the size of the circle corresponds to the number of crimes, right? So the diameter of the circle, or the edge to edge size of the circle, is relative to the number of crimes committed in that latitude, longitude coordinate system right there, right? And with the higher counts being the light yellow and the darker counts being a dark purple and magenta being in between, right? So that is very interesting. That's very useful. I think if we go over here, we have another chart over here. Let me try to double click on that and blow it up a little bit, or drag it. This should let me zoom in, I think. Okay, there. Zoom out just a tad. So this, I think, is the first real meaningful, interesting chart that we see. We're looking at density map plot. Okay, this is called a cluster, right? These are, scatter map box based on clusters. These clusters over here, with clusters being 1,500, 1,500 different crime categories, right? But I think this chart is actually more interesting, and this is where the rubber starts to meet the road. So before, we're doing EDA, exploratory data analysis, to try to understand what's the meaning of the purpose of this data. How can we draw insights from the data? How can we extract something useful and make an informed, intelligent decision about the data that we have loaded into this data frame and into this plotly map? So that's where we are, and you can agree or disagree. It's a free country, right? But I think we're starting to get something that's very useful and very interesting here, because we're looking at longitude, latitude, right, by the hour of the day. So I think we're finally starting to get something useful. Before, we're looking at the color was the counts, right? That's how we get the size of these circles over here, the counts of crimes in that vicinity. Now the Z coordinate is based on the hour of the day, and you can see like late at night, this is 24 hours, right? So midnight through 1, 2, 3, 4, 5, this is 5 a.m. 10 is 10 a.m. 15 is 3 p.m. 20 is 8 p.m. As these colors get lighter and lighter, if I zoom in, you can see a lot more crimes are occurring in the later part of the day. After 3 p.m., we get into 4, 5, 6, 7, 8. 8 is 20. By the time we get to 8 p.m. and midnight, there's a lot more crimes over here. And you can see the neighborhood where these crimes are concentrated right here. So you see a little bit Times Square, a little bit out here in Queens, a little bit over here in the Bronx. Down here in Brooklyn, you can see some yellow. Let me zoom out a little bit. Right, so we're starting to see a very interesting picture. I think, but we still don't have all the information we need. We have longitude, latitude, we have the hour of the day, but it's not enough. I still don't have enough to make a really intelligent decision here. So let's continue with the analysis. But I think we're getting close, right? So we have a eureka moment based on time of the day and the longitude, latitude. I think we're starting to get some really good insights about this data. So let's follow through with 4 steps. We're going to group similar longitude, latitude coordinates together. So we have, like you saw before, about 433,000 data points, I think, right? So 433,000 different longitude, latitude coordinates. That's a lot to get our arms around us. But if we can take that, right, get our arms around this beast, this behemoth that we're trying to deal with, that we're trying to tame, and say everything within 20 meters, 20 square meters is consolidated into one single longitude latitude address, we can take this primary longitude latitude address and say this is a focal point where we have to send the police teams and make a dispatch to this general vicinity. Okay, within a 20-meter range, we're going to be pretty close to the center of where most of these crimes have occurred. And if it's a dark purple or a low frequency count for crimes, we're not too concerned. Maybe that was a one-off. Maybe that was just a random act of violence or something, right? But if you have repeated offenses in these light yellow bands over here, that's where we have to concentrate the police efforts, right? That's where we have to dispatch the troops in the highest concentration because that's where the crimes are concentrating. Okay, so we're going to aggregate the description of the crime. We're going to aggregate longitude, latitude coordinates based on a 20-meter range. Okay, anything within that 20 meters is going to be consolidated into one specific longitude, latitude coordinate. And then we're going to show the results of these crime scenes in descending order of the rank. Okay, so we're going to rank all these and sort them in descending order. So we're going to go ahead and clean up all these coordinates. Okay, that's what this code is doing right here. And we're going to create this data frame right here. So we went from 430,000 crimes down to 108,314. So we cut the number of longitude, longitude coordinates by 3/4, right? So now we're dealing with 1/4 of the original latitude, longitude coordinates. Okay, so we're getting it down to a more um, a more consolidated, concise, distilled data frame where we can actually manage this, right? To manage 433,000 records is a little bit unwieldy. If we get it down to just over 100,000, we can manage this data set a little bit more efficiently, okay? So now we're going to look at the distance threshold. Like I told you before, the Earth radius is this much. We're going to divide the distance threshold by the Earth radius, right, to get this down into a meaningful metric that we can manage and get our 20 square meters. Like you saw over here, we want to get 20 meters for a bunch of crime scenes, but just one. We'll label it as one scene, so we know everybody's on the same page. We know exactly where to go. What's the latitude and longitude coordinate that we have to make a dispatch for NYPD to get to. Okay, so we're doing a few group bys based on the latitude and the longitude. If these are substantially similar, we're going to combine those into one latitude and one longitude. Okay, so we're taking 433, condensing that into about 100,000. That's what the group by is for. Okay, and then let me see if I can find 20. Where's that 20 again? Is it coming? Oh yeah, distance threshold equals 20. Perfect. So we have 20 meters diameter. That is going to show us the circumference of the circle, and within that circle, we're going to have one latitude and one longitude combined. So if we have 20 different lots of lawns that are combined into one, we have one spot just so we know where to congregate, consolidate, and focus all of our efforts. Okay, so that's why we have the 108,000. Then we're going to go ahead and do the same thing for the description of offense. This is offense description and crime count. So we're going to take a bunch of offense descriptions. If we look at that over here, that is coming up right about here. Okay. So we're going to take these and consolidate that into a list with these longitude, latitude coordinates consolidated over here. Okay. So we see 4673 minus 73, 964. Okay. You see that 46,7 714, 46714 minus 73913. Okay, so everything looks to be in good shape. We're going to consolidate that again based on the offense description. Okay, and we get down to 75,000, almost 75,000 records. So we went from 400,000 down to about 100,000 based on the offense description. Now we're down to 75,000 coordinates, and you can see how these are coming up over and over again. So that's that, because these are substantially similar coordinates. I can say take everything within a 20-meter diameter, and everything within that circle, the diameter of that circle, or the diameter is n, the circumference is the area of the circle, and label that as one crime scene. Now we have crime count 269 plus 4 plus 7 plus 24 plus 1. That's how we get 362, because we're taking all of these lat long coordinates, consolidating that into one, and then we're going to say 269 petty larcenies. We have some 4 felony assaults, harassment 7, burglary 24, burglars tools 1. But again, everything is tied. All these crime count metrics are tied to one lat long coordinate. Okay, so we're in good shape. Now, at this point, we have 75,000 almost crime scenes. I'm going to take this down just to 1,000. I'm going to cheat a little bit, guys, but honestly, like, this takes a really, really, really long time on my laptop to finish. I need a powerful computer that I don't have access to. Maybe NYPD has that. Hopefully they have that. I don't have that. So I'm just going to take the first 1,000 so I can slice through this and deliver some type of solution. If I tried to do this for all 75,000, this thing would be running for days and it would probably never even finish and probably crash, or who knows what. But I don't want to wait for 3 or 4 days or even more. I can't even tell how long it's going to take. So I'm going to get something done and be efficient and scale down to just 1,000. But I'm going to get a result and deliver something. I'll have a deliverable that I can show Mayor Adams. Okay, if this runs for 24 hours or 48 or 72 hours and I have nothing to show, then nothing's happening, right? Nothing's getting done. Nothing is getting solved. If I can solve 1,000 of these records, or identify 1,000 records and gain insight from 1,000, there's still almost 74,000 to go, but at least I have 1,000 done. At least I have something. This is doing a reverse geocoding right here and getting a location based on this lat long coordinate. So this is pretty cool. I have another video how to do geolocations and reverse geolocations. This comes from a library called Nami Natim. Is that how you pronounce it? I'm not sure. But it takes about 1 second to get one record filled in. So you can see it would take at least 74,000 seconds to get all these on my computer. And yeah, again, if I had a super fast network of clustered computers and I could knock this out in a couple of minutes, I would do that, but I don't have that, right? So this is the next best thing. I'll just get 1,000. It's better than nothing. So this is reverse geocoding with these coordinates. I can go ahead and assign a location. That's what I'm doing. I'm appending location onto this data frame, and it comes from this. I can clean this up a little bit. Some people like to put it on the next line. It depends. If it goes really far off to the right, I'll put it onto the next line. Whether you use this convention right here or this convention, doesn't even matter, because Python will just ignore all the white space. I prefer this a little bit better if it's on one line. Some people like 2 lines, so I like 1. So yes, so now we have the group. This is just the ID, the offense description. So this isn't super important. This is important. Crime count is important. Total crime count. So everything that matches this lat long coordinate, you can see here, if you look visually, all of these will match, right? And this is the actual address. So we derived that using the reverse geocoding method right there. So we have our location, so we don't have to tell NYPD, hey, go to latitude 40.750.423, comma, negative 73989288, whatever the heck that is. Just say, guys, just go to 130 West 34th Street. That's Koreatown, Chelsea District. Boom, they're on it. They're gone. There's 336 crimes committed in recent times. So we know there's a high concentration of crimes in that area. If we dispatch NYPD to the area, we can prevent a lot of crime and potentially solve a lot of crime, right? Here's the full address. Now I've got the full address. So Koreatown, New York, New York. Here's the zip code 1001. That sounds like the first zip code ever invented. And we are in the United States, of course. So this is the most important thing. Take the NYPD, dispatch however many police you think it takes to handle. Now, this is historical. We're not going to have 336 crimes committed today or tonight after 8 p.m. We saw that was the trend, right? But I mean, we can negotiate this. Maybe it's maybe it's half dozen cops, maybe it's a dozen cops. That is the highest location of crimes that we can identify in this data set. So that should be the focus for the NYPD going forward. Okay, that's the head. We're looking at the head. We're sorting this in descending order with a rank of 1. Remember, we assigned a rank back here. I have to go find it now. I don't know where it went. Come back here a little bit. Oh, here. Okay, so here's the ranking. Sorry, here's the ranking. There's a bunch of them, so let me eliminate any confusion. It comes from this. This right here, dot rank, does all the ranking for us. Okay, so that's how we get these ranks, and it's based on these counts right here. And again, this is the physical location. Here's the lat long coordinates. If that helps you, it doesn't help me too much, but I can use that to get this. Okay, so we're in good shape now. We have the head. This is the tail. Now we have ranking of 51. So we see already the rank dropped from 1 down to 2. So we have 336 crimes here. That's the sum of all of these guys over here. So 47, 1, 224, la 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 la, down to here. Then we have the second rank, 19, 15, and those sum up to 261. So those are the heads. Those are the most important places to focus the effort for the NYPD. This is rank 51, so much lower rank. We only have 58 crimes compared to 261 or 336 over here. So now we don't need so many cops. Maybe 2, 3, 4, maybe. And this is the location, 450 police officer, Tremont, Bronx. So if I put that into Google Maps, let me just see what this thing looks like. Maps. I'm always curious to see maps. I love maps. I love looking at maps and seeing what's there. Okay, so Mr. Google will take us over there, hopefully. Okay, and this is it. That's it right there. So that is that street location. Police officer Jill Garcia Place. So that's interesting. Are crimes being committed there directly in front of the police officer? Maybe not. Maybe this is where the paperwork is being filled out. 450 police officer Jill Garcia Place. That seems like it's a data quality issue. I think this should be where the crime is committed. So already we can see a process where we can improve these metrics right here. This makes sense. 130 West 34th Street, Koreatown. Unless that's another police station, unless that's how they do it, they just list the police station closest to where the crimes occur. They should be listing the location where the crime occurs. So that's, I think, where most of this happens. But there could be an anomaly here. This could be a misnomer over here. I'm not sure. I mean, you have to talk to somebody that produced this data set and get a little more insight into this. Now, the last thing I'm going to do here is take everything and plot this on a Folium map. Again, you don't have to worry about all the code. It's a little bit convoluted here, but it's not too bad. I was playing around with this yesterday. Essentially, we create a Folium map. If I go here, Folium, is that folium.com now? Just give me a second here. Folium. No, I don't want Bing. I want Google. Google's still better than Bing. Probably always will be Folium maps. And then here's Folium documentation. Okay, so this is good. If you have some free time later today or later this week, take a look. Okay, don't look at that one. That's nothing. Okay, here comes Folium map. So they're going to give you a lot of detailed information. It's rich, very insightful, very mature type of mapping tool here. And they have all kinds of cool, interesting, fun things you could do. This is like geography, color coded. You can put all kinds of markers on these maps, interactive maps. Folium. Let's take a quick look at this. Is this useful or not? Sometimes you just have to hunt and peck around for these things and see. Okay, so here's map marking points. Okay, you can create a heat map down here. So here's a heat map. So there's all kinds of really cool things you can do with these Folium maps. Here's clustered maps. If you zoom in, these actually explode out into different clusters. And if you zoom out, then they will coalesce into clusters, right? So here we have 35, but if you zoom in, then you have clusters and subclusters. So that's really cool. Oh, shoot. Did I lose my thing here? Shoot. Clicked the wrong thing. Sorry, guys. Sorry. I thought I clicked that map thing over there. I clicked on the wrong thing. Okay, hopefully we didn't lose everything. I think this is all saved. Sorry, that was my mistake there. So that you rush into it. An ounce of prevention is worth a pound of cure, right? Okay, so I think everything was restored. Let's go back to where we were before. Down here, we saw that. There's our maps. Okay, there's our heat map. This is what I want to show you with Folium maps. So I would encourage you to go ahead and explore Folium and see how that works. What I'm doing here is taking the offense description, splitting it by comma. So I did this last night. It took a little testing and a little sort of like coalescing to get everything to work out. Once you split this, you can have a line break and present everything on the map by location, total crime count. This comes from here. If I do Control F, crime count comes from here. This is a total count, right? This is a description. And then we're taking the offense list and splitting that based on commas, right? So comma delimited to come up with the offense list. And when we plot everything, we get this down here. I can zoom into my Folium map and you see all this, the location, the total crime count 336. And if I click on it, we'll get everything listed vertically with all of the types of crimes here. So this is easy to read. You know the crime count and you know the location. This is Koreatown, I think 130 West 31st or whatever that thing was. Let me go back and see what that thing said. 130 West 34th. Okay. West 34th. So dispatch half dozen or a dozen police officers to this location. This is the highest count of crimes based on the data that we saw. Here's another crime count. And if I click on this, we can see the list here. Actually, more variety of crimes, but lower count. So 153 versus what was that, 330, 340, something like that. And if we go over here, we'll see another crime count. Here's one over here. And we see only only 5 types of crimes, but 89 total crimes in this location. Okay, so we could send some police officers over here, just north of Columbus Circle. So anyways, we took a lot of data, distilled that into a ranking of where are the most frequent counts of crimes, right, based on the frequency or the overall counts of crimes, and then plotted everything on the Folium map so we could see in detail the location of those crimes. And then when I click on it, we see the exploded list vertically, right? Everything is listed out for us with the number of crimes, the location, the types of crimes, and the map over here. You can see if you just put the mouse over, it goes horizontal, comma delimited, but when you click on it, you have all of the easy to read vertical arrangement of all those crimes. That comes from, again, over here, the offense list. When you click in this tooltip, it pops up. So to be ideal, I play around with this, I didn't get it going. Here's the horizontal list. If I put the mouse over, you see petty larceny, other state laws, non-penal law. So when you just mouse over it, it goes horizontal. When you click on it, it goes vertical. And that's what you see here. So I'm not a professional coder. I'm just a hacker. Been doing this a long time, but I never even took a course in computer programming in my whole life. I just read a whole bunch of books and just learned hands-on. So it would be interesting to see when you mouse over it to get that list vertical. I couldn't figure out how to do that. When you click on it, I could get it vertical because that comes from here, right? That's the tooltip. But when you do the mouse over, I'm not sure where that's even coming from. I spent a lot of time on this yesterday. I'm not going to spend any more time, but I think we got 99% of the way there. It came out pretty nice. I'm pretty happy with the overall outcome here. So I'm going to go ahead and download the HTML file. I'll do it right now, and I will share the video with all the source code with you guys in just a bit. As soon as I have a chance, I'll post it on YouTube, and you can download the file, get in there, explore the data, and analyze it for yourself, and make some enhancements, some improvements, and see how you get along. Hopefully that's helpful. If you have some feedback, post it in the comments. If you'd like to see something similar to this but different, then go ahead and put that in the comment too, and I'll take a look at that stuff whenever I have a chance. If I can get to that, I'll swing back maybe later this week. If you have comments, let me know, and I'll try to address those issues or those comments or those concerns. That's it, guys. Wrapping up right now. Thanks for your time. Take care. Goodbye. Hey there, everyone. My name is Ryan Schewel. Welcome to my analytics channel. So in the topic today, I want to talk about commuter gravity models and understand how people commute from their home to their work. Okay, so the computer gravity model basically comes from Newton's laws of gravity, which is all based in physics, right? And the equation is basically attraction equals mass 1 times mass 2 divided by the distance squared. So I studied a little bit of physics in college, never got my degree. I took a bunch of classes, but I ended up getting my MBA in finance instead. So I know a little physics, I know the math, I know the statistics behind it. And basically, this is called a gravity model because people are attracted to their work. That's how they get their income. That's how they get their paychecks, right? So sometimes people commute within the same city. That would be a short distance commute, and a long distance commute would be outside of the place where you live, right? So I live in New York City. If I worked in New York City, I would be making a pretty short term commute to get to work. Some people commute from Connecticut into New York City. Some people commute from New Jersey into New York City. Some people around New York City just stay in New York, and some people from New York go to either Connecticut or New Jersey. That would be the reverse commute. Some people go from New York to Nashville or Miami or Los Angeles or San Francisco. That's really a long distance commute, and that is definitely the reverse commute. But anyways, like I found this data online. It came from this website right here. Okay, so commuting flows, that's what this is called apparently, and 2016 and 2020 it was the latest. Now it's, let's see, October 5th, 2025. So this is like 5-year-old data, but this was the most recent that I saw. If I click back here, they have older data, 2011 and 2015, 2009 to 2013, so on and so forth, right? So I just got the most recent one, and it came from the first file. So if you download it and take a look at the file, this is basically what it looks like. This is the Excel workbook right here. So you have FIPS codes. These are codes for, I think, counties around the United States. I think that's what that means. And you have the county name. Yeah, these are counties. This is the state. This is county code. This is county name and state name, county name, and workers commuting flow. So you can see how workers move from one location into another, right? So that was the motivation for my analysis. And I put this file on my desktop right here, and I called it commuter data, XLSX. So if I hit Control Enter to refresh, we can import this data. I have to rename the columns because the data actually, if you look at this close, it actually goes from column A to column I, and the data starts on row 7. So I said these are the headers, or this is the header right here, right? But some of these cells are merged cells. So this is the bane of existence for anybody that works in Excel. If you have these merged cells, this goes from A7 to D7, but if you look close, the cell reference is just A7, right? When you merge these cells, you take the upper left-hand corner of the cell as the cell address. That's what it's called. This is workplace. This is called E7 if you look at it, but it actually goes from E7 to H7. So anyways, that's kind of just a little Excel nuance. Try to stay away from that if you can. If you get involved in that stuff, good luck to you. It's a pain. It's a real pain. I've been down that path before. But anyway, so the data primarily lives in columns A through I. The header is in row 7, and we want to go down to the end and capture everything. So the number of rows is 1, 2, 2, 3, 4, 3 minus 8. If you look close, this is where the data really lives. Let's just ignore the headers for now, and we'll ignore this stuff at the bottom. Even that is a little bit messed up because I have some merged cells at the bottom. So yeah, just be aware of that. This is the mess, okay? But really the data sits here, right? So that's how I set up the code to ingest the data, and then I am renaming the columns from 0 up to 8. There's 9 columns at 0 base. We start with 0, we go up to column 9, which is actually column 8 in Python world, and I am assigning actual names because if you look closely at the data, like some of these things are repeating, right? We have state FIPS code and county FIPS code or something like that. I guess these are a little bit different. This one doesn't even have a name. I want to assign a name to that, right? So I had to do a little manipulation in Excel to fetch the data and to pull that in. That's what this is for. And then I'm going to normalize all the FIPS by taking 2 places of precision there for that code and 3 over here for this. So I'm just trying to mimic what I see over here. I see 2 and I see 3, right? In Excel, if you hit this thing right here and convert to number, all the leading zeros drop off, right? So this is actually 1, but the county FIPS code is 001, right? It's not just 1, that's how they do it. So I want to just maintain the integrity, keep everything the same here. So I have 01, 001, we have 001, 001 over there. So I think the way they do this is origin state FIPS and origin county FIPS. And anything with an O is an origin. So this is origin, this is destination, right? So D is destination, destination state. So the origin state is Alabama, the destination state is Alabama. So these guys stay in the same state. Do they stay in the same county? They actually do in this case. So origin state is 01, origin county FIPS is 01, and the destination is 01. So these workers, 8,671 workers, stay in the same county in the same state. That's how you can interpret this number right here, okay? So that just sets the precedent for everything else. So hopefully that makes sense. Let me go ahead and hit Control Enter to refresh this. Again, OD is basically short for origin and destination. And if you look closely here, these are all the origins, okay? So anything with a leading O is origin, leading D is destination, and these are the counts of the commuters. So that's what that means. So we have 1,121,034 origin destination pairs. So the origin and destination are the same in this case. So I wouldn't count that as a commuter because you could drive maybe a couple of miles, maybe, who knows, 5-10 miles. So you could still be in the same state, you can still be in the same county, but we're really focusing on this over here, 154 million workers that go outside of their county to get to their work. So I live in Queens County, New York. If I go to New York City, that's a different county. If I go to Brooklyn for work, that's a different county. If I stay in Queens, then I would fall into this bucket right here. Most people do not live and work in the same county, right? So we're going to kind of ignore these people. 121,000 is de minimis, it's pretty small. We're really going to focus on 154 million active workers that commute outside of their county for work. And if you look closely here, I'm doing a couple basic analytics just to understand what is happening here. We have residence total, out of state jobs total right here, and the from state is this, and net across the state is this number, so negative. So it's about 42,000 people leaving Alabama every day for work and commuting into other states or other places for their work. So I think that makes sense. I can look at a couple of these and vouch for this. Is about 1.77 million residents of Connecticut. Out of state commuters is 126,000. Jobs total is 173,000. So some people stay in Connecticut for work. The large majority move outside of Connecticut. From out of state is about 85,000, and negative 40,000 every day go outside of Connecticut, probably to New York City. There's a system called Metro North. It's a train that goes from Connecticut to New York and back and forth. So there's about 40,000 people that go weekdays from Connecticut into New York. So Connecticut's are losing commuters are going into New York City, maybe even New Jersey, perhaps Rhode Island, perhaps Massachusetts, right? But I would guess most of them come into New York City. If I go down here and do a quick sanity check and look at New York, so I see 9.21 million. This is total residents. So I think that makes sense, residents of New York. So what is the second column here? This is out of state jobs total. 9.62 million, and we have 615 to from out of state, so people coming from other states into New York, and New York gets residents, right? So we had negative in Connecticut. People, for the most part, are leaving Connecticut, coming into New York City for the jobs. Maybe they go to Queens, maybe they go to Brooklyn or New Jersey, but New York is net positive jobs, right? People are coming from New York City into New York. If I do one more quick sanity check, so I see Jersey has about 4.3 million residents, negative 324,000 per day commuters. So they're going out of New Jersey into adjacent states. It could be Pennsylvania. I will go out on a limb here and say most of these people are going into New York City. They probably live in Jersey City, maybe a little bit further west of Jersey City. And the cities are very close to New York City, coming from west to east, commuting into New York. That's why we have a negative number here. So this is negative New Jersey going into New York City. Quick sanity check, that makes sense to me. Okay, so let's go ahead and create a Sankey plot. Now I want to understand visually what these flows look like. So Sankey plots are great for looking at things moving from one destination to another. So people traveling on airlines, if you're going from New York, either LaGuardia or JFK. Both of these airports are kind of close to where I live. To another airport, it's very easy to see this using a Sankey plot. Any kind of flow, a migration pattern of movement of people or things, even like supply chain management. This would be a good visual for supply chain management. So I'm going to look at all the flows and understand the sums of people. I'm doing a group by sum of workers from origin state to destination state to see where these people are coming from and where they're going to. This is the big, probably the most important thing in this part right here of the code. We're looking if the level equals the state. I want to sum all the workers from the origin state to the destination state and understand how these people are moving. Now, if I go down a little bit further, I can also look at per origin number, right? And look at the top ranking movements of workers, right? So I'm creating 3 charts here. I'm creating 3. So looking at the state level, the per origin number of workers, okay? And if workers is greater than the minimum value, I'm going to go ahead and plot that. That would be the second chart. And the last chart over here is the origin label, destination label, and the number of workers. And again, I'm summing the origin label workers and summing the destination label workers to understand, again, the patterns of these movements. I want to understand how people are moving from one location to another location. It's going to be states, it's going to be counts of workers, and things such as this, okay? So when I hit Control-Enter to plot this, Control-Enter to run the script, and I'm going to have basically 3 different plots. Okay, so here's my New York plot, and when I put the mouse over this, I can see all the counts here, okay? So I can see the details of people moving in Kings County. So this is actually Brooklyn. I have to look that up. Why it's called Kings County? Because we have a Queens. I live in Queens. It's basically one of the 5 boroughs. It's like almost a suburb of New York City. I don't know why do we have a Kings County. Let me look this up real quick. Now I'm curious about that. Where did the name? Maybe that was county come from. Okay, that's fine. Maybe it was originally Kings, and then it was like the nickname was Brooklyn or something like that. Before English control, the area was a collection of Dutch settlements, including the village of Brooklyn, I guess. And the English took over from the Dutch and named it Kings County, maybe after the king of England or something. Kings County. The name of the region changed to Brooklyn after its original Dutch village of Brooklyn. Oh, that's interesting. I never knew that. Okay, so whatever. It's the same thing. Brooklyn and Kings County is the same thing. So this is Brooklyn. People going out of Brooklyn, 577,000, and they could be going to Queens. They could be going to New York City. They could be going to Jersey, all over the place. People coming into Kings County or Brooklyn is 275,861. Now, New York is the biggest one in, is 1.7 million commuters. So 1,745,906 commuters per day into New York City. Out of New York City is 125,065. We have the top 10 counties over here. So that comes from, if I go back here, you'll see the top 10, right? Maximum number of nodes is 10. So I'm looking at the 10 biggest. If I set this to something like 50 or something, it would just be a big sloppy mess because now you're having the top 50. So I'm trying to filter out the smaller numbers of city commuters and just look at the major ones, right? That's why I set that to 10. But you'll see here in a second when the image is generated, if I set that to a higher number, you can see most of the commuters. Oh yeah, now it's having trouble calculating that too. Because the number of commuters is pretty high, and we're looking at like all the details here. Okay. It still says wait. Yeah, maybe it's too much to calculate. And this computer is pretty old. Is this going to work? Yes, it did. Okay, so now you see the top 50. And this is interesting. You can click, you can drag around, you can move this. It's animated. It's very dynamic and very changeable, right? So even that doesn't work. Let me go back to 10. I think 10 is good. 50 on my computer is a lot, and it's almost crashing my system here. It did freeze. So let me set this back to 10 and redo that. Okay. Wait. Oh, okay. Yeah, let me redo this. All right. Okay. Note to self, just on an older computer, even though this is a solid state drive and I have a lot of RAM on here, these are big calculations, right? And that's a big lift for this kind of system here. If you're doing this on a super powerful computer, I'm sure it'll work fine. On something that's just a ThinkPad T14 ThinkPad that's a little bit older. Um, I mean, just cross your fingers. That's all you can do. So, anyways, we see the number of commuters into New York City and out. We see this is Kings County. We see over here Queens County. So 251, 254, 144. People coming into Queens. People going out of Queens is 594,683. District of Columbia is in the top 10, so it shows up over here. Kind of small relative to the rest of the country, right? If you look at the Northeast, the tri-state area, most of the population is very concentrated here. If you look at other cities, obviously there's commuters in Texas. We have Dallas over here, and this is going to be Dallas County, and we have the counts over here and the number in and out. But it's relatively small compared to, the tri-state area, New York City, Connecticut, and Jersey. That's where most of the commuters are. You see something over here for Georgia, definitely Atlanta, Fulton County, and over here is Cook County, so that is Chicago. So it's a nice breakdown of the top 10 commutes across mostly the tri-state area, but a couple other areas too. Now in the second chart, we'll see flows greater than 1,000 workers. Okay, and then in the third chart, we'll see the 6 busiest nodes. So here's the top 1,000 state to state, greater than 1,000 workers. You see New Hampshire over here. New Jersey is pretty big. Total out, total in. District of Columbia is over here. And then you see even some smaller territories. North Dakota, Rhode Island shows up. What do you see down here? Iowa, Nebraska. That's interesting. So Nebraska comes through down here too. But they're relatively smaller, right, compared to the tri-state area, which we see over here. If we look at the global 60 busiest nodes, this is kind of what I was looking at before when I had the top 50. Now you can see over here, New York, again, 1745906. That matches this right here, 1745906. So that's out of New York and going all over the place. So this commuter is going from New York. Where is this? We just lost that. New Jersey, New York, out. But where was the other one I just saw? I just had it up here. I'll get this out of the way a little bit. Ohio, we have the commuters there. DC, we have the commuters over here. And a few other things. Anyways, I think these Sankey charts are pretty interesting. I came across this thing a few years ago, and I just thought it was a very nice, easy way to understand the flows of something, whether it's people commuting from one state to another. That's exactly what we see here. People flying from one airport to another, migration patterns over time, people just moving from one location to another. But again, it doesn't have to be people, it's just flows from point A to point B, from origin to destination. Okay, we even have Alaska out here. 1,584 people commute out of Alaska every day, every workday at least, and people commuting in is 9,107. Okay, so there's my New York. That's what I was looking for before. So New York, we have all the commuters. It makes you see all the flows again, where people go when they leave New York and where they go to. And when you highlight each of these little bars over here, you can see where the people are going to. So where is it? New York to Texas. We have New York to Texas down here, I think. Was that? Try to get just a little bit better over here. I'm trying to understand New York to Texas. I think we have some. Maybe not, though. Maybe we don't. this out of the way. This. I think I do see some people going from New York to Florida. I think I found it. Okay. So that's what this graph is great for too. Oh, oops, it's bouncing back now. Give me a sec. Uh-oh, I'm losing it again. Go over here. Is that gonna stick? I just want to get that line right there. Okay, and it's very sensitive, so let me get the mouse and then stop. Okay. Very, very sensitive here. Okay, Florida, Miami-Dade County to New York. New York County, we have 477 workers. And we see the visual plot of that, and then you have all the other details of everything else. So it's pretty cool for these kind of visual presentations, right? So we see left to right, the nodes are all the metro areas, the links are the direction of flows. So we just saw New York to Florida. What was that, 477 or whatever? This stuff is hard to zoom in on. 477 workers, right? So maybe consultants, maybe managing consulting, maybe lawyers, maybe who knows what? I don't know what the occupations are because the data doesn't have that. But anyways, you see the counts of the flows of people going from point A to point B, from origin to destination. The width of the line shows the number of commuters. So the more commuters, the wider the line, right? So this is a little bit wider than New York to Florida. We saw 477. That makes sense to me. It's just coming straight from the data. I'm not manipulating anything here. And New York to Bronx, 29,000. Just again, evidencing the bigger the line, the more dense the line, the fatter that is, or whatever you want to call it, the wider it is, the more number of people that is being counted there. So New York Northeast is really a mega region that totally dominates everything, right? If you see the top 10 commuting hubs, origins, and destinations, it's really New York, some Connecticut, some Jersey, things like that. You see a little Massachusetts, Dallas, Cook County, things like that. But that's really the exception, not the rule. You see bicoastal super commuters exist, but this is a niche. We saw 477 going from New York to Florida, so that does exist. That's a real thing, but it's not huge, right? It's pretty tiny. The direction matters, right? So if you're going from Philly to New York City, that direction matters. If you're going to New York to Philly, that's the opposite, and that direction matters too, right? So that's what the Sankey charts excel at. It's really good for those types of things. And we see large hubs of residents, and then the metro areas that they are associated with, whether it's New York or Queens or Kings County or something else, right? So the bigger the bar, the more commuters, and the smaller the less, right? So it should be pretty intuitive there. So let's move on and look at another flow rendering of the data. This is called a chord diagram. So we draw different chords between the origin and destination city. So it's somewhat similar to the Sankey chart that we just saw, because we can see the origin and we can see the destination, and then we're doing the same types of things, all the summing and the counting and all that. But like we saw before in the image above, we see the same numbers, right? So if I go to New York or New Jersey or whatever, where's my New York here? I don't even see it. Oh, here it is. Okay, so New York, we see total out 204, total in 615, right? So if you look at that close, I see 204,880 people out, total in 615,235. If I go back to the Sankey, we see kind of different numbers over here. Total out is 125,065, total in 1745906. Because you're kind of looking at a couple different things. So the numbers don't change, but the graphs represent slightly different views of these commuters. So you can see New York turns green when I put the mouse over it, right? Some people in New York go to New Jersey. That totally makes sense. Some people in New York go to Connecticut. That totally makes sense. But there's a few smaller populations like we saw before. Some go to Miami. So where is my Florida over here? Florida. So that should show up. Florida is kind of like southeast. I can see a little tiny bar flashing, right? If I go down here to Florida, I see total out 111,163, total in 63384. And that's totally fine, right? It's kind of just a different rendering of the commuters. So the arc sign around each metro area equals the flow, like we saw before. The ribbons connect pairs of cities where commuters are coming from and going to. These are the origins and the destinations. And the thickness of the line connecting these different points shows the flow volume, right? Just like we saw. So the Sankey charts and the coordinate diagram are the same in that respect, but the most attentive people will notice that they're not exactly the same because there's an element of directionality, right? Sankey uses the links exactly as you pass them. So we go from origin to destination, and that's exactly what it looks like, right? In the chord diagrams, the direction, I set this to false because A and B and B and A end into one ribbon. We don't really split those out. So it really depends the kind of view you want to see. Now you can force the chord diagram to show exactly what the Sankey diagram does, but by default it doesn't really do that, and it's intended for a slightly different purpose. So if you want to collapse, not compose. If you want to collapse everything together, the chord diagram is really better for that. It just says, okay, here's all the commuters, okay? Everything, everywhere, all at once, and that is great. If you really want to set this out and kind of bifurcate this thing and show, okay, the people are coming from this location, going to this location, and then moving on to another location potentially, maybe moving to a fourth or even fifth location, if that's your commuting destination or commuting pattern, the Sankey plot is better for that. If you want to just see big picture what's happening and everything kind of collapses together between origin and destination, the chord diagram is really better for that. So you really have to, and again, you can force these to be exactly the same, but it kind of defeats the purpose, right? Like chord is kind of big picture, overall flow, and the Sankey is more like details of every nuance of everything, and anything that happens in between as well. So the Sankey really shows in and out, and everything that happens in between. Okay, the chord diagram kind of collapses everything, so it's a little bit neater. It's a little bit, maybe you could say it's more appealing. Maybe the Sankey is more appealing. It really depends on what you're trying to accomplish. So you really have to pick the best tool for the job. I tell everyone that I work with the same message, right? I've been a consultant for like 22 years here, and I always encourage people to use the right tool for the job. I won't go off too much on a tangent, but I've seen people use Excel for all kinds of things. There's an old saying, if all you have is a hammer, everything looks like a nail. I've seen people literally build systems using Microsoft Excel. I've seen people build, and for a system, you need a real system, whether it's SAS or maybe, what is it, Salesforce, or maybe Java, or maybe Python. Python is a good system, but you don't use Excel as a system. I've seen people build websites using Microsoft Excel, which is insane to me. Just use HTML and JavaScript and some Flash, put some Flash in there or something like that. You don't want to use Excel to build a website. You don't want to do that, right? You want to use the right tool for the right job and solve the actual problem. Don't create more problems. So that's all I'm going to say about that. If you're building websites using Excel, then maybe you and I need to have a discussion about that. Control Enter. So here's just one more quick plot that shows concentrations of commuters from one location to another. This is all states, all links, everything summed together. So you can see there is some darker numbers over here. So darker represents higher. District of Columbia and Maryland. So this is going to be darker. 297,000 commuters. That makes sense. That's a pretty dense hub for commuting Vermont to District of Columbia. I'm kind of surprised that shows up, but I guess there's enough workers to get that kind of darker. And over here we have New Jersey to New York. That totally makes sense, right? Because you have a lot of people in this tri-state area. If I look at Connecticut to New York, Connecticut to New Mexico, that's actually 0. Oh, New York is down here. Connecticut to New York, we have 36,000. Jersey is higher. That makes sense. I know a lot of people in Jersey that come into Connecticut. Over here we have Virginia, Maryland. Those border each other, so that makes sense. You're going to drive over the state line. New Jersey, New York, we just saw that. So this is interesting too, because here we have origin New Jersey, destination New York, 436. Here we have origin New York, destination New Jersey, people doing a reverse commute 112K. So anyways, that's a heat map. I think that was pretty interesting. I've got one more for you, and then I'll wrap up this discussion here. So I have some state centroids. These are latitude, longitude coordinates for the center of each state in a dictionary format. And that's why we have the curly braces here. Okay, so we have our dictionary. We can use state synonyms, right? DC for District of Columbia or DC for District of Columbia, because sometimes they have slightly different names in the data set. Sometimes it should be New York. It should be two separate words, but if you look in the data, you'll see a couple that's merged together. I think that is a data quality issue. So we have to take that, normalize it. We have the out label or origin and destination label. So we're going to map those together, create a list over here to create nodes. And just for your own edification, I'm using Plotly graph objects. So this is going to create a bunch of different polygons and different shaped objects to create the states that represent the United States. And I'm going to create different hubs of commuters representing the city of origin and the city of destination. So when I run this, you'll see the effect right here. It looks kind of like a network graph, but it's actually a Plotly graph. And you can see all the counts of commuters here. So Washington to California, whoops, I just lost that, is 1591. Oregon to California is 3576. California to Oregon, 3576. We just saw that. Okay, Missouri, we see Missouri to Oklahoma, 8465. Missouri in, 209,000, out 165,000. And if we zoom in a little bit, you can see where they're going. From Missouri to Kansas, from Missouri to Illinois, from Missouri to Iowa, from Missouri to Arkansas, from Missouri to Oklahoma. All right, that is a little bit shorter, smaller bar here because it just represents the thickness of the bar. The fatness represents the number of commuters. And Missouri to Oklahoma, 3465. Right, that's the 3465, that light line that you see there. Missouri to Oklahoma, 3465, right? So it's a little bit fatter. And Missouri to, where is it? Missouri to Arkansas. I'm looking for that. Missouri to Arkansas. Not seeing that, that's fine. It's just not popping up here. Arkansas to Oklahoma, 6120. But I think this graph is pretty interesting because it shows you the counts of the commuters, the city where they're going from, and we found the centroid. So it looks like it's a little bit off, right? Because it's not going to New York City. We're looking for the geographical center of the state to kind of spread things out. Otherwise, it's going to be very concentrated and very confusing and jumbled up here. And we don't, we can get these details. There's a few ways to create this graph. There's probably at least a half a dozen ways to do this. I think this makes a lot of sense. There's different ways, right? You can go from the city of the commuter to from the origin to the destination city. I'm just looking at the state view over here. I already have all the details of the cities over here if you look close, right? Like these were the first couple graphs that we looked at. Oh, this is state to state. This is county to county, right? So if you wanted to do this view, you could do this. I'm doing state to state. That's what I have down here. And I think just because there's so much concentration between DC, Virginia, and Maryland, everything would get jumbled up, and I think it would be more confusing than helpful. So I don't want to create any element of confusion. You see that sometimes in charts and graphs, it gets overwhelming and people just don't even understand what they're looking at. That's basically useless, right? I want to create utility and create something that people can understand and comprehend and benefit from, not look at the chart and get confused, right? So that's why I'm looking at the geographic center here and doing all the counts of these items. So that's it. I'm at 35 minutes, almost here. I'll try to stop it. I'll wrap it up in the next couple of seconds here. That's it. So that's commuter gravity mapping and doing all the counts of the commuters, the from, the to, the origin, destination, plotting, charting, different visuals to show the flows, and then the geographic regions, and showing how the commuters move from place to place. So this is the source of the data right here. I would encourage you to go ahead and get that and just play around with this stuff, right? Make a couple little changes. You can change the filtering over here for these Plotly Sankey charts right here. If you look close, you'll see that I'm doing some filtering right here, right? Maximum number of nodes. This gives me the top 10 cities. right? Minimum value of workers is 1,000. If you want to see a smaller number, 500, just turn that down to 500. If you want to see, just the larger commutes, like the big heavy duty commuters, make this 10,000 or maybe even 100,000, right? Have the big picture and maximum number of nodes down here. It's going to do the same thing. This is showing the counties, right? Flows of people from one county to another, commuting from county A to county B, or origin to destination, rather, and the maximum number of commuting sizes I set to 60. If you want to see bigger, just make that number bigger. If you want to see smaller, make it smaller. It's pretty intuitive. So that's it, guys. I'm going to save this code. I will share all this with you so you can have everything, right, and explore how this works and just learn. I think this is a great educational experience to learn how Plotly charts work, how networks are built, right? I'm using a Plotly. It's called a Plotly graph object. These are very interesting. Go ahead and Google that if you don't know what that is. I'm using a heat map over here, using chord diagrams and Sankey plots as well. So that's it, guys. I'll wrap it up here. I don't want to drag on and talk about this ad nauseum. I think that's good enough. I think I covered the topic pretty thoroughly. So that's it. I'll share the code with you and I'll drop the video later today. Thank you for your time and I'll see you in the next one. Take care for now. Bye.
Hey there, everyone. Today I want to talk about a unique concept I came across kind of recently. I think I discovered this a while back. I didn't really pay attention, didn't really dig in until somebody explained to me that it's a major problem for themselves. And I thought for a second, let me pause and see how big of a potential problem is this thing really. I think I've discovered this, or it's come up on my radar at some point in the past, but I never really dive into it, so I didn't really know how much of a pain in the butt this can really be. But the concept actually has a few different names. It's name normalization, also known as label consolidation, also known as entity resolution, also known as data deduplication. So in any kind of environment, we always want to deduplicate things. We want to create duplicates and triplicates and quadruplicates of data. That's kind of insane. I've seen that done before. I'm not sure why people do that. But we don't want to do that, right? We don't want dupes in our database and our data sources and our spreadsheets or AWS or Azure databases that we work with on the cloud, right? We want to deduplicate data, but sometimes you'll get data that comes from many different sources that actually is not duplicated, but we start to combine it, you create your own duplications, sort of as a course of doing business, kind of accidentally. But there's ways to handle that and to treat this efficiently so you don't end up warehousing lots and lots of duplicates that are essentially the same, but you keep only the unique records that you need. And I know for a fact this is a problem in businesses like credit cards. Right? Credit card companies have to deal with purchases and sales transactions all the time. And different credit card companies will represent different transactions slightly differently or wildly differently, right? But we can standardize this data so it can be consumable and digestible by a normal human being without creating frustration and stress for the data management team and for the reporting team and the data scientists and the engineers and all this stuff, right? So let's say we have a list of data that comes from different credit card companies. I won't name any names because I don't even know exactly how they do this, but I know that they do something very similar to this, right? So a credit card company can record a transaction at Starbucks coffee receipt. It could be called Starbucks coffee purchase. It could be called Starbucks coffee small. It can actually have the name of the town where the transaction occurred. All right, so we have Boston, New York. Here we have food purchase. Now this doesn't look like Starbucks. This is different than Starbucks, but certainly Starbucks sells food and they sell brunch items and items fit for human consumption, right? So this could be Starbucks. It doesn't look like it. I'm going to say it's probably different. And these transactions look very different from Starbucks. I don't think Starbucks is selling clothing. There might be a handful of exceptions, but I'm going to go out on a limb here and say not selling clothes, no pants, shirts, socks, or hats for men. So I think these are different transactions. Now, again, they could be coming from the same credit card company producing these transactions, or come from a different credit card company, right, that has different naming conventions and a different way that they collect their data and report on their data. And this is fine. It is what it is, right? So we'll just try to come up with a couple of techniques to manage this process and make sense out of it, so we can alleviate any pain, frustration, and headaches dealing with this data, right? We want to make it as seamless as possible and streamline the whole reporting process, right? Or data collection process, or data science and predictive analytics process. Whatever you're doing, we want to try to make it as easy as possible. Okay, so there's a couple techniques. These are just 3 of the more common ones. There might be other ways to handle this, and that's up for debate too. We could sit down and discuss this. You could meet with your team and say, what alternative methods could we consider? But I think these 3 that I'm going to introduce are probably the most common here. So we have something called fuzzy matching. So I've introduced this in a couple other videos. This basically looks for similarities of words and tries to look for words that are spelled substantially similar and match those together. And if the words are different, those will be matched with other words that are similar to those words but different from the non-matching words, if that makes sense. Okay, so we have the categories. I put everything into a nice little dictionary. So we have the key value pairs. Here's the key, coffee, food, clothing, and here's the value. So a dictionary has key value pairs, a little bit different from a data frame or a list in Python, right? I talk about all these data structures in a couple other videos. I'm not going to get into it now because it doesn't really matter. It's just a way to contain the data, right? So I have a small script for all keywords. We have the keyword in the category. So this is the key, right? And this is the value pair. So these keys and values are matched together. And okay, so here's an example of a list. So we saw the dictionary above. Here's a Python list. The dictionary has these curly brackets, and you have the key, and then you have the value, which essentially is a list inside of a dictionary here. And here you just have a pure list. Okay, so I'm going to go ahead and run it. Now, given what we've learned above, we're going to see how fuzzy matching handles this issue, and does it actually handle it or does it not? So we have coffee, food, and clothing. These are the items that I'm looking for. Coffee, Starbucks coffee receipts, pants from New York, purchased in New York. Okay, and then dinner, retail, not a lot of description there, but we know this transaction was for some type of sit-down dinner, right? So we have the match categories: coffee, clothing, and food. And that matches this, right? So this is Starbucks, that's your coffee, that matches that, that's fine. Here's your clothing, okay? Pants, New York matches clothing, and here's your food. So mission accomplished, right? I think that was helpful, kind of useful. Though, I mean, I think it leaves a little bit to be desired. Are we really handling all this mess over here and consolidating that, or getting this fitted nicely into a tight, crisp sort of data structure? Not really. We definitely found the fuzzy matches over here. So I think it's somewhat useful, but I think we can do better. So let's look at another example. This is a clustering technique. We're going to use k-means clustering. Okay, and again, we have the items set up in a list. So we have Starbucks coffee receipt. We have Starbucks coffee purchase, dinner retail, pants, socks with an ampersand at retail. That's how this credit card company reports it. And then we have branch sales. So looking at k-means clustering, TF-IDF vectorizer. So this converts all words into numeric vectors. Computers work very well with numerics. They don't work very well with words. So we have to vectorize these. Once we vectorize it, we can make sense of all of these different items and see how they cluster together. So let's see, Starbucks coffee receipt goes into cluster 2, okay? And Starbucks coffee purchase goes into cluster 2. Okay, I think that makes sense. So these clusters are a little bit arbitrary, but anything that has Starbucks coffee is going to go into cluster 2. So I think we're handling this case very well. This is dinner retail, cluster 0, pants, New York, cluster 0, and brunch. So I think we we have a problem here because pants is going into cluster 0, and the food items, brunch sales is going into 0, and dinner is going into 0. So I have a little concern with this one right here. This one's weird. But socks goes into cluster 1. That's nice. I would expect pants to go into cluster 1, to tell you the truth. This doesn't seem to be working. There's a few different cluster methodologies we can try. I believe there's about 10 or 11. There's all kinds of things out there. I have another video that talks about the different ways to do clustering. So we could try different clustering technique. K-means is not necessarily the best. It's probably the most popular. But it really depends on the types of data that you're dealing with to determine, is this the absolute best way to do your clustering or not? So I'm not going to dig into it too deep. I just made a quick attempt to solve the problem. The first one worked, leaves a little bit to be desired. I'd like more detail here. The second one really didn't work because we have pants going in cluster 0 with dinner. So that's not working for me. I'm going to discard this. The first one, I'm going to take that to the side because I'm looking for a little bit more power here, or a little bit better reporting capability, and it's just not coming through. So I'm going to try a heuristics approach. So what is heuristics? It's a big word. You probably heard it thrown around a couple times. Maybe haven't heard. Basically, heuristics is a way to use to do a very quick and dirty analysis of something and get a very close approximation to an actual result, but you can't guarantee it's 100%, right? So it's very quick. It's going to converge quickly and easily. You'll get your solution extremely fast, right? If you do a full-blown non-heuristics analysis, it's going to take much longer, on the magnitude of, I don't even know, depending on your data set, could take hours, days, maybe even weeks to get a result, right? A heuristic is going to produce a result in a tiny fraction of that time. It's going to be mostly accurate, but again, not 100% guaranteed. But in most cases, it's going to be good enough given the time that it takes to run, and it's going to be extremely accurate, upwards of 99% accurate most of the time. So I think heuristic is a good approach to try here. So I have the categories again in a dictionary, and I have my words over here. Now, stop words I'm going to take out. I don't think that lends anything to the analysis. Like New York and Boston is not going to help me determine the type of transaction. So some companies use this. Purchase, I know all these are purchases, okay? This is coming from a credit card company. A receipt is not going to help me. The ampersand is not going to help me. So I'm taking these out, right? Men, I don't care if it's for men or women. I'm looking at what type of purchase is this. That's what I'm concerned about. Now, maybe you want to know, is this a purchase for a man or for a woman? Maybe that is important for you. In my example here, I'm just kicking it out, saying that's not important. So I just ran that. I don't know if you saw it or not. Control-Enter runs it. It flashes for about 1 second. The heuristic is so fast, in a fraction of a second, it's actually done, and it spits out the result, okay? So let's go down and see what they created for us. So we have items, Starbucks, coffee receipt. This is coffee, Starbucks coffee. Pants is clothing. This is the category. Dinner, retail is food. Okay, I like that. Shirt is clothing. Men is clothing. Hat is clothing, right? Brunch, food. Latte, coffee. Okay, that's good. Thought I made a mistake, but it's actually correct. Socks is clothing, and food is food. So there we go. We have 100% accurate. Ran in a fraction of a second, and we have all of our items listed out there, and it's neat and it's organized, and it is deduplicated. All the labels are consolidated. The names are normalized and structured, and I think we're in a good spot right now to start moving forward with our analysis. When I look at this at the beginning, this is a big mess coming from 3 different major credit companies. Okay, and of course it's a very small sample. They're going to send you hundreds and hundreds of thousands of transactions, probably millions of transactions, right? So we want to get that into a state that's feasible to work with, nice, tight, crisp, and everything is buttoned up very nice for you right here. So that's what we get with the heuristic approach, right? So again, fuzzy matching looks for name similarities and corrects for misspelling, and the strengths are handling misspellings and typos. It's very flexible in matching names, products, addresses, all kinds of things, right? But the weaknesses is computationally expensive, and it doesn't always give you the full description that you're looking for. That's what we saw in that first example. And it's not inherently grouping items like k-means clustering, right? So k-means clustering is great for getting predefined categories of data, right? The strength is you don't need to set up the categories. It's going to figure it out for you automatically. So this is unsupervised learning, right? Supervised is classification and regression. Clustering is unsupervised. You don't even know what the outcome is going to be. The computer tells you what it's going to be. You just say, give me a cluster, and it produces those clusters for you. So it's pretty nice in that respect. And it scales to large data sets. Although if the data sets get really large, it's going to slow down, and it's going to take a long time to converge, right? So that is one weakness. It does require some tuning, right? You have to set up the problem initially. And these tend to start off with the k-means, and a lot of these clustering, they start off randomly. So if you run it a few different times, you can actually get different cluster outcomes, right? So you might have to run that multiple times until you're happy with the final result that you're getting. If that's sufficient, then you can stop. But it might not be a one and done type of run. It might require several runs, okay? But the heuristic turned out to be the best approach of these three. It uses a rule of thumb to find predefined patterns and make categorizations of whatever data you're working with, right, to make ultimate decisions or to help you make improved, more informed, more insightful decisions. That's what we're doing here, right? So it's fast and efficient. You saw the thing run in a fraction of a second, easily to interpolate the results, right? The first example of fuzzy matching, it produced results, but it was really sparse and it really left a lot to be desired. The heuristic approach really gave us everything we wanted, and it's pretty comprehensive and very complete, right? Any kind of weaknesses, it does require some setup, right? And you have to define the rules up front. So it's kind of the opposite of clustering, where there's no rules. The computer figures out the rules automatically. It tells you what the final result looks like. You have to set up the rules, but then the final product is a lot tighter, crisper, cleaner, and it's packaged up in a way that's ready to be delivered to your stakeholders and to your colleagues, your teammates, and anybody that needs to see this stuff, right? So that's it. Hopefully you learned a couple new things today. I learned a couple things when I put these scripts together. I'm going to save this code and share it with everybody. I always save all the code. You don't have to understand all the details of this. You can click it and run it and then take your time and go through it and learn at your own pace, right? It's a little bit too much to get into with every video to go through every single detail of every line of code. I think it would take way too long and I would lose people along the way, so I don't do that. But I try to give you a general overview and take you through the main points of this teaching lesson, what we're trying to achieve, and then how to get from point A to point B or wherever you're going, however far you need to get to the end to deliver the results that you need for your team. Okay, so that's it. Thanks for your time, everybody. Enjoy the rest of your day. Goodbye.
Hey there, everyone. My name is Ryan Schul. Welcome to my channel. I talk about all kinds of subjects related to data science, machine learning, artificial intelligence, deep learning, financial matters, and so on and so forth. So today I have a really cool lecture for you. It is all about analyzing New York City energy costs and energy consumption. Okay, so I found some very interesting data on the internet that I started to analyze a couple of days ago, and my findings are very interesting. I came to a conclusion which completely makes sense, and I think is plausible and reasonable, and you'll see why at the end. So hopefully you can hang out for the whole session here and make it from the beginning point, which is right now, right to the very end of this, which I'll promise I'm not going to drag it on. Some of the videos, honestly, like went on for close to an hour. One actually went over an hour. I'm not going to subject you to that kind of treatment on a regular basis. Maybe never again. That one was a very long video, but I'm going to try to keep it very short and crisp and right to the point. Okay, so why should we even be interested in analyzing New York City energy consumption and related energy costs, or for any city, for any major metropolitan area? There's several reasons why we might want to undertake this kind of analysis, right? If we can identify high energy consumption areas based on zip codes or density, residential patterns, or energy consumption patterns, we can better understand how people use energy, try to understand the potential effects on global warming, understand how people spend money on energy, maybe reduce the cost of energy, or just use more energy more efficient, right? So we're going to look at a few different topics today and try to attack this problem from different angles. We're going to look at the building types and which buildings use more energy and which use less. We're going to look at multifamily housing versus commercial versus things like libraries and police stations, fire stations, so on and so forth. We're going to try to understand the overarching socioeconomic factors, right? How that influences people's sociology or interactions with other people. We're going to try to understand seasonal patterns and variations and try to have a better appreciation for peak demand and how we manage that demand effectively, right? We're going to look at some possible renewable energy and electrification potential alternates to traditional energy. I mean, we just touched on it just a tad. It's not really, this lesson is not about that, but renewables are a viable alternative to dirty energy, which is basically oil. Nuclear is actually considered clean, believe it or not. The cleans are nuclear, hydro, wind, and solar. Nuclear is actually considered clean, but the dirty energies are coal, um, oil, burn oil, things like this. So if you can manage these resources better, it can lower our carbon footprint, right? And possibly reduce our energy costs overall, right? So we're going to take a quick look at renewables and just have a better understanding for energy efficiency and any compliance requirements that go along with that, right? So I'm not going to actually run this data because it takes quite a while to do the analysis. 30, maybe 40 minutes, maybe even longer. So I don't have a super powerful computer here. I'm not doing this on the cloud. I wish I had access to this stuff, but I simply don't. I do all the analysis on my laptop. So that is kind of a constraint here. And I don't have tons and tons of resources. So for me to do comprehensive analysis would take quite a while. I did it earlier in the day, and that's it. I'm just going to preserve what I had. I'm not going to rerun these in real time. So normally I would click on the cell, hit Control Enter to refresh the cell, and you would see all the updates coming live. But it's actually so slow. I don't think that's a good use of time. So we're going to avoid that that technique. But I will share all the code with you, like all my videos. Once I post a video, I'll share all the source code so you have that available to you, and you can do the analysis at your leisure. Okay, so when you have some free time, you can go ahead and do the same analysis I'm doing here. You'll have the same exact code. So everything should be tip-top shape for that, okay? So let's look at the first assumptions here. Winter and summer, we have somewhat of a peak. I'm multiplying the normal factor by 1.15 in the winter and 1.2 in the summer. So in the summer, we use more AC. In the winter, it's more heat. In the spring and fall, it's more mild, at least in the region where I live. I'm in New York City, so I'm putting a small damper here in the spring and curtailing the energy usage and related energy spend in the fall. But then there's going to be a slight uptick in the summer and the winter, okay? And I have all my notes here explaining why. So if you live anywhere around New York City or Northeast United States, you would understand that. Pacific Northwest probably has similar weather patterns, maybe a little bit more rainy, maybe not as quite as dramatic weather fluctuations or temperature fluctuations. But in New York City, this analysis is literally based on New York City, right? So I think these assumptions I provided here are pretty realistic, okay? So I just have one field. I have energy. I don't have daily, monthly. I don't have weekly energy, right? So I'm dividing by 12 and then multiplying by a factor over here to get monthly, weekly divided by 52, and daily divided by 365, and multiplying by a small factor. So there's a lower and upper bound for that. That's how I'm getting these numbers here. And you can see in the data frame how everything shakes out. This data set actually comes from here. So I have this link in the bottom. Oops, what happened there? I have this link in the bottom cell right at the end here. What I'm looking at here, this is a plot of New York City and the major energy utilizers here. So this is, if you zoom in here, you can see some pretty interesting things. So we're going to reproduce a kind of a similar map at the end here. You see this is a multifamily housing unit, year built 1947, and there's the address here. This looks like the next door neighbor, so year built was the same. Here you have a different address. This is the Lower East Side now, and construction time was just about the same, 2 years, no wait, 10 years, 12 years later, okay, so on and so forth. And you have different metrics here. So downtown, this address is Water Street when the building was built, and then this is an office building, So you have some basic information. I'm just showing you this because this was my data source. I hit download CSV, and that became this source that we're using right now, this CSV file, okay? So you can go ahead and download that. And again, if you go down to the end here, I list the resource. That's the first one here. The second one is called GeoJSON. I'll show you that really quick, and then we'll move back here. So GeoJSON comes from here. I found this online. Took a little while to do the research and to like hunt and peck around for the different data sources, but this one seems very reasonable. I had some false starts. I went down some rabbit holes and didn't accomplish too much. But finally, after a lot of searching, I found this. So you can download that from this URL. Download the GeoJSON. We'll be using that in just a minute. And then at the end here, I have a Manhattan zip code map. So you can see where all the zip codes appear in Manhattan, and then you can apply that to your final, what we call it, just final analysis. What we end up with at the end, it looks very similar to this. It's pretty much analogous to this map right here. And you will need a Google Maps API. You can just Google it. Just go to Google free Maps API, Google Maps. Everybody uses it in your car when you're driving. When you're driving, you have a desktop application too. That's what this is. And if you go over here to apps or APIs and service on the left, you can have your own API right here. You can get it for free. Takes almost no time, maybe 30 seconds if you're a little bit slow, maybe 60 seconds to get the API downloaded and installed for your, or just approved, right? And then you'll hit the API endpoint from the code over here. So those are the data sources. These are my notes. This is the first data source. Energy use 19, sorry, not 1900. What am I talking about? 2022 was the year, right? And this was the source right here. So you can go ahead and download that so you can follow along in the lesson plan here. And then you can see we'll have things like address, zip code, building type. So we have hotel. There's all kinds of commercial, some schools. You have things like library, fire department, police department, so on and so forth. This is the energy feature that I'm using. I'm dividing by 52 to get weekly, 12 to get monthly, and 365 to get daily. This EUI is a concentration or a, what is it called? I guess I forgot what the terminology was, but I defined it a little bit later. Let me see. EUI is some kind of concentration of energy use. Where is it over here? Sorry, let me just, I won't get too distracted here. EUI, energy unit intensity. Okay, so the per square footage of energy use. So EUI is energy use intensity, and we will use that a little bit later in the analysis too. Okay, so we have all the data. We're doing some feature enhancement or feature engineering by creating new features. We have a energy monthly, weekly, and then daily over here. And then we are filtering just for New York City zip codes. Okay, you can go all over Queens and Brooklyn and Bronx and Staten Island if you want. This analysis is just focusing on Manhattan. So I'm just using the zip codes between these ranges, right? So anything between 1001 and 10282, these are New York City zip codes. Okay, so I'm importing that, converting the zip code to numeric. So these come as strings. I think in this type of analysis, I think either a string or numeric is fine. I converted to numeric and it worked fine. I think either one is fine with these types of things. With latitude, longitude coordinates, and we use those a little bit later, those definitely have to be numeric. Those can't be strings or the analysis will fail. I think with a zip code, either a string or a number will work. Now, obviously, like a zip code is not a normal number, so you can't do any kind of addition or subtraction on those zip codes. That doesn't make any sense. But it's just basically a geological identifier, right? So we have the simple conversion done over here. I'm looking at the head of the data frame and showing us the relevant address, zip code, building type, okay, hotel, worship facility, so that's a church, number of floors, the energy consumption, so that's pretty important, right? And then the features that we created over here. So where are they? Monthly, weekly, and daily. Okay, and then we have another feature that we'll parse out in just a bit. This is called fuel mix. They'll tell you the percentage of the overall metric that we are using here for energy, right? Where's my energy? For energy here, and you'll see the overall percent based on oil, based on coal, based on steam. If they use that kind of thing in New York City, they don't use a lot of steam, although I think a couple buildings on the Lower East Side actually do use steam, but that's not a primary source of energy. Usually it's coal or oil, right? Love ice water. Okay, so moving on here. So continuing with the analysis, we're going to go ahead and get feature named fuel mix. So I just mentioned that just a moment ago. We have this field over here that we're going to parse out. We have fuel oil, and then the code associated with that, and then natural gas is another type of energy supply that we use, right? So this comes to us all kind of packed into one single feature right here called fuel mix. But if we unpack it, we can get details about oil 1 and oil 2, two different types of oil, presumably natural gas, electricity. So this is the source of the energy that's consumed in New York City, right? You have diesel, oil 5 or 6. So they have several differentiators for oil, and then district steam. And then when you parse it all out, that's what it looks like. So you have this is the energy concentration per square foot. This is the original energy. And then fuel, 2 and 4 natural gas, electricity, diesel, and district steam. Okay, so hopefully that makes sense. Everything is being sort of unpacked a little bit if everything is packed into one feature, and we're doing some basic feature engineering where we create new features from existing features. So this is where you would import your API key. The 2 reasons I'm not going to run this code in real time is because I would need my API key to hit this Google Maps API endpoint that I mentioned before. It goes right here, right? But I can't reveal my Google key to you guys because it's strictly personal and confidential, obviously, so I can't give you that. And again, this analysis takes way too long. If I do it in real time, it would probably take 35 to 40 minutes, maybe exceeding 40 minutes, and I don't want to chew up 40 minutes of your time. So I'm just going to step through the code. I'm doing some basic narration here. Don't worry about what this cell does, all of this stuff. You have Folium maps, pandas, data frames, GeoPy, encoders, addresses. We're converting the address to a latitude, longitude coordinate down here. And then we're assigning everything back to the original data frame. But you don't have to worry about all the details and nuances. The code will work as is, okay? I can basically guarantee you if it works for me, it'll work for you. The only issue you might have is if you try to run this and it says package not found or library not found Folium, it's giving you an indication of what the issue is. So you go to your Anaconda prompt and type pip install Folium, PIPINSTALFOLIUM, and hit enter in your Anaconda prompt. If that's your issue, if you already have Folium installed, then that's a non-issue, right? You have the library, you can utilize it. If you don't have the library, it's going to prompt you with a little tiny error down here, okay? And it tells you, okay, you don't have Folium, you have to go ahead and install Folium. Now, I'm not sure why it doesn't just do that by default. You would think if the computer is smart enough to say, okay, you don't have Folium installed, let me go ahead and install that for you. But it doesn't do that. It's not designed like that. The only reason I can think of is maybe packages have extremely similar names and you might get the wrong one and the name could conflict with another naming package or another name convention that you have installed in your environment, and that can cause some downstream issues. So maybe the designers of these pip packages thought a long time ago, you know what, we'll just force the people to install it if that's what they really want. We're not going to auto install it. That's the only thing I can think of. Never really looked into it that much, but that kind of makes sense. Otherwise, if the computer knows that this is missing or this or whatever, it should kind of do it by default, but it just doesn't, right? So, so that's it. That's the whole setup that we're dealing with here. We're going to aggregate the columns right here and convert all of these to numeric, okay, because they actually come to us as strings. This is string, all of these are strings, so I want to convert these to numerics. So I'm going to go ahead and put all of those into a list, and if I look for that, I am going to go ahead and I'm sorry, this isn't the conversion, this is the aggregation, okay? So I can type all this out, but if you use it once, or certainly if you use it more than once, you probably want to have this in the list. You can iterate through all the items in the list. And this code right here, this simple one-liner, basically captures this logic right here, right? When you go ahead and doing the sum by zip code, when we're grouping by zip code, it's aggregating all of these columns right here. So let me just take a quick step back right here. Yeah, it's fine. It's fine. Okay, so let's move on. Let's move on. That's fine. So everything is totally fine up to this point. We do the aggregation by zip code, and then we take this long column or a whole bunch of columns like this and melt it into a long vertical data frame. That's what melting is doing right here, right? So when you say df group.melt, it's basically taking an unpivot. A pivot would be a long, drawn-out, multi-column data set. An unpivoted data set would be just a few columns with lots and lots of rows. It's also called melt, or it's also called stack, right? So if you take a bunch of rows and stack them on top of each other, or melt it into a vertical column, or a few vertical columns from many multiple columns, that is the equivalent of an unpivot. Okay, if you have a wide format or a pivoted format, then everything's stretched out with lots of columns and not so many rows. Okay, so that's how we get that. So this is what I thought I saw before. This is what I'm looking at now, is actually converting all of these into numerics. So if I could do control enter or control find for column and energy columns, I'm converting every single column right here to numeric, okay? PD to numeric, so pandas to numeric, just to make sure all of these are numeric. When I ran through it the first time, I realized they're all strings or objects, and Python, a string and an object are the same thing, right? But we can't do mathematical operations on strings or on objects, so we have to convert those to actual numerics. So pandas to numeric helps us do that. So that's how we get that, okay? And then we see the final result over here. You can't tell just by looking at it, is this numeric or is this a string? We kind of can a little bit, because you would have like a decimal place. You could have 10001.0 or something if that was a string, right? So that's numeric. That's how we can tell. But these look all numeric to me. But again, to test it, really you have to look at the data type to know for sure. But I just converted there, and I just confirmed right there. So I did a quick sanity check. So these are all numeric, right? These are floats, and we want to capture a float, or we want to convert that to a float. So we have this decimal point precision right here. Otherwise, everything would be converted to an integer, right? It would be rounding down right here, 93, and no, it would round down to 58. Right, and so on and so forth. But we have floats here, so it captures all the decimal points with extreme precision there, right? And certainly on the latitude, longitude, we need that kind of precision. If we're looking at these these lat long coordinates, sorry, I've had a bit of a cold here for a while, for a few months actually. It's dragging on. So we want all of these to be float numbers, okay? So let's go ahead and convert this into our first graph. So we're looking at these metrics right here from this data source. Sorry about that. So we have our metrics here, and we're going to convert this into a Plotly bar chart. So if you want to see basically what this looks like, you can go over here and Google this. I love these Plotly charts because they're dynamic, they're interactive. You can put the mouse over it. The details of the data underneath the mouse pop up, right? You can see here, count is 11, count is 13, count is 24, 10, and what was that again? 15, and then 8, and then you can zoom in and you can zoom out to get extreme detail on these objects too, okay? So it's pretty cool how you can interact with these Plotly charts. I like it a lot. I use these in a lot of my demos here, so take a look at that when you have some free time. So yeah, we're going to create a Plotly bar chart. Here's the data frame. The x-axis is going to be the horizontal. The y is going to be the EY. That's the concentration of energy used per square foot. And okay, without further ado, we're going to go ahead and plot that, and we get this nice little chart down here. So we can see here, this zip code 10001 has an EY of 624 or 642. Okay, this zip code 10002 has slightly less, 305. This is 64. This one's higher, right? 1336. And you can see the higher the density, or the higher intensity, the bigger the number, and the darker the color. So that has a higher EUI. That's darker. That is darker. That's probably the highest one. And these are muted a little bit, and these are totally different color, right? It goes from dark blue to lighter and lighter blue to light red to dark red for the very short EUI. So these basically are low energy per square foot usage, right? That's low energy per square foot, low, 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 all the dark reds, and the dark blue is high EUI per square foot. So we can, that's looking at the EUI, okay? If I go over here, we can look at the daily energy, okay? And I set this drop-down control to look at the different features in its data frame, so I can get EUI, which is, again, density per square foot. This is daily by zip code across Manhattan. This is weekly by zip code across Manhattan. So you can see it goes up to almost 4 million. If I go back to daily, that is just over 500,000, 624. Then it goes 438, right? For weekly, monthly, we are looking at 21 million. And this is gigawatts, by the way. This is gigawatts. And this is, oh, the next is annual, okay? And 228 million for this zip code for the entire year, okay? And these are pretty relative. You can see that this zip code 10003 uses predominantly more than 10001, and 1 uses more than 10002, okay? So you have this nice interactive chart here that you can play around with, and that comes from Plotly, right? And you have these different metrics. daily, weekly, monthly energy, which is actually annual, right? And then EY, which is the square footage concentration or per square foot utilization of energy. Okay, so that should make sense, hopefully. So here's the next data source that I'm pulling in. So that comes from over here, right? And I shared that with you guys. I showed you an example of that. That comes from here, right here, and you download the GeoJSON. I share this link with you at the bottom of the workbook here. So essentially, this is all JSON data that has to be ingested as JSON, then converted into GeoJSON. So there is a few things in this file, including, well, you can look at it right here. Zip code, it's called mod z CTA. You have to look up what that is. I looked it up. Didn't make a whole lot of sense, but there was a reason for that. They have population estimate per zip code, and then they have the geometric figure of the zip code. So they actually have like the boundaries of each zip code, which you'll see in just a few minutes when I get over there. It actually helps you to create a chart that's very similar to this. Okay, so we see all the buildings, all the footprints, the layouts of all these different longitude, latitude coordinates across New York City, including building address and so on and so forth. This view, which we're going to try to reproduce to some extent. I didn't get this kind of granular detail with my data. I couldn't find that somewhere. Like, I don't know how these guys got that, but I got to the zip code level. I just couldn't get more granular than that. But then again, yeah, like it shows you the layout, the latitude, longitude, the coordinates, and then the grid view of Manhattan, right, with a little bit more granularity than I was able to procure, but we're going to get pretty close there. You'll see in just a minute. So that basically gives us the parameters or the outline of the lat and longitude coordinates mixed with the zip code for each zip all around New York City. Okay, remember we're looking at this from a zip code level. That's the goal eventually. The first pass through we don't get there, but we will with the second or third iteration. You'll see that in just a minute. So yeah, I'm going ahead and pulling in all this data. And again, the reason we get this is to get the parameters of the zip codes all around New York City, right? So it shows us like the upper bound, the left to right, north, south, east, and west parameters for all the zip codes. That's why we pull this in, and we have to merge this with the original data frame that we had back here that has zip code. Fortunately, that's how we do the merge, right? But then it has all the other things like daily energy. Well, I converted that. That's the feature engineering. Energy, EUI, address, and so on and so forth, right? So we're merging together two data frames. Each one has relevant information. I couldn't find any one data frame that has everything, so I had to pull two from two different sources and then merge them together. And you'll see that in just a moment here. So the MOD, whatever this thing is, I can't even say what it is. Dataset refers to the modified zip code. Okay, I guess mod is modified. Zip is Z, right? CTA. Who knows what CTA is? I don't know if it really matters. But this is all the zip codes around New York City and the geographical boundaries of those zip codes, right? So that's where, based on these coordinates right here, we get the geometric north, south, east, and west parameters of each zip code, so we can isolate those and then pinpoint where they are relative to all the other zip codes. So that's how that works out, okay? So scrolling down a little bit, we go ahead and do, I think we did the merge here, right? Yeah, here's the merge. So the original data frame was this right here, this guy, right? So we're pulling in this data from the source coming in as JSON. We convert that to GeoJSON so we can do the merge. The merge happens right here. This is the energy data frame. This is the GeoJSON data frame. We merge those together and we come up with this. Okay, so we have address, zip code, energy. There are the features that we broke out. Everything was packed together. We separated it into the 6 different categories that we have. Lat long coordinates, latitude, longitude. This is the zip code right here. I'm looking at both and then merged together. This is what we have. So the geometry is that right there, right? And then we have all of the features from the first data frame, the grouped by data frame, right? So this is the first GDF, comes from DF and grouped, DF grouped together, then we come up with GDF, okay? So geometric data frame, that's what that stands for. So hopefully that makes sense. So now we are going to go ahead and convert all of these metrics into gigawatt hours. Okay, this is a conversion. So I looked this up online. We had originally energy, right? We divided by 365 to get that, 52 to get that, 12 to get that. Then we multiplied by this factor to get everything into gigawatts. So we have a little conversion going back and forth. Pretty straightforward, pretty simple to do. This shows me all the building type unique counts. I don't think I need that. Let me get rid of that right there. I don't need that per se. And then we're going to go ahead and plot that geodesic data frame, GDF, geodesic data frame, or geometric data frame, whatever you prefer. We have latitude and longitude. The energy in gigawatts, okay? This is annual use now, so it isn't the daily, okay, like we see over here. Where's my daily energy, weekly, monthly, okay, and we had the original energy, so we convert all of those using this simple little mathematical operation right here to get daily energy, gigawatts, weekly, monthly, and this is annual. Okay, so that's it, guys. Pretty straightforward, pretty simple. When we plot it, we have this nice little plot that shows up over here. Now, this isn't everything. I think I picked 1,000. If I search for this, 1,000, let me see. Can I find it? Yeah. So, nope. I think there's one more. Let me see. It just lists two, right? Okay. It doesn't matter. It doesn't matter. Okay. So we have this map, which looks pretty nice. Again, it's a Plotly map. It's pretty cool because you can zoom in, you can zoom out, you can see what these things are. We have an office building over here. You can tell by the, what's this called? The legend. You can tell by the legend on the side what these things are. This is an office building. This is office based on the color right here. This is a hotel. And the size of the circle represents how much energy that that unit or that object uses. So if this is office building, it uses 19.9 gigawatts. This is an annual basis, okay? So almost 20 gigawatts per year. This is multifamily housing. This is multifamily housing, multifamily. This is a hotel, okay? This is an office. This is multifamily housing, and so on and so forth. And if you click on this, you can turn these on and off. So you see multifamily housing disappear and then reappear. And then if I go down here, we can see the same thing with office. If I click that, they disappear and then they reappear. So this is pretty cool. I kind of like it, but I wanted something a little bit more intuitive. So I went above and beyond and converted all of these zip codes based on the parameter of the north, south, east, west border of the zip code into actual zip codes. And I wanted to plot that because that represents this view a little bit more similarly than the circles do. Okay, the circles are nice, but I wanted to get something that is more representative of city blocks. And I could not find the detail where I have all of the buildings like on this block. If you zoom in, you can probably see there's going to be a couple different buildings. I know that's a Chase building. I used to work down there. Across the street, you have, looks like 3 buildings. This is one. I think that's Brown Brothers Harriman. This is Zuccotti Park. And then this is one building over here on this view right here. You can tell between Maiden Lane and Liberty Street, you have a few different buildings. So I could not get that extreme detail of the shapes of the buildings. I tried a bunch of different things. Nothing really worked out. So I settled on the GeoJSON rendering of the zip codes over here. So you have 10001 again, that zip code, and we have all these geometric figures that we can convert into zip codes and then match based on the address and the overall energy utilization and the energy cost too, to marry everything together or to merge everything together. So that's the objective here. So we're pulling in this zip code boundary GeoJSON to help us with those defined boundaries. So here we can see the GeoJSON underscore data is the data set. We have the zip code to get the location. This shows us the ID as zip code. Remember, modified something, PA is zip code, whatever that thing is. And then energy, gigawatts, it's going to be the color that we use. And then the zip code is going to be the hover name. So when you put the mouse over it, we will see the zip code pop up, right? We have the center for this lat long coordinate. I just picked something that is kind of in Midtown Manhattan to get us off to a good start, right? You can pick downtown, uptown. If you don't pick that, you don't know where the map is going to start off. It could be north, south, east, or west of the city. I put these default coordinates just to help us get off to a good start here and plot this like right in the middle of Manhattan. So we have Midtown right here. We have the different zip codes, right? So that's what Plotly is giving us. And again, I like these Plotly charts just for that fact. The mouse, when you plot over it, it shows you the detail of the zip code and then the energy used. So here's 12 gigawatts per year. This is 12.6. The colors are pretty similar. Just almost the same thing, just off a little bit. Okay, so these buildings I think are pretty efficient. Again, the darker the red, the lower the energy use. This is a little bit lower, 4.25. This is 12 gigs. Here's 33 gigs. This is high energy consumption, 84 gigawatts per year. This is 84.3, 84.8 gigawatts. We go down here a little bit. So these guys are in between, right? Not too high, not too low. These are a little bit more energy conservation, energy aware. Their energy use is lower. This one's a little bit higher. And then you go down here. This is pretty low. Not even 1 gigawatt hour used per year. So that's pretty efficient. And then down here you have 37. So this is probably a lot of park space over here or something like that. And then you have 31 gigawatts. Okay, so almost done here. Just bear with me for a couple more minutes. So we have the group by zip code, building type. I want to look at the daily energy gigawatts, weekly, monthly, and then overall energy, right? And I want to sort this. So I'm sorting in ascending equals to false. So basically that's descending order with the highest to the lowest. So the highest energy use, 137 gigawatts per year. That's multifamily housing. This is the daily, weekly, and monthly, and that is zip code 10028. If we go up there, we should see that pretty easily, I think. 10028 should be like a dark red, right? 10029, 10035, 10028. Well, the neighbor seems to use a little bit more. 10021, 10028, or 10029. You know what? That might be something just slightly off here. I thought it said 10028. But it might be bleeding over into this next zip code in a little bit. So it's pretty close. We might want to do a little bit of investigation just to see a little bit deeper. Like, is this 100% correct? And does it match with what we see over here? Now, on the surface, I'm saying this is realistic. This is plausible. I think it passes the validation test. I think it passes the sanity check. But you know what? I just hacked this code together in a couple days. So I didn't have a team looking at it. I do all this work by myself. I don't have anybody to work with. It's just me doing all of these demos and these teaching lessons. So I think this is pretty close. It would be good to have a second pair of eyes on this. That would be nice, but I don't have that kind of opportunity to pass this on to somebody else. I have to do it by myself or it just doesn't get done. So here we can see multifamily housing. We saw traditionally that these buildings tend to use a lot of energy. K to 12 school uses less energy. That makes sense to me. Kids are gone on the weekends. They're only there 9 a.m. until like 2:30 p.m. For some reason, the schools get out at 2:30. My wife and I were talking about this today. I have no idea why. You'd think the kids would stay in there until 5 or 5:30 when the parents get home from school, but nope. They get out at 2:30 while the parents are still at work. So the kids are just there using less energy. Fire stations not going to use a lot of energy. Library won't use a whole lot. All these New York City libraries are closed on Sunday, unfortunately. So there's one full day. They're not using hardly any electricity, maybe for those exit signs that stay red all the time. But beyond that, they're not using a whole lot of energy, right? So these fall into the lower end of the spectrum, and these multifamily units are on the high end, right? Let's look at EUI. So again, zip code, building type, and we are sorting this in descending orders. So I set ascending to false. So we can see the highest EUI, residential care facility, library, museum, worship facility, other restaurant, bar, and then K-12 the school. These are low per square foot. So it's a different metric, right? It's not for the whole building, it's per square foot of the building, energy consumption, right? So similar but different type of metric from the daily, weekly, monthly energy, right? And I think we are almost at the finish line. I want to look at this, again, group by zip code, and look at the total energy divided by the population. So we have total energy divided by population here. And we can see which zip codes are the least efficient. 10069 is the least efficient. 1004 is close. And these are the most efficient. 10032 is 95%. EUI. So again, that is energy use per square foot. I believe that's what it is. I just found out about this stuff the other day, so you can Google that. EUI energy. I think this is per square foot, and this is the most efficient. 1031 is the most efficient zip code by energy use per square foot. Okay, so that's it in a nutshell, guys. We have the NYC zip codes. We plotted everything based on the parameters of those GeoJSON files. And we see a single large apartment building can consume 5 to 10 gigawatts per year. And then, and such buildings will contain, or it may contain 100, multiple hundreds of units. Like the building where I live, we have almost 400 units for the whole building. So it's quite a few residential spots for people. When you get up to 400, that's pretty large, and it can be 100 to 150 annually. And this sounds pretty reasonable, right? Based on what we saw on these resources over here. So this site, this right here, remember you get this file GeoJSON, and then this is the zip code of the whole city. You see 10002 down here, 10013, 10004. Okay, so we have 102, 1013, 1004 down here. If we go back and look at the map, this should be pretty much the same. 1002, 10013, and 10004 right at the bottom, the tip of Manhattan, right? The southern tip. So I think everything looks good. Looks like we're in good shape here. I have just a couple more notes. We can derive key insights from studying different metrics based on New York City energy consumption, predict and imagine supply and demand. That's what we're trying to do here. Impact of external factors. Can be extreme weather, can have an impact on energy use. By all means, that is definitely something to consider, right? Cost optimization, right? How can we reduce these costs? Now we know what the costs are. The next step in this analysis will probably be cost mitigation or cost optimization, urban planning, and sustainability. How can we continue to strive to create energy efficient buildings and build a sustainable infrastructure in New York City, right? So that's something that we can do in the next step for this analysis. I didn't do that actually, but that would be the next logical step. And then climate change adaptation or adoption, just to understand what kind of potential impact large quantities of energy consumption can have on the local area, and then far-reaching consequences too. Is there collateral damage to upstate New York for burning and consuming coal and oil and dirty energy? What kind of impact is that going to have on the sparser populated areas, right? New York City is very densely populated, and upstate New York is very sparsely populated. So what would the impact be on those guys? That could be another step for additional analysis here. So that's it, guys. I'm going to wrap it up. Thank you so much for your time today. Hopefully you learned a thing or two here in this analysis. I definitely learned a couple things putting this stuff together. Hopefully you did too. So that's it. I'm going to save this code and post it. So check that out when you get a chance, and I will see you in the next video. Bye. Hey there, everyone. My name is Ryan Schewel, and I created this channel called Straight Data Science probably about 9 months ago, and I go through all kinds of different topics, some related to finance. That's what I studied in school. Some completely unrelated to finance, and it can be all kinds of different analyses that I do, but I think all of it is practical and useful, and I share my findings with you here. So the topic that I want to talk about today is New York City subway ridership and how we can do analysis to gain more insights and understand the patterns and the frequencies of people moving around New York City using the subway. So basically analyzing NYC subway ridership isn't just about counting people on trains. It's really serves a whole bunch of different purposes. Some of them are very critical too, especially for the city making decisions across urban planning, topics like transportation policy, public safety, equity, and even the overall economics of New York City too, right? So there's a few different reasons why we would want to do this type of analysis, probably for urban planning and infrastructure optimization, policy and budget decisions, economic and business impact, emergency response and public safety, overall sustainability and environmental planning, and even equity, and accessibility, right? And how do people get around? How do people get from point A to point B? So let me go ahead and kick this off. I found this data set. I think this is going to serve the purpose quite well. I was actually planning to do this type of analysis a while back, like a few months ago, and I looked around for the data. I couldn't find it, so I put this on the back burner. But just recently, I think it was like literally this morning, I found some data that looked pretty useful. So I decided to take my ideas and create a Jupyter notebook and then record a video about what I did. So let me show you the data real quick. This is running. I see the star and the hourglass up there. So this was the source of the data. I just took a little sample initially. Now, let me ask you, is this a definition of beautiful? When you see this, you think this is Mona Lisa, this is just Monet style art. This is actually very ugly for me, right? But in the computer science world, it's very easy to store information in this format. This is called JSON, Java String Object Notation. So for storing data, it's very efficient to read and to write this data. For a human being to look at this and say, what is going on? Like, I couldn't even begin to comprehend, right? But again, for storing data and for reading and for writing data, this makes a whole lot of sense, okay? So that's why we use JSON strings. There's a few different formats. There's actually many, many different formats, but JSON is pretty popular. Parquet is another format that's compressed that tends to be pretty popular, especially in the big data world. It's up and coming and getting much more popular right now. So those two text files, CSVs, these are other popular ways to store data. I think the JSON stuff is one of the top storing types of data or formats of data, right? So if you go down here, it's pretty comprehensive. And I'll tell you, wait, it actually keeps going, right? Yeah, okay. So yeah, pretty massive data set. So I started to poke around here this morning and I realized, okay, basically I was just fetching the data just the normal way. Here's the JSON link right here, right? So I said, go ahead, make a request to this and then pull in the data, right? So here is the request.json. This is how this works. So basically set a couple parameters here. I want 150,000 records and I'm doing something pretty interesting. It's called basically stratified random sampling, right? It's a little bit of a tongue twister, but you're taking different strata, which are different levels or different groups of data, and you're taking random samples from each one. So the issue I ran into, like just getting access to the data is where I spent most of my time for this project right here, because I kept getting January, I got January and February, then I got 4 days of the week, but Monday was completely empty, Saturday and Sunday was gone. So that was bizarre. I was thinking like, of all this data, why am I getting these different random chunks of data, right? So I set the request to 10 million. So at 10 million, it was running and kind of chugging along, but it couldn't complete. And I think it probably had a timeout or just stalled, or maybe just the memory got filled up and it just couldn't do it anymore, right? So I came up with a different technique, stratified random sampling, again, to get these different strata so I can get all the months of the year, all the weeks of the year, and all the days of the week, because I wanted to do my analysis and see like what are these different patterns of people using the subway at different points of a time during the day, right? So you can imagine overnight during midnight, 1, 2, 3 o'clock, the ridership dips quite a bit, right? At peak hours, like the morning rush and the evening rush, it jumps up quite a bit, and you'll see some charts that depict that in just a moment here, okay? So that I knew that's what the end game should have been, right? But I kept getting these chunks of data that wouldn't help me do that type of analysis, and I had big gaps in the data. So I had to go back and come up with this technique to do the stratified random sampling, just so I can get data from these buckets and make it somewhat comprehensive, but make sure all of these categories are represented too. So the day of the week, the time of the year, the hour of the day. Otherwise, the analysis just looks bizarre and it doesn't make a whole lot of sense, right? So sometimes you have to kind of step back when you're working on these problems and think of the different approach. So there's another case, kind of similar, kind of different too, where I was working on a model one time, and a couple of times actually, it just took a really, really, really long time for the model to run. It took hours and hours, and I thought there's got to be a better way. So I did some research and figured out that if you use a heuristic, It's basically a representation of the data, but it's not going to be absolutely perfect and precise, but it's going to be very, very, very close, and it's going to run very quickly. So if you take a random sample and achieve your goal and you get your job done, I think that is far better than trying to fetch all the data or getting chunks of data, but you're missing big pieces of data and you have these big gaps. That doesn't make a whole lot of sense, right? You want to finish the project. You want to make it work. So if you need a heuristic and make it work fast, because you don't have days and days to wait for them all to run, or take a stratified random sample from your data and get the output you want, I think that's far superior than just giving up or just having huge gaps in your data and you're missing stuff. That doesn't make any sense, right? So sometimes you have to get clever and almost a little bit cunning in your approach to how you solve these problems, right? And figure out what the end game is, and then work backwards from there and say, I know I want to get to this point, and then figure out, okay, what do I need to do to get there, right? So that's what the exercise was about today. Stratified random sampling and a heuristic would have been a nice approach. It didn't really apply in this instance, but that's something to consider for these cases where you have long-running models, okay? So I put that in my notes down here. So we're getting all the months. You'll see that in just a minute. And we're taking equal-sized chunks. That's what this is. So 150,000 records from these months. But again, the data was so massive, I had to do that just to get this thing done and just to be able to answer the questions that I wanted to answer. Okay, so we're taking chunks. So it does look a little bit gamey, and it does look like, okay, we have 150,000 from March and from May and from December. But guys, that was the only way that this was going to happen. Okay, otherwise the data set is just too massive. You saw it. It's this thing over here. It's this beautiful looking creature over here. So sometimes you just have to get creative in your approach. So I think this is almost done. It's looping through all these strata and getting the data 12.1 to 1.1. So I think it's almost done. We're going through the entire year of 2023. Okay, so I think this is representative. If you have these weird years like 2020, we had COVID. Is that really what you want to analyze? COVID? Maybe, maybe not. I just wanted to take like a normal sample of data. So I think the entire entire year of 23 is fine. I think that's a good sample or a good starting point. And again, we're working with samples of data just to make this thing work. Okay, so hopefully this is done. I've got some notes down here about what I was doing just above. Okay, and the first time I started way too small. I only had 15,000 records and it wasn't enough. And like I would have to see even, I don't even know how many people ride the subway, millions every day, right? Let me check this out. This is why this data set is so massive. How many people subway daily? Okay, that's a change on the weekends versus weekdays. 3.6 million daily riders. Okay, so that's a lot. And they're capturing all the information from all these riders. So probably twice. You're probably taking it to work and home from work, maybe 3 or 4 times if you're running errands or going to the gym, right? So to capture, wait, what was I already forgot? 3.6 million, probably twice a day or more, and collecting all of that for all of 2023. So that's a lot of riders. Let me do one more quick analysis here. Calculator. No, this is very, very general, okay? But let's just say 3.6 million, 3,600,000 times, I'm going to just go out on a limb and say 2, okay, times 365, very general because it's going to fluctuate during the summer. Oops, go back, clear. I'll clear the whole thing, right? 365 times 360,000 times 2. So 2.6 billion records per year, just general, right? Just generalizing. And that's only for 1 year. So I don't even know how far back in time this goes. If I look at this is 2024. So that's the most recent that they have here. I guess they didn't collect 2025. And it goes back here to 2024. And this is not sorted in any specific order too. So these years are going to be all over the place. Anyways, the point is massive, massive, massive data set. So you have to get creative with how you work on this stuff. Okay. So the data comes in. that's fine. This is my data frame here. So I'm looking at transit timestamp, transit mode, subway. I think they're all going to be subway. I don't even know why they have a category. This is station ID, station complex. So that's the name. And then the borough, payment method, MetroCard or Omni, and then fare class, full. I think they have different classes like student class, ridership. So this is a number of people that went through this station in 1 minute. I think that's how you interpret that on that date. Okay. Then you have number of transfers. That's probably going to a bus, lat long coordinates. So that's helpful too. And then georeference. Okay, so that's it. Basically, it's the counts of the riders on the subway over a period of time. So that's what we're looking at. So I took the data, okay, transformed it into something that's a little bit easier to work with. So I have a couple things I'm doing over here. I'm getting the hour, day of the week, and month, because that doesn't come very easy to work with, right? So I have to parse that out from there. That's the year. This is the month. And then what? 0101. Okay, so January 1st, 2023, and this is the time. So that's how they're doing it, right? So I want to get the time, the day of the week, and the month of the year. So this is called feature engineering. I'm basically just parsing out from that timestamp right there that has all kinds of details. I just want to chop it up and make it a little bit easier to work with. So I have hour, day, and then month, and then making sure that this is actually a real timestamp, okay, and then looking by riders by hour. So we're doing a group by hour, and then summing all these, right? So we get the comprehensive number of customers that go through each station by hour, right? So again, the time of the day, I think they give it to us per minute, but we're collecting it, we're aggregating that up into hours. And then since they don't give us the month, really, they don't give you a whole lot. All they give you is this thing over here, right? So 2023 0101. So we have to get the year, month, and day out of that. So that's what this is all for. So now we have these new features over here on the right. This is called feature engineering. And I have the hour of the day of the week, and the month of the year. So I think that's a little bit easier to work with versus what they gave us, right? So now I can create my first chart. I'm going to look at the ridership counts by hour of the day. So pretty straightforward. I get the riders by hour, right, doing the aggregation that I had above. So, let me expand this too. So I did create a couple data frames over here. So the original data frame is this right here. This is data frame.head, and I printed a little separator over here. That's all it is. Then they have riders by hour. Okay, so you go down here, ridership by hour. So you have 0 through 23. They're using military time here. And the ridership counts. You can see it goes down at 3 and 4 o'clock in the morning. That totally makes sense. And then we have by day of the week, and then again, the counts of everything, or the sum of everything. And then by month. So we have everything laid out, but it's not plotted for us. So I want to create a plot so it's just easier to visualize, because if I look at this, or if I give this to any stakeholder, they're really not going to know what to do with it, right? They probably put that into Excel and try to plot it or something. Same thing with this. Like it tells a story, right? And this is all correct. I'm sure it's correct, and I'm sure it's interesting. But when you look at these plots, it's just a lot more rich. It's a lot more meaningful, right? When you create the chart, it has to answer questions. If it generates a whole bunch of questions, it's not a very good chart. If people look at the chart and say, oh, yes, this makes sense to me, and I understand, this is a great visual, that's a good chart, right? You want to answer questions, not create questions. So I'm basically getting the hour sorted. So we're doing sort values, so it's sorting in descending order. And I have the original data frame that's called riders by hour. If I do Control F, paste that over there, you'll see that. So here's the original data frame up here, rider by hour. That's how we got this right here, right? And then I'm just recycling that, or reusing that to get my chart down here, and I'm sorting it in order, because a lot of times, most of the time, it doesn't come just naturally sorted in order from 0 to 2300 hours. Normally, you would have to convert that yourself. I mean, it could randomly work out like that, but usually it doesn't. And if you rerun it another time, it probably wouldn't be in the order that you want, right? So you kind of want to force these things to follow some kind of pattern that's coherent and consistent. I guess sip of water here. Okay, so the chart is running. The code is running. It's building the chart. Honestly, it's a little bit slower than I thought because I was testing this code before I turned on the recorder, but I'll just let it go. Basically, again, this is sorting the data frame. This is doing the sort over here, right? And Control F if I put that in, you can see we're just creating categorical codes. So for 24 hours, 0 to 24, where that's the range, 0 to 24. Then we sort the list over here, and then we use that object. This is a data frame object. Plot hour on the x-axis and ridership on the y-axis. Okay, so now we got our chart. Let me run the next one because that could take a couple of minutes, and I'll run the next one after that. Oh, that one's already done? Well, that was fast. Okay, so for some reason, the first one took 5 minutes, and the second one took 1 second. But anyways, we have what we need here. So you can see ridership dips down overnight, 470 riders. 470,000. Okay. Yeah, for a second, I think it's a little bit higher. 269K. 3 o'clock, we hit the nadir or the low point, 219K, and then it kind of spikes up a little bit. So people are getting ready, I guess, hopping on the subway, going to work at 4 a.m. Maybe essential workers. 5, 6, 7, 8. This is 9, 8 o'clock. So the ridership is at its peak, 6.4. And then this is 9 o'clock. So most people are at the office. And most people are where they need to be. You have some people come in a little bit late. Maybe at this point they're running errands, going to the doctor, or whatever it is that people need to do. Now we're at 2 p.m. This is 3, 4, 5. So here's the peak. 1700 is 5 p.m. And I kind of hard to read that. 7.1 million. And this is 6.4 million. So here's the peak. 5 p.m. 6, 7. 8 is 2000, 9, 10, and this is 11 p.m. And we still have 1.25 million people on the subway at 11 p.m. Okay, so that is a normal day on the New York subway. So this is by day of the week. So Monday, Tuesday, again, I'm doing the sort. So I'm creating categorical codes over here and then sorting everything. So ordered equals true, and then using that data frame. So this is riders by day. This is riders by hour. So different object, different data frame, right? So feeding in different slice of data. So we have Monday, Tuesday, Wednesday. There's a big spike up here, 15.36 million on a typical Wednesday. Now remember, this is for the whole. This was what the whole year of 2023. Okay, so we saw over here. On any given day, there's about 3.6 million people on the subway. So it's 15 million. Can sound a little bit high, but that is over the course of 2023. Remember, that's how we fetch this data. So Thursday, again, pretty high, equal to Wednesday. Tuesday is a little bit lower. And I'll be honest with you, I think there wasn't like a big dip on Tuesday because I did that random stratified sampling because that was the only way I could get this to work. It just happened to miss some Tuesdays in there because I would expect like Monday, Tuesday, Wednesday, Thursday, Friday to be somewhat consistent. I can definitely see lower ridership on the weekends. People aren't going to the office, right? They're doing recreation activities, going out to Central Park or going to play or running errands or whatever. So I would expect a dip on Saturday and Sunday. This totally makes sense. This Tuesday, I think it's an issue with the random sampling. But again, I had to use that technique where I would have no charts, no video, and no analysis here, right? That was the only way to get it working. So again, I think Monday through Friday is going to be pretty consistent. You could see some work from home Monday and Friday, right? So those might be a little bit lower. Wednesday, Thursday totally makes sense. Tuesday, I'm guessing it's the randomness. And we just didn't happen to pick up as many records for Tuesday as would have been nice, but that's fine. It is what it is. So here's January again for all 2023. So 4.4 million people. February spikes up a little bit, almost double. March kind of similar to February. April, there's a little dip. May, June, July. Now in July, people are out of town, going on vacation. So ridership dips. I think that's what that is. And that's it. So that is ridership by month. For 2023. Now I want to look at the top most frequently used stations based on number of swipes. Remember, we're counting all the people that go through all the turnstiles, and we have the station ID and the station name. That was in the original data set. So these are the top 10 stations. We're getting the N largest. Okay. And again, this is station complex. That's the station name. And we're doing the group by ridership. So I already knew this one, Times Square. So 2.9, wait, is it 2.9 or 29? 1, 2, 3. Yeah, 2.9 million for 2023. There's no other filters or anything applied here. Grand Central is close. It's not that close. It's off by 1 million, but that's number 2. And Herald Square is number 3. Union Square, that's a big one, 14. And the top 10 rounds off with 74 in Broadway. So that is, I think, oh, that's Jackson Heights. Yeah. So they made it to the top 10. Wow. I didn't expect that. But all these others, these other 9, I could have guessed that pretty easily, but I didn't know that this would make it to the top 10. Here's the bottom 10. Broad Channel, Beach 105, Beach, Aqueduct, Racetrack, I think I know what that is, and Beach 90. I don't even really recognize any of these, so these are not places I would go. I think this is on the A line maybe, and it's pretty far out, Far Rockaway or something like that. So anyways, I thought that analysis was pretty interesting. Now let's create a heat map so we can visually see what's going on here. Okay, so I always say a picture is worth 1,000 words. If you take a visual and show it to somebody and they can understand quickly and easily what's happening, like these bar charts over here, that makes sense to me. Okay, all this makes sense. Then I don't have to spend 1,000 words to explain what's going on. I can have a very short conversation with someone, give them a printout, or just share my screen with the person because they're looking at a plot or some kind of chart, and they can visually see how everything works out. Okay, so here we have a heat map. If I zoom in on this heat map a little bit, you can see there's a lot of concentration of subway usage. Over here, this is going to be Times Square. Okay, they give us the lat long coordinates. And this is going to be, I think, Grand Central. Yep, that's Grand Central. I can recognize that. So these are the 2 that we just saw are the 2 top most frequent. And what was number 3? No, over here, number 3 was 34 Herald Square. Okay, so let's look for that one. So this is the corner of Grand Central, so that makes sense. And then 34th Street, Herald Square, that is right over here. So that's number 3. So that's the top 3 plotted in a heat map. So I think those are pretty useful. Now let's look at another map over here. This is a cluster heat map. So a normal heat map is great for visualizing values in a matrix, like a matrix rendering or some type of color intensity. The purpose is to show patterns, trends, and magnitudes in the data, and rows and columns stay in the original order. We're just showing like what's the concentration of the data that we're looking at here. This is people going in and out of different subway stations. And it's used for correlation analysis, traffic volumes, and activity levels. So it's working perfect for us over here. So a clustered heat map is a little bit different. A clustered heat map not only shows the heat map, but it reorders all the rows and columns based on some type of hierarchical clustering. Okay, so it takes a small mathematical calculation and looks at the difference, or the difference between 2 data points. And the less the difference, the closer they are. So those will match up and those will end up in the same cluster. If it's too far apart, then those will get reoriented into another cluster that's homogeneous with the other items in that cluster, right? So all the clusters in the whole data set, if you're assigned to a different cluster, they're heterogeneous. If everything is clustered in the same cluster, then it's homogeneous, right? So let's zoom in here and check out this map. And again, the cluster heat map not only shows a heat map, but it reorients the columns and rows based on like that mathematical expression I just explained to you. So the purpose is to reveal structure about natural groupings in the data. This applies to algorithms like Ward or average, and groups items that are similar together, right? And this can be a dendrogram. That is one type of hierarchical clustering. And there's a few different approaches to try to solve this problem. I think there's like 8 or 9 different types of clustering methodologies. So you can see here, everything that's cluster 7 is Midtown. So this has high concentration over here. And again, what are we basing the clustering on? Latitude and longitude, right? So how close these subway stations are together. So you can create the clusters a bunch of different ways. The counts of the frequencies of people going into the subway or using those subway stations, or the lat long coordinates of the subway station and where they're located. So that's how I did this. So you can see everything is orange is together, everything that's blue is together. That makes sense. Here you see some yellow out here. This is cluster 18. So geographically, these are closer together, right? This is cluster 12, and over here we have cluster 12. So Upper East Side, Upper West Side, and over here we're getting out of Manhattan. Now we're into, I think this is Bronx over here, right? So this is cluster 6, and this is cluster 6. So geographically, all these items are clustered similarly together. Okay, so and then I did one more test. So basically, class testing one. Let me change this to one. One just didn't work out at all. I actually deleted it. Okay, so I want to look at just make sure that this is the right format. So I want to make sure everything is numeric. Ridership should be a number. Sometimes these things come in as labeled data. So if you see that, you have to convert that to an actual number. So I thought, let me look at some type of anomaly detection to see if there's anything in the counts of the ridership that could be anomalous or different in different types of scenarios, right? So an anomaly is an outlier. I was just curious to see, are there some outlier events here? Is there something that throughout 2023 looked weird? Was there some type of event that was different from most of the other events? So that's what this anomaly detection does for us. It helps us look for things that are unique and unusual and just doesn't fit the pattern of the entire group. So I did the isolation forest. I have a couple videos on my website about how that works. That's a very interesting technique to find these outliers. And I plotted the results over here, and I just found one single outlier, January 3rd, 2023. And I didn't like how this chart spikes and moves around and bounces around. It's very erratic and very, very bouncy. But it is what it is. Sorry, we're trying to do anomaly detection. I didn't find any anomalies. I was thinking of deleting this whole thing and not even putting it into the video, but then I thought I'd leave it just to showcase. Like sometimes you'll run experiments, it doesn't really work out, and that's fine. You try these things and you see what works and you use what works. And if it doesn't work, that's fine. You move on and you try something else, right? You try different experiments. That's why it's called data science. We run experiments and you'll never know before you run the experiment what the outcome is going to be. That's impossible to know, right? You run the experiment, and based on the outcome, then you determine, does that match my hypothesis? So the hypothesis is an estimated guess. You'll say, I think this is the outcome that we're going to see. I feel like the data is going to say this. I believe we'll see this when we look at the final report, right? So you run the analysis, you do your experiment, then you see if the results of the experiment match your hypothesis. If it does, that's great. Then you've proved your point. If it doesn't, you have to reform or reorient your hypothesis. You can't change the data to match your hypothesis. That's insane, right? You create a hypothesis, run the experiment. That's the data science. If it matches your hypothesis, great. If it doesn't, then reform your hypothesis, right? Or run some more experiments or try something else to get creative, become innovative, right? And just try different things. So that's what data science is all about. Just trying different ideas, testing those ideas, and seeing what the outcome is. So that's it. Hopefully this was useful and helpful. I try to make all the videos practical and just give you different demos of what you can do with data science and different techniques that can be applied. So I think this stuff is pretty interesting, and hopefully you find it interesting as well. Okay, so I introduced a few different concepts here and a couple different topics. So I think we beat this horse to death. I'm going to wrap it up here. I'm going to share all this code with you. So I'm going to download this as an HTML file, and I will post the code. I post the video a little bit later today. So you'll have all this code and you can run it for yourself and test the functionality of everything and hopefully learn from it, right? I share all the code that I have here with other people to drop knowledge and just to share something I think is interesting with other people, so collectively everybody can learn together. Okay, so that's pretty much it. I'm going to wrap it up, and I will see you guys in the next video. Bye for now. Hey there, everyone. Ryan Schewel, Data Science Channel. So today I want to introduce a topic that I was working on several months ago. I got sidetracked. I was doing a bunch of different things. I got distracted by a few different other topics and some other videos I was focused on. But I came full circle and I finally figured out how to do this thing. And I want to introduce this topic to you today. So this is how to optimize Airbnb prices to maximize revenue using Python and Jupyter notebooks, of course, right? So all my videos are using Jupyter notebooks. So originally this is going to be how to optimize hotel prices. I looked around for a long time and kind of gave up. I was looking for data about Marriott and Sheraton or some other hotels, some other major hotels. I couldn't really find a whole lot, so I settled on Airbnb, but it's almost the same thing. Like if you're renting out your place, whether it's Airbnb or Sheraton or Marriott, doesn't really matter, right? Like how do you optimize the whole pricing process to produce more revenue for yourself? And it's kind of surprising. And I have a couple other videos on this topic. It's very, very interesting. It's all about economics and human psychology. My undergrad degree was actually in psychology. My master's was in finance. But actually, if you lower the price just a little bit, you can stimulate more demand and actually create more revenue for yourself. That's the end game here. That's what we're going to try to achieve. And I will show you how to do that, okay? So we're going to look at Airbnb style listings. I couldn't find those hotel prices like I told you, but we're still going to infer price dynamics and understand basic economics too, okay? Economics of hotel bookings or Airbnb bookings, which to me is essentially the same thing. Maybe a hotel and Airbnb is different, but as far as I'm concerned, it's almost exactly the same thing because I can't tell the difference. So we're going to extract temporal features from reviews that I am actually downloading from a source. I will show you the source down here. I'll take you down here just real quick. I got this from Kaggle. I don't know that much about Kaggle, but it seems to have some pretty interesting data. So you can get the source, and I'll share all this code with you at the end, right? So you can download this code and run your own analysis, right, on this. And then obviously like modify it just a little bit if you have your own hotel pricing, or if you actually do work for Marriott or work for a big hotel chain or work for Airbnb, you can do this analysis exactly for yourself. You change the input just a little bit, but the outputs are going to be almost the same thing, right? I mean, like obviously it's going to be a little bit different based on the data that you feed into the model, but the whole simulation and the whole process can be the same things, right? So I'm inputting the data from here. That's what I got from Kaggle. I'm getting the last review and converting this to an actual date time. So sometimes this data comes in not as a date, it comes in as an object or as a string or something like that. So if you want to do some kind of analytics based on dates, you have to convert that to an actual date. If you have something that looks like a date, but it's not a real date, and you try to do some kind of time analytics or time series analysis, it's not going to work. It has to be a real date. As long as this comes in as a date, you're fine. If it doesn't, you have to convert that to a date, okay? So we have the month review and the review based on the day of the week. And I'm just trying to take this data and do a little feature engineering. This is called feature engineering, where you have features that are given to you and they don't really come in the way you want. This can come in as a non-date. It looks like a date to a person, but to a computer, it could be a non-date. So sometimes you have to extract or convert that to a real date and extract Monday, Tuesday, Wednesday, Thursday, or the time of the day, or the month of the year, things like that. Sometimes you have to introduce concept called mapping, right? Sometimes we have to map the data. So maybe we don't have January, maybe we don't have February in the data, but you can manufacture that, you can create that. That's how you do feature engineering, right? So we're going to go ahead and input the data that we get from Kaggle, okay? And this is what it looks like originally. So we have the host ID. That's not too important to me. I don't really care about that. Host name, again, no care. Neighborhood group. So that's kind of important. Neighborhood, latitude, longitude. That can be very, very, very important in this analysis. I'm not using that too much, but I'm really focusing on like the room type. Again, this is Airbnb, the pricing, minimum number of nights, number of reviews, last review, so on and so forth. And then we get over here. So review month. So that is what I created. That's called feature engineering. Review day of week. Okay, so that is another example of feature engineering, and then month name, and then day name. So when this comes in, like I have this last review, 10/19/2018, I have to go to the calendar and look it up. I don't know what is that? I guess it's October. I can tell that. Is that Monday, Tuesday, Wednesday, Thursday? I don't know. It's actually a Friday, right? So we're taking this data and converting that into a more manageable, more useful type of orientation here, right? So now I want to look at, like, on average, what is the average price um, based on the month and based on the day of the week, right? So I'm going to do a simple analysis right here, get the average of price right here. So mean in the statistics world, mean means average. Average is average. I don't really use average. I think in Excel world, they use average because it's more for um, like just generalist, right? In the Python world, they use mean, which is actual average, right? That's the terminology there. So we get the average price based on the month and by the date of the year. I think this is kind of a anomaly or a mistake over here. This just came in the data. This is what I have. So we have actually a month called 0. I think this is a mistake or somebody didn't fill out a form. And we have Monday through Sunday down here. And again, we have 0. I think somebody just didn't fill this in. It's just a blank, so it goes to 0. I could drop those off. I don't really care about it for this type of analysis, right? So let's go down here and we will set up and train and test a model to help us do our predictions, okay? So I've got so many videos on my channel about this. This is all data science. So if we feed in different features into a model, these are the features here: neighborhood group, neighborhood room type, minimum number of nights, availability out of the 365. And again, that all came from the data. And if you go back to the data and look at things like ID, like user ID, username, I don't care about that because that doesn't affect the price. I don't care if your name is Bob or George or Harry, it doesn't matter, right? Like, what is actually going to have an impact on the price? We're trying to predict the price. The Y variable is the price that we're predicting right here. This is the price, right? What's going to have an impact on the price? Not the person's ID, not the person's name. That has nothing to do with it. Which neighborhood are you in? Are you in Brooklyn or are you in Queens? In Queens, which neighborhood? Are you in Sunnyside or are you in Long Island City, right? I live in Queens and Long Island City. So I know these neighborhoods, right? And that will impact the price that you charge for your Airbnb. But the person's name has no impact whatsoever, right? So you have to pick the right variables to train the model. So we went ahead and trained the model. We're using Label Encoder and XGBoost. So this is the boosting model I'm using, and the root mean square error is 0.42, and the R squared is 0.60. So 60% of the time, the predictions that we can make are correct, but 40% of the time, unfortunately, are not correct. So 40% of the time, we're making mistakes. So that's kind of a big margin of error. Like, you really want these things, you want the R square to be close to high 90s, 95, 96, 98, 99%, close to 100%. You'll never get 100%. I've talked to people and had painful conversations. I want 100%, 100%. You're never going to get there. There's always going to be something that comes up that prevents you from getting 100%. And there's a term for that. That's called life. Okay. That is life. So sometimes life interferes with your analysis, and that's okay. But if you can get up to the high 90s, that's fine. So that was XGBoost model. That's what we're looking at here, XGBoost. So I tried another model, LG BM regressor. So this is a light boosting remodel. So pretty similar concept, pretty similar. So let me go ahead and run this. And we're getting still pretty similar RMSE. Root mean square error is 0.17, which is lower. So lower error, but R squared is still the same, 0.60. So it's not great, right? But that's okay. I think what we have to do is just be creative here and be innovative and open our minds and say, okay, maybe this isn't really like a real data science problem. Maybe this isn't really machine learning. Maybe there's a different approach to solving this problem, okay? I said this in so many of my videos. You have to use the right tool for the job. If you pick the wrong tool, the outcome is not going to be great, right? I've worked with people before. It's kind of one way years ago. I worked in a place that tried to use Microsoft Excel to build a website. You have to use like a website tool to build a website. You can't use Excel. Excel is a data analytics tool. You can't build a website. I kind of like advocated against it, but nobody listens, right? And they built it and they failed. Okay. We have to use the right tool for the job. That's the point. So maybe we're trying to use these data science methodologies and it's not working out. So we need a different approach. Okay. So I'm going to try SciPy Optimizer, which is an optimization tool which helps you to optimize your pricing metrics, right? Like, how do we create the right price? How do we model this correctly and efficiently and do this the right way, right? We have to use the right tool for the job. If you cannot do that, you're not doing your job. Whatever you're hired to do, you're not doing what you're hired to do if you can't use the right tool. So let me go ahead and run this. Okay. And this is how this stuff works. This is an iterative process. You go through many different iterations. You have to try this, you have to try that, you have to try another another concept, another thought, be creative, go out of the box, be innovative, right? You have to be very innovative in your approach to solving these types of problems. It's not like you just go in and boom, done, and it's over. It's not like that. Maybe sometimes, but it's very rare. Normally, you have to try different approaches and have different perspectives on the problem. And obviously, you have to understand what the end game is, and you achieve the end game. You solve that problem, but the path that you take there, or the bridge that you have to cross, can be different, right? There's no guaranteed same rubber stamp the bridge. We're always going to do this. We're always going to do that. No, there's different approaches to solving the problem. So this is just a slightly different approach. So we're using an optimizer. There's several actually in the Python world. There's linear programming, SciPy Optimize. There's GarobiPy. I've got videos on all these things. You can check it out. It's very interesting. You have to use the right tool for the job, right? So we have the the task here that we're running. And we are trying to find which can we charge a higher price and based on listings attract more people, or lower the price just a little bit and motivate people or incentivize people to come in and stay at the Airbnb, right? So in this example, at $200, the expected demand based is very low. At 125, the expected demand is higher than the expected demand at $200. So if you list it at $200, yeah, you might have a couple people coming in, one per week, maybe two per week, maybe not even one per week. I don't know. I mean, you have to test it and see what happens. If you drop it to 125, you can have a lot more people, a lot more turnover, and make a lot more money. So here's the question. If you get one person at $200 per week, you made $200. If you have five, 125 per week, what's the math in that? 625, 5 times 5, I think that's it. I think it's 625. So would you rather have $200, right, and have one person, or have $625 and have five people come in? And I know there's cleaning costs, there's other costs associated. I'm kind of like skipping over that right now. Okay, this is this more basic type of analysis. But do you want one at $200? Do you want to earn $200, or do you want to earn $625? Like me personally, I'm not really like a huge capitalist person. I need money to pay my bills, but I'm not like money envy and money hungry. Like I know some people are, but yeah, 625 sounds better. So I'll lower the price, right, and stimulate demand. I've got a couple videos on my channel about how to do that. So the original price was 149 based on the day of the week. And here's the name of the place they're staying. It's based again on the neighborhood, square footage, maybe the view. I live in New York City, or just one stop away from New York City. Um, the view that you get. There's all these different features that impact the cost of the price, right? But if the original price was 149, based on the day of the week, there's probably more people hanging out Friday, Saturday, maybe a little bit Sunday, rather than Monday or Tuesday. And the optimal price would be a little bit less, right? So this is 225, the optimal price is a little bit less. 150, optimal price is less. 89, the optimal price is actually more. So this guy is giving away his place for $89. He can make 125. Same thing, 200. You have to drop it here, okay? People aren't coming in at 200. You're just not interested. You're not getting the foot traffic. You're not getting demand. You are getting a little bit more, a couple dollars over here. Not big money, just a couple bucks. The original price 150, drop it to 125, you're going to get a lot more demand, right? So that's how these things work, right? You have to optimize the process, drop the price a little bit. Sometimes you raise the price and you make more, like that's just common sense. But sometimes you actually have to drop the price, and it's not super intuitive. And I know that, I get that, okay? But sometimes you drop the price, you stimulate demand, and eventually you'll actually make more money, right? So it's win-win, right? So you have a little bit more cleaning costs, a little bit more cleanup for your crew. But if it creates more money and more revenue for you, you're probably going to be better off, right? Again, the original stimulus for this whole video was hotel rooms, right? I was looking at like Marriott, I couldn't find the data, or a couple other big names, Radisson, Sheraton, or a couple others. Courtyard, I think it's owned by Marriott. So looking for that by selling Airbnb data, but it's the same concept, right? You want to build your business and create more revenue and more stimulus, more demand for your services. Otherwise, you're just sitting around just um, you know, who knows what, tapping your hands together. You're not doing anything useful. You're not doing anything productive. I think you have to adjust your price optimally. And I have several videos on my channel about how to do this. And that creates a better experience for everyone. Maybe it's lower price. The consumer comes in, has a great experience, gives you more reviews, and boosts your business and builds more for you, right? So in this analysis right here, the total revenue gain for the whole data set was $17 million. Okay, so we created $17 million in more revenue. Now, this is live listings. You have to go to the data set, you have to download it. I can show you where this thing is. Where is this on my hard drive? A, B, NYC. Oh, yeah, there it is. A, B, NYC. Okay, so let me go down here. A, B, NYC. That's it. Okay. So this is my desktop. It's based on the solar eclipse. We had the partial eclipse a couple of years ago in New York City. Everybody wanted to see it. Honestly, it wasn't a big deal because we were like 90% eclipse or something like that. It really wasn't a big deal. It looks like a little cloud in the sky. So this was the original data set. And there are 48896 records minus one. So 48895, right? Because the first one is the header. So that's what the data looks like. And we created $17 million in value, okay, over the entire data set. This is the whole thing, not per user, not per Airbnb host, right? But $17 million. But that's a big savings, right? Like if we optimize the whole problem and summarize everything, the average gain per listing is $365. So that's per listing, okay? So the whole thing is 17 million saved, 365 per row. This is still savings. There's savings out there all over the place. It's like walking around and you look down, you see a $100 bill on the ground. You know what? I'm going to bend over and pick up that $100 bill, okay? Because that's free. It just takes no effort. I've talked about this in my other videos. Optimization is a free gift to the world, right? You don't really have to do a whole lot. You don't have to invest in strategy, planning. You don't have to invest in new technology, new architecture, new infrastructure. No, just run your business more efficiently, and you make $365 basically by doing nothing, right? But just by very um, simple adaptation or utilization of mathematics. That's all this is. So we're optimizing business, make $365. I'm sorry, I misspoke. I don't bend over and I see a $100 bill on the ground. I see three $100 bills and three $20 bills and a $5 bill, right? So I just made $365 by basically doing nothing. I didn't have to work for it. I didn't have to invest in architecture, infrastructure. It's just right there. You just grab it. That's it. So this is based on, this is a histogram showing you the percentage gain right here. Okay, so most of the gains are kind of small. We saw that 365 is on average. These guys over here make more, or gain percent. Okay, not gain in dollars. This is a different thing. So this is the gain in dollars. This is gain in percent. So most of the percents are kind of small, like 5%, 50%. But this guy over here had a 265% gain in revenue. And again, you could increase your price, and that could be intuitive, that can make sense. But sometimes it's just decreasing the price and stimulating that demand. Okay, that's called economics. So which properties actually benefited the most? Let me hit Control Enter to refresh this. And this Tribeca 2,500 square foot property was the number one winner. The price was originally $575. Drop it to 500. Drop it to 125. You get a lot more foot traffic there, and the percent gain is 695%. You make 700%. This guy's charging $575 per night. How many people are going to pay $575 to stay at your Airbnb per night? I'm not going to do it. I don't know personally anyone that's going to do that. Of all my friends or all my family, my whole network, I don't know anyone that's going to do that. Maybe there's some crazy couple out there. I'm just going to throw down 575. Most people are not going to do that, right? If you drop it to 125, you're going to get a lot more business, and your gain is going to be almost 700% more revenue, right? That is a win, 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 win. That is a win. This is number two right here. The original price is 500. Yeah, I'm walking away from that. I'm not going to spend $500. The optimum price is 125. the percentage gain is 400%, that's a win. Just drop the price on things. Too expensive, you're getting no people in there, or you're in the wrong game. Maybe you shouldn't be in Airbnb. Maybe you shouldn't be doing that, right? Okay, here's another one. Just maybe it's greed, maybe, oh, I want too much, or I don't care about people, or I hate people. That's a whole nother topic, right? He's charging 425, drop the 125. Your gain on your business is 215% gain on revenue, right? That's huge. That's absolutely huge. So these are the top three. You can go through all these, right? Do your own analysis. I am going to wrap it up. That is how you optimize Airbnb prices to maximize your revenue. Okay, I tried to do it on hotel prices, couldn't find it. But again, if you have your own data set, drop it in, change a couple of the variables, your input to the data source. A couple of field names will obviously change, but you're looking for, what's the price, square footage, view, neighborhood, things like this, and the model will run, right? So I designed all of my models to be pretty much just plug it into your data set and it's going to run. It's very generic. It's not customized, but you will have to change a couple different things. So I'd encourage you to download this data set, experiment it, run with it, and get intimate with it. But like obviously your data is going to be different than my data. Download this from this data site and you'll have exactly the same thing. But this is just a hypothetical example I'm showing here. If you want to do this for your actual business and boost your revenue by $17 million, right? Or what was the other thing? 365 um, per listing. This is how you do it. Okay. So again, Ryan Schewel, Straight Data Science. I'm going to wrap it up. I'm going to throw this video up on YouTube a little bit later, and I will share all the code with you, like I share all my code samples. So thank you for your time. Hopefully this was educational and informational, and maybe a little bit inspirational too. Okay. Thank you, and I will see you in the next one. Goodbye. Hey there, everyone. My name is Ryan Schewel. Welcome to my YouTube channel. So in the narrative today, I want to discuss racing bar charts, and I'm going to make this a real-world example. I try to make all of my videos here about real-world solving real-world problems, and I try to make it very relevant and very true. That's why I called the the channel is called Straight Data Science. This is just straight truth and nothing but the truth. Okay, so I'm going to use a real world example, and basically we're going to look at how YouTube subscribership has increased over the years. So let me start off just by running the video here. Running the animated chart here, and I'll show you how I created the chart in just a minute. When you hit the play button, you can see all of these numbers are increasing over time. So this is getting the counts of subscribers of different YouTube channels. Okay, so you can see here, it's almost like a kind of competitors in a race, and you can see the bars are moving over to the right and in an increasing fashion, usually, although sometimes they decrease too, because you can get more subscribers on YouTube, you can lose subscribers, right? Sometimes people say, oh, I want to subscribe to your channel, they click the button, but then sometimes people change their mind, right? And they unsubscribe, so you can lose subs. They're called subs, right, for short. So you can see the numbers are increasing here, almost like racers on a racetrack. Mr. Beast is in the lead. I don't know if you've seen his videos, most likely you have. I think he has something like 400 million subs now, which is more than all the population of the entire United States, counting every man, woman, child, and baby in the US. So I imagine a lot of his subs are international as well, because babies are not watching his channel, I'm pretty sure. But he has quite a following, right? So he's pretty much in the lead most of the time here. You can see T-Series and Coco Melon nursery rhymes kind of switch back and forth a little bit, but probably a third of the way into this, I think T-Series takes a second position and it never looks back after that. But I think Coco Melon started above T-Series. Yeah, so that's true. And then you can slide this over and you can see it. You can hit play, you can hit pause. So it's kind of neat. You can change the visual rendering of these images. I'll show you how to do that in just a second. Let me let this thing finish off here. So Mr. Beast is up to 300 million. Dips down a little bit. And again, this is real data that I scraped from the YouTube API, which measures all of these things, right? And I'll show you in just a minute how to do that. I want to kind of let this race just finish off here. And Mr. Beast is kind of crushing it here. And we are almost at the finish line. like 432 for Mr. Beast, 302 for T-Series. And if I go to YouTube and actually look at these numbers, we should see exactly the same thing, right? So www.youtube.com. Let me go over here and we'll see the evidence for this in just a second here, okay? So my computer load up here, render the screen. Okay, so Mr. Beast, right? That's what we're looking at. Okay, I think you have to put a space between it. I think it's smart enough. Okay, so I think this is the one. 433 subs, and he has this little panther image over here. Oh, okay, let me pause that. I don't need to listen to that thing. So 433 million subscribers. That's what we're looking at, okay? So does that match this 432? I actually ran this yesterday, so I think in the past day he got an extra 1 million subscribers. Let me rerun that, okay? Let me rerun the algorithm. I'll take you through this in just a moment. Control Enter to run. Okay, and I think we have what we need. Okay, go down here. 432. It says, so tell me 432, and that page says 433. You know what? I think what's happening here is that YouTube isn't always up to date. They will take a couple of days to refresh everything on their servers. So what the API is showing us might be slightly different than what we are seeing down here. But it's pretty close. 432. This says 433. It's pretty close. I think what is rendered in this page is slightly different than what we're getting from the API. And I've seen those messages. I've been a member of YouTube for, I don't even know how long. It's been a long time. I've only been posting videos here for a year, but I think I've been a member for like 18 or 19 years. And I've seen that message pop up. So they do have to reconcile these things with what you see on the screen and what they see on the back end. And it is not done in real time. I know that for a fact because I've seen these messages pop up and they basically just say, hey, give us a couple days to make all these updates in. We have to validate and verify a few things too. So 432 for T-Series, if I go over there, that should be pretty close, maybe spot on. 432 T, I think there's a hyphen in between. Okay, so that's the one. I see 303. So I see 303 subscribers here. Let me pause that. I don't want to hear that thing. 303, and that is what I'm seeing here. So it's the same thing. It's pretty close. I think they got another 1 million subscribers in the last 24 hours or so. If I go to just pick one over here, PewDiePie. That thing used to be pretty huge. I don't even know what that is necessarily, but that used to be pretty big. PewDiePie, and they're saying 110 PewDiePie. Let me see if I can even spell this right. No idea what this even means, but this guy has a lot of subs. Okay, so 110 million subscribers. You can see it right there. Okay, 110. And that one is right on the money. Okay, and WWE, I'm not even sure what that thing is, but they get a lot of subs, whatever they do. WWE. Enter, and let's see if we can find this. And 110, I see 110 right there. So that is spot on. Let me pause it. I want to hear that right now. Okay, so 110 million, and that's exactly what we're seeing over here. So I think everything reconciles, everything works, right? Let me take you through the code real quick, and I'll show you how I put this together. Basically, going to my YouTube API key, I keep this on my desktop. You can reference that right here. If I put that into the code, I couldn't share the key with you because it's personal, it's confidential. You have to sign up for your own key. It's totally free, very easy to do that. Go to youtube.com and just Google it, YouTube API key, and you can sign up for that. Right, totally free and pretty easy to do that. If I go over here, probably do it right now. And YouTube API overview, just go here, read the instructions, and you'll figure it out. It's pretty easy, right? So I put that into a text file, and I can reference that. If you want to run the key just raw right in here, you can do that. You can't share that code with anybody, right? So this is just a better practice, I think, to put it into a file and reference the file and then pull it from that source, right? And I have mine on the desktop. You can put it on a network drive, you can put it anywhere you want, but you should really put it in a place that's safe and secure and just make a reference to that, fetch the key, and then you can run all your analysis on that. If you put the key directly in the code, that will still work. That's okay. But then you can't share this, like you couldn't do a demo like I'm doing right now. You can't give the code to anybody because they would have your key, right? So I think it's better just to make a reference, fetch it, and then you can do what you need, right? So here's the channel input. I've gotten these top YouTube channels. These are pretty much, I mean, this could change a little bit over time, but I think these are pretty much like the top 25. I'm going back in time 120 months. So this is 10 years. And I'm just looking at monthly data. So I'm getting the month-end data. When YouTube updates that data, then we're going to pull it back. If you want to go back 5 years or whatever, 20 years, that's fine. I'm going back 10. I think that's fine for this demo right here. But it's up to you. You can pick what you want, right? So these are variables that can change as needed. So I set up some parameters down here. I'm looking at snippets and statistics. I had to look through the YouTube API documentation and figure out how some of this stuff works. It's a little bit tedious. I'm not going to like downplay that, but you can figure it out. And they give you all kinds of demos and they give you sample code. A lot of this is just copied from their documentation. Copy, paste it into a Jupyter notebook, and you'll have most of what you need. Okay, so I create a couple UDFs. These are user-defined functions to resolve the channel. This is helping me get information about the channel and all the statistics around the channel. And these are some more channel stats, right? So any kind of snippets or statistics, the ID of the channel, the title. That's why I'm going to YouTube API and fetching all this information, pulling it back so I can get the counts of the subscribers, so I can do the analysis and build that dynamic chart that you just saw, right? So current snapshot. So this is getting the API, sending that from my desktop into YouTube, making a request, and based on my request for information about counts of subscribers, it's coming back, right? Going back 120 months. So 10 years in time, and pulling back all of the statistics from the channel. We have the title, number of subscribers, that's what I'm counting right here, number of views, the videos, and hidden subscribers too. There could be like another category of subscriber called a hidden subscriber. So there's different things you can look at, right? If you go back to the YouTube channel over here, there's other things that we could be counting, right? It doesn't have to be subscribers. It could be number of clicks, number of views. They have all kinds of statistics over here. So I don't think I want to look at this thing per se. Let me go back a little bit. I don't want to look at that either. I'm not even sure what that is. Kind of scary. And go back to Mr. Beast. That one is kind of normal, I think. So this is Mr. Beast meeting T-Series for the first time. These are like the top two with subscribers, but this is a short. These shorts are a little bit different. Let me try to get to just a normal video over here. Oh, that's on T-Series again. Sorry. So got a little bit off track here. Okay. This one, I have no idea what's going on here, right? No idea. And let me pause it too. But look, you can look at number of subscribers, number of counts of views for each video. You can look at that. Number of videos. I mean, how long ago the video was posted. This was 3 weeks ago. You can look at all kinds of statistics about comments that are posted, replies to comments. These are the replies over here. I have a couple videos on my channel to show you how to do all this fetching of YouTube information, pulling it back into your notebook, and then doing analysis on like the number of counts of subscribers. That's what we're looking at here. Number of views, comments, replies to comments. It's all kinds of data that you can pull out from YouTube, right? So anyways, when I run this, Control Enter to run it, you can see I get a data frame. It comes back pretty quick, pretty easy. These are the top 25 channels, right? And then these are the counts of each one. On the top, you can see the column header. On the left-hand side, you can see the time series. So this is pretty standard. Like a lot of times in any standard database, you'll see the time on the left-hand side. It could go across the top. That would be kind of weird. I've seen that a couple of times in my career on Wall Street. I've been on Wall Street for a little over 20 years. I've seen that a couple of times, but that's pretty rare. Normally the date goes down vertical, and then you would have the headers, or you can have some kind of detail and the actual number or the header can repeat in the rows, right? And then you can have all the details out to the right with the date on the left-hand side too. So this is just how it appears in this data frame. This is pretty standard practice right here, but you don't have to do it. There's a few different ways you can set that up. So you go ahead and make the fetch to YouTube, go ahead and pull it into a data frame, and then you do the plot over here. Okay, so everything comes back in the Plotly format. If you don't understand Plotly, there's tons of data online about how to create Plotly charts. And this site right here is very good. I like this a lot. Plotly Graphing Library. I think this is the one. Let me see. Yes. So you can see all the different types of charts they have here. So bar charts, pie charts, bubble charts, scatter plots, histograms, funnel charts, waterfalls. What I'm using is called an animated chart, and they have animated charts too. Just take a look at this stuff. Very interesting. You'll find tons of information. When I plot this, you already saw before what the visual looks like. It's pretty cool. It's very interactive and very dynamic. If I wanted to change it just a little bit, just to have a little bit different sort of type of display here, there's different ways to render the chart and to display things differently. So again, take a look at the documentation. There's tons and tons of stuff over there. This is based on all the colors, different colors of the rainbow. I think it's called the rainbow. So you can have different, what is it called? Different hues, I think. That was the other image that we just saw. Or you can have this just totally different plots based on different colors, right? So when I play that, you'll see kind of the same animation, and everything moves from left to the right as it increases. And this is in ascending order. This is going ascending, so the smaller at the top and the bigger at the bottom. And this is just a pretty cool, pretty common way to showcase here how this racing bar chart is set up and utilized. And I think this is a very practical use case for this. So one warning, I would just say be careful not to hit YouTube's daily quota. They limit you. It's kind of strict, like how many requests you can make per day. You can do a few. You can test it out. If you copy and paste this code as is, I guarantee it's going to work. I tested this pretty extensively. Everything works. If you run this code multiple times and all of a sudden it doesn't work, it's because you hit those rate limits, right? So I don't know what it is offhand. You'd have to look in the documentation. They're kind of stingy with this data, so you can run it a couple times per day, maybe 3-4 times per day. But if you do this 10 or 12 times, I can pretty much guarantee you're going to get errors, and it's just going to shut down for probably 12 to 18, maybe 24 hours, and then you can rerun it the next day. But they do limit you if you're trying to throttle the system and just gas it and just try to extract all this data. They don't like that because YouTube's just serves so many customers. I think they just get overwhelmed with requests and they have to cap it somewhere, right? So that's why they do that. So they could disable the code for up to 24 hours. So if you see an error, don't worry about it. Just copy and paste the code. I guarantee this will work. If you hit those errors, wait 24 hours and then it will work again. So that's it, guys. Just wanted to showcase the charts here and show you how this works with a real world example. I saw this a while back and I was kind of motivated by that to create my own example of a racing bar chart. So that's it. I'm going to wrap up the video. Thanks for your time today. Hope you appreciate it. Hopefully you learned something new. I learned a couple of things when I put this script together, and I think it's pretty cool how all this stuff works out. So that's it. I'm going to wrap it up right now, and I will see you guys in the next video, which I'm going to post pretty soon. Thank you. Bye. Hey there, everyone. My name is Ryan Schewel. Welcome to my channel. So this is all about analytics. I try to make everything practical and realistic, so I call the channel Analytics in Action. I used to be more focused on data science, but honestly, I talked about many topics in data science and kind of ran out of things to do, sort of. So I decided to make the channel just broader in perspective and wider and more far-reaching. So I updated the name of the channel, and I'm going to not say focus just on data science. Maybe I'll talk about that a little bit, but let's just look at the big broad picture of the world of analytics. Okay, so in the narrative today, I want to show you how to build a radar chart, okay, or they're called radial charts. So I got the inspiration from this link over here. This is called Visual Capitalist. This is their take on it. Okay, I'll show you my version in just a minute. So this came up on my radar a few days ago. I like the overall visual appeal, the way it kind of like pulls you in and makes you very fascinated about what's going on here. But it's also and while it's kind of complex, it's also very, I would say, simple in terms of how it presents the data too, right? So you can see the radial chart, you can see everything circling around here. You have a nice little map of the world in the background. And I think the ranking of each of these is associated with the like the mark in the map where the label is. So I think this number one is Kosovo, number two is Saint Martin. I don't necessarily see that right here. I think Saint Martin is like off the coast. Oh, no, I do see. Yeah, so that's number two, and number three is Marshall Islands. So I'm trying to see. Oh, I do see that over here. Okay, so I see the top three. So I think it's visually appealing. It draws you in, but it's not overly complex. It actually takes something that's somewhat complex and actually simplifies it. And that's what you want to do with any kind of chart, right? You want to take something that's kind of difficult to explain, plot it, or chart it somehow, and have a very engaging visual and that answers a lot of questions. And if your chart is raising questions or making people confused, it's not a good chart. Okay, so this is their data over here: Kosovo, St. Martin, Marshall Islands in the Pacific Ocean. This is Caribbean, this is Europe. So we have the data right here, pretty straightforward. They have the top 25. I'll admit, okay, guilty as charged. I did not get these on the second page over here. I didn't get 26 through 42. I only took the top 25. If I updated the data, I would have all 42. I'm a little bit lazy, so I'm not going to go ahead and do that. I'm just going to get what's on the first page. And I think that's totally fine. And if you want to find out more information on these radar charts, so you have radar charts in Plotly, in Python, sorry. And it's pretty straightforward. You have your data frame over here. I'll show you in just a minute how we get that. You have your rho, your theta, and you just plot this thing out, right? So pretty straightforward. This is the same plot. It's filled in. This is, again, similar type of thing, right? So this is a scatter plot now, and it's filled in with the rho and theta. And over here, we have the original data frame, and we have the plot, right? So that's how these things work. Here's another tutorial over here. I would encourage you, if you're interested in these things, go take a look at it. It's pretty straightforward, guys. So you just have the data frame over here. The data frame is used in this scatter polar over here, and you just fill in R. This is the rho. This could be frequency. Theta is the direction. Color is strength. Symbol is also strength. Okay, you can see the strengths over here. Size is frequency. So the bigger the size of the object over here, whether it's a square or a diamond, it just represents a higher frequency. And this is, I guess, wind data. I guess that's all it is wind data. So here you can create a pretty interesting, very engaging chart with just a few lines of code, right? And Plotly does the whole lift for you. So I would say just Google that. That's literally all I did. Radial charts, Plotly. That's why I got that. So here's my take on that data. And I don't want to copy anyone and plagiarize anything that's being done. So I made mine a little bit different, but kind of definitely like in honor to the person that put together the chart on this site over here. I think they did an excellent job. I'm going to try to show my own take on this kind of thing. Okay, so no plagiarism. That's certainly not my intent. It does look a little bit similar, but it's not going to be the same thing. Okay, so so that's it. I think that's enough setup. So we have the data down here. Everything is going into this data frame right here, and I'm just doing a little bit of modification to the data frame. In the data science world, these are called feature engineering exercises, right? So I'm creating a new feature from an existing feature and just replacing anything that has a percent sign just with a blank. And the reason to do that is because you can't plot percents, right? So we get the original percentage, and we can see in the data what's happening here. This is negative 9.69%. So the country lost 9.69% of its population. That's what we're looking at, right? So countries with shrinking populations, this is down 5.17%, and this is down 3.35%. And again, I'm creating a couple new columns from the existing columns. I want to get the absolute value of these rates. So the original rate was negative. I need an absolute value. Basically, you can't plot a negative in Plotly. If you think about it, like a 1 is a 1, a 2 is a 2, 100 obviously is 100, but anything that's negative, you can't plot that because a negative doesn't exist in the Plotly world. And I think that makes sense too, okay? So that's how they set it up. I can't think of how you would plot a negative. Maybe you can come up with some creative way. I think the designers of Plotly just said, we're not even going to deal with it. We'll have everything in the same relative scale, but it has to be positive. So we're just taking the absolute value there. The theta is, I'd have to look this up. I think this is the change. I have to look in the Plotly documentation. Maybe I'll look at that right now because I knew that before. I actually forgot. Plotly. Theta value. So let's see what they say. Uh, doesn't really even say it, or I'm not seeing it here. I forgot. I think this is the change, though. I think theta is change. So I don't see it there. That's weird that Google doesn't even have it. But I think that is the change or the overall relative change. And the bar width is going to be a fraction of everything here. So we have 25 different records, starting with negative 9.69 and going down to negative 0.31% change. So it lost that percent of the population. The bar width is going to be pretty much the same for all of these. So we just take 25 divided by 100. I think that's how that number is derived. And the color starts with a darker pink and then goes different shades over time. Okay, so let me create the data frame, control enter to run the script in the cell, and I will drop in the code when I post this video later so you have everything. So here's the data frame. Pretty easy to construct that. So again, absolute value, so we can get a positive number. We can't plot negative numbers. The theta, oh, here it's in my notes. For the angle in degrees where the bar is placed around the circle. So that's the theta. Okay, it's not really a change. It's the angle of the degrees. The bar width is to show the angular width of each bar. That's pretty self-explanatory. The color shows the categorical style, and it changes slightly relative to all the other items being plotted here. So it changes relative to its peer group. And the label just shows the HTML format. So when we mouse over it, when we plot the chart and put the mouse over it, we have a nice little bubble popping up. I think it's called a tooltip, or I think it's called a tooltip that pops up. Okay, so again, I'll share all this code with you. I'll take you through the high level, what it's doing. Let's go, let's swing over to the chart and see what's being done here. So just like we saw in that chart before, we have the larger countries here. I put the mouse over it. That's what the HTML is doing. So the mouse goes over and the bubble pops up with all the details. So you can see this is number 3, this is 2, this is 1, and you can see the details there, right? So negative 0.69, negative 0.517, negative 517%, and negative 3.35%. Again, this is shrinking population over time, and the circle goes all the way around to the end. Hungary is the last country, negative 0.31. If we go back to the data frame, we see the same thing here. Hungary, negative 0.31%. Okay, so mine is a little bit similar to the other. I have the black background, but I don't have the global plot in the middle. I don't want to copy these guys and plagiarize things. And again, this is my own code, my own take on what they're doing. So I think it comes out pretty nice. This is the end of the code. I will step through some of this script because I think the details are extremely important, and it's not that complicated if you break it down. So like I showed you in those Plotly charts before, we always start with the data frame, right? If I do Control F, I can see all the references to the data frame. So this data frame is constructed over here. Then I'm going to reference all the different, not all, but most of the different columns in the data frame. So for the first position here, again, we're taking absolute value. That's going to be the bar. This is the degrees. Is that how it's being defined here? Or the angle in degrees where the bar is placed around the circle relative to the peer group. This bar width comes from over here. So bar width is going to be the same for all of these bars. So it's always the same relative. Now you could do different things like maybe the absolute value could be the bar width. I could actually try that. I could do absolute value over here and see what the difference is. ABS, ABS. Didn't even try that. I just went with the bar width. Yeah, so it's a different visual. But when you take the same relative amount, you take 100 divided by 25, you get 12.5 or whatever that was. So this is bigger and bolder. It kind of stands out, but this is so tiny right here. It's almost unnoticeable. So I think if we stick with the original, where is it over here? The original concept, I think that's just a little bit better. So this was called what? Bar width? Yeah, let me copy it. I like to copy rather than type things out, kind of lazy like that. So we'll go back to the original design. I think this is good. So you can see the bar width goes all the way around and everyone is relatively the same width, right? So we get this full coverage of the circle. The whole thing is covered up and this looks nice. Otherwise, Hungary is so tiny relative to the others. It's almost disappearing, right? It's almost unnoticeable. So that's it, guys. That's what I want to show you to keep in mind. So everything looks a little bit complicated, but it's really not if you focus on these things, right? So the R comes from the data frame column ABS. The theta, which is the degrees around the circle, comes from the theta, right? The bar width we calculated by 100 divided by 25 because we have 25 different countries here. The color is just the color that I assigned. I'm trying to make it somewhat similar to the other colors we saw before. Then you have line markers, line widths, things like that. We are going to take the rank of the country and the region and the rate strength and pop that into the chart too. And there's going to be a couple more things that I'm interested in doing here just to kind of make the chart look a little bit similar to what we saw before. Now I can actually comment this out and rerun this and we should get something pretty interesting, but it's going to be kind of different from the original. Yeah, so we start to miss some of the labels and I do like those labels. So I'm going to include that. But not all of these things are required to run this, right? Like if I take out the inner rank dots, we're going to miss the rankings, but we don't really lose a whole lot. We still get the most of the effect of the chart. But if you want to see those little rankings inside, I think that's how the Visual Capitalist actually did it, because I did see that they had rankings inside. So I added that in. But again, this is so tiny in here, it's hard to kind of see it. You can zoom in, you can see this is 1, 2, 3, 4, 5, and they all go in a descending order from largest to smallest. So I think it's okay, but it might have more of effect if these higher rankings are larger. Like you can see the bar kind of extends horizontally just a little bit more, right, for the bigger numbers over here, and it's very tiny for the small ones. So maybe that's another layer that you can add into it. But I think I pretty much got what I needed to get out of this thing. So again, you would reference the data frame, Control F, to look for all the data frame references over here, and then the column in each one, right? Then we can build the outside perimeter. So we're getting absolute values and the theta, that's the degrees around the circle, right? And we're getting the outer radius again from the theta and the label. So data frame dot label. Down here, we're getting the inner rank dots. I just showed you that. And then you take everything, put it together. So you're kind of creating these different multiple layers, dump everything into the Plotly chart, and then figure.show right here will show the chart. So everything kind of gets layered in, packed in together, and then you show the chart. And that very last line will display the chart as we intend to do it. Okay, so that is kind of it, guys. A little bit complicated, but not bad. Use Google, use ChatGPT. These things are your friends. And that's it. I just wanted to show you how you can go ahead and create a radial chart. I think these things are very useful, very interesting as well. And you can have a lot of fun, right? And take something that's kind of complex over here, right? If you just print that out or just put that into a PowerPoint deck, that might be a little bit confusing to people. If you take all that data, pop it into a radial bar chart and present it in this fashion, I think it really pops off the screen, it captures people's attention, and it really makes a pretty powerful statement. That's it, guys. So I'm going to wrap it up here. Thank you so much for your time. I will download the copy of this code right here, export it as HTML, and you can download that file. It'll have everything you need. I'll drop the video a little bit later today. You'll have the code and the video, and you're good to go. Put that into your Jupyter notebook and test it, tear it apart, put it back together, and see what you can do with it. That's the best way to learn these things. Okay, so that's it, guys. Thanks for your time, and I'll see you in the next video. Take care. Hey there, guys. My name is Ryan Schul. Welcome to my channel. So today the narrative is about standardizing multiple date formats. Okay, so we can get one single unified standardized format for all dates. And then once everything is standardized, we can do joins, we can do concatenations, and all kinds of fun, exciting, interesting things, right? But if dates come to us with all different formats, you really can't do anything with that. And this is it might sound a little bit weird, might sound a little bit unusual, but I dealt with this firsthand. I've seen this a few times in my career. I've dealt with this firsthand. I worked in a place where a project manager took about 6 months to set up the whole initiative and their planning and like tracking all the progress of this thing. You can do this in one afternoon. I don't know why this thing took 6 months. I could do this literally in a couple of hours. I put this project together, I think, in less than 1 hour, but why it took 6 months for the whole coordination and planning. I guess you need to feel important. I guess you need to make yourself heard, and you have to have a voice, right, in the meetings and things like this. I don't know why it takes 6 months, guys. This is a 1 hour job. This is it. So why do we have to standardize formats for dates? Basically to create unambiguous joins and merges. If a table has strings or different dates, it could be 08, 09, and another can have timestamps. You see this all the time in the data world. You can have datetime 64 or ISO format, right? So you have to, sorry, you have to take this. Sorry, I've had congestion for like 10 years. I'm sorry. But you can take all these different formats and standardize them and consolidate them into one single unified form, right? So you can take accurate aggregations, group bys, resampling, daily, weekly, monthly, rolling windows, time series analysis, things like this, deduplication, reconciliation. I worked in the reconciliation business for a little over a year, reconciling all different kinds of reports all over Wall Street. You can do downstream simplicity, right? You can take your models and your formats and just streamline them to the next team, right? I worked in a place that had like 400 different models, and one model feeds into another model, and you had this one streaming down and this one upstreaming and downstreaming. Very complicated. You can straighten that out and figure it out using different types of charts and graphs. Plotly will do that for you pretty easily, right? And what was the one? I forget the name of the thing, but it shows you the flow of movements. I forget the name. Now this is bothering me. I have to look this up, guys. Charts, flow. Oh, here it is, Sankey. It's called the Sankey chart. When I saw it, I recognize it. So you can do Sankey plots, right? Once all the dates are formatted and standardized, you can do so many different things, right? But if you have all these different date formats, you really can't do anything. You're kind of dead in the water. You're just sitting there, just thinking like, how do I get out of this spot? How do I make a move? How do I do this, right? So let me show you right now. So let's say you have different formats. You have to do a little bit of data cleaning or refinement. It's called data refinement, right? Or just clean up the data. So anything that has backslashes, maybe you just have to put a dot in between. Anything that has different types of characters between the dates, you have to clean that up and just make everything the same form, right? So if you have things like January, February, March, April, right? You have to clean these up into the same forms. If the numbers are greater than 2 and greater than 12, or if one part is greater than 12, but one part is less than 12, you might have a date, and day, and then month, or you could have month, and then day. So in the United States, you tend to see this format most of the time, day, month, and year. But in some European standard calendars, you see the month and the day, but you can tell if it has 13. So if this is a 13 and this is a 12, you can There's no such thing as 13 months in a year, right? So you know the 13 has to be a day, right? And you know the 12 has to be a month. But if you have um like 12 and 13, then you know that this has to be the month and this has to be the day, right? So certain conventions that you can follow, the certain relationships that adhere to how dates should look, right, in different countries. If you go across different countries and different regions, they can look a little bit different and it can be misleading. But you have to take this and just consolidate this into one form that kind of makes sense and that universally is recognized by everyone. I don't care if you're in the United States. I don't care if you're in Kansas, Ohio, Oklahoma, New York, California, Texas, or Florida, or if you're in Iceland or France or Spain or Bulgaria. Like, you have to take this and get this into some form that everybody can understand, and you can share this universally very quickly and very easily, right? So let me show you a couple different date formats. We have month, day, year. Okay, so that's pretty easy in the United States. You know, this is August 25th, 2025. This is August 25th, 2025. And year is implied. Like, sometimes the year is left off, but if the date comes to you like yesterday or today, and you know this is 2025, then that's the year, right? You just append the year on there, right? If you have 2025-08, you know that this is the month and this is the day. There's not 25 months in a year, right? Like, you know this. You have to have some baseline for comparison here, right? But once you know that there's 12 months in a year and there can be up to 31 days in a month, sometimes it's 28, right, for February, sometimes it's 29 if you have a leap year. But you have to know like the baseline comparison, and then you can start to make estimates and judgments and start to fill in the gaps here, right? This is also gap analysis. So this is August 25, August 25th. This is missing the 25th, but we know it's the same date. You know that August 25 is 25, right? 25, August 25. So you know that this is the year, right? Or this could be the year, but you have to understand like the year is the current year, and then this is the month, and this is the day, or this could be the day, or this could be the year, or this could be the year. But you have to set like benchmarks and controls and guardrails to try to guide everything into the same universal relationship, right? And then you can have sometimes periods. So here's a month, day, and then year, right? Or this could be a month and then year and then day. That would be a little bit unusual. I haven't seen this too much, but look, I've worked on Wall Street for 20 years. You see everything, right? After a while, you see everything. So this could be, this should be the day, the month, and the year because this has 2025. 13.2. Now we're getting into a little bit different kind of thing here. But you know this cannot be the month. It's not 13 months in a year. This has to be the date. So it has to be February 13, 2025, right? It has to fall into that convention. This is unambiguous, right? This can be a little bit ambiguous, right? You can interpret this a couple different ways. So this is August 25th, 2025, or August 2025, and this is the 25th day in August. That's a little bit ambiguous. This is not ambiguous. This is only one way to interpret this, right? This is the same, right? So this is kind of flipped over a little bit disoriented, but you have to know that it has to fit into this bucket. It has to follow these guidelines or these rules, right? So let me go ahead and run this script, and I will share the script with you guys. I will drop the script in my notes when I post this video later today, or give you a link so you can download the script. So you can see everything is in a list here, right? We append everything to a list, right? And the list comes from right here. This is the list defined by the square brackets. So these are pretty obvious right here. This thing is a little bit weird looking, but that's fine. We're just going to strip out the promo. This thing has none. None is none. That's just nothing, right? That's nothing. And this is just a blank date, right? So we have the raw dates here. This is what we're looking at, raw dates. Okay, so, okay, everything looks fine down to here. Promo has promo. We want to get rid of the promo. We want to just clean it up. Again, refinement. We're refining the data. We're cleaning. We're disambiguating the data, or unambiguating, whatever the term is. I think disambiguating. And this has nothing, and this is nothing, right? So nothing is nothing. I can't get a date from nothing. Nothing's going to happen here. But these dates look pretty decent. They're in good shape, right? I can do something with that. That one needs a little cleaning. I'll take care of that. So we have the date standardized and then the date ISO over here. So the ISO, remember, this is just a way of universally standardizing all the dates I think around the whole world. Let me look this up. ISO dates. Look this up real quick. I've worked with this in the past, but it was a long time ago. ISO standard uses the year, month, day to avoid ambiguity, and date interpretation across different countries. For example, April 3rd is 2024, 0403. Okay, so this is a universal way of getting everything standardized in the same relationship so everybody understands what this is, okay? So we have the raw date, we have the date standardized, and we have the date ISO over here, okay? So let's say we have a data frame with a raw date and a couple different date types over here, okay? And we want to go ahead and apply those dates and match those with what we have in our original data frame over here. Anything that matches up. So I work in finance pretty much my whole career. I did a lot of like time series analysis, a lot of equity reporting, equity analysis, right? Is a stock worth $25? Is it worth 26? Is it worth $200? Things like that, right? Some fixed income analysis, did some derivatives back in the day against foreign exchange, FX as well, but like equities is really my bread and butter here. So let's just say you have equities, right? You can join different equities, closing stock price from Yahoo Finance. I use this a lot in a lot of my videos. You can join this. Once you standardize the dates, you can join this to your data frame, right? And do any kind of analysis you want. Pull in different components for your equities, look at different components from the balance sheet, the income statement, the cash flow statement, all these things, right? You can look at this pretty easily once you have the dates standardized and set up. But let's say you just have some very simple KPIs. I don't even want to go into equity analysis, right? I don't want to analyze, is the stock worth $25 or is it worth $400? Like in this case, I don't care. I just want to match the dates. And I want to make it even easier, not even looking at equity data. I just want to look at just some basic KPIs, right? Key performance indicators, right? And I just want to match these based on the dates. If the dates match up, I can join based on the KPI and get my KPI data. Again, I have KPIs right over here and I have dates right here, right? These are my KPI dates right here, right? I've cleaned up all the dates from the data frame. It was kind of messy before, but we've refined it. We have reconciled the dates, right? And I want to join those with my KPI numbers. So I can definitely do that once the dates have been cleaned up. If the dates have not been cleaned up, right? If they look like this thing over here, this is just an absolute mess. I can't join anything because nothing is going to match. It's like if you're using Excel, you want to do a VLOOKUP or something like that. That now Excel has some different lookups. When I used to use it, I haven't used Excel for a long time. When I used to use it, it was mostly VLOOKUPs. Now I think they have a couple other alternative ways to do the matching. Index match is one. I use that a lot in the past. So if you want to use an index match or a VLOOKUP, that's fine if you have your dates. If they're all messy, nothing's going to match, right? So you have to clean this up. Once you have the dates set up, you have the raw date, the event, and the actual dates, right? The cleanup date, this is a refined, improved date, and you have the KPI. You can do all of these things, right? Once the dates have been cleaned up, you can do these matches, you can do these joins, right? So what can you give me a minute, please? Can you give me a minute? Okay, sorry, my son just barged in here. So how do we standardize the dates in plain English? So I showed you the code, right? I gave you all the code, and I'm going to drop this when I drop the video later today. Control Enter shows you the list of the dates. It's kind of messy, kind of dirty, kind of funky looking, right? But once you clean that up and do the merge, you have everything that merges or matches with your KPIs, and you have the report done, guys. This takes a couple hours. It doesn't take 6 months. I don't know what the project manager was doing. I wasn't in charge of that guy. He didn't report to me. I would, like nowadays, I would just override that and just say, listen, let's just get this done in a day. Like, I don't know why it takes 6 months. But anyways, that's the way it was before, right? And there's protocols and like this guy reports to this and you have to do this thing and you can't step on this person's toes or they're going to get upset and they want a paycheck every Friday. So anyways, there's a very efficient way to do this. We're streamlining and standardizing multiple date formats, right? So it's pretty easy to do this kind of thing. So in plain English, what are we actually doing? Early checks for defaults. If the cell is empty, just return a none, just do nothing, okay? If it's empty, like this cell over here, right here. There's nothing I can do with that. There's nothing I can do. There's no date. I would go back, not to that project manager, but I would talk to another project manager that was more competent and that actually coherent, and say, listen, we're not getting dates. Let's backfill these dates. Let's just get this filled in, and talk to a business analyst or somebody that can actually do the transaction, right, and get that fixed. But if there's nothing you can do, right? Nothing is nothing. So reference year is that this year, if you're getting the data in real time and pretty frequently, like daily or weekly, then you can assume that this year is this year. 2025 is 2025. Right now it's August 26th, 2025. That's what this is, okay? We'll never have another August 25th, 2025. When today is gone and done, it's done. It's not going to be repeated, right? But if you know that you have to pen the year, and this is the current year, and you have to pen this onto your month and your date, then just do that. That's all you have to do, right? So normalize, make it parsable, remove any kind of like weirdness. 25th is just 25. First is just 1, right? It just standardize this and just make it uniform. So strip parenthetical promotion, okay? So August 25th, there's a promotion. Just take that out, cut it, parse it, make that into an actual date. Unify separators, dots and dashes. Detect if there's a month name. If some weird convention comes up, just handle it, right? There might be some outliers. There might be a couple of weird things that pop up. Try to deal with it. If you can't deal with it, you're going to get these things over here, okay? And if you have a couple, that's no biggie. That's no loss, okay? You have 2 dates that are missing, so no one's going to lose sleep over 2 dates. But if you can get these backfilled or filled in or retroactively updated, that's good. If you can't, then you can't, okay? And decide what the convention is. Is this month and day, or is this day and month, right? So in this country, usually it's month and day. And European countries, I believe it's usually day and month. You just have to decide what the convention is and use that, right? If there's a math name, use day first. If it's numeric only, use a heuristic. A heuristic is a way to define how something should be done pretty efficiently, pretty accurately. It might not be 100% absolutely guaranteed to be correct, but in most cases, it's probably 99.9% accurate, and that's good enough, right? If you have something that's 99% done and you can do that quickly, efficiently, just do that, okay? You don't have to take months to do this thing, and if you drop a couple of records, it's okay. If you can get most of the stuff out the door, get that over the goal line, score a goal and get 6 points, then go for it. Do that, right? You don't sit around for months and just think and opine. I've worked with people that said, I have to opine. That's form an opinion. It's a legal term. It means form an opinion. I have to opine about this. I have to opine about that. I have to opine about different things. No, you don't. Just do your job. Just do what you have to do, right? Who is sitting in the office with no opining other than like lawyers I worked with 2 decades ago, okay? Don't do that. Don't do that, guys. The second number is greater than 12. It has to be month, day, right? There's certain conventions, there's rules you follow. Otherwise, fall back to the preferred day first flag. Parse with pandas, right? Pandas is a very powerful library. In Python, that's going to do the lift and shift for you. Try it, pi, date to time. I've used this countless times. I don't know how many times. Thousands of times, maybe over 10,000 times, right? A lot of times that will get you where you want to be most of the time. Sometimes it will do all the work for you. Sometimes it will do 99% of the work for you. And then there's outliers. You just have to clean those up and handle those on a case-by-case basis. If that fails, try opposite day first. If that fails, return none. Maybe there's a flag. Okay, I know there's a problem here. I know that we can focus our time and attention on these 2 records. We don't have to spend 6 months on these records, right? This is done. 1 hour, done, all done. We can focus our time and attention on these 2, try to get those cleaned up. And if it doesn't happen, it doesn't happen. You have most of what you need. Return timestamp, normalize to midnight, date only, and you can render it with ISO and use this convention, year, month, date, if that is your goal too, right? There's a few different ways to skin this cat here. It's really up to you. It's a little bit arbitrary, but you should still standardize those dates and get what you need and get the thing straightened out and get it mostly fixed. If you can deliver 99% of the project in 1 day, then I think your boss is going to be thrilled. I think the team is going to be very happy. I've worked in these places before, guys. Like they'll give you 6 months, 9 months, sometimes 12 months to do something. You can do it in a day. then kick back and relax for the next year, right? You don't have to do a whole lot. It says send a couple emails, keep them happy, keep feeding the managers, right? That's all you have to do, and take care of them, right? But if you can knock it out quick and easy, then that's what you should do. Okay, so this is my narrative for standardizing multiple date formats into one single format. I'm going to wrap it up here. We're at 20 minutes. Probably dragged on a little bit longer than it needed to. It probably could have standardized this video. I'm talking about standardization, right? Probably could have standardized this video in maybe 5-10 minutes, but whatever. I want to cover all the bases. I want to cover all the points here. So I think we did that. Mission accomplished. I think this is a good outcome. So that's it. Just keep an open mind with these things, right? Anything is possible. There's no limitation. You should be optimistic. Don't be pessimistic ever. Pessimism is basically guaranteed failure, but be realistic too. Don't be optimistic and just say, I'm going to just knock this up in 2 minutes, and then you can't, and then you get pessimistic. Don't do that, right? Be realistic. Mostly, if you have to lean one way or the other, go optimism, okay? Be optimistic, be positive. Don't be pessimistic and think that the glass is half empty. Just be optimistic, right, with your analysis and with your thought process, okay? And you'll get there. You'll get what you need to do. And Google it, right? If you get stuck, Google it. Google is a skill. Google's a skill. I'll tell you that right now. So that's it, guys. I'm going to wrap it up here. Thanks for your time. Thanks for sticking through to the end. I'm going to post all this code. I will save it right now. I save as HTML. I will upload this. All the source code, you have everything you need to get this done, right? Do all the refinement and the formatting and everything to clean up your dates. And then it's up to you to showcase your skills and impress your boss. I'm giving you the foundation to step on. Isaac Newton once said, if I've seen further, it's because I stood on the shoulders of giants. He was referring to the fact that he built mathematical models, basically calculus, and a lot of the advanced math that we use today for all kinds of physics, biology, chemistry, data science, engineering, a lot of things that we use today, even electrical engineering, right? Chemical engineering, things like that. He built the foundation for that, but that was only because he could stand on the shoulders of people that came before him and built the foundation of mathematics, okay? If it wasn't for that, he couldn't do his job, but he was in the right place at the right time, just like you are, just like I am. Right place at the right time, and we can do phenomenal things because we have stood on the shoulders of giants, guys. We stood on the shoulders of giants, okay? And we have seen further. That's the point. So I'm going to leave you with this. Thank you for watching this thing to the end. I appreciate that. Hopefully this knowledge drop was useful and educational and practical. I'll share all the code, I promise, and I'll drop the code in the video and very soon, and I'll see you in the next video when I post that a little bit later today. Take care for now, and I'll talk to you soon. Bye. Hey there, everyone. Ryan Schewel here. Welcome to my analytics channel. So in the narrative today, I want to take a look at retail price optimization based on different price changes, right? And we're going to look at the elasticity of demand. If price goes down, does demand go up? Or is there not much of a change? And if price goes up, does demand go down? Or again, is there not much of a change? We're going to look at a few different scenarios and cannibalization modeling. Now that is a mouthful, guys. That's a mouthful. So I want to focus on a hypothetical scenario. This is going to be Starbucks. Okay, this is a little teeny tiny itty bitty little company. Not sure if you've ever heard of it or not. You probably have though. So we're going to look at Starbucks, and again, this is hypothetical. I don't have Starbucks data, but I think it will illustrate the point pretty well. So I'm going to make some assumptions here, but they're all credible and highly realistic. And again, I don't have Starbucks data, and there's no way I would have that because I don't work for them. That's highly private and confidential, but we can go ahead and simulate data that should pretty closely represent Starbucks pricing, menu items, and we're going to go ahead and change the prices up and down and see what kind of impact that has on demand. Okay, so I'm going to go ahead and run this first script in this first cell, Control Enter to run the code. Okay, and as always, I'm going to give you all this code. This is all the source code that I used for this project. I'm going to share it with you guys so you don't have to take notes. You don't have to try to memorize things, but try to learn it. Download the HTML file when I post it later today. It's going to be underneath the video. I'll give a link to a Google Drive. file. This is going to have all the source code that you see right here. Okay, so you don't have to memorize anything or try to capture it on paper or something like that. I'll share that with you. Okay, so in the first case here, we have item, base price, and cost, and that is basically just coming from different categories, right? We have coffee, tea, bakeries, bakery items, snacks, things like this, and then classic vanilla, caramel, hazelnut, honey, almond, pumpkin, and coconuts. Okay, so again, I don't even know if they have coconut on the menu. Pumpkin, I'm pretty sure it is like mid-October right now. It's October 19th. So pumpkin is definitely on the menu. I think they have these items. Again, I think it's pretty close. Maybe one thing is off. Coconut, do they have it or not? I'm not sure, but it sounds plausible, so I'm going to go with this. So we have the item, the base cost, and the actual cost right here. Okay, so let me run the next cell and go into the next step here. So this is a good start. Let's simulate 365 days of prices and demands and costs and revenues too, and then look at the profits over 50 Starbucks items, okay? We're gonna see which items have more price elasticity and which have less. So I'm looking at the year, this is 2025, start date is gonna be January 1st, number of days is 365, so we're gonna go from January 1 until December, was it 31, 30? How many days? 30 days has September, April, June, and November. I think it's 30, right? Oh, let me look at this thing right here. Whoops. Whoops. Okay. Oh, yeah. Expand this. Go to December 31. Yeah, so I thought. I always forget that one for some reason. Okay. So January 1st to December 31st. Okay. So we're going to have weekly data points. And at the end, I'm going to make some assumptions about holidays. So around November and December, I'm going to add a small multiplier, assuming that more people are going to go out for Starbucks beverages or snacks around the holidays. Okay. People are just festive, they're in a good mood. You're going to share drinks and time with friends and loved ones. So I think that is pretty realistic to have a little bumper on the holidays. I think that makes sense. And we're going to look at things like Thanksgiving, Black Friday, and Christmas around the end of the year. And they understand there could be other bumps earlier in the year, maybe springtime, like early April, maybe around when the kids get out of school, maybe early June, maybe 4th of July, there's a bump. Again, I don't have this actual Starbucks data, so I don't know how it works. I would assume there's probably some increases around the holidays. Definitely Thanksgiving, Black Friday, and Christmas. I'm going to make those assumptions. I think it's safe to go out on a limb there. Is there increases in people going to Starbucks? Is there an increase in frequency around Memorial Day, Labor Day, 4th of July? I'm not sure. Maybe not. Maybe it's de minimis and we can't even measure it. So anyways, I'm going to capture a few bumps in the data around the holidays, and I'm going to look at the menu data frame we have over here, baseline demand, base price, and the elasticity. So again, elasticity is the stretchiness of the price based on the change in the price, or sorry, stretchiness and demand based on the price. So if a product is highly elastic, you can raise the price a lot and demand will increase. Okay, demand is very stretchy, it's very elastic. If you decrease the price a little bit and demand increases a lot, that's elastic, right? If you increase the price or decrease the price and demand doesn't really change, that's called inelastic. It doesn't really stretch up or down, right? Like people have their fixed prices in mind. Maybe it's $3 for a coffee. Maybe if you change it to $3.10 or $3.15, demand won't change, right? Maybe if you lower it by 10 or 15 cents, demand won't change. That's inelastic, right? It's inelastic, it's not moving. If you change the price up a little bit, demand goes down a lot. That's elastic, right? It's very stretchy, it's moving a lot. If you change the price down a little bit and the demand surges, it goes up a lot, that is elastic, right? So big moves are elastic, small, little, tiny moves are inelastic. Okay, so we have the data. I'm going to go ahead and look at things like cost, total cost, revenue, and profit, right? So we're running the business here. We have to understand just basically the demand, like I just mentioned, how does it change as a reflection of the changes in price, right? How many unit cost increases are we dealing with here, right? What's the total cost? What's the revenue, right? Because the revenue is the cost minus the raw materials and things like hiring more baristas to serve more drinks, right? If you increase the number of employees you have at the site, your profits are going to decrease. But if you're selling more and more beverages, more and more snacks, the revenue is going to increase and offset the increased labor costs, right? So the profit is the difference between the total cost and the revenue, and we have the date over time, so we know where we are at this point in the year. Okay, so Control Enter to run. So we'll refresh a cell and regenerate all the data here. And it's pretty straightforward, just basic accounting and finance. Hopefully this makes sense. We can see we have 18,250 days. This is 365 days and 50 items per day. Again, in this simulation, real world is probably going to be a little bit different. You'll probably sell more lattes, more cappuccinos, more coffees, versus some other products which you might have fewer sales. We're just trying to create like a base case scenario where we're looking at everything, all the items, and the demand, cost, total cost, revenue, profit, and the date over 365 days. So that's the goal here. So we can see demand overall for vanilla espresso is 156,000. Here's 154,000 for espresso, and so on and so forth. Coconut latte, 143,000, and caramel cappuccino, 141,000. So that's the demand. Here's the revenue, and here's the profit. Again, you have your top line revenues. You have to subtract out costs of goods sold. That's the COGS. Things like labor costs, even keeping the electricity on. You have to pay for the rent, things like that. Like this is going to be the profit over here. Okay, so after you subtract out all your expenses, let me see something. Okay, profits. Yep. That looks good. Okay, so we're looking at just basic gross profits. So all we're doing is taking out the cost of goods sold. So you have the overall revenue. What does it cost to generate that revenue? All the raw materials, right? So you have to pay for the milk. You have to pay for the coffee beans. You have to pay for the cups, right? And the tops and the stirrers and the sugar and the half and half and all that, right? So this is your cost of goods sold. You have to pay that money to operate your business. So you have your top line revenue minus the COGS. Then you have your gross revenue. You also have your net revenue after all the expenses, after you pay for electricity, your labor force, that's the staff, right? All the salaries, things like that, 401k, what else? Healthcare, things like that. That would be the net profit. We're looking at gross profit in this case. So let's make a copy of the sales data frame. And when we make changes to the sales, we are encountering, and if we encounter some mistakes, we only have to come back to the point where we redo our work at this step. We don't have to go all the way back to the beginning and rerun the process all over again. So if you've seen my other videos, I do this a lot. Here's my sales data frame, Control F, and pop it in here. You can see where it's coming from. Okay, so sales data frame is the last thing we did with these group by aggregations. We're doing sums of demand, revenue, and profit. So we're summing all these, getting this nicely packed into a data frame, and then sorting the values by revenue in descending order. So if you look here, this is the biggest revenue, 11,000, 2,800, 14,000, 1,400, and 999. Okay, based on revenue in descending order. Okay, so that is how we get the sales data frame. But I want to take that, make a copy over here, and just create a basic data frame. So again, I'm creating a copy so I don't have to go back to the original in case somehow this thing right here gets messed up a little bit with some calculation. We don't have to go all the way back to the beginning and redo the analysis from the start. We can just come back here. We know that this is fine right here. We'll make a copy and continue with the analysis. Control Enter to run. Okay, so at this point, the price of a latte is increasing and cappuccino demand, if the price of the latte increases and cappuccino demand rises, that is a positive cross elasticity. Okay, so if both drop, that is complementary. Okay, so again, Google this if you don't understand the concept. I'll try to explain that again as easy as I can. More elastic means you drop the price a little bit and demand increases a lot. Increase the price a little bit, demand decreases a lot. That's more elastic. If it's inelastic, it's not going to change very much, right? The variability of demand is not going to change. If you increase the prices, demand will be basically the same. If you decrease the prices, demand is basically the same. That's inelastic, right? So we can see here, anything that has a negative elasticity, increase prices, decrease demand is a negative relationship. Decrease prices, increase demand. Okay, so you can see, is this positive or negative elasticity? Closer to zero means very inelastic. Beyond 1 is about normal elasticity. Beyond 1, like 1.4, this is more elastic. This is less elastic, right? This is about normal elasticity, not too much, basically inelastic. This is inelastic. This is more. little bit more, a little bit more, and that's pretty elastic, right? So anything close to negative 1.0, basically inelastic. Lower is higher, um, higher elasticity, right? And if you have a higher negative elasticity, then again, there's negative impact, negative relationship, lower prices, demand surges, increased prices, demand drops, right? So here we have values are negative as price increases and demand decreases, right? Any kind of inelastic relationship, demands don't drop as much when you raise prices. That's inelastic, right? And if it's elastic, revenue is unchanged for small price changes. But if it's elastic, demand is very sensitive to price changes. Again, small change in price down, huge increase in demand. Small change up, big drop in demand. Okay, so that is price inelastic, right? So let's build an optimization model at this point because I want to try to understand how elastic are these items on the Starbucks menu based on the change in price. So we have the prices over here, elasticity, base demand, and then overall profit. And remember, that is sales minus COGS equals profit. You can also call that um, total revenue, total cost minus revenue is profit, right? Oh wait, I'm sorry. Here's the total cost. This is your revenue, and this is your profit, right? So I'll go down here and we can see the inelastic and the elastic outcomes. And from here, I'm using SciPy Optimize to try to minimize the impact on the change in prices, right? We want to see mathematically or statistically how elastic these different prices are. That's the goal, right? So we get to the base price and base demand, and then we're going to go ahead and change these slightly by changing the price, right? And we have a bound of 2.5 to 6.0. This is in terms of dollars. So the cheapest item on the Starbucks menu is assumed to be $2.5. The most expensive is 6.0. Now I live in New York City. In New York City, they actually have the highest price of Starbucks coffees anywhere in the United States. So everything is just more expensive here. So hopefully these prices kind of make sense and kind of represent what we are looking at here. In your neighborhood or your region of the country might be a little bit different. I think 2.5 across the US is pretty reasonable, and 6.0 for the highest price item on the menu. I think that's pretty reasonable. In New York City, it's probably going to go over 6.0, and it's probably not going to go as low as 2.5. Maybe 3 would be the lowest for a cup of coffee. I'm not sure. Trying to generalize across the entire United States, okay? So here we go. Classic latte, 6.0, that's $6. This is $6. Classic espresso is 6. Classic Americano is 6. Macchiato is 4.6. So you can see all the prices here. These are all 50. Coconut latte 6. This is 5.3, 6, 3.49. Okay, so this is actually a very useful diagnostic. Again, this is probably generalized to the entire United States. I'm not saying this is your local Starbucks prices in your local region, but probably representative of the overall pricing ranges for Starbucks, right? So the elasticities, again, are inelastic if it's near negative 0.1. Pushing price up increases revenue. With healthy margin, it also increases profit minus unit if we hit the cap, okay? So let's assume some pricing constraints to make this analysis more realistic. Cap the change at 10%, right? So if we increase prices more than 10%, there's probably going to be a pullback, and people aren't just going to continue to pay more and more and more. Probably there's going to be some boycotting of Starbucks items, right? People might say, I'm not going to Starbucks, it's just getting too expensive. That's a more realistic assumption, okay? So instead of just having open season on prices, you can do whatever you want. I'm going to say there's a limitation, 10% increase in prices. And again, this is all fungible and changeable. You can make this to whatever you want. I think 10% is realistic. Okay, after that, I feel like people are just going to walk. You're going to be walking them right out of the store if you increase prices more than 10%. That is my assumption. So you can change that if you think it's 8, 9, 10%, that's fine. Maybe 12, maybe 15% people are walking out of the store. I'm not sure. I think 10% is a good basis. You can change it, and you can go through iterations of this and see what the final outcome is, and then try to gauge it based on that, okay? So here we have the cost dictionary, base price, and base demand, and the percentage cap is 10%. Like I said, increase in 10% right there. And the minimum margin has to be 30%. So as Starbucks, I don't work for Starbucks, okay? But if I did, I'm going to say I want a minimum margin of 30%, or I'm not even going to operate the business there. I'll close the shop and go somewhere else after I have to pay my employees' salaries, the rent, healthcare, 401k, what else? All the raw materials, right? All the inputs for all the coffee, drinks, all the beans and the milk and the cups and the lids and all that. I still need to make 30% margin, or it's just not worth my time. I'm not going to get into the game. I'm not going to jump in here if I can't make at least 30% margin. I'm going, okay? So there's a cutoff. There's some bounds, okay? That's called a bound, an upper and a lower bound. We set some upper bounds right here. I need to make at least 30% or I'm closing the shop. And the percent cap that I can pass on to my customers or that I can adjust up and still expect to get customers is 10%, okay? So again, these are somewhat fungible. These are, I wouldn't say arbitrary, but I'm testing the waters right here. I'm going to say, does this make sense? I'm going to test it right now. I'm going to test this hypothesis. Does this make sense? Can we still operate, given these margins right here, okay? So we have the low cap, the high cap, the low high over here. This is going to set a floor and a ceiling. So the ceiling is the maximum we can go in terms of prices. The floor is the minimum that we can go and still stay in business, okay? Now we can't have a negative profit. That doesn't make sense. We're going to close down the store. We're not going to make money, or not. We're not going to lose money and continue to operate. If we're losing money, we're leaving. So we're looking for a negative profit. If that exists, we're going to close the shop. But we're trying to avoid that too. But we're going to set a constraint on the high end and on the low end. So ultimately, I want to look at prices, the base price, the cost, elasticity. Again, that's the stretchiness of the demand based on a change in price, quantity, revenue, profit, and I'm going to go ahead and run this. I think I just hit refresh. Let me just do it again to make sure. So the current revenue is 67,236, and the profit is 36,966. So when we optimize this, the revenue actually goes down a little bit. We go from 67K to 66K, but the profit actually goes up a couple thousand, right? So the offset 7, 8, it goes up about $1,800, even though the revenue went down about $1,000, right? So we're still winning. We're still making money here in the optimized scenario. In the optimized charm, we are making about $66,295, almost the same as this. The profit is exactly the same. The only difference when we charm these prices, it means instead of getting a price like $4.02 for coffee or for cappuccino or whatever, we charm it. Charming is kind of a cute little term. It means make it look more appealing, make it look more attractive. We'll set this as $3.99 or maybe $4 even. We kind of round these off or make it more appealing for the customer to engage with the business, right? If you say 4.02, first of all, who's carrying around 2 cents with them? They're probably going to use a credit card. If they have to pull out cash, you're going to give them what, 98 cents and change if they pay with a 5, and then the person has to carry around 98 cents and change in their pocket. Probably not too attractive of a scenario for the customer, right? Or what is it called? Member? What is it called when you go in Starbucks? Who's the next? Not customer. What do they call them? Forgot now. Sorry, not member, not customer. Oh, yeah. Starbucks guest. Who's the next guest? Okay. So maybe it's not too appealing for the guests to carry around 98 cents and change in their pocket, right? So we charm the prices to make it $3.99 or $4 even. That's all we're doing here. So we're optimizing the revenue right here, 66,300 approximate, and the profit is about 38,000 here. The revenue is slightly higher, but the profit is slightly lower, right? So net, we're still ahead $800 in this scenario with the optimized pricing over here. And the $800 is not a lot, but I'm just showing you like the mechanics of how this works and the economics behind this, okay? So we've charmed the prices. Let us go ahead and recalculate these prices, and you can see what kind of impact it has. So the classic latte is 4.38. Okay, over here, the classic latte was 6.0. So the optimization model found out that 6.0 is too high. Nobody's going to be buying these lattes. It's just too expensive, right? The classic cappuccino is 6, classic espresso is 6, and Americano is 6. So the top first food items here, or first items, not really food, is $6, right? For latte, cappuccino, Americano, yeah, espresso and Americano. That's what we have there. So if we optimize the prices just a bit, we can say latte, cappuccino, espresso, Americano is actually 4.8, 6.0. So we'll leave that as is, 5.9. That's pretty close, 5.38. So this stayed essentially the same. This was exactly the same. The optimized price for the latte is 4.38, and for the Americano is 5.38. So here we see a perfect example of dropping prices, building goodwill with the customer, getting more people into the store, generating more transactions. That's actually helping the retail outlet. Starbucks itself is actually making more money, even though they're dropping their prices. More people are coming in because they're stimulated by these lower prices to spend more money and engage with the business more. So I think that's very fascinating, right? And I hope this is a message to all the retailers out there right now. We are looking at sky high prices, inflation like I haven't seen in a long time. I'm over 50 years old. I can't remember a time in my life when these prices were just out of control. It seems like everything is on fire right now, right? Everything is on fire and there's no extinguisher in sight. I would make the argument if you reduce the prices, you will stimulate demand. That's what this whole price elasticity thing is about, right? You lower prices, you generate more demand, you'll actually make more money as a retailer, right? That is the onus is on you as a retailer to drop these prices and make it more affordable and more attractive for customers to come through your door. And ultimately, they will spend more money. You're going to benefit from this drop in prices. Let's look at another example down here. We have coconut at the end. So latte, cappuccino, espresso, Americano, and macchiato, right? So we have 5.6, 3.9, 4.9. That's basically 5. That's almost 5, 4.9, 3.3. Let's see what these coconut beverages were above. So 5, 6, 3, 9, 4, 9, 4, 9, 3, 3, right? Over here, lo and behold, 6, 6, 6, right? So this is too high. People are not going to buy it. 5.3, 3.4 for number 4 to the end. This is the last one. So 4, 3, 2, 1, 5.3, and 3.49, right? So 5.3, we can lower that, make more money, and 3.39, and we can lower that and make more money. So again, I'm proving my argument here. Lower the prices, stimulate demand. This demand is highly elastic, right? You're going to sell more stuff, generate more profit as a retailer. You'll be better off. You're building rapport with your customers. You're building goodwill. More people are coming in. They're bringing their friends. They're spending more money. Ultimately, your profits are going to grow, and people feel better too because the prices were actually lower, right? If you raise your prices so much, like $10 for a cup of coffee, nobody's going to come in and buy that coffee. Maybe you'll sell 1 or 2 cups throughout the day. You're shooting yourself in the foot if you do that, right? The prices are too high. You're leaving a lot of money on the table. Lower the prices based on some kind of economic or optimization simulator like we created here. You're going to generate more demand, more revenue, more profit for your retail outlet than you know what to do with, okay? It's not just raise prices and charge as much as you can. That's how you make money. You have to be intelligent about this. You have to be smart, right? And work with the customer. Do what's in the best interest of the customer, and they will reward you with sales, right? With charges on their credit cards. They're gonna buy more because the prices are lower, and it just feels better for the customer, more value, better experience, and it's win-win, right? Win for the retailer, win for the consumer. Okay, so one more scenario down here. The prices, we were looking at price maximization, and there's a penalty or penalized profits minus don't move too far penalty. This is inelastic demand, right? Again, I said if the prices go up a little bit and demand doesn't change, or prices go down a little bit and demand doesn't change, that's inelastic. Prices go down low, demand jumps up, that's elastic. Prices go up a little tiny bit, demand drops, that's elastic. So let's look at a couple more scenarios. We're almost done here. We have the item price now, optimized price, the quantity now, optimized price, percent change, revenue now, and profit now, profit, optimize, and profit change. So go ahead and hit Control Enter to run this. So we can see current revenue, optimized revenue, slightly higher. Revenue change, negative 3.2. Actually, no, it went down a little bit in this scenario. Current profit 3.6, optimized profit 3.8, and change in profit 1.24. Oh, that's what we saw before, right? So 3.6, 3.8. That is exactly what we see over here. Oh, shoot, it's going out, right? So I have to change this and refresh the screen. Sometimes my computer has think amnesia or Alzheimer's, one of these things, because it keeps forgetting what's going on over here. So if we go down here, so where was those numbers? Yeah, okay. Yeah, so that's what I'm looking at. So we go from 3.6 to 3.8. So the profit increases a little bit, 3.6K to 3.8K. That's exactly what we're seeing on here, 3.6K to 3.8K. So the profit increases $1,242. And you can see the breakdown for every single item. Price now, the optimized price, percentage change, quantity change, revenue, and profit change. Okay, so everything is broken out. You can see everything right there. I think that's a pretty nice view. Tells you everything you need to know. Every single item, all 50, optimized price, current price, and the change in revenue if you increase or decrease. Okay, so just a couple more things to get through here. We're looking at, again, the overall group of all these items, the item itself, the array, the item I, which is the row. We're going to iterate all through these items, right? And then the data frame price item itself. So we come up with this as the current price and the optimal price. Now I like these a lot. Let me change this just a little bit. Should work. Let me see. No, it doesn't like that. That's in the wrong spot. Okay, so let me change it over here. So that should work. I think that should work here. Let me see. No, it doesn't like that. You have to get these arguments in the right spot, right? So that could work too. Behind the, yeah, that's fine. Okay, maybe just make it a little bit bigger, 600. So the height will be 600 now, a little bit easier to see. I had a slider control here so we can see all these items. So this is a Plotly chart. You can zoom in, you can zoom out, you see all the details, double click to go back. The current price is here and the optimal price is in red. The current price is in blue and the optimal price is in red. So you can see in some of these cases, Starbucks, you can actually increase your price and demand won't change, right? You can make more money, but in some cases you have to reduce the optimal price to generate more profits, right? So this is going to look at everything holistically and comprehensively and see what those changes, those realistic changes are to continue to, to be a value add to the neighborhood coffee demographic, right? And actually make more money for the retail outlet and actually create more value, the appearance of more value or more appealing price point for all these items on the Starbucks menu. So Control Enter. Okay, get my coffee here. And then here we can see a bar chart. Again, Plotly, I like this because you can zoom over all the charts or mouse over all the lines here and you can see what the difference is. So the profit change by item, the honey latte can have the highest change and increase in profit. So if I look over here, honey latte, that sounds a little bit weird when I say honey latte, but maybe, let's see if I can find it. No, it doesn't look for those data frames, right? So honey latte, oh, here it is, okay. So the price now is 4.92, the price optimal is 5.42, and the percent change in profit is 100%, or percent change in price, 10%, percent change in quantity is going to go down just a little bit, but not much. The revenue will decrease just a little bit, but the change in profit is actually up, right? So if we go back here to this chart, we can see that. So honey latte is the most elastic. The most inelastic is caramel cappuccino. I think that is at the bottom of the list. Yes, it is. So caramel cappuccino, we start at price now and price optimal. We start at 6.39. We have to actually drop this to 6.0 to generate enough demand to make this profitable and have the appearance of being profitable or a good value to the customer. This is going to be price change down, right? We're decreasing. Quantity change actually increasing more. So we're selling more. The negative 50 shows the revenue change negative 50 and the profit is negative 0.81. So this is highly inelastic, right? As you increase the price a little bit, people are going to rebel. They're not going to buy caramel cappuccinos. If you decrease the price a little bit, people are maybe buy a little bit more, but not too much. This is highly inelastic. That's what this chart shows us. So that, again, this is the before current price and then the optimal price. Down here, we have the profit change by item. So here's the maximum change in sales based on a lowering of the price. And here is the minimum change in sales based on an increase in price, right? So you can see negative 100 is dark red and positive 100 is navy blue. So we have one more chart over here, control enter, or maybe two more. This is showing by the day of the week. Monday is 0, it's zero based. Python's always zero based. So this is Monday, Tuesday, Wednesday, Thursday, Friday, sales peak. People are probably going out, in their lunch break, late morning, coffee break, looking forward to the weekend, ready to spend more money on a Friday. Sales dip a little bit Saturday. People are probably traveling, doing things with their family, playing with the kids, the pets, things like that. So sales are down a little bit Saturday, but still pretty robust, right? Sunday's probably almost the least. We have 285 demand. Monday is 249. So Monday is actually the least. Sunday is dropping down, but you can see over the course of the week, this is DOW, day of week. Monday is 0, Sunday is 6. You can see Monday is the slowest, and Sunday is the next slowest. Friday is the highest. Here I have the seasonal factor. Remember at the beginning I said there's going to be a bump around the holidays. So you can see this is pretty flat. Again, I don't have the actual Starbucks data. I made this up and I tried to make it as realistic as I can, but I didn't add in a holiday bump for Easter or for 4th of July or Memorial Day or Labor Day. I don't know if those really exist, maybe to a slight extent, possibly, but I'm certain there's a bump around Thanksgiving, Black Friday, time like that, and around the holidays. This is Christmas and New Year's. People are in a jovial mood. They're festive. They're spending more money. They're out shopping, and they're buying Starbucks. Okay, so that is it, guys. That is my take on menu price optimization, looking at elasticities of demand based on changes in prices, and overall cannibalization of products. Right, we're modeling the cannibalization. If you start selling more and more and more, what is it over here? Caramel cappuccinos, you're probably going to cannibalize some of these items over here because there's only a limited amount of funds. People just have a certain amount of disposable income. They can't spend all their money, right? So you can't sell more caramel cappuccinos and more of this, more of that, more of the other thing, more and more and more. There's going to be cutbacks and there's going to be offsets, right? So you can sell more honey lattes, chocolate Americanos, vanilla macchiatos. Yes, but it's going to eat into some of the sales of some of these other items too, okay? Inevitably, you're going to cannibalize yourself to some extent because there is limited money in everyone's wallet, right? People don't have unlimited funds. There's limitations to everything in life. That's a fact of life, right? That's not going to change. There's always limitations for everything we do. So that's it, guys. I'm going to wrap it up here. Thanks for your time. Hopefully this was enlightening and somewhat entertaining. Try to drop knowledge wherever I can and fill in knowledge gaps and help people to understand and appreciate these topics to a greater extent. Okay, so I'm going to wrap it up here. Thank you so much for your time. I appreciate you sticking through it to the end. I'm going to post this source code so you'll have everything you see here, and you will have the video a little bit later today. I'll drop that this afternoon. When I get back, I have to run a few errands right now for my son and for his school. But later in the afternoon today, I'll drop the video and you'll have all the source code and you can copy and paste it and run this on your own system. Thanks again, and I'll talk to you guys soon. Goodbye for now. Hey there, everyone. Welcome to my channel. My name is Ryan Schewel. It's all about data science, machine learning. I think you know the routine. If you've seen a couple of these videos by now, hopefully you have. If not, then better start watching. Good stuff, guys. You're missing out if you're not watching this stuff. I try to dig into all kinds of different topics. A lot of those are financial related, but I touch on everything from weather to things like global warming, statistical analysis, machine learning, deep learning, things like this. Right? So this one is a little bit different. This is about analyzing NBA statistics and what we can derive from this data set, and then what kind of interesting questions we can answer, right? So I'm going to try to look at things like player development, stats about different players, strategic decision-making, about the teams, coaches, things like that. Just touching that a little bit. Don't get into it too much. Scouting and recruitment. So that is definitely a topic that we can touch on as well, and very relevant to all these NBA stats, as well as MLB, NFL. You can imagine, right? Pretty deep and rich territory for all kinds of analytics, right? Contracts and salary negotiation, fan engagement and broadcasting, right? Fan satisfaction or enhancing the fans' experience, optimizing team efficiencies, right? Performance improvements, things like that. And we can do historical analysis and trend identification as well. So really the sky's the limit here. We can do all kinds of things. And there's several different API endpoints that I found here. So I would invite you to explore and try to find a few more by yourself, right? Try that on your own and see where you get. Leave comments in the comment section if you have questions or if you get stuck on something, and we can learn this stuff together. I'm not like a huge sports nut by any means. So some of these things are a little bit new to me, but I tried to do some Googling and my regular due diligence to prepare this video, and I'll show you what I came up with, right? But then there's all kinds of different endpoints here that you can explore in this type of data set that I found. So everything is coming from a few different NBA data points. I'm sorry, API endpoints. All the data is fetched from a bunch of different API endpoints. I go to the API, pull it back, and then you can pass in parameters to to define your request right here. So I have a season parameter. I'm passing it into this endpoint right here. Now, some of these run pretty slow, so I'm not going to run this in real time. Actually, I think this first one goes pretty fast. Let me see. I think the first one's very fast because we're only getting about 250 players in the NBA. At this point in time, there's about 572. And you can imagine that some players get older and they retire, or maybe if there's an injury or something, then they're not included in the season. So I guess this number is going to bounce around a little bit. This is rows and columns. So 572 is going to be the number of NBA players in this season, 2023 to 2024. Okay, and then we have 66 columns, and you can see it right here. By default, the head just shows 5. If you put like a 20 in here, you can see everything, right? I think you know how this goes. And if you do this, it displays everything. You'll see the 572, okay? So that's how those things work. By default, really all you need is 5 to get a sense of what's going on here. And we have the player ID, name, nickname, so on and so forth. Some of these things, I don't even know what they are. I'm not like a huge basketball fan. I'm just trying to learn this stuff as I go. But I see points over here, plus, minus. This must be, I don't even know what that is. I'm sorry, guys. NBA fantasy points. Okay, if you're on a fantasy team. And field goal ranking, field goal percentage ranking, things like that, right? So we have some pretty rich stats on each player. So this particular players data set with the 572 NBA players, this one seemed like an obvious choice, so I pulled that one in. This one is going to take a little bit longer, so I'm not going to run this, okay? I have a note here. This takes a while to run. Some of these I ran last night. As I was having dinner, I put the computer on the side, and it did take a while to run these, so I'm not going to do it now, but I would encourage you to go ahead and do it. When you set this up, you can test all the code yourself. I'm going to share all this code with you, so you have everything. You can run this yourself in your own Jupyter Notebook, Data Lab, or whatever you have set up. You can run this in Anaconda, in Spider, whatever you have, right? And I would encourage you to do that, but it does take a little while to run some of these, so I'm not going to do that. But then with this one, DF personnel, it seems like you get more. This one was, yeah, this was interesting too because I found height, weight, the season, and then obviously the player name. Player name is important. All these players have an ID too, so you have a unique numeric identification for each player. Each team has its own ID, right? And then you have the team name. So we probably identify with the name a little bit more, but whoever's using this data is going to rely on the team ID to do mergers and joins. We'll see that in just a minute, how that works. Team city, from year to year, things like that. So I got this mostly for the like the physical attributes here, the height, weight, things like that of each player. I thought that was important. And there's a couple more I'm getting. So this is 3 of 4. So yeah, I ended up using 4 data sets. This is, let's see, shooting stats for each player. So you can imagine if you have one player, you have a whole bunch of shooting stats. That's why the records are blowing up down here. So we had 250 players, but now we have 11,520 different records. This is rows. This is always rows, comma, column, right? If you look at this, this is going to be rows, 11,520 rows, 28 columns now, because this is all the shooting stats for each NBA player. So you have the game date, right? And you have multiple dates throughout the whole year. You have the 23-24 season. So you can imagine 250 people. But then as you get to the shooting stats, it's going to blow up quite a bit in terms of the number of rows that we can fetch when we make the request for this API endpoint. And then you'll get win-loss. So that's for the team. Field goal attempts, field goal percentage, 3-pointers, right? Things like that. So I thought that was pretty relevant. And there was one more data set I pulled in. And this is the shot list. Okay, so, and you can see again, now some of these actually didn't come back. I guess making this request, it had issues. Let's see, error fetching data for player. Like, I couldn't find this player, right? So originally the player was in the list, it was at 250, but I think there's about 65 or 70 or so we just couldn't find the player identification for. And that's fine. It is what it is. If you just make the request and the data's not there, it's not there. There's not too much we can do about it. But again, I thought this data set was pretty relevant and pretty interesting because you get things like shot zone area, shot zone basic, location X, and location Y. And I'll show you in just a second why that's important. And you can see how this data set, again, is expanding even more. And that's why it took a while to run. So I'm not going to rerun it in this instance right here, but I would invite you to do it. It's going to take probably a good 30 minutes or so to make all those API requests. You have to go up to the endpoint, make the request, and fetch it back. And then you'll probably have some issues because it can't find some of these players. And again, it is what it is. There's nothing we can do about it. But this data, I think, is very, very interesting because you have things like the shot type. So we have 2-point field goal, 2-point, 3-point field goal. And then you'll have like descriptions of the shot, right? So here's a layup, step back jump shot, alley-oop, and then a shot made or a shot missed. So this is pretty cool. And then you'll have the shot zone area, right? And then you'll have the distance from the net, less than 8 feet, 24 plus feet, 16 to 24 feet. And I would imagine, because there's so many of these, we have 42,580 for the season, right? For all these players. Now the data set is getting pretty deep in terms of the number of rows. I would imagine that the NBA has some kind of sophisticated camera setup where all this is automated and it's just constantly capturing the distance to the basket. Was the shot made? Was it missed? Was it made? Missed, distance, and who's doing the shooting? The players. The technology must be pretty sophisticated. I can't imagine that people are doing this. The cameras must be capturing the player based on the jersey number, right? So it's identifying who made the shot. Was the shot made? Was it actually missed? Where in the court they were, how far away. And when we get data like this, we can do some pretty cool XY coordinates, like any kind of two-dimensional space. The X is going to be horizontal, the Y is going to be vertical, right? And you can do an XY plot so you can see the horizontal, any kind of thing can be plotted in 2 dimensions, right? Like bell curves are very common, any kind of time series analysis where the time would be horizontal and the up and down movement of whatever you're analyzing would be vertical. This, we're going to look at the shots made and the shots attempted on the courts. Okay, so when you go ahead and run this, and once all the data is loaded in from those 4 API endpoints I showed you, it's pretty quick and easy to run the rest of these. So this one, I actually created a shot chart to denote where the player was on the court, okay, who's making the play, and then you go over here. It's going a little bit slow. Okay, and let me, sorry guys, it's going a little bit slow here. Why is it? I think it's just freezing up for a second. And okay, here we go. Yeah, it just took a little while to respond. I guess it fell asleep or something. Okay, I'm tired too. I'm tired. Take a little nap after this one. So anyways, this is pretty cool because you can get the distance right over here, right? So that came from the previous data set that I just showed you. Made or missed. Red is going to be missed. Green is going to be made the shot. Okay, kind of like the stock market, like red is bad, green is good, right? This is kind of the same thing. Red is bad, green is good. So you want them to make the shot. And if you zoom in, it's pretty cool. You can see all the spaces on one side of the half court area where each shot was made or missed or attempted, right? At least attempted for, and the distance to the bucket, right? So here's 22 feet, here's 21 feet. This should be just about the same, 21, 21. Those are pretty close, right? This is about 21. And all the reds are misses, right? And all the greens are made. So this is a Plotly chart. I came up with this idea based on this over here. I like this image a lot. I saw this online yesterday. I tried to replicate that. There's a few of them over here. If you go searching for NBA data shots or something, like, oh, here it is, NBA shots data half court. So they have these sophisticated cameras that take all these images of each player and where they were in the court, made the shot, missed the shot, so on and so forth. So I found these charts and I thought this is kind of interesting. Like this one over here, it's kind of cool. It's basically like a density-based kernel chart, okay? And they created a small drop-down control so you can select who you're focusing on for all of these shots. Right now, this guy right here, Colin Castellon. So I'm not a huge NBA person. I don't even recognize some of these names, right? But it just came from the NBA data. So I'm guessing um, some of these players, I'm guessing all these players are real players. And some of them I don't really recognize the names. I was looking for like Steph Curry and LeBron, but I don't see them. But again, like I didn't get every single player, right? It takes quite a while to get all these players. I think I took a sample of 250, so it's definitely possible that like some of the players are missing here. But if you want to go back and get all of the players, by all means, you can certainly do that, right? I'm trying to take a smaller subsample just to demo how this code works and to show you a couple key points for NBA analytics. But this is not a comprehensive list of everything in the whole NBA universe, right? And let me go back. Just let me get a couple more of these guys. Jake La Riviera. All right, and then again, you can say, so this one's pretty far out, 45 feet, missed, 42 feet, missed, but most of these, pretty close to the bucket. These guys are hitting a lot of these things, right? So I thought that was pretty cool. Again, just trying to replicate this chart that I saw over here. And that's what I love about Python too, right? So it's pretty flexible, pretty scalable. You can do all kinds of cool, interesting, useful things, adding a drop-down control just to filter out what players you're looking at, adding a realistic basketball half court, the position from the bucket, made the shot or missed the shot. So you can do some pretty cool analytics over here, right? So I just wanted to showcase that. And what else do we have? Oh yeah, so points and points per game. Okay, so just with some basic math over here, we can get all the DF players. And by the way, maybe I skipped a step over here. If I just go back, I can do Control F to go back here for all players. This was the shooting area that I just showed you with each player. And if I go back here, DF all players, looking for the first instance, I can scroll up here. And the first time I was using this is right here, right? Oh, so yeah, so this comes from all players. And then I did a simple merge to get all these data frames combined, MERG. Just if you want to see how this works. Okay, so when you get this DF sample players, that's the data frame we were just looking at, DF personnel. This is stats like height, weight, age of the player, right? When you merge these two together, you have DF final, and then everything comes together in this big universe that has all the data, right? So all the stats on the players, the stats on the shots made and attempted, and attempted, made, attempted, missed, things like that. Height, weight, age of the player, things like that. So merging together all the data frames really gives you a very rich source for doing all of your analytics all in one spot, right? So I think, where did we leave off? Oh yeah. So here's the shooting area with the individual players shooting. Here's points per game, okay? And I'm sorting this. You can see sorting in ascending order. You only have ascending. You don't have ascending and descending. In some languages, you have both. In this Python language, I believe it's just ascending equals false, right? Do they have the do they have descending? I think so. No, they don't. Okay, so ascending equals false or ascending equals true is the same thing as having descending, right? So if ascending equals false, it's equal to descending, and we're in descending order. So the higher number is at the top. That's how that works. Okay, so you have the player name and then the points per game. So you can see that easily these are the top 3 players. I'm listing the top 10 just by getting all the data and taking the head of the top 10. Remember, a few minutes ago, I showed you the data frame. You can leave this blank and you'll get 5, right? So here's the top 5. If you add in the number there, then you get the top 10 or the top 20 or whatever you have. Top 50 if that's what you want, all right? So refresh the data frame, you'll get the top 50 players by the points per game, right? So that's how that works. I think that's pretty cool. I did top 10, right? Top 10 is good. And then you have the bottom 10 over here. So points per game, bottom 10. I'm guessing these guys didn't play, right? Or they're seriously underperforming. So I'm just guessing that the players in place. So they have 0 points per game. But these are the top scorers over here. Points per game, PPG. Then down here, so I'm merging 2 more data frames together, DF players, and it says sample because it's not all the players. Remember, I'm looking at, I think it was 250 out of the 500 plus NBA players, just because it takes a long time to run the code. If you want to get to 575 or whatever it is, 550-ish, go for it, right? If that's what you want, just change that flag in the very first data frame, very first cell where the code sits to get the players. So I'm doing the merge here on these two. So DF personnel, remember that has height, weight, age, things like that. And the players based on player ID. Now you could do it based on the player name. You could merge based on player name and it's probably totally fine. But we tend to use IDs a lot in the data science space just because the ID is a very unique number. I suppose two players could have the same name. They would definitely have different IDs if they had the same name. Now, this is probably not the case. I don't think there's anyone in the NBA playing now that has the same name as any other player, but I suppose you could. But that's why we have IDs, right? So every ID is going to be unique, even if by chance two players happen to have the same name, right? Maybe it's two Larry Birds, maybe it's two LeBron James. Highly unlikely, but we would do the merge based on the ID just in case that did happen someday. Who knows, right? It's a crazy world. We could have two NBA players named Steph Curry someday. And then we have the player name. So I thought this was an interesting analytic data point or analytic perspective, player name, and then height, and then the points. So it seems like height and points is kind of correlated, although not necessarily, right? This guy only has 75. This guy's 1357, and this guy's actually taller, right? So maybe as you get taller and taller, maybe it doesn't work out, doesn't correlate to maximum number of points all the time. And look at this guy, he's 7'1", has 0. Now that might be a data quality issue, or he's on the bench a lot. I'm not sure. But anyway, yeah, I don't know. I didn't touch any of this data in terms of changing it. So maybe that is a data quality issue, or the guy maybe he was injured for the season. He was out for the whole season. I'm not sure. But anyways, that's an interesting talking point. Like, why is this 0, right? So if we're doing this, in a professional business setting, that's something that we would look into. Why is this guy getting 0.71? He's dominating in terms of height. Is he just getting no game time or what? I'm not sure. So moving on, here's a couple more things I thought were interesting. Points per game broken up into different buckets. So based on tallness, and this is our range here. So we have 4 buckets here: short, average, tall, and then very tall. And we have these ranges. So there's range 1, 2, 3, and then 4, right? So you have 5 numbers, but like 4 buckets or 4 ranges because you have the beginning and the ending. Then you have these ones in between. So short, average, tall, very tall. Points per game. For very tall, again, it kind of decreases a little bit, and we kind of saw that over here. For very tall, right, points per game goes down a little bit. This guy's pretty tall. He has a bunch of points there. Tall, pretty high points. Tall, not so many points. Tall, none points. And then as you're going down a little bit in size, actually the number of points on average increases, right? And you see the same thing corresponding over here. So tall gets quite a bit of points, average a little bit less, short a little bit less, very tall kind of dips down less than the short guy over here. So maybe the short guys are hustling a little bit more. Maybe the tall guys are a little bit less coordinated. Who knows, right? So this I thought was interesting too. Here's player name and then points per 36 minutes and then points per minute. So this guy leads the pack right here, Giannis Antetokounmpo. And honestly, I don't even know who this guy is, but points per 36 minutes is pretty high up there. So maybe he's like it's like a dominating guy. That's why 31 points per 36 minutes, and then points per minute. He's coming out number 1, 2 over there. And Steph Curry, so he's number 2 actually. So just under the number 1 guy, and I certainly know that guy, right? So Steph Curry. Let's go over here. Let's see. Steph Curry, yep, of course, right? So he's a dominant player. So a couple more things I thought were interesting. The top 5 by points per game. So player name, points, and then points per game again. So you have different kind of metrics. So I was looking at the points per 36 minutes, right, for 2 halves, points per minute, and then points per game. PPG is points per game, right? And then broken up by buckets again. So tall, average, short, very tall. So again, that kind of like dips down a little bit. So we saw that before. And then I created a chart. So we're looking at df final, again, is the data frame that we pack everything into, doing those merges that we saw before. So the personal statistics, all the shooting percentages, shots attempted, shots made, things like that, right? So we combine everything at the df final, and we're looking at the age and then the number of points, and the color of the chart is based on the height of the player. So you can see over here, some of these players are a little bit older, 34, and some of them have pretty high points per game. So 19.56, this is 22. Oh, total points. Sorry, these are total points. And then the height, and then the age of the player, really. So it's really all over the place. There's not a whole lot of correlation between these types of statistics. Here it is in terms of different perspective now, season experience. So how many seasons has the player been in the NBA, and again, points on the y-axis. So you pretty much see this universally. The numerics would be on the y-axis, and then the distance or the time or something like that. In this case, age and season experience is the x-axis. So it's a pretty normal way to display your charts, right? Here I created a 3D chart. So I think these are pretty interesting. It does get a little bit confusing, right? So you have to kind of make sure that this type of chart is appropriate. I've seen this used. Sometimes it's appropriate, sometimes it's not. So this is a guy, couldn't really pronounce his name before, and I still can't now. Giannis Ant. Let me call him Giannis Ant. And we can see in terms of points per game, he pretty much dominates, right? And that's exactly what we saw back here, right? So points per game, 30.4. We see the same thing in this 3D plot down here. Right? And it's just over 30 points per game, 30.4. So same thing, 30.43, same metric. You can see he pretty much dominates. I think this chart is interesting, but you have to be careful with these 3D charts. It can get very confusing too. So you have, if I zoom out, you have the height sort of on the depth of the chart over here, the age on the x-axis, and then the weight of the player on the y-axis, right? But of course you can change all these and flip these around to be kind of a different perspective. So I think this works, but it gets very busy and very convoluted. So when you're working with these 3D charts, you have to kind of be careful. So I think it works because we have this number one player down here, and that's pretty easy to visualize and pretty easy to see it. But if all you had was like a bunch of greens and navy blues, I don't think this chart would be very effective at all. It'd be more confusing than illustrative. When you use any kind of plot, you want to tell a story, you want to illustrate the point that you're trying to make, right? You don't want to confuse your audience, you want to enlighten your audience. So if you're doing that, any chart is great. If you're using a chart that's mostly confusing and not very educational or not very informative, then that chart is kind of wasting everybody's time, right? And it's hurting more than helping. So I thought that one was pretty helpful. Then I came up with a couple custom metrics down here that I looked at. So shooting efficiency, looking at field goal percentage, 3 points, and then attempts, and then the EFG, and then plotting everything over here. So we have the player name and then the stats in each player. This is rebounds, assists, and defensive stats. So again, just looking at these different statistics, kind of different perspective over here. And then we have the DF final with the player name and usage rate. So this is basically, I had to do a little research to figure this out. This is how useful the players are, how much they're used on the court, right? So I thought that was kind of interesting. I want to share that with you guys. And then we have just another cut of the data down here. So player name, points, assists, rebounds, blocks, and then the cluster that I'm assigning these to. So you did like a small K-means clustering exercise down here to assign different players to different clusters based on these stats right here. Okay, so you always scale the cluster, right? So you get everything that's kind of like off on one side or like an outlier, and you kind of scale it down to the same relative metric or measurement, right? So everything is kind of like clustered together. Because if you don't do that, if you have a couple of extreme outliers, it's really going to blow up your cluster, and it might do some weird things that you don't want, although maybe that's what you want too. It really depends on what you're trying to achieve. Sometimes you want to keep those outliers as outliers. Sometimes you want to pull them in to the rest of the group. It really depends on the type of analysis you're trying to do, right? If you're doing an analysis just to find the outliers, then of course you want to leave them alone. If you want to consider the outliers with the rest of the group and make that homogeneous instead of heterogeneous, then you would do you would scale the whole group and bring everything together on the same relative scale, right? So just a couple more metrics down here: points per game, steals, rebounds, blocks, things like this. This is the overall composite performance. So I created this based on a few different metrics, the points, field goals, assists, things like that, and got the composite performance overall, top 10 players, based on all of these metrics combined, right? So you see Steph Curry a little bit lower down here, right? So when you analyze the data this way, this guy actually comes up on top. We sorted this guy as the number one on some of those other metric scales that I used before. So this time, if you slice and dice the data a little bit different, now he comes in the number 2 position, and Steph Curry typically is like the top guy in the NBA, but here he's down 1, 2, 3, 4, 5, 6, 7 in 7th place. He's not the number 1 anymore, right? But it really depends on what you're trying to achieve and what you're trying to accomplish here. This composite performance, I think, kind of makes a lot of sense here. And then the compromise is that Steph Curry isn't number 1. And a lot of these charts, the way you look at the data, he comes out on the top, right? But this way he is not. And then down here we're looking at the top 10, the bottom 10, right? So here we're taking the head, we're getting everything from the top. The top is like the head, and the tail is the bottom. So this is the bottom 10 sort of worst players. Maybe worst isn't a good name, but not best. You can call them not best if you don't like worst. But these would be like the top 10 best players. These would be the top 10 not best if you want to be a little bit courteous about that, but basically these are the worst. Okay, so that's it. That's my findings on the NBA. If you guys like this stuff, leave some comments. I could do NFL, Major League Baseball, hockey, things like that. I kind of get into sports. I'm not a huge sports nut by any means, so some of the stuff I would have to do my due diligence and research and analyze before doing a deep dive into this. But I thought it was pretty interesting and pretty useful. So if you guys like it, let me know. That's pretty much it for NBA Performance Analytics. I'm going to wrap it up now, and I'll see you guys in the next one. Bye. Hey there, guys. My name is Ryan Schewel. Welcome to my data science channel. So in the project today, I want to take you through the ins and outs of supply chain management, and we're going to look at an example of supply chain bottleneck, where you get into a spot where the supplies, the raw materials, whatever you're shipping, just can't go, and there's some issues, and you have to try to manage that efficiently and effectively, and actually try to predict what kind of issues could disrupt your supply chain, right? So you want to minimize the risk of disruption and have a smooth operation. That's the whole point here. So why does interpretability of a model matter? We're going to look at a couple examples of doing the modeling and then how to interpret the results of the model. It's actually very important because this enables us to debug and improve the model to help it make accurate predictions. And if it's not very accurate, we can tune the model, we can add hyperparameters and things like this to improve the performance, or we could just test a different model, right? There's about probably 44 or 45 regressors at this point, and about the same number of classifiers, right? So if one model doesn't perform well, we can plug that one out and plug in a different model, or again, apply hyperparameter tuning or performance improvements, tweaks to help the model to make better predictions. So bottlenecks are disruptions in supply chain, and they can come from overall inefficiency in the system. Common causes are shipping shortages, container scarcity, port congestion, things like this, right? Labor shortages, factory workers, drivers, warehouse staff boycotting the job, right, or walking out. Things like manufacturing delays, raw material issues, unavailability, quality materials. It could be poor quality, and they have to destroy the batch and remanufacture. All kinds of things could disrupt the system, including external shocks, right? Things that we can't even really control. We can try to anticipate it and try to work that into the model and try to make predictions into the future based on external shocks. But these are more like strikes, tariffs, geopolitical conflicts that we really can't control, right? This is beyond our control. So let me import the data here and show you how this works. Control Enter to run. Okay, and the source of the data comes from over here. I give you the source right here. So if you're looking for this data that comes from there, you can copy and paste that link into your browser and download the CSV file, and you'll have everything you need. So this is what the data looks like. We have product type, SKU, what is this? Availability, number of products sold, revenue generated, customer demographics, stock level, lead time, order quantities, shipping times, so on and so forth, shipping carriers, shipper, supplier name, location, and what else we got over here? Production volume, manufacturing lead time, manufacturing costs, routes, and overall costs. Okay, so pretty basic. I can go ahead and do some EDA. This is exploratory data analysis. This is looking at different carrier A, B, and C. So believe it or not, this is what the shipping characters are called. You think they would have something that's a little bit more definitive, some name that actually describes who this is, but this is how the data comes to us. So we're just using what we have. So shipping carriers, and shipping times, right? So the y-axis is measuring the shipping time, like how long it takes to move the raw materials around. That's the shipping time, and then this shipping carrier comes from here, right? And we're looking at box plots, so we can see the longest shipping time here for carrier B is 9, a max of 9. That could be days, it could be weeks, it doesn't specify. The minimum is 1. I'm guessing it's probably weeks. We have the Q1 and Q3. So Q1 is 3.25. So about 1/4 of the material shipped come in 3.25, let's say, weeks. Let's say this is international shipping, 3.25 weeks. Sometimes in Q3, it can go up to 7, and the max again is 9. So these box plots are really nice. It shows you the distribution of the data, and given the highs and the lows too, right? So again, the high over here is about, it's kind of hard to read. I think that's a 10 that I see, and the low would be 1. This one's a little bit easier. This is 10. I can see that. And the median is 7, and minimum is the 1. Okay, or the minimum is 1. So supplier name, again, very generic supplier, 1, 2, 3, 4, 5. We're looking at average cost by supplier, and the plot comes from here. We're getting the average cost, putting that into the box plot, or into the bar plot. The first one is a box plot, right? This is a Plotly box and a Plotly bar. So in the first case, we're just using the raw data frame. This is DF for data frame. It comes in with shipping carriers and shipping times natively. That's given to us. If we want to look at the group by supplier name and get the mean cost, we can use that for average costs, and then we have supplier name and costs built in there, right? So that's how we get the bar plot and the box plot. So let's look at the first model here. I'm going to hit Control Enter to run it, refresh it, and make sure everything is fresh and loaded into the system. So I'm going to look at the independent variables. Anything for the features, the X features are independent. This comes from DF encoded. We have to encode all the variables because some of these variables are not numeric. Anything that's numeric can be fed into model, just as is. So anything like availability, number of products sold, revenue, price, this cannot be fed into the model. We have to convert that. Okay, anything that's not numeric. So carrier B, supplier 3, Mumbai, these all have to be encoded either using a process called one-hot coding, or label encoding, or what's the other one? Categorical encoding, right? So it's 3 ways to do the encoding. I have a video about that: one-hot coding, label encoding, and categorical encoding. So anything that is a number has to be encoded, and this is the dependent variable that we're testing to make predictions on. This is the overall cost to ship the materials. Okay, so we want to understand how much does it cost and what is the overall bottom line expense to us if there's a bottleneck in the system and it causes our supply chain to to be interrupted or to be disrupted, whatever you want to call it. So I'm using a random forest regressor right here, training, testing, model. Here's my model. I fit the model. And then based on that fit model, I'm just calling it model. It could be RF model, doesn't matter. Control F, I'll show you where this goes. So we train, test the model over here, fit it, and then call the model, dot feature importance. Okay, we want to look at which features have the most significant influence on the dependent variable. So which of these independent variables above over here have the highest statistical influence on the dependent variable? Again, the dependent is cost, and the dependent is cost, and the independent is everything else. Okay, so when I look at this, I can't tell like what is driving the cost. Is it route? Is it product type? Number of products sold? Lead time? Manufacturing cost? So on and so forth. I can't tell, right? But the model is going to tell us. So we look at the feature importance. We're trying to predict the statistical influence on the target variable, order quantities actually has an influence on the cost 14% of the time. The next biggest feature importance item here is lead time. The third would be shipping costs, production volumes, and manufacturing costs. And these have the least impact on the cost of the product. So product type, inspection results, shipping carrier route, and supplier name. So yeah, it doesn't make sense that the supplier name would affect the cost to ship the product. I think I can figure that one out. But the route actually doesn't have much influence either. I did not know that. And the shipping carrier doesn't have much influence either. So you know that these are pretty I guess negotiated prices. Like all these carriers have very similar costs. Otherwise, if the cost of the shipper influence the cost of the product being delivered, this would be at the top of the chart here, right? So all these costs for all the shippers that we're using, what did we say? It was three, I think, or three carriers. So shipper is different, I guess. But what's the shipper over here? Let me look at it. Shipping carrier. Oh, A, B, and C, right? So A, B, and C, they have pretty similar costs, right? This is the shipping time. It doesn't show us the cost over here. That's fine though. Average cost by supplier, these are all pretty similar too. Okay, so the cost is not a big factor on the total cost for this for supply chain network. So now we have some information. We can start to make some very intelligent decisions, right? But we want to look at the model and have the model explain to us what's happening, right? So we're going to learn from the model what's going on here, because I can tell you from experience, the random forest model is really a black box. If you look here, we're using random forest regressor, again, to try to predict the cost for this supply chain network to ship the items, right? So when everything goes to this random forest regressor, what this model is doing is taking every possible combination of every feature, slicing and dicing it every possible way, and looking at the outcome of the influence on the target variable, which is the cost, right? So it could be the first two columns, the first and the third, the first and the fourth, the first and the fifth, and it goes through all those columns, and then the first, second, third, right? Second, third, fourth, fifth, sixth, things like this, right? So it takes, and then 1, 2, 3, 4, and 1, 2, 3, 4, 5. So you look at every combination and see which combination of those features are having an influence on the cost, right? But to break apart that model and understand under the hood what's really going on is actually kind of complicated. There's a few things you look at called Gini impurity and entropy, and is the impurity decreasing or increasing? If it's decreasing, the model is learning better. If it's increasing, the model isn't learning quite as well, right? So you can have a couple of parts of the model that you can sort of like pull apart and analyze, but overall, it's very hard to tell what the random forest model is doing, right? So we want to take a different approach and look at two methodologies to help us determine what's really going on with this model, right? So we're going to look at SHAP and LIME. Basically, SHAP stands for Shapely Additive Explanations, and SHAP draws on cooperative game theory to assign important values to each feature. So like we saw before, this is feature importance. How important is this feature to predict price? This has 14% influence on price, right? The lead time here has an 8.5% influence on price, and this has about 6.9, almost 7% influence on price. So we can see that, right, for the feature importance. That's kind of how SHAP works too. It's looking at the important features to drive the target variable, right? And what has a statistical impact on that target. So it's like determining each player's share of team success. This is using a concept called game theory. And SHAP provides basically a global overall model behavior and then local or individual predictions based on insight, making it very versatile, right? So we have the overall model behavior and then the individual predictions for each feature in the model. Okay, so an example would be a credit scoring model. SHAP might reveal that a customer's income contributes 40% to the credit score, but the credit history accounts for another 30%, right? So this kind of insight or clarity can help loan officials understand and explain and make accurate decisions about which customers to do business with, right? You don't want to do business with somebody that's going to apply for a credit card, take your money, and then never pay off the balance of the card, right? You want to make sure that the person is going to repay. If you know 40% is based on the person's credit score and 30% is based on credit history, now you're 70% close to understanding what is driving that target variable, right? So that's how these things work. The strength is consistent and mathematical rigor based on Shapley values from game theory. It's model agnostic, right? So it works in any model in the machine learning universe, and it offers rich visualization like summary plots and force plots into intuitive understanding plotting system, right? So we'll see like a vertical plot in the layout and then a horizontal plot in the layout of that. Okay, so I'm going to go ahead and run the model, Control Enter. We have the XGB regressor now. So this is XG Boost, a little bit similar to the random forest regressor that we saw before. The difference is this is a boosting model. That's why it's XGB or XGB booster. The other random forest is an ensemble, what's it called? Booster, a bagging model. That's a bagger. So you would take everything and run it in parallel. That's how the random forest works. Everything is done at the same time. With a booster, you try one model and then take the best results from that, move it into the next model, take the best results from that, move it to the next model, and so on and so forth. So in both cases, you would run through a bunch of models. That's why they're ensemble. But one boosts everything up to another level. That's the XGB. And one bags everything together at the same time. So we have the model here. We fit the model. And the model is going into Shapley Explainer. And we can see here the lead times, locations, shipping costs, routes, and prices. All of this contributes, again, to the ultimate cost of making the shipment. Okay, so you can see the vertical layout, the lead times, location, shipping costs have the highest influence. The lowest influence is supplier name, manufacturing costs, and inspection results, right? So down here you see the name, right? Inspection results and product type. And you see inspection results, manufacturing costs, and supplier name. So where's supplier name over here? I don't see it. Oh, here. So it's toward the bottom. And like I said before, like, well, why would the supplier name influence the cost of the product? Really, it doesn't, right? Unless maybe you're dealing with a big brand product like Prada or Louis V or something like that. But that would be more like the manufacturing name. Like the supplier name really doesn't really matter unless Louis V does supplying too, and you're paying a premium for that. So the name of the shipper, the supplier, doesn't add anything to the cost over and above what other shippers would add. So basically the horizontal axis impacts the model's output. The further you are from zero, the greater the impact, right? And there's a left and the right side too. So on the right side, you'll see more reds. This feature increases the predicted cost. And on the left side, you see more blues. These features lower the predicted cost. So everything on the left-hand side of this axis, it splits this in the middle, is going to lower the cost, right? That's the target variable that we set over here. Okay, and everything to the right of this line that splits everything in half is driving up the costs on this side. Okay, so that's how you interpret the model. Again, blues have lower feature values, reds have higher feature values. The lead time is a top feature. The blue is a low feature, and the red has high feature value. Okay, the lead time is a top feature. Blue dots have short lead times, and red dots have longer lead times. So this is more neutral or slightly positive. This can have a negative SHAP value. So again, the blues on the left are going to pull everything to the left. On the right, it pulls everything higher to the right? So lead time, location, shipping costs are the top three. We see that lead time, location, shipping costs. Some low values, blues, reduce the cost, while other red values increase the cost. Shipping costs, higher shipping costs, reds generally push the prediction up. Right, and lower shipping costs pull the whole thing down. The costs are lowered, right? Round out the top ones over here, routes, price, and order quantities. I think that's it. Routes, price, and defect rates actually comes before order quantities, but they're pretty close. Probably substitute one for the other. So again, some routes likely encoded as red values are going to be more expensive. The blue values are going to be less expensive. Higher prices are going to be red, sometimes increasing overall predicted costs, like what else? Shipping routes. If you take a longer route, it's going to cost more. You burn more fuel. If you pay more for the fuel, that's going to drive up your cost too. Okay. And then order quantities. Higher quantities usually increase costs, right? If you order a couple items, that's probably not going to cost too much to ship. If you order a couple thousand items, that's guaranteed to drive up the cost of shipping, right? So pretty intuitive. Now, let me see. This line, guess actually, I'm looking at this right now. I think this actually goes in the next section. So let me cut that out. Oh, that goes there. This goes here. Okay. Okay. I put that in the wrong spot. Let me fix that up. And I don't need this. Okay. So we got the first part of SHAP done. Now we're looking at SHAP waterfall. So this would actually look kind of like a cascading waterfall, believe it or not. So we have the top value 529.24. You can see this at the bottom. This is E of f of x. F is a function of x, and E is just the variable that we're using here. So 52946, this is a baseline prediction. This is the model's average output across all training data. So the average cost for everything and the whole like system here is $529. As I say, with the unit is probably per ton or something like that. I'm not sure exactly because the data doesn't specify. But let's assume 529, about $530 per ton to ship the product. The f of x is at the top. It's 187.52. This is the final prediction for this particular observation. Okay, so again, we have the local predictions right here, and we have the global predictions. So the global would be 529 or 530. We can just round it. And then for each of these individual items here, these different features, it's about 187.75. That's what it is. Okay. So the plot shows how each feature pushes the prediction from the baseline to the final value. So we have some things that pull up the feature 0.43, 21.78, driving up the cost. We have a lot of features here pulling down the overall cost. So we go from 529 that actually revenue generated is offsetting some of the costs. Shipping costs is offsetting some of the costs. Maybe they're what would that be? Like you have a network that you work with or a partner that you work with, maybe that offsets the cost. Customer demographics is dragging down the cost. If I see this route is increasing the cost, availability is decreasing, price, location, defect rate, and lead time is decreasing a lot. So we go from 529 to 187 when you look at all these individual contributing features here. So basically, the lead time drags down the cost a lot, pretty substantially, like 126 over 529, almost about maybe 20%. So essentially, this is telling me if you have enough lead time in your order, you can pre-order everything you want and save yourself from paying a higher premium at the end. And then you have to pay a lot more because you're in desperate need of these products and your warehouse is running so low on these supplies, right? So if you plan ahead a couple of months, maybe 3 or 4 months, and you can build up the inventory in the warehouse, you could save $126. Again, this is making an assumption per ton because you anticipate the need for these products being sold. So that's another part of the business. We're looking at supply chain. But if you work with forecasting or pricing or something like this, and these guys collaborate with your team because you're on the supply chain team, they can say, okay, we can forecast this revenue, we can forecast these prices, we can adjust the prices and move more inventory. Then the supply chain guy has to say, okay, I can get 4 months worth of inventory. I have to put in an order quick though. I have to get it now, and it's going to save me $126 per ton. Okay. So this model right here, the SHAP model, is really breaking apart the random forest model and showing us how all these influences contribute ultimately to the cost of the product, right? When I look at this, I don't get any kind of story like that. I don't have any background, any insight. When I look at random forest, okay, it's telling me feature importance. That's very useful. That's helpful. But SHAP is really exposing what this model is doing, right? Because it's showing you all the details, all the features from a global perspective and from a local perspective, right? These are all the local features that feed into that model comprehensively, right? So that's it. And then we have the values over here. Okay, we just discussed that. There's 2 positive values, right? Pulling up the cost, but most of these are negative and they're actually pulling down the cost. So it's saving you a lot of money. So despite all the downward pull, Route 1 slightly pushed the cost up, and a few other negligible features added up to less than $1 per ton, right? So that's what we're looking at. The model predicts low cost 187.75 because this product has a short lead time, low defect rate, and is cost efficient. Now, let me see. I think that changed 187.75. Again, making the assumption dollars per metric ton shipped. That's the assumption here. It doesn't specify in the data. That's a reasonable expectation. And location has a reasonable price and availability. has also an impact on the total cost to do the shipping. So that's one model. So we have the SHAP model. We just explored that. Another model is somewhat similar, slightly different. It's called LIME. This is local interpretable model agnostic explanation. So like the first one, Shapley is model agnostic, LIME is model agnostic. Doesn't matter which model you feed into it, it can handle it, right? It can handle the input. Like what's agnostic mean? It doesn't matter what is underlying. Email could be agnostic to a PC or to a mobile phone or to a Mac. So it doesn't matter if you log into your email on a Mac, on a phone, or on a PC, you can access your email. It's agnostic to the tool that you're using or the device that you're using. Okay. So Lime takes a different approach, somewhat similar but kind of different, focuses on individual predictions by approximating the complexity of the model, okay, and making interpretations like a linear model in the vicinity of the prediction. It's like zooming in on a single decision to see what tipped the scales in your favor or in your disfavor, okay? So for a neural network predicting sentiment of customer reviews, sorry, I have to get my ice water or my throat is going to explode. I don't know why I have all these throat irritations constantly. It's very hard to talk, but it is what it is, right? So to understand what a neural network is doing is extremely complicated. That's even more complex, more of a black box than the random forest model, right? So you really need a model like SHAP or LIME to expose what the model is really doing, because it's a black box. You don't know. You have your inputs, you have your outputs. You have no idea what's going on in between all the neural network connections, okay? A little bit like the human brain. Like you have inputs through your eyes, through your ears, through your nose, touching, feeling, tasting. Those are your five senses, right? And your mind is processing all that information, and then you can have some type of output. Like you could taste ice cream, right? Your mind is making a determination, and your brain can form a coherent thought, and then your mouth speaks. This is delicious ice cream. This vanilla with Reese's peanut butter cups mixed in is delicious, right? Like what's going on in your brain to form the tasting and the sensations in your mouth, and then come out with a final report on that ice cream. There's a lot of stuff going on, but it's very hard to understand and interpret all the nuances of that, right? It's a black box. The human brain is a black box, and these models are the same. You can't understand what the model is doing. You take the output, and if it looks reasonable, you accept it. If not, then you test a different model, right, and get away from the black boxes. But you have to have a lot of confidence that this is doing what you expect it to do. But the upshot here is that the line model and that the SHAP model will help us expose the inner workings of that and understand what the model is doing on a more granular level. So model agnostic, ideal for explaining individual predictions such as fraud detection or text classification. Okay, also great for easy implementation interpreting, especially for simpler models. For more complex models, it'll handle it as well. But simpler models are just going to be easier to understand and to explain to your customer base. The limitations can be unstable due to random sampling during perturbation. This is like the ingestion of the data and the model doing all its work. And it's less effective for highly complex models where local approximations may oversimplify what the model is actually doing. Okay, so let me go ahead and run it, Control Enter. So the X comes from the original variable that I set over here. So remember, with SHAP, we're feeding in the model, we're testing the model over here. This is XGBoost. The X comes from the F encoded. So we're taking that X variable. This is all the independent variables. Remember, the original X variable comes from here. Okay, we're encoding all the features. Features goes down here, right? So this is flow. You have to look at the flow here. This is XOR features. I'm calling it features. This is almost the same thing. This is target. So now, again, we're using the features or the X. You can call it whatever you want. Typically, the naming convention is X. We set the X over here. Look at the I location. This is the index location of I. And we're looping through all the different rows of features, or not rows, different columns of features, right? So we're making a prediction based on each one. We see the predicted value over here is 187.75. And 90.61 is the max. So the minimum is 147.13. The the average or the most likely, I think, is 187.75, and the max is 960. Again, the assumption is this is dollars per metric ton to do shipping. We're trying to predict the cost, right? So the line is telling us the summary of the top left box, 581.59 is the predicted cost. So where's the 581? Let me look over here. I think it's changed a little bit when I ran it. So I'm going to put 960. This is the max, really, 960. And the min is 147, 147, and the most likely is 187. Okay, so I fed in some more data before I tested it, so these numbers come out a little bit different. 187 is the cost. The minimum 147 and the maximum cost per metric ton is 960. The orange bars show how close the predicted value is to the upper bound. Okay, so again, kind of like the shop, the positive is on the right side, negative is on the left. And with the shop, you have the right, or the red was on the right rather, and then the blue was on the left. Now we have orange on the right and blue on the left. So kind of similar, a little bit different. On the left panel, you see features sorted by their influence on the prediction variable, right? So we have some negative influences. Location and defect rates are pulling down the cost. Routes and order quantities and customer customer demographics or something. I'm not sure. That's getting cut off. Oh, demographics. I see it over here. Customer demographics are driving up the cost. Shipping costs and availability of products is driving down the cost. Inspection results and lead times is driving up, or lead times greater than 25. That makes sense. 25 days, or this could be weeks. I'm not sure. We don't have the units. Greater lead times are driving up the cost. Lower lead times are saving money, right? So it's pretty intuitive. This is pretty nice how this works out. So the largest driver of predicted cost is large order quantity, right? Do we have order quantity? And we see that here. So I'm going to get rid of this 0.96 because I was doing a different experiment before, but it's the same concept, right? High lead time and manufacturing lead time also push up the cost. Do I have that 29? I don't, so I'm going to get rid of the numbers just to make this more generic. Probably talking about days there. However, short lead times for the delivery and low shipped costs help reduce it, right? So that makes sense. That's pretty intuitive. This is saying low defect rates and reasonable shipping time also suppresses costs. That makes sense, right? Totally makes sense. This is totally intuitive. Now, on the net, the upward factors outweigh the downward factors, landing the prediction at net. 187. Okay, so I'm going to put that over here. Running a different process before, so the numbers are all different, but the concept is exactly the same. Okay, so now I want to look at the SHAP values. Again, using X columns, these are all the columns of the independent features. Remember, the independent features was everything that we used to predict the cost. And we're looking at SHAP values greater than 1, anything that has a very low influence on the target variable. I'm not too interested in that, but anything that has like at least 10% or greater, that could impact the target variable. Let's look at it. If it has a 1% influence on the target, I don't really care. You could look at it. It's probably a waste of time. That would be considered de minimis or of minimum usefulness, right? So we don't really need to get too concerned about that. So anything greater than 10%, we're going to go ahead and do one-hot encoding for that, right? Yes, so we have the product type, price, availability, and so on and so forth to convert everything to numeric. Now we can use a plotly plot to go ahead and look at the intensity of the bottlenecks that can cause a disruption in the supply chain, right? So now we have the bottleneck flags. That's everything over here. These are all the flags. Again, taking binary values to say, is this going to have an influence on the cost of shipping, and try to anticipate what these bottlenecks are going to be and then manage that expectation accordingly, okay? So we see product type has some influence, price, availability, but this kind of scattered all over the place and it's kind of just a mess. So any good chart should answer questions and not generate questions for you. So when I look at this, I'm kind of saying, okay, bottleneck or not bottleneck, everything is binary. We don't need these things in between 0.8 0.6, 0.4, or 0.2, it's a binary outcome. It's a bottleneck or it's not a bottleneck, okay? So there are a lot of bottlenecks here, but where they mostly concentrated, it's kind of hard to determine that. So I would say this heat map is not super useful, but it's good. It's a good first start. But let's see if we can get this into a state where it's just more useful, right? Let's look at the top features here. So we're going to sort everything in descending um, sort values based on bottlenecks flags in descending fashion, right? So ascending equals false is the same as descending. I don't even think they have descending in this case. It's either ascending true, so we're going from high numbers up to low at the top. Descending, the high numbers are at the top, and then you go down to low numbers at the bottom. So ascending equals false is the same as descending. We're getting the top 10, and we're going to run the same heat map. Control Enter to run it, and the subset df, if you look close, it comes from here, right? Originally, we used bottleneck flags. So if I Control F that, you can see the highlight. Bottleneck flags come from here. That's what we produced from that one hot encoding exercise. Now we're looking at the top 10 bottlenecks. Now this is a lot more useful. So we can see product type actually has some influence on the cost to do the shipping, right? So anything that's light over here, anything that's kind of like a tan color, I'm not super interested in. It just means no bottleneck. We don't have to get concerned about that. But any of these dark burgundy things that's colored like red wine, these are bottlenecks that we have to be aware of. So number of products sold, that could be a bottleneck. Availability, again, this heat map just helps us to focus on what's very important here. Lead time, almost everything except for this is a bottleneck. And over here, shipping times, everything but 1 is a bottleneck, right? Over here, everything but 2, supplier name is a bottleneck. Although that looks kind of weird. Like, I'm not sure how a supplier name can create a bottleneck for your supply chain distribution channels, but according to the model, there's some influence. I wouldn't say that's huge. The name of the shipper should not cause a bottleneck, but it must bleed into the target variable somehow. Okay, so moving on here, we're almost done. So basically, we took the top 10 bottleneck items or counts, right, and converting that into a chart that makes a little bit more sense than this. This is just too busy and it's too confusing. This is a lot more useful right here. The production volumes has a huge influence on bottlenecks, and manufacturing costs has a huge influence on bottlenecks. So production volume, so if you produce a lot and then you ship a lot, then you're probably not going to have bottlenecks. If you do production once a year, right, and then there's a stimulus for the product, but it's only made once a year, and you're already sold out and the warehouse is wiped out, then production volume is going to have an impact on the cost, right? So that makes sense. And what was the other one here? So everything has an impact on the bottleneck or creating a bottleneck. Manufacturing costs. So basically, if the manufacturing costs increase, that can affect bottlenecks too. Maybe it's more expensive to ship. It's harder to get the raw materials. It's harder to manufacture this thing. Once it's shipped, it's more unpredictable about the volume that's going to be sold or something like that. So we have to set up another meeting with the forecasting and pricing crew so we can understand that better. So this is just a basic histogram now, or bar plot of all of the counts of the bottlenecks. So inspection results, if there's a lot of inspection results, that's going to slow you down and it's going to take longer to ship from point A to point B. Order quantities, that has an impact, right? So these are all bottlenecks that we can use to predict what is going to impact the cost of shipping. Lead times, production volumes, routes, lead times, again, I see the issue here. Lead time has no S over here, and in this case it has an S. That's a data quality issue. I'm not changing anything here, guys. Like if I was doing this for my boss, I would clean that up and drop the S or add an S onto the first. All I'm doing is reporting what was given to me. So that's a data quality issue coming from Kaggle. Supplier name. Now this one's interesting. I'm not sure how the name can impact the cost and create a bottleneck, but it is coming up as a pretty high count. 54 records are being counted here. So this does have some kind of influence. So to do a deeper dive, I would either myself or I would ask somebody to go and look into this. Like why is the supplier name causing causing some kind of impact on the cost of shipping a product through the supply chain? So the way to do this pretty easy would be a cause and effect or causal inference kind of analysis to see what kind of cause the name has on the cost of shipping, right? There's always a cause and effect. If you have a cause and effect, there that could be handled with a causation model, right? Or a causal inference model. So that one looks a little bit weird, but I'm sure there's a reason for that. The causation analysis would determine that shipping carriers, number of products, product type, customer demographics. So these have less influences on the bottleneck or creating the bottleneck and influencing the cost of the variable, the value. Shipping costs, again, over here, manufacturing lead times and transportation modes. So apparently this is shipping through boats or airplane or something that can have an impact. I'm guessing most of these long distance products are going on boat, and most of these boat costs for shipping are probably pretty efficient. Like they're pretty close. I'm guessing that there's not going to be a huge influence. Otherwise, transportation modes would be way higher on the left, and it would cause a lot more bottlenecks. I'm guessing they just put everything in containers, drop it on a big ship, and that's it. I don't think too many people are shipping by train or by airplane or boat. I think here everything is going by boat. Otherwise, transportation mode would have an impact, and it has almost none. Okay. So that's it. The final takeaway here: you can predict and explain supply chain bottlenecks using real-world indicators, shipping, labor, tariffs. You see the Trump tariffs are kicking in now, so inflation is already up like 2.5%, maybe 3% in the past couple of weeks. You can feel the impact right now in real time. Wealth and worker strikes that can cause an impact on your shipping costs, right? Machine learning for forecasting is very useful for helping us to make these predictions and do these forecasts into the future accurately. Feature importance to identify key drivers and the cost of shipping, right? We saw that. That was the first model that I showed you. They're in the forest and the plot lead result. And causal tools to determine true levers of disruption. Again, like I would use a causal inference to try to determine why that supplier name is having a count of 54 times. This is creating bottlenecks in our system and causing the price to skyrocket up. So that is interesting. I can't totally explain that, but the point of this analysis was not to explain shipper name influence on cost. It was comprehensively to look at everything, everything in the universe. And I think we did that, guys. So that's it. 40 minutes. These things tend to go long. It always feels shorter. It feels like 15 or 20 to tell you the truth, but done a few of these videos recently and they all go over 40. Not sure why. But I want to tell the story, and I think the mission was accomplished. So I told the story of everything from supply chain bottlenecks and making predictions and counting, and then determining what has the influence on the overall shipping cost. So mission accomplished, guys. I'm going to wrap it up here. Thank you so much for your time. Hopefully this was informative and interesting and educational and even inspirational. Try to make it that way. So yeah, I'm going to wrap it up right here, and I will talk to you guys in the next video, which I'm going to drop pretty soon. Thanks. Goodbye. Hey there, everyone. I'm Ryan Schewel. This is my channel, Straight Data Science. Thanks for showing up today. So in the project today, I want to look at optimal price points for a hotel, right? If you raise your rent or raise your rate on the hotel, whatever it's called, rent, rate, I think it's rate. If you raise your rate, you can make more money, but if you raise it too much, you're going to turn away people, right? They're not going to want to go stay at your hotel. They'll say, hey, this thing is too expensive. I'll stay at the competitor's hotel, right? If you lower your rate, you can incentivize more people to come to the hotel. They'll be motivated to stay at your place, and you're going to get more business. But if you lower it too much, you're not going to even break even. You're going to lose money, right? You have to at least break even the same business. And really, you want to make a profit. Ideally, you want to make a profit. So what is the optimal price point to get enough people inspired to stay at your place, right? But not charging too much so they walk away, right? So that's what we're going to look at. So we can maximize revenue, right? The right price balance between room occupancy and profit, and how much you charge. If you don't, you stay empty and you actually lose business. So that's even worse. We're going to look at that, right? Improve occupancy rates, respond to seasonality and special events, segment or target customers, right? We can slice up the marketing effort into different segments and different groups. I used to work at a couple of banks where we would market credit cards. Before I showed up, they would just blast out tens of thousands, maybe 100,000 envelopes to all the people. I saw it in my own building. When I got home from work, they would just dump it right in the garbage, right? It's total waste. When I showed up, we had targeted marketing, right? So we know who to contact, how to segment the market, how to get people to sign up for credit cards if they want credit cards, and all the people that had enough or didn't want a credit card, we wouldn't even bother them with the advertising. That gets annoying. It's called a nuisance, right? So don't do that. Boost competitive positioning. We can do that. Forecast demand more accurately. And for our customers, get fair value, right? Customers love value and they understand value. They know that. They can recognize that. They can identify with that, right? Time booking strategically. We can create knowledge around optimal price points, windows for opportunity. This enables travelers to book more rooms. We can evaluate cost and the overall customer experience, right? And plan travel budgets better. And again, motivate people to stay at the hotel. Raise the price too much, people are going to walk. Lower it too much, and you're losing money. You want to find that sweet spot right in between, right? That's the Goldilocks place or whatever it's called. Goldilocks is a perfect. Wait, what is it? Goldilocks and the Three Bears. Yeah, just right. You want it to be just right. That's what I was thinking of. Goldilocks. Okay. Anyways, okay, so let's go ahead and create some data. Now, I don't work at Marriott. I don't work for Hyatt or any Radisson or any of these hotels, so I don't have their data. If you work at a hotel like this or any business, you can use this economics for any business. I have several videos on my channel about how to optimize price and get more revenue from your customers and create more satisfaction for your customers, build your business, right, and build your brand too. So I have several videos on my site about how to do this. I don't have Hyatt data. I don't have Radisson or Marriott data, right? So I'm going to create this. So that's what I did. I have holidays here. So around the holidays, I would expect a little spike in the business, right? People are traveling. They're going to take time off from work and stay at the hotel. So the overall dependency, or not dependency, the overall demand is going to be based on the day of the week and whether or not it is a holiday. So we have to flag these as holiday or day of the week or weekend, okay? So if it's a base price, if it's a holiday, it's price times 1.8. We can actually bump it up a little bit. If it's holiday, Friday and Saturday, there's more demand for Fridays and Saturdays. Tuesday and Wednesdays, there's going to be a little bit of a discount because not too many people are traveling. We might get some people on Monday. Monday might be kind of a flat day. Sunday, people are probably checking out. So we're not really too concerned about those, but definitely holidays, Fridays, Saturdays, and Tuesdays or Wednesdays, we are going to offer a discount, right? So we get our adjusted prices and we have the base amount down here. We have price elasticity, right? Price elasticity is 1.0, negative 1.0. This is a sensitivity of demand as price increases, right? So this is a key to the whole thing here. Price elasticity. If there is a lot of elasticity, then it's going to bend a lot or change a lot no matter what the price is. If there's no elasticity, you lower your price, you just lose money. If you raise your price, you lose business. If there's price elasticity, then you change the price and people will still come to your place, right? It's elastic, it's bending, it's changing, it's more flexible. If there's no elasticity, then it's kind of just dead, like nothing's going to happen, right? So here's the data frame that we get. And we know that for every 1% decrease in price, the number of bookings increases by 1%, right? So decrease the price, bookings increase. Negative 0.5 means 1% price drop and only 5% bookings, and negative 2.0, 1% price drop and 2% bookings, right? So less and less price elasticity, right? So that's what we want to find out, the sweet spot here. What is the demand and the price change percent based on the base price and then the adjusted price as well, okay? So that's the data frame that we just created here. So we can look at bookings of revenue based on this. The demand score is the maximum rooms. Demand score times maximum rooms is going to be bookings, and bookings times adjusted price is the revenue, okay? So bookings times price, this is the revenue here. Bookings, here's the price, and we have 1,080. 36 bookings, 120, right? So the price is down, more bookings, 4,320. Adjusted price, a little bit higher. We have 30 people coming in, about the same, 30 people, 120, 36. So 430, 4320, 4320, 4320, okay? So let's go ahead and look at a scenario where prices are increased by 5%. So we want to look at revenue discount minus the revenue is going to show us the revenue gain, right? So we had the original revenue. We just saw that adjusted price discount, right? Price change percent discount, and the demand score discounted drives bookings discounted, revenue discounted, and revenue gain. So it's actually a loss over here, loss, 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 loss. So we're losing revenue because there's not enough price elasticity here to justify the increase in the rate, right? So again, more elasticity, increase the rate, and people still come. Less elasticity, increase the rate, and people are just going to say, no, I'm not interested. I'm not going to go, okay? So we can go ahead and plot the results over here. So this was, in this scenario, we are increasing the price by 1.5%. So 5%. I'm sorry, 5%. Increasing it by 5%. Okay. And this is the result here plotted. Revenue decreased by 2,436. 1,785 decrease. Okay. 2,576, 1,875, 2,576. It's bouncing a little bit, and then it goes back over here, -432. But what if we what if we decrease the price 10%? So in this case, look at this. We increase the rate by 5%, 1.05 times the adjusted price, okay? The F times adjusted price 1.05 gives us the adjusted price discount, right? So we increase it 5%. And this is the revenue. This is the bottom line. So we have less people coming, right? Due to price elasticity. Now we're decreasing the price of the hotel by 10%. Okay, we're multiplying the adjusted price times 10% discount. So multiply by 0.09. Let's replot this and see what we get here. Now we have a profit, right? Because of the price elasticity. So we make $3,412 in profit by decreasing the room 10%, right? So we offer a discount of 10%, advertise that to people, and they're going to come out of the woodwork. Even when it decreases, it has 1368, over here 3182, 1368. So it's kind of choppy. It jumps a little bit, but we're still making money. Over here. We're still making, we lost $14. Okay, it's $14. That's a tip at my restaurant, so we lost $14, but we're still making a lot more money, right? So the whole point over here is increase the rate by 5%, increase the adjusted price by 5%. You're losing money across the board. Every single thing is negative. Decrease the price 10%. Okay, adjusted price decrease 10%. You're making money in every single room here, right? So let's go ahead and plot this. We have the monthly summary, group by month. So I have several videos about group bys in the data frame, group by month, aggregate by revenue, sum, right? Usually, I have a couple of videos about this. Like in the data science world, even though we have all kinds of amazing statistics and mathematics and like this crazy analytic processes, most of the time it's a sum or a count or an average. I would say at least 95% of the time, you're doing the average, you're doing a sum, or you're doing a count. 95% of the time at least, right? You get these crazy analytical processes, but most of the time it's straightforward sum, or count or average. So all we're doing is taking sum. This is a monthly revenue gain by discounting the price. So we're grouping by month. So this month, by decreasing the price just 10%, that was it. We made $8,193 more dollars. $5,000 here, $6,000. Okay, over here, $8,000, 5, 6, almost 6. This is 6. This is 6. This is $7,000, 7, almost 8, and 7,200. Okay, so take that to your boss. Hey, say, hey, boss, we discounted the prices 10%, and we just made a ton of money this year, right? And this is looking into the future. Right now, this is mid-June. It's June 18th, 2025. Look at these profits for the rest of the year. So there's 9, there's 6. I'm going to call it 12. This is about 6, 18. This is about 24, 25. Okay, it's 25. This is 31. This is 8. 8 and 31 is 39 plus 7. So 39 plus 7 is what? 46. You just made $46,000. Take that to your boss. Hey, I just made you 46K, okay? 46 grand, 46 big, just by lowering the price 10%. You don't have to do anything else. That's it. You just made an extra 46,000. You're welcome. Thank you very much. You're welcome. Now we're modeling responsive price system to the foundation of revenue management. And this can be applied to hotels. That's what we're looking at. This can be airlines. This can be ride sharing companies. It doesn't matter, right? This is dynamic pricing. Uber does this. Hotels are doing this, right? Airlines are doing this. I'm just showing you how it works behind the scenes so you can learn this stuff too. So go down here. We are going to look at another example now. Again, we have the holidays. The day of the week is holiday. And then the base price is 120 per night. So I'm not going to go through all the code. It took me a little while to put this together. But you can look at this. I'll share all the code with you guys later today. When I post the video, okay, I'll drop the video later on today. You can check it out and I'll share all this code with you. So what do we get down here at the end? This is the discount level, elasticity, the total revenue, the revenue by the weekend, and revenue by days, okay? So we can go ahead and recreate the data frame down here with all the holidays and the dates, and the base pricing is holiday, is not holiday, right? So that all plays into the whole scenario right here. So create the data frame again, and then we can find out the elasticity, -2. So more elastic, 1.5, not quite as much, 1.0, just a little bit, and 0.5, not very elastic at all, right? So this is the discount level here. So we have a lot of money coming in, right? At the discount elasticity 2.0. It's a little hard to read this chart, but I plotted it down here. Okay. So on the x-axis, we go from 0 discount up to 20% discount. On the y-axis, we have the elasticity, okay? And the total revenue shoots up as the elasticity increases, right? So the brighter the color, the brighter the yellow, the more elastic, the darker the color, the less elastic, right? And you can see, based on the discount level and the elasticity, who is going to check into the hotel more, right? So we go from 0 to 20%. The y-axis, we go from -0.5, -1/2 to 2.0. And the elasticity, as discounts increase, we know that as discounts increase, we know that revenue decreases, revenue drops. But if we don't discount inelastic products, it reduces revenue, okay? So if the revenue increases with moderate discounts, it peaks around 10 to 15% and then flattens because of price elasticity, right? Like, people know there's no discount. I'm not going to go to the hotel, right? It's too expensive, but you offer me a decent discount and I'm going to show up. I'm going to be there, right? So what's the takeaway here? More responsive customers act to price changes, right? More negative equals more sensitive to discounts, -0.5. Price insensitive, right? Inelastic demand, -2.0, highly sensitive, and it's very elastic demand. So the more the discount, the more elasticity, and this represents how the hotel is discounting, right? From 0% to 20%. Brighter yellow is higher total revenue, and dark purple is lower revenue. So we have higher revenue over here, more elastic, and less revenue down here, less elastic, okay? So that's the takeaway. And what else? Elasticity 0.5, brighter at 0%. Discount revenue declines as you increase discounts. Okay, that's just common sense. And deeply discounting the room boosts demand significantly for higher elastic customer segments. Okay, so let's look at one more example down here. Control Enter to refresh. We have the day of the week and then the optimal price. So if it's a Friday, this is your optimal price here, 116 per night. Saturday, 115. Monday, there has to be a discount. 98 is the optimal price. Thursday, 98. Sunday, 96. Wednesday, 92. And Tuesday, $91 is the optimal price. Based on the month of the year, these are the optimal prices over here. 103, 103, 102, 101, 101, 101, 101. June and April are about the same, about 99. 90, yeah, 98, 99, that's it. So if you are interested in seeing which hotel brands are owned by which, I would say check out this website. I looked at this a couple days ago. This was my motivation to create this scripts over here in this project. You can see which hotels own which other hotels, right? It's a whole like conglomerate of hotels over here. It's a bunch of stuff, right? So I thought that was pretty interesting, and that was my motivation for doing this. So that's it, guys. I'm going to wrap it up here. hopefully that was enlightening and informative. I learned a lot putting this project together. Hopefully you can learn a couple things by following the code, following the logic here. I'm going to share all the code. When I drop the video a little bit later today, I'll share the code with you guys too, so you have everything. You can copy and paste it and run it in your own Jupyter environment. So that's it. Mediocre one today, not short, not long, just in between. I'm going to wrap it up here. Thank you so much for your time. I really appreciate sticking through to the end. And I'm going to wrap it up here, and I'll see you in the next video very soon. Thank you. Goodbye. Hey there, everyone. My name is Ryan Schewel. Welcome to my channel. This is all about data science, machine learning, deep learning, artificial intelligence, and I mix in some other things as well. Now, this is one of these other things. I was thinking about this concept fairly recently, just a few days ago. So I put together a couple scripts to showcase what is the true cost of buying a car. Okay, so if you want to buy a car and you go to the dealership and it has a MSRP, manufacturer's suggested retail price of $25,000 or whatever, right? You think, okay, the cost of the car is $25,000. It's actually could be substantially more than that, right? It could be closer to 28, 29, 30,000, maybe over 30,000, because there's a lot of ancillary costs that are not negotiable. You cannot just find a loophole and say, okay, I don't want to pay this. I will pay this one. This is kind of trivial, but I don't want to pay this big one over here. No, you have to pay pretty much all of these expenses on top of the MSRP cost of the car. Okay. Now, some might be somewhat negotiable, but for the most part, most of these are not. Okay. So let me take you through everything so we can see the hidden costs that actually build up pretty fast that tally onto the total cost of the car, okay? And when you have this knowledge, you can make better financial planning and budgeting decisions, knowing that the car's true cost is almost guaranteed to be higher than the MSRP, but it helps you to make better informed decisions. You're more prepared for cash that's needed up front, right? For all of these obligations that you have to commit to when you buy the car. And you can make smart decision makings and actually have negotiation power. If you say, okay, the cost of the car is $25K or whatever, and there's another $10,000. No, it probably wouldn't be that much. Maybe another $8,000 on top of the 25. So what is that? 5, 5, 6, 7, 8. 33,000. You could go to the dealer and say, listen, the true cost of me buying this car is not 25K, it's actually 33K. Will you negotiate with the price a little bit? Because I was planning to pay around 25K. All of a sudden it's ballooning the 33. How can we work this out? How can we come to an agreement here so we can complete this transaction? Okay. When you know the total cost of ownership, you're more empowered, you have more information, you can make more intelligent decisions. Okay. So let me take you through it here. I put together some scripts, tested it and debugged it, and I think this should work pretty well. Let's take it for a test drive, no pun intended here. So the purchase price, I'm going to say 25K for the vehicle. Sales tax, usually 6% to 10% on, on average, but we can impute this value, or we can plug in this value, whatever you think is the most accurate that reflects the actual tax on your vehicle, right? And it's different for all different states across the US. I'm going to say $2,000. No, I'm going to put it in percent. I'm going to put it in percent. So 10% would be 2,500. I'm going to put in 8%, okay? Just spitballing here. Total registration fees, I'm going to say 500. Dealership fees, and this could be some kind of ancillary thing that you maybe not are aware of at the beginning, but they're going to introduce you to these extra fees before you exit the dealership. I can guarantee that. Inspection and smog tests, that is not negotiable. You're going to have to pay it. Insurance, first year. Where I live, it's pretty expensive. If you're in a state with fewer people and fewer expensive houses and expensive cars to hit, then it's probably less, but $1,500 is pretty close for my area. So extended warranty, the default is about $1,200. I'll go with the warranty. If it's a brand new car, maybe you don't need it, maybe you want it. It's really up to you. Now, that's one of those costs that maybe you can put in zero. And if you don't need the warranty, if you think that's not going to be very useful for you, just put in zero. But by default, it's probably going to be about $1,200. Other miscellaneous costs, I'm going to put in $200 just to be safe here, because I don't want to go to the dealership with 25K knowing that the car costs 25K. And then we get this weird surprise because we have all these ancillary extra charges tacked on to the 25K. So I went ahead and input all the values. I'm going to create a chart here to see what the visual breakdown is. So that's the cost of the car, 25K. That's exactly what we said initially. But there's a bunch of ancillary extra costs over here, not really superfluous, but probably mandatory and probably not going to get out of this, right? There could be some wiggle room at some point, but that's really up in the air. There's no guarantee of anything whatsoever. So the cost of the car is $25,000. That's actually 86% of the total cost of everything because you have all these extra charges baked in here. So you have another 14% of charges above and beyond what it costs to buy this car for $25K. Okay, so here's the purchase price. Here's the insurance, the breakdown, extended warranty, sales tax at 8%. Wait a minute, I think I put that in wrong. Sales tax could be higher than 8%. Let's come back and fix that. We'll do one more example here. Okay, the percent of total costs relative to purchase price of the car is actually 15% higher. Okay, so you take 100 minus that, and you'll get about 15%. Okay, so 15 plus this 86 should add up to 100%. So let's go back. This sales tax thing, I just noticed that. I tested this the other day, and I thought it was right, but maybe I have to put in the actual amount of the sales tax. Let me see where sales tax, 6% of the price. Yeah, I see what happened. So that is okay. That's okay. I'm not going to change anything. I think I just misread that when I was going through the first time. Let's do another example. The car is a little bit more expensive this time, $35K for the car. Sales tax, I'm going to put in, last time I put in a percent, that was the problem. It was $8. I was thinking 8%. I'm going to put in $2,500 for sales tax. Title and registration fee, $500, I think, is a good baseline number. $400 for the dealership registration. Inspection smog, probably $50. I don't think that's a huge hit. Insurance, yeah, probably $1,750. Now the car is a little bit more expensive than in the last example. Extended warranty, I'll go with it because better to be safe than sorry. And other miscellaneous costs, I could put in 0 for this. Put in 0, okay? We've already paid enough. Let's go ahead and plot this and see what it looks like. Okay, so we have the original $35K, but we have a lot of extra costs here that we have to account for. The other miscellaneous I said was 0. Let's look at the breakdown over here. Okay, so $35K, that's about 84% of the total, but we have all these extra charges down here that add up to be quite a substantial amount. And it's actually an extra 18.29% in addition to the $3,500 that the dealer was charging us, right? So that's pretty substantial. That's something that we really need to be aware of before going into the dealership. So we know the true cost of the car is much closer to 40,000. I think in this case, a little bit over 40,000. I should probably print that out. I'll change this a little bit so we have a good breakdown here. But it's much closer to 40,000. I think a hair over 40K. But that's something that you should be aware of when you go to the dealership. Don't just think, okay, the car is 35K. I'm going to give this guy 35K exactly, and you're driving off the lot. It doesn't work like that, guys, right? There's always these extra ancillary, almost annoying. These are kind of nuisance charges, but they're mandatory charges, except for maybe miscellaneous other. All of these, I guarantee you're going to have to pay the insurance. The warranty might be optional. It's really up to you. It's probably a good idea to get that. Title and registration fee, that's mandatory dealership documentation fees, mandatory smog fee, mandatory sales tax fee, mandatory. You can't wiggle your way out of it. You're going to have to pay these fees. It's better to know this upfront when you go to the dealership. And this could work to your advantage, right? When you have this information and this knowledge, you can say to the dealer, look, the total cost of ownership here, when I drive this thing off the lot, is not 35K. It's a little over 40K. Are you willing to negotiate a little bit on the price? Can you come down a little bit so we can get closer to that 35K? Because right now, if I give you your asking price, I'm actually paying over 40K. If you can drop the price, maybe 5-6%, something like that, we can get this closer to 35K, including all the ancillary extra charges here that are not negotiable. We have to pay these charges. If we pay an extra 18%, but the dealer takes off an extra 8%, that will definitely work to your advantage. But you only know that when you have this information, right? When you go to the dealer and you are very transparent and you lay that in front of the dealer and say, listen, I want this deal to be close to 35K. How can we make this work? What can we do to do this transaction? Okay. So that's it, guys. I just wanted to share that information with you, drop the knowledge here so you can make more informed, intelligent decisions for yourself. Okay. I'm going to add a couple little extra lines over here to clean up this part at the end. So you know the breakdown of these charges here, but I'm going to wrap up the video. I'll make the changes and I'll share all this code with you guys when I post a video later today. Thank you so much for your time. And as always, I will see you in the next video, which I'll drop pretty soon. Thanks again, and I'll see you soon. Bye. Hey there, everyone. Ryan Schewel here. Welcome to my channel. So, in the topic today, I want to talk about the actual true cost of buying a house. So, when somebody sees a house listed for whatever it is, $500,000, $1 million, $2 million, 250K, right? That's the cost of buying the house. But there's several other costs associated with. Sometimes they're hidden costs, but they're really exposed at the end. They're not necessarily exposed at the beginning, because obviously that makes the true cost of the house a little bit more than what the advertised cost is, right? But you still have to pay these costs. There's really no way around it. There's no loophole. There's no option that you can avoid, right? It's not negotiable. You have to pay these costs, right? So with a house, you'll have the closing costs, things like property taxes, insurance, maintenance, HOA fees, right? Home ownership fees, mortgage interest, inspection fees, utilities, setup, things like this, right? So it just gives you better flexibility and your ability to plan and budget more appropriately when you have all this information at your fingertips, right? You can make a more intelligent, more informed decision and understand what it really, really, really costs for you to get into this house, right? When you make smart decisions, you can actually have more negotiating power, right? And you can actually say to the seller, look, there's ancillary costs here. Can you come down on the price of the house, maybe 2%, maybe 3%, something like that? You can negotiate things, right? When you have leverage like that, right? And you have to understand the total cost of ownership is really greater than what is advertised for the actual house. I can virtually guarantee that, right? So I put together a script that is going to help us make these decisions and make it the appropriate determinations. So we have the purchase price of the house. This is the main cost, right? There's things like closing costs, property tax percent, home inspection, loan origination fees, title insurance fees, moving fees, homeowners insurance, legal fees, and maintenance reserve, right? So I'm going to go ahead and run this script and just input some information into these prompts when I'm prompted for this. So the purchase price of the home, I'm going to say is $500,000. So 500,000, enter. Okay, what is the closing cost percent? So a common closing cost is around 3%. Yours could be 2%. You have to collect this information and put this into the model so the model can create a report for you. And the more accurate the inputs, the more accurate the output, right? So the report will be very accurate if your inputs are correct. So enter annual property taxes, about 1 to 2% of the cost of the property. I'll do 1.5, okay? I live in New York, so there's high taxes here. Enter the home inspection fee. I'm going to do the default. It's about $500. Enter loan origination fee as a percent of the purchase price. 1% is probably pretty accurate. And enter title insurance fee. It's going to be probably about 1,000. I'll do 200 just to be conservative here, right? I'm going to overestimate. Enter estimated moving costs, 3,000. So my wife and son and I just moved recently. I think we paid 2,000, but we just moved literally 1 block away from where we lived before, but again, it's New York City, so everything's expensive. Enter annual homeowners insurance, $1,200 is the baseline here, and that's pretty accurate. That's about what I pay. Enter legal fees, saying $1,500 is the norm, and I'll put $1,500 in here. Estimated percent, maintenance reserve as a percent of the total cost. I'll say 1%. We put in $500,000, 1% would be 5,000, right? Hit enter. So we have the original purchase price, closing cost, property tax, so on and so forth, right? So, you know what, I will go ahead, I'll do this one more time. Instead of getting just ahead, I'll get all of those. So, okay, so we have a nice breakdown now. Now we can go ahead and plot this, Control Enter to plot, and we can see what this looks like. Okay, so $500,000, clearly that is the brunt of the total cost of doing this transaction here, but there's other costs too associated with this, right? Closing costs, property tax, loan origination fee. So let's take all of these costs and look at a percent of the total of everything. So we're going to sum up everything and see what the total breakdown is. Okay, Control Enter. So we know the total amount is $500,000. This is about 92.78% of the cost of the house. But there's other costs associated with this house, right? So if I copy and put this into Excel, I suppose I can do everything in Python. Let me just open up Excel and look at this. So there's about 70.78. There's about 7% above and beyond the $500,000, right? So 7 times 5 is 35, probably about $35,000 in addition to the $500,000 closing costs, right? So I don't know about you, but for me, 35,000 is somewhat significant. That's kind of substantial. So I want to know about that up front, because if I saved up a $500,000 for the house, maybe there's a little buffer, $500,000 and 10,000, so 510,000 for the house. I still wouldn't even be able to afford to buy this house, right? Because its closing costs are kind of a nuisance here, and it's costing a little bit more than I expected. So let me put this over here, and what's that thing doing there? And shrink this down a little bit. Not that much, okay? Okay, more. Okay, so here's the cost of the house, but in addition, put some formatting on there. In addition, we have another 3,600, 3,800, 8,900. Wow. So if I go over here, 538. So we have 38,900 above and beyond what we paid, or 38,000 divided by that, right? So it's about 8% higher than the actual cost of the house. So all the closing costs and everything, all the ancillary costs, everything all in, combined, all inclusive, is 8% more than the total cost of the house, right? So if you look at the house and you say it's a $500,000, that's great, but there's other costs associated with closing for that property that you really need to be aware of, or else you're gonna be caught off guard, and that is gonna be a nasty surprise. Let's look at one more example. 1 million. Closing costs, I'll do 3%. I think that's pretty standard. 1. Okay, annual property tax, 1%. It's probably higher, but I'll just go with 1. Home inspection fee, let me say $750. Loan origination percent as a percent of the loan amount. Enter title insurance. So I'll do 1,000. I think that's pretty accurate. Moving costs, I'll do 3,000. Homeowner's default. Homeowner's insurance. And legal fees, I'll do 1. I know the lawyer that could do this, and he has a pretty good rate. Maintenance reserve, 1%. Okay, so here's the total breakdown. Purchase price, 1 million. Closing costs, 3,000, so on and so forth. Let's look at the plot over here. So here's the 1 million. Closing costs, 30,000, 10,000, 10, 10, 10. Okay, and then let's look at the breakdown again down here. So amount is 1 million, percent of total, 93.73. That's pretty similar to what we saw before. Let me plug it in here. Okay. So in this case, the closing costs above and beyond what we paid for the house is an extra $66,000. So that's pretty substantial. So guys, this is something that you really have to be aware of and acknowledge that the closing costs on the house could be a substantial amount relative to the cost of the house. So in this case, it's 7%. And I could probably put that a little bit better, -1. So it's a 7% to get into the house above and beyond what the closing, what the house is advertised at. So with this knowledge, you can say, look, I've done my due diligence. I have finished my homework here. It's going to cost me $166,950. You can say to the seller, would you be willing somehow to come down 7% on the cost of your house so I can purchase this thing? All in, all inclusive, with all the closing costs associated with this, because this is not negotiable. I cannot get out of this. Would you be willing to come down 7% so I can get into the house for 1 million clean, and you are done, right? All in, all the extra expenses for 1 million, if that's your grand total, maybe you can save 7% and you can actually pay 1 million to turn that key and to get into your brand new house rather than paying $1,066,950. Okay, so that's what I want to show you. Just all the extra costs associated with purchasing a house. It's not just the cost of the house. There's a lot of other associated charges that go with that. So that's it. Hopefully that was insightful and informative. I want to drop that knowledge on you guys. I came across this years ago when I bought my first condo. Eventually, after a couple of years, moved into the second, then moved into the third, which is the current place where my wife and I live. So every time it wasn't a surprise because I did my due diligence ahead of time and I knew what I was getting into. If you don't do that, you're in for a rude awakening, my friends. I guarantee that, okay? But with this information, when you're armed with this kind of insight, you can make more informed decisions and go to the seller and say, hey, is there some wiggle room here? Can you come down a little bit? Because I really want to pay close to 1 million, not 1,066,000, okay? So I'm going to wrap it up here. Thanks for your time, guys. and I will post all this code when I post a video later today. Thanks again, and I'll see you in the next video. Bye. Hello there, friends. My name is Ryan Schewel. Welcome to my data science channel. So in today's topic, I want to talk about something that I discovered very recently, and it is about the argument or the debate over when there will be more dead people on Facebook than people who are alive on Facebook. So at first I thought this doesn't really make any sense. Why are we even having an argument about this? But then I realized very quickly, as more and more people join Facebook, the numbers will grow, right? The accounts will grow, and you'll have more and more new users. But eventually, at some point, all these people who are on Facebook will be passing away. It's a very sensitive subject, and I'm very well aware of that. I had a good friend pass away about 3 years ago. His profile is preserved on Facebook perfectly. It's a memorial to this guy, and really a testament to his greatness. I had a friend pass away just over a year ago, and just a couple days ago, I saw a message pop up on LinkedIn, not Facebook, right, but another social media account or platform, whatever, and it said, "Congratulate Victor. He's been at such and such bank for 3 years." Sent him a congratulatory message, and I thought for a second, no, Victor is not with the bank. He's not. He's not with us anymore. And then I started to think about this is actually a pretty interesting question. When will there be more people who are deceased that have accounts on these social media platforms, and they will outnumber the counts of people that are alive and that are active users on these social media platforms? And because this is a very sensitive topic, I want to just make a quick note about the existence of God, and I think it gives us comfort and just overall assurance that there's something better than just this life, right? You go through life, you have your character, you have your personality, you have your soul, right? And what happens to your soul when the person passes away, when they move from this life into the next life? I think that's very important to contemplate and to consider. I came up with 3 arguments outside of the Bible, and we have the Bible, which was written by men, but divinely inspired by God, right? If you don't believe in the Bible, I think there's still some very strong evidence for the existence of God in the world. And I know not every person on planet Earth will believe in the Bible and will acknowledge the legitimacy of the Bible, but I think it's important. I mean, personally, I do, but I think it's important to consider the existence of God outside of the basis of the Bible, right? So if you don't believe in that, I give you 3 very strong arguments why there is some type of God entity or some type of universal creator and sustainer of the entire, our solar system, our Milky Way galaxy, the entire universe, everything, right? I think basically the universe had a beginning and it will have an end. The Bible speaks to this, and even atheists acknowledge that there was a beginning and there will someday be an end. Okay, I think universally everybody acknowledges that. But what caused the creation of the universe? There's still some controversy around that. I think it was God that caused it. Some people said it was a big bang. I don't think a big explosion can create the universe, but that's what some people believe. Number 2, there's a universal standard beyond us for a creator of goodness, justice, and love, and et cetera, et cetera. And everybody around the world acknowledges. Everybody in the world understands what love is, okay? And everybody, let me get a sip of water. Everybody will understand that you shouldn't mistreat people, you shouldn't steal from people, you shouldn't murder people. These are bad things. Where did this universal constant of governance come from? Right? If you acknowledge that it came from God and He introduced love and gave us love, that's easier to accept than just, well, somebody told me to love my parents or my brother or my sister or my best friend or my spouse. I don't think so. I mean, that's love on a small scale, but how does everybody on planet Earth know about love? I think it came from God. That's what I think. And also, we live in a finely tuned universe. I'm going to give you guys a link. You can look this up on YouTube or just type fine tuned universe and customize your search any way you want, and you'll come up with a bunch of resources. And there's at least several dozen different things that have to exist for life to exist. You need gravity, you need electricity, you need electromagnetism, you need magnets. If we didn't have magnets, and if we didn't have lightning, if we didn't have gravity, that goes without saying, we wouldn't have life on Earth and in the entire universe. Well, I don't think there's life beyond planet Earth, but we wouldn't have life on Earth. And all of these things have to be so precisely tuned to a level of precision that's almost incomprehensible. And if any one thing was just a fraction of a human hair, slightly more or less, or deviated just a slight, minuscule bit, a tiny bit, we wouldn't have any life on Earth too. So I think everything in the universe is so finely tuned. There has to be a creator and a sustainer bigger than space, time, and matter to create space, time, and matter. Like, I can create a laptop, I can create a car. It'll be hard for me to do that. I can create a bicycle because these things are smaller, right? I would exceed the space, time, and matter of that object. I couldn't create planet Earth. No human being can do that, right? You need somebody that basically transcends space, time, and matter to create space, time, and matter. Okay, so that's all I'm going to say about that. We can get into the analysis. Now, I found this link that seems very realistic and pretty plausible, so I'm going to use this as the basis for my research here. So I found these numbers for 2024. There's 3.07 billion users of Facebook. In 2023, it's about the same. 2022, a little bit less. Going back in time, a little bit less, and less down here. So you can see the numbers increasing, but it's increasing at a decreasing rate. Okay, so it's really slowing down. And I think the adoption of new users on this platform called Facebook is inevitably going to decrease over time. And that's where the argument comes from, that there will be more dead people with profiles on Facebook and any social media platform, LinkedIn, take your pick. Eventually, the deceased people will exceed the alive people on any one of these social network platforms. Okay, so I came up with some numbers here that I think are plausible, and it makes sense. It makes sense to me. I Googled this a little bit, and I came up with some other numbers that kind of validate my analysis here. But this is kind of an estimate. It's a best guess, and nobody knows for sure what these numbers are going to be, right? Even Mark Zuckerberg and his top lieutenants at Facebook really have no idea when the dead will exceed the living number of counts of people on Facebook. Nobody knows this, right? So we're going to make some assumptions, and it's going to be somewhat liberal, but I think it's going to be very believable and very plausible at the same time. Okay, so that is going to be the basis for the analysis. So I have age groups down here, and then the percent of each age group. Okay, so these came from over here. Okay, and these are basically the numbers. I'm just going to assume that this is pretty accurate. I really don't know, but I mean, it seems realistic, so I'm just going to go with that. So we have the age groups here. We have mortality rates here. So this comes basically from life insurance mortality schedules. Talk to any life insurance agent. They can validate this, or you can do a Google search online and come up with these numbers, mortality rates, and mortality rate increases, again, by age group. So we're breaking these people into different buckets or different groups or different bins. You can call them bins or buckets. And we're going to do the analysis based on that. So I chose to use Monte Carlo simulation. So Monte Carlo simulator basically will go through a whole bunch of iterations of almost randomness, but it's basically all anchored to these requirements right here, or these constraints. So we have age groups, mortality rates, and mortality rate increases. But I'm going to run 10,000 simulations because I don't know if I just do one simulation, is that going to be accurate? 2, 3, 4, is that going to be accurate? Probably not. But if you do a whole bunch of simulations, it will be pretty accurate. Okay, so I'm going to do 10,000, and I'm going to make a forecast into the future for 200 years. I'm going to assume a growth rate for a new adoption of 0.01, and the mortality rate increase will be 10%. Okay, so at a certain time, the numbers of dead people absolutely outnumber the numbers of living people. That's not even a question anymore. At the beginning, when I started thinking about this, I thought that's kind of crazy, but that's actually that's a fact. That's inevitable. The only question is, when will this occur? Will it be in the next 10 to 15 years? Probably not. Next 20, 30, 40 years? Probably not. Next 50, 60, maybe. Probably a little bit longer than that. Definitely less than 100 years. Okay. Everybody that's alive today won't be around to see this happen, but I bet within the next 70, 80 years, maybe 90, probably a little bit sooner, the number of dead people on Facebook with accounts that are still up and active as a memorial to the deceased, those will outnumber the number of living active users. Okay, so that was my analysis. I did some very basic Monte Carlo simulation. So we're looping 200 times while years less than max years. Max years comes from over here. Okay, max years is 200. We're going to do 10,000 simulations for each iteration. An iteration is one cycle of a loop, right? So we're going to loop 10,000 times and do that for 200 years and then plot the results down here in the chart. Let me run this and kick it off just so you can see how everything works. And by the way, I'll share all this code with you guys. Okay, you don't have to take notes. You don't have to, get your pencil and paper and start writing this down or write it on your computer. Okay, I'll share the code with you so you can have all of these numbers just by copying and pasting the code into your own Jupyter notebook and do the analysis for yourself. Okay, so let me change a couple things here. There's the graph coming up. It's a little bit slow to respond. My computer is just getting old, and talking about dying, I think this thing is going to computer heaven pretty soon. This thing's getting a little bit old and just tired and just worn out. So I think we might see a little lag here with this chart being replotted. It should be pretty quick, within a second or so it should respond, but you can see there's a slight lag here. I'm sorry, buddy. Computer's just getting old and might be time for a new system here pretty soon. Okay. So the number of years, if I go out 100 years, the red line here represents number of deceased users. Green shows number of active users logging in at least one time per month, right? And this is all linked back to the data that I found on this web page over here. If you go down a little bit, you'll see some different metrics. This is just for the United States. And they'll have a couple things here like, what is this? Active daily users. So some people log in every day. Some people log in once a month. Okay, I think this is monthly. Yeah, this is once a month. So we're going with the bigger number here and the broader, just to say, okay, if a person logs in once a month, that's an active user. Deceased user obviously doesn't log in at all. I think the crossover rate is going to be around 90 years, but we can make some adjustments. So in this Monte Carlo simulation, you can see everything initially was calculated, and then the plot was created right down here. Right, so we have the user-defined function right here doing the simulations for us, but after that, we can interact with this plot and change some of the assumptions ourselves, so we don't have to rerun the entire analysis. It's already been done for us, but we can look at different pieces of the scenario that comes from the Monte Carlo simulation, right? So right around 70 years up to 80, between 70 and 80, we hit that crossover point, right, where the red line exceeds the green line. So I think right around 75, 74, 75 is the approximate crossover point, maybe a little bit less, 74. Right now it's 2025. So by approximately the year 2100, the number of profiles on Facebook that belong to deceased people will exceed the number of profiles that belong to living active users on Facebook. So about the year 2100 and about 73 or 74 years from now. But again, there's assumptions being made here. If Facebook adds more new users and the growth rate increases at an increasing rate, then there's going to be more active accounts on Facebook, right? As new users come onto the platform at a more aggressive rate, faster and faster, then new users will outstrip the deceased, right? But if the mortality factor increases just to depreciating healthcare, exposure to decent healthcare, mortality rates can increase. Into the future, 20, 30, 40 years from now, are we starting to run out of food supplies? I don't know. Will we run out of oil and access to To cheap energy, probably. I mean, I've seen some statistics that are staggering. They said the end of oil will occur in about 40 years. If we actually do run out of oil in 40 years, then we don't have Facebook to worry about. We have much bigger concerns than just that, right? So I think something like this kind of makes sense. Growth rate of new users is probably about 2%, according to the website. I did some research. I think that's probably pretty accurate, and mortality could be about the same, 2 to 3%. But even if I do this at like 2%, the precision is a little bit different here, but it doesn't even matter. If I do that up to 80 years, I think 80 to 85 years, I think we'll see a crossover with the deceased exceeding the number of new active users or current users, right? Maybe up to 90 years. But my guess is that the number of new people to join Facebook is not going to be 2%. I think it's going to slow because they already have so many people now. It's already a very mature technology now. Are you really going to get 2% growth? You could or you could not. So that's why I did the analysis to look at this from a few different ways. The number of years into the future, we're making a projection into the future number of years, the growth rate of new users, and the mortality rate of existing users. Right, so it's a multifaceted problem. There's three major variables that we can tinker around with and try to get like an approximate estimate of when we will achieve this crossover rate. So again, nobody knows what that is going to be, but we can make some assumptions. I think this is an interesting type of analysis too, just for what I said, because you can mess around with the number of years that the forecast goes to the future. You can mess around with the growth rate of new users arriving on the platform, creating accounts, and increasing the longevity of Facebook into the future. And the mortality rate can change 40 or 50 years from now. I've heard estimates that say we will probably run out of oil in about 40 to 50 years. And if that happens, I think global populations are going to be decimated, and the number is going to crash. The human population number is going to crash if we run out of oil. That's why we have the population boom that we have right now. If I graph that, I've seen these graphs before. Let me see. Personally, I think human human numbers increasing over time. I don't even know what to call it. Human numbers increasing over time, or whatever. I guess human numbers increase. Oh, so here it is. Is a like population boom or something like that, right? So all these charts really take off since 1800. So all these charts kind of follow the same pattern. Since around 1800, human populations have been increasing at an increasing rate. This is where we are right now, 2025. So right about here, 7.8 billion. I think it's about 8 billion, maybe closer to 9 billion people. And it could be increasing up to 15.6 according to this chart. I think personally, if we run out of oil, human population numbers are going to fall off a cliff, and it's going to be cut dramatically over where it is now just because of the discovery of oil. That's my personal opinion. We found oil, and it made it easier to live. We can fly in airplanes, we can drive cars, we can take boats, we can use electricity, right? 200 years ago, we had no electricity. Now we have electricity, and all this contributes to an increasing population boom, right? Once oil ends and we run out, then nobody knows what's going to happen. So there's a lot of assumptions. That's the point. I don't want to go way off on that irrelevant tangent there, or irrelevant topic, but I made the chart so you can play around with it and interact with this thing, and I think it's a very interesting exercise, no matter what happens with the supply of oil or the number of users on Facebook. And that's it. So I'm going to wrap it up. I have a couple of notes down here about exponential growth, linear approximation, how I came up with these numbers, and mortality rates, and so on and so forth. And this is a link to that Facebook page where I got the data source. Okay, so you can take a look at that when you have some free time. And that's it, my friends. Hopefully you found this interesting and insightful. I'm going to end the video in just a moment here. I will share all this code with you so you have access to all this. You can copy and paste it into your own Jupyter notebook and do your own analysis, and then tinker around with those sliding controls, and then see what kind of outcome you get. Okay, I think it's going to be fun and interesting, and you can talk about this the next time you're at a cocktail party, and you can really dazzle the people that you interact with. Okay, so that's it. I'm going to wrap it up, and I'll see you in the next one. Bye. Hey there, everyone. My name is Ryan Schul. Welcome to my data science channel. So in the project today, I want to take a look at potential places where we can open a new Starbucks restaurant. Okay, originally I was thinking about where could we open Taco Bell's. I like Taco Bell, but Taco Bell honestly is like kind of a little bit low class. I was thinking, okay, maybe something a little bit higher end, a little bit Chipotle-ish, and I could certainly do that. But I thought, let me just level it up to a whole nother level. Let's look at Starbucks. I think it's pretty refined type of restaurant, very, very engaging type of experience, and it's more of a gentrified type of um, interaction too. When you see Starbucks come into a neighborhood that is a little bit dilapidated and a little bit kind of depleted of resources. If you see a Starbucks come in, it might mean the neighborhood is turning around and getting a new injection of adrenaline boosted into the local neighborhood system, right? So I decided to settle for Starbucks. So I went ahead and put together some analysis. And I want to share my findings with you right here, right now. So why does this matter? This basically gives us a granular estimate, not just a yes or no, are we going to be profitable or not profitable, but all kinds of scenarios in between. We're going to look at some regression analyses and some classification experiments, and we're going to see how things shake out. Okay, this is going to enable ranking of candidates for different locations based by profitability, overall profit potential for different restaurants opening up in different neighborhoods, right? Helps with budgeting, forecasting, scenario planning, understanding foot traffic. Increases by 10%, what kind of impact is that going to have? If we lose foot traffic by 10%, what kind of impact will that have, right? What if scenarios? What if this happens? What if that happens? What kind of outcome can we expect? Why does this matter? It's easy for executives or real estate teams to act on this information. It allows for building decision support tools and really quantifying decision making, right? And we're looking at different scenarios where we can actually harness different insights and produce different insights into different scenarios and make intelligent, informed decisions based on quantifiable material, right? That's what we're looking at here. And we can model for risk tolerance and adjust for profitability and adjust based on different thresholds, 50% confidence, 70% confident. Like, how confident are you, right? And how much does this matter? I think we're going to look at things like that. So we have to gather and prepare data, looking at existing Starbucks store data, latitude, longitude, so we can see where they are dispersed geographically, sales, customer traffic. Is it urban, suburban? Is it drive-through? Location attributes, foot traffic, population density, demographics, labor costs, competitive presence, right? Do we have Dunkin' Donuts right across the street, or half mile down the street, quarter mile, 2 miles down the street? Where are we located compared to our competitors? And what kind of amenities are nearby? Are there office buildings? Are there colleges? Are there malls? Are there transit stations? Are there shopping centers, right? That's what we have to try to identify and understand. So I looked around for some information. I found some data over here on this website. You can take a look. It was somewhat informative and a little bit useful, but not really. It's really lacking a lot of information. This has Starbucks locations worldwide. It has mostly lat long coordinates and a couple other very basic information, but it's really lacking in a lot of things. It doesn't have like city, state, population density, demographics, things like this. And it certainly doesn't have any kind of like labor costs, unemployment rate, competitor density, things like this, right? These are things that Starbucks has and it collects, but they hold it tight to the vest or close to the vest, whatever the term is. They're not going to expose that. They're not going to give that to you, right? So I came up with realistic estimates of what these should be. I think it will serve the purpose here. I think it's going to be pretty meaningful, pretty realistic. Hopefully it hits the point. If not, I mean, we could dial it in, dial it down a little bit, dial it up a little bit. I don't work for Starbucks, so I don't have access to this information. And if I did, it would be personal and confidential. I certainly couldn't share it in a public domain like this right here, YouTube. So we're going to make up some hypotheticals, but again, this can be realistic and try to create a scenario that we can analyze and derive some some utility from, some satisfaction from. Okay, so that's what it is. It's made up data, but it should represent actual numerics and actual quantifiable numbers that Starbucks would have. Okay, again, I don't work there and I don't really care what Starbucks is doing. I'm trying to recreate a scenario that is hypothetical, but mostly realistic. So we have a few cities here and located in a couple states, lat long coordinates. I am going to create details of city, state, lat longs, population density, median income, demographics like educational level, percent of residents under 35 versus over 35, square footage of the restaurant, labor costs, unemployment rate, competitor density, and nearby amenities. And I'm going to create multipliers for each one of these variables over here. Okay, so let me hit Control Enter to create the data frame. You'll see what it looks like: city, state, lat long, demographics over under 35, commercial rent per square footage, labor costs, unemployment, and so on and so forth. Okay, so let's go ahead and create our first machine learning algorithm. So I'm going to use a regression algorithm. We have city, state here, which are not numerical. Okay, so we have to take these and label and code these, or one-hot encode or categorical encode these, right? We have to get these labels or text or string into some type of numerical representation. So the computer knows lat long, it knows foot traffic, it knows numbers. Anything that's numeric, the model is going to know. It's not going to know what New York is, and it's not going to know the abbreviation for New York is NY. It doesn't know San Francisco, it doesn't know CA. So I'm going to create some synthetic label encoding just to represent these strings right here as numbers. Okay, and again, there's three ways to do this: label encoding, one-hot encoding, and categorical encoding. And there's pros and cons to each of these. I have a whole nother video dedicated just to encoding, so you can check that out on my site. So just trust me right here. We're going to encode these. I'm going to feed that into a random forest regressor, and I'm going to set number of estimators to 50. We're going to go down number 50 levels. Maximum depth is 10. Maximum feature square root. The number of jobs is -1, and the random state is 42. So we start randomly and we end up randomly. But again, the way the random forest works is we're looking at Gini impurities. If the impurity is increasing, we stop going down this path and we go into an adjacent path. And if that is increasing in impurity, we stop that and go into an adjacent path. We want the impurities to decrease over time, so we get more and more realistic predictions for our outcomes. So the overall R squared is 0.87. So 87% of the time, we're making accurate predictions into the future. Unfortunately, about 13% of the time, it's not going to be accurate, right? It's going to be just a random guess, because the computer is trying to estimate and figure out what is most likely going to happen, but it can't do this with 100% mathematical precision. There's a little bit of deviance, there's divergence, there's a little bit of confusion in the algorithm's ability to make predictions, but 87% is fairly accurate, right? We like to get close to 0.9. Over 0.9 is better. High 0.9 is 0.97, 98, 99 is very good. If you get too perfect, that's 0.9999, you might be overfitting the data, and you might have to use a couple techniques to sort of like scale back the way that the algorithm is working, so it doesn't tend to overfit and learn all the nuances and all the details or all the noise of the system. You want it to learn the major details of some of the minor details, but not every single detail. You want the model basically to learn the system and to make accurate predictions into the future on scenarios that it has not seen yet, right? Because it's going to memorize all the scenarios it's seen. It knows what the inputs are, and if it sees the same inputs, it knows what the outcome is going to be. You want this model to generalize on scenarios that it hasn't seen, but it's pretty close to scenarios that it has seen, and it can make a prediction into the future. So the model has been trained, tested, 87% accurate. Let's say we're going to open a new Starbucks store in New York. This is a lat long coordinate. Foot traffic is 8,000. We're going to say per day, okay? Total population density is 200, and this is 25,000. So this is probably upstate New York somewhere. Median income for the neighborhood is 85K. Education level is 0.7. 70% of the people have college educations. Percent out of 30 is 0.55. So kind of scaling under 30, not so many older people, more skewed towards lower aged people, younger people. Commercial rent per square foot, labor costs, unemployment, compensation, competitor density, and nearby amenity score 0.5. Okay, so we have these variables. This is going to be similar to a scenario that we've already seen. It says city, hasn't seen city. Wait, let me try this again. City should be in there. Oh, I think I know what it's doing. Okay, so let me see. Okay, let me see. Let me see what this thing did. I think I know why. Display. Okay, so let me see. Whoops. Let me see what the head is looking like now. City. No, that should be fine. City is city, right? For okay, label encoded city. Obviously, by city. One. Okay, so one is New York. Let me see. One is New York. Yep. And then state is 1 and 5. So state is 5. Okay. So for city, let me see. Something's definitely a little bit weird. I just ran this before, so this should work. Like sometimes I don't understand these things. I literally just tested it before I turned on the recorder and everything was fine. Then you hit record, and of course I don't edit any of these things. So it probably would behoove me to learn how to edit these things. One of these days probably save a lot of time for myself and for you guys, the audience as well. So one of these days I should learn. I have a cheap recorder here, so I'm not even sure I can even edit these things per se. I mean, I think you just hit record and just go. But maybe, let me see. So one hot dummies use PT dummies instead of label encoder. They should use transform instead of match dummies. City state, column encoders. Okay. Column and city state. Well, that's what they had. New York, New York. We go back. New York, New York. Transform. And column state. Okay, let's try that. Game for that. State. Okay, state. Oh, okay. So I think I need that too because you have to label code it. City and state. So so I know that. Let's see what this does. Okay. So the encoding is fine for column city state. If new code, new store code. Should work. Why is this not working? This is city and state. Could not convert to string to quotes. Let me see. Let me see. It's kind of amazing how it works. And then you turn on the recorder, and then it doesn't work. So not sure about that. But I did the label encoding. I did the decoding over here. So city, state, everything else is numerical, right? So that is totally fine. But I want those two because that is going to make a difference, right? So if you label encode, I did that. Make sure you apply the same encoder during training. Label encoder, right? We get rid of that. And that is label encoder. strain. I did that. Predicted profit. Okay, so let's get to the bottom of it, and that is going to be that, right? So it coded it. I just don't know why I can't decode it. Uh, let's see. Maybe I feel like use stored col. Coder. Oh, yeah, maybe that's too much. Maybe that's too many encodings and decodings. Let me try this. Okay, got it. I had extra encodings in there. Okay, so anyways, we got 0.87% accuracy. So 87% of the time, we're going to make accurate predictions, 13% of the time. However, it's going to be random or it's going to be a little bit off, but it's going to be pretty close if we're right at the margin. The cutoff for this here is a threshold of 100,000. We're saying if greater than 100,000, we'll open a restaurant or open a new Starbucks. If it's at 100,000, we won't. If it's less than 100,000, we won't. So if it's close, like 105,000 in profit per year after all the expenses, right? This is the net profit after we pay for the raw materials, the resources, the labor, all the 401ks, the salaries, healthcare benefits, vacation, all this for all the employees, all the coffee beans, the transportation, the gas for the shipping, the supply chain management, all this stuff, right? If we have 212,000 net after all the overhead, we are going to go ahead and open a store. That's going to be profitable. So that's what this regression analysis tells us. We trained and tested the model over here using random forest regressor. Okay, so the dependent variable right here is annual profit. What determines annual profit? It's all of these variables. So city, state, latitude, longitude, foot traffic, so on and so forth, except for annual profit, because that's what we're testing for, right? So we're gonna leave off annual profit. We're gonna drop that out and open store. That is the classifier. We're gonna see that in the next step. Are we gonna open the store or not open the store? So we're gonna drop these two from our independent variables and use everything else. So everything from the left of here, right, between the beginning and ending, and we're trying to predict annual profit. 87% accuracy. This says we're gonna have $212,000 in profit. If I change one of the variables over here, all of a sudden labor costs goes to $122 per hour. We're gonna see this decrease, most likely. Control Enter. 209 decreases, not a lot, but decreases a little bit. Comparative density, if this is 4, maybe if I make this 20, we'll see that decrease or increase just a little bit. That's weird. Nearby amenity stores, if it was 0.85, probably decrease, right? 210, 201. So you change these variables over here and the output is going to change, right? That's the whole point. Now let's say we're looking at a classifier. The classifier, we're going to train and test it again. We're looking at an accuracy of 0.94, higher is better. 0.10 is the best. 0.99 is pretty close. 0.94, recall 0.987, 96. So all high nines, very good accuracy, precision, recall F1 score. And you can see the same repeated down here, 93, 94. Recalls a little bit lower here, 74, 99, 96, 82. Overall, very accurate classification technique, right? And again, we're looking at all the independent variables. So all these variables over here, right, except for annual profit and open store. So annual profit is the regression analysis that we're doing here. Annual profit is going to be $201,498 in this case. The classifier is a label. It's binary outcome, yes or no, true or false, on or off, up or down, left or right, whatever the thing is. Open the store or don't open the store. This is a binary outcome right here. So based on all of these random forest classifying models that we trained and tested over here, this is a training, this is the Y training. So the X is all the independent variables, the Y is all the dependent. We are measuring the ability of the model to make predictions based on the X test. So you have the training here. The testing is what we're trying to predict. So the training, I explain to people as training is like if you're a college student, you go to class, you're in lecture, you do the homework, you read the book, that's all you're training. The test is when you take the test, You prove whether you've retained the information, yes or no. Did it sink in? Did you internalize it? Can you regurgitate it? Can you generalize that to new problems, yes or no? Now we're seeing the same thing over here. Let me see what the heck changed over here, because I don't know. Everything was working fine. Don't know what's going on. And of course, I have to go pick up my son from daycare camp because he's in camp now for the summer, and I have to get going. But I have to finish this thing because I can't go ahead and do an edit. I have to figure out how to do the edits on this thing one of these days. So soon. I think it's the same thing as before. So New York is the string, and it doesn't like strings. I understand that. So the classifier has to label and code everything, but it should have done that over here. That's what the encoding is for. Training, testing, for applying. So wait, let's see. So if I label and code these, new store, classifiers, new store copy. So I'm going to copy that from the original. This is always good practice to copy the original data frame. So if you're making changes on a copy, it's just changes on the copy. If you make changes to the original, then you want to go back. Then you could be in a tight spot. You have to reload the original data and run through the whole analysis again. It's really best practice to copy things over and work from the copy. Then if you make a change accidentally or intentionally, it's not going to affect the original data frame, right? So you're safe. This is just a safer practice over here to do it this way. So let me go ahead and see if I can make the prediction. Okay. So I think I had an extra line in there or two. One thing can mess up the whole analysis, right? So again, the regression, we're looking at numbers. We're looking at a continuous outcome, 201,498. That's very specific, right? Numerics represent a regression type of problem. A classifier is shown in the form of binary outcome, yes, no, on, off, true, false, something like that, or some labeled data. So it can be orange, apple, grapes, banana, pineapple, coconut, something like that. That could be a classifier, right? If you look at an image, classify the image as some type of fruit. It could be a watermelon, doesn't matter, right? Could be large, medium, small, extra large, something like that. That's that size of that shirt or those pants or whatever. That thing is classified as a certain thing. So in this kind of scenario, we're not working with numbers. We're looking at classifiers, and we're saying the binary outcome is if we achieve a certain assumed level of success, we will open the store. So we're 96% confident that the store will be successful based on this, not based on this representation, but it goes hand in hand with this analysis, right? So we said the arbitrary limit for success is 100,000. If we can achieve 100,000 net income in profit, we're going to open a store. If we can achieve a certain level of success based on the accuracy, precision, recall, F1 score, this is the ability of the classifier to learn and to make predictions. 96% of the time, we will open the store and we will be successful. 4% of the time, we'll open the store and it won't be successful. That is called the cost of doing business. That's just how it goes sometimes, but 96% of the time, we're going to be successful. So let's go ahead and set up some clustering exercises, and I want to understand how all of these variables based on the annual profit, commercial rent, labor costs, and foot traffic, what is the summary cluster for all of these variables? And we're going to assign a cluster here. There's 5, 4, 8, 9, 7, 6, 2, 0, 4, 3. So we have 10 different clusters. I believe what I set for clusters over here. If I look close, 10. So you have 10 clusters, starts with 0, goes up to 9. So there's actually cluster 10. This will be cluster 1. They just represent it as a 0. And these are the annual profits for each one. All these clusters are over 100,000, so all these stores are successful. We have the commercial rent per square foot, the labor cost, and the foot traffic. So we have everything clustered together nicely. Let's look at a SHAP plot. SHAP is going to show us two different plots. In the first plot, we see the global features, everything comprehensively. And this is going to tell us on the x-axis how much each feature increased or decreased the model prediction. The color features Red is high, blue is low. So red, you can see on the right-hand side of the median here, blue is low on the left-hand side. Each dot represents one data point, and the population density and foot traffic have the strongest effects, positive or negative. So population density and foot traffic, just because they're elongated the most, foot traffic has an effect on the success of the store, and median income of the store has a success on the store. So you can imagine it makes total sense, right? Look at this, guys. Population density, the greater the x-axis, the longer it is, the more success on the store. Again, high is red, low is blue. So we want to see more dots to the right. High, that's going to guarantee success. There are some to the left, and that's going to offset some of the success, but still, overwhelmingly, we have success. More foot traffic, more success, more median income, more success. So labor cost per hour doesn't really determine the success of the store. Maybe incrementally, if labor cost spikes up a little bit, maybe it's going to have an impact, but essentially it's no impact. Percent of population out of 35, we don't care. Longitude, latitude, we don't care. Competitor density doesn't have an impact. Nearby amenities doesn't have an impact. And sum of score of 5 or greater doesn't have an impact. So we can see here the overall profitability of a store on median is $122,095 per year. Remember, 100K is the cutoff. If we can achieve more than 100K, then we're going to go ahead and build a store. So the second graph tells us that. The first tells us overall, comprehensively, what's going to determine the success: population density, foot traffic, and median income. The second is more of a local type of analysis, right? The first is global, it's macro analysis. The second is local or micro analysis. The Sharpe value impact by model input is affected by each dot, each single prediction, high or low, from the median number right here is 154026. Population density and foot traffic are the most impactful features. High values are red, low values are blue. Low values push profits down, high values push profits up. Higher values decrease predictive profits, and nearby amenity score has a smaller but positive influence when high. So again, population density, foot traffic, and median income all play an impact on the store, positive or negative. Labor costs, latitude, longitude has no impact. State, college education, and the other features have no impact. So everything comes down to population density. If you understand that well, you will know how successful the store is going to be. Foot traffic in the neighborhood, not necessarily in your store, but you're going to get some collateral effects from more foot traffic. More foot traffic means more business in your store. And median income, if people have more disposable income, they'll spend more at Starbucks. If they're living hand to mouth, you're not going to have as much people shopping in Starbucks, right? So let's look at the Haversine longitude, latitude, distance between these coordinates, and we have the latitude, longitude right here. We're looking at the Haversine distance. Haversine is the curvilinear surface of the Earth, and the distance between longitude, latitudes, and what kind of impact that is going to have, right? So the list of longitude, latitude coordinates for candidates in certain locations impacts the profitability of the store and is a competitor at least 2 miles away from an existing store. That's why we're calculating the Haversine distance. The Haversine is the curvilinear distance on the surface of the Earth between longitude and latitude coordinates. It's not, as the crow flies, it's not like linear as you drive your car. It's curvilinear because it's based on the circumference of the Earth, right? So we're looking at least 2 kilometers away from an existing competitor or another Starbucks store, because we don't want to cannibalize our own business, okay? So if all these things align, all these different features align, and we find a great place to open a store, but there's a Dunkin' Donuts right across the street, or Tim Horton, if you're in Canada, they sell coffee, Tim Horton right across the street, or another Starbucks directly across the street. You walk out the street and you see at Starbucks, you're face to face, facing off at the Starbucks. You might not want to open a Starbucks there. You could cannibalize your own business, right? So we want to find the best locations based on median income, latitude, longitude coordinates, like foot traffic. What was the number one driver over here? Population density, right? If all these align, but you have a competitor right across the street or within 2 kilometers or another Starbucks, that could cannibalize your own business. Within 2 kilometers, you might not want to open a Starbucks there. Now you might, I live in New York City, I've seen Starbucks right across the street from each other, and both are lucrative, both are profitable, right? So it might make sense to do that, but you might want to second guess your decision and just try to look for something that's less cannibalistic and just more profit driven in terms of there's no Starbucks serving this community, so we can open one with a high degree of confidence that the Starbucks is going to be profitable. So I have a map here. If I zoom out a little bit, you can see the locations here. The blue dots represent stores that are recommended to us based on the whole DF filtered data frame that we set up over here. This comes from filtered candidates, which comes from here, all right? Candidate for candidate and candidate coordinates. And the candidate is not too close to a competitor or not too close to another Starbucks store. If you don't meet those criteria, we have the longitude, latitudes. We have a few in Boston. We have several in New York. If I zoom out, you can see some of the other cities that we picked. Chicago. This is Atlanta, Georgia. If I zoom in there, we can see the locations that are being recommended to us based on all the criteria that we looked at. Disposable income, what else? Foot traffic, things like this, right? And is there a competitor across the street? Yes or no? So these are locations that are worth further investigation. These are places we want to, set up a meeting with our colleagues and have a conversation. Does this make sense to you? Does this make sense? Because this makes sense to us. Does it make sense to you? Now we're looking at the clusters that we set up previously in one of the earlier experiments that we ran. Now we're looking at clusters, again, based on longitude, latitude coordinates. And here's New York. I'm going to zoom in on New York. This is where I live. So I would recognize some of these spots right off the top of my head. So Long Island City, that's where I live. So annual profit, 144K. This is cluster 4. Profit, 134K, 199K, and 185 cluster 4. This is cluster 5. Cluster 2, cluster 0, 153,000. So again, this is a starting point for a conversation with some of our colleagues. We'll set up a couple meetings and, pitch to them our findings here. And here's the final map I came up with. This is looking at longitude, latitude, again, annual profit. And in the city, open a store equals 1 if it's green, otherwise it's red. So all these come up red. I can zoom in here and I can look at the stores that are being recommended to us. So Astoria, I can zoom in here. 6.0 in the pop-up. This is, I see the annual profit, 189 profit, and row is city, 6.0. What's the 6.0 represent? Cluster? Row is city, right? Let me look at one thing right here. I think these are clusters, but I'm not totally sure now. Well, they all be the same then. Wait a second. Okay, so I think the clusters are going to different cities. That's what it is. So the clusters are going to different cities. The cluster comes from here. This is in our data frame, right? This is the annual profit. This is regression analysis that we did initially. This was to open a store, yes or no. 1 means yes, 0 means no. And this is the cluster that falls into, and this cluster comes from, STR comes from previous experiment that we ran over here. And this is based on the k-means fitting. So based on the fitting of those k-means profitable, this is the data frame called profitability, and it goes into that cluster, okay? And then it's mapped in Foley and Plotly. So this is Houston. This would be cluster 3. So it's just taking all of the cities and assigning these to clusters, whereas in the previous example, it would create different clusters inside the same city, right? So I'm not saying one is right and one is wrong. It's just different methods, different way to skin the cat. We have, just city number 6 and then cluster within the city. Okay, I see. And this is just clusters in the same city with the profitability showing when you zoom in and it pops up in the bubble. So this store is going to make 143,000. That's making 121, 178, 177. And these downtown 212 per year, 200,000 and 183. So getting a lot of hits. Maybe we have to increase the threshold beyond 100,000 up to 200,000 if the total profit, the total net profit after all expenses, everything is paid and done for, all the salaries, all the raw materials, all the supply chain management expenses, the rent, everything is paid. If you have 200,000 in profit or more, maybe we should just consider these stores. If you want to saturate the market a little bit more and go over above and beyond, maybe you have a lesser threshold, 150K, but I set the threshold for 100K, and I'm kind of second guessing that. Maybe that's too low. Maybe we need more. Maybe we need to amp up that threshold over 200,000 or more. But still, overall good analysis. We know where to open these stores. We have a lot of information here now to start a discussion with the finance team, with the operations team, the real estate team, the accounting team, the tax team, all these teams. We can start to set up some meetings, sit down with these guys, showcase our findings, and get buy-in from them, get feedback from them, and then determine the next steps here. So basically, profit estimation, check. Decision troubleshooting, check. Prioritization, strategic planning. We used regression to predict how much it's going to cost, how much we can make from each store, ranked all locations by profit, and budgeting ROI estimation. Furthermore, we did an experiment with classification. We found out what's applicable, what's not applicable, built in, yes, no decisions, so binary, right? Filter for variable profitability only, and risk management, go, no-go decisions. That's it, guys. In a nutshell, that's how we can open new Starbucks restaurants. I had initially called it open 10 new Starbucks restaurants. Is way more than 10 here, okay? But we can refine that. We can filter down. We can open restaurants making over 218,000 or 200,000 a year and over. So that's an easy fix. But definitely a good baseline for comparison. It's a good starting point for a conversation. And we have a ton of information here where we can move forward and set up some intelligent, very informed, very meaningful conversations with our colleagues, and then push this over the goal line, past the goal line, and get over the finish line, and get to the next step and start, start pumping some money into these scenarios and into these real estate investments, and start building up some hardware and some stores and some outlets to do transactions with our coffee consumers. Okay, so that's it, guys. I want to share my findings. Hopefully that's useful, informative, and relevant, and motivating and stimulating, and all these great things. I did this analysis a couple days ago. I wanted to share my findings with you. There you go. I am going to export this file as an HTML format. Okay, and I'm going to save that down, and I will share all my findings with you a little bit later when I drop the video a little bit later today. And you'll have everything you need, share all the code with you, and you'll have that when I drop the video in a couple hours. Got to go pick up my kid from his camp. When I come back from that, I'll post a video on YouTube. There you go. Let me know if you have questions. Hit the like button, subscribe if you haven't done so already. And yeah, post some comments in the comment section. Let me know your thoughts. I think the accuracy of this analysis is spot on. If you find a deficiency or I missed something, or something was calculated incorrect, let me know about that. I don't make too many mistakes, but I have made some mistakes in the past, and people brought that to my attention. I fixed it. That only happened once in the past year or so, but I fixed it and made it right, and that was it. So share your thoughts, your opinions. Love to hear about it. Thank you so much for your time, and I'll see you guys soon in the next video when I post that, probably in a day or two. So talk to you soon. Goodbye. Goodbye for now.